Welcome to the first lecture in our series on Bitcoin and cryptocurrencies. I want to start by introducing the four lecturers who are going to be speaking in the series. The first lecturer is Joseph Bonneau. He's a postdoctoral researcher in computer science at Princeton University. The second lecturer is me, Ed Felton. I'm a professor at Princeton in computer science and in the Woodrow Wilson School. The third lecturer is Arvind Narayanan. He's a computer science professor at Princeton. And fourth, our special guest lecturer is Andrew Miller. He's a PhD student in computer science at the University of Maryland. There will be 11 lectures in total. In this lecture, number one, we're going to do two things. First, we'll introduce some cryptographic primitives that turn out to be necessary for talking about cryptocurrencies. In particular, we'll talk about cryptographic hashes and digital signatures, and we'll talk about some of the ways in which those are used to build cryptocurrencies. And then at the end of the lecture, we'll start talking about cryptocurrencies, and I'll give some examples of simple cryptocurrencies that illustrate some of the design challenges that we need to deal with. I want to apologize for covering the cryptographic material at the beginning. Unfortunately, we have to eat some of our vegetables a little bit in order to lay groundwork for the cryptocurrency stuff. So if you came for the cryptocurrency stuff, let me assure you, first of all, that we will get to it in this lecture, and that having laid the groundwork in this lecture, there's going to be a lot more specifically cryptocurrency-focused material in later lectures. All right, so let's get to it. In segment 1.1, we're going to talk about cryptographic hash functions. We'll talk about what they are and what their properties are. And then later we'll move on and talk about what their applications are. So a cryptographic hash function is a mathematical function, and it has three attributes that we need to start with. First of all, a hash function can take any string as input, absolutely any string of any size. It produces a fixed size output. We'll use 256 bits in this series of lectures because that's what Bitcoin does. And it has to be efficiently computable, meaning given a string, in a reasonable length of time, you can figure out what the output is. So that's a hash function, but we're going to need hash functions that are cryptographically secure. The cryptographic properties of hash functions are a complicated topic in general, but we're going to focus here on three particular properties, and I'll explain in a minute what those are. In particular, that the function is collision-free, that it has a hiding property, and that it's puzzle-friendly. And for each of these, I'll talk about what the property is, what it means, and then I'll talk about why it's useful to have a function that has that property. So first, collision-free. So the first property that we need from a cryptographic hash function is that it's collision-free. And what that means is that it's impossible, nobody can find values x and y such that x and y are different, and yet the hash of x is equal to the hash of y. And so if we look at the operation of the function as depicted by one of these red arrows, here's x and h of x, and here's y and h of y, then nobody can find a situation like this, that you have an x and y that are separate, and yet when you hash them, they hash to the same value. Now, one thing to notice is that I said nobody can find. I didn't say that there is no collision. Because if you think about it, there has to be a collision. Collisions do exist, and to understand why that is, we can use this diagram. Over here on the left, I'm depicting all of the possible inputs to this function, which can be a string of any size. And over here, I have all of the possible outputs, which has to be a string of 256 bits in size. So the right-hand side here, the outputs, there are only 2 to the 256 possibilities. Over here, there are more possibilities. And so if you think that every point over here on the left is going to be mapped by an arrow to some point on the right, you can see that as you go from all the points over here on the left into the right, it has to get crowded. And in fact, that there have to be multiple values over here on the left that map to the same output over here. In fact, in general, there will be a very large number of possible inputs that map to any particular output. So collisions do exist. I said before, nobody can find a collision, and that's the key question. We know collisions exist. The question is, are there any collisions that are findable by regular people using regular computers? Okay. Now, to make things even worse, I said that it has to be impossible to find a collision. Let me tell you how to find a collision, because there's a method that's guaranteed to work. And the method works like this, that we're going to pick 2 to the 130 randomly chosen inputs over on the left cloud of that previous diagram. And if we pick those 2 to the 130 randomly chosen inputs, it turns out there's a 99.8% chance that at least 2 of them are going to collide. And so this is a very simple method for finding a collision. It works no matter what the hash function is. But of course, the problem is that this takes a very, very long time to do. you have to compute the hash function 2 to the 130 times. And that's, of course, an astronomical number. This method works no matter which hash function we're using. There's still a 99.8% probability that this works, and if it doesn't work, just try it again. It'll probably work the next time. But this doesn't really matter. And the reason it doesn't really matter is that this procedure takes 2 to the 130 steps in order to get to that high probability. So we can say something like this. We can say that if every computer ever made by humanity was computing since the beginning of the entire universe up to now, the odds that they would have found a collision is still infinitesimally small. So small that it's way less than the odds that the Earth will be destroyed by a giant meteor in the next 2 seconds, which didn't happen. Okay, so we know how to find a collision, but this method takes too long to matter. The question is there some other method that could be used on a particular hash function in order to find a collision? And that's the question that is harder to answer. Is there a faster way to find collisions? Well, for some possible values of hash functions, of course there are. For example, if our hash function were to simply take the input modulo 2 to the 256, that is, it just selected the last 256 bits of the input, then we would know an easy way to find a collision. One collision would be the values 3 and 3 plus 2 to the 256. So for some possible values of the hash function, it's very easy to find a collision. For others, we don't know. Now, one thing I need to note is that there's no hash function in existence which has been proven to be collision-free. There are just some that people have tried really, really hard to find collisions and haven't succeeded. And so we choose to believe that those are collision-free. Okay. Now, what good does collision freedom do us? If we can assume that we have a hash function that is collision-free, then we can use that hash function as a message digest. And what I mean by that is the following, that if we know that x and y have the same hash, then it's safe to assume that x and y are the same. Because if someone knew an x and y that were different that had the same hash, of course that would be a collision. Since there's not a collision that we know of, then knowing the hashes are the same, we can assume that the values are the same. And this lets us use the hash as a kind of message digest. Suppose, for example, that we had a file, a really big file, and we wanted to be able to recognize later whether another file was the same as the file we saw the first time. Right? So one way to do that would be to save the whole big file, and then when we saw another file later, just compare them. But because we have hashes that we believe are collision-free, it's more efficient to just remember the hash of the original file. Then if someone shows us a new file and claims that it's the same, we can compute the hash of that new file and compare the hashes. If the hashes are the same, then we conclude that the files must have been the same. And that gives us a very efficient way to remember things we've seen before and recognize them again. And of course, this is useful because the hash is small. It's only 256 bits, while the original file might be really big. So hash is useful as a message digest, and we'll see later on in this lecture and in subsequent lectures why it's useful to use hashes as message digests. So the second property that we want from our hash function is that it's hiding. And the property that we want is something like this, that if we're given the output of the hash function, that there's no feasible way to figure out what the input x was. The problem is that this property doesn't exactly hold. And to understand why that's the case, let's look at this example. So here, what we're going to do is an experiment where we flip a coin, and if the result of the coin flip was heads, we're going to return the hash of the string heads, and if the result was tails, we're going to return the hash of the string tails. And now we're going to ask someone who didn't see the coin flip but only saw this hash output to figure out what the string was that was hashed. That, of course, is going to be easy. It's easy in this scenario to find what the input string was. It's easy to find x. You simply compute the hash of the string heads and the hash of the string tails, and you see which one you got. And so in just a couple of steps, you can figure out what x was. So the reason this example failed, that is the reason why an adversary was able to guess what the string was that there were only a couple of possible values of x. And so if we're going to have a hiding property like this, it needs to be the case that there's no value of x which is particularly likely. That is, x has to be chosen from a set that's in some sense very spread out, so that this method for the adversary of just trying all the possible values of x, or just trying a few values of x that are especially likely, is not going to work. So the hiding property that we are going to need to set up is a little bit more complicated. And the way we're going to fix this problem with the common value x, like heads and tails, is we're going to take the x and we're going to put next to it, we're going to concatenate it with it a value r, which is chosen from a distribution that's really spread out. And so this h of r concatenated with x, that means take all the bits of r and put after them all the bits of x. And so what we're going to say is, given the hash of r together with x, that it's infeasible to find x, and that this will be true in the formally stated property that if r is a random value chosen from a distribution that has high min entropy, then given the hash of r concatenated with x, it's infeasible to find x. And what does high min entropy mean? Well, it captures this intuitive idea that r is chosen from a distribution that's really spread out. And what that means specifically is that there's no particular value that r could have had that would occur with more than a negligible probability. So for example, if r is chosen uniformly from among all of the strings that are 256 bits long, then any particular string was chosen with probability 1 in 2 to the 256, which is truly a negligible value. So as long as r was chosen that way, then the hash of r concatenated with x is going to hide x. And that's the hiding property that the hash function will be deemed to have. OK, now let's look at an application of that hiding property. And in particular, what we want to do is something called a commitment. And this is kind of the digital analogy of taking a value, a number, and sealing it in an envelope and putting that envelope out on the table where everyone can see it. Now, when you do that, you've committed to what's in the envelope. But you haven't opened it. It's secret from everyone else. Later, you can open the envelope and get out the value, but it's sealed. So commit to a value and reveal it later. We want to do that in a digital sense. So to be more specific about what is the API that we're going to provide here, the commitment API looks like this, that there are two things you can do. First, you can commit to a message, and that's going to return two values, a commitment and a key. Think of the commitment as the envelope that you're going to put on the table, and the key as a secret key for unlocking the envelope. Then later, you allow someone else to verify, given a commitment and given a key, which you've told them in the meantime, and the message, they can verify that that commitment, key, and message really do go together, and this will return a true or false. Okay, now to seal MSG in an envelope, what we do is we commit to the message, and that returns a commitment and a key, and then we publish the commitment. That's putting the envelope on the table. Now later, to open the envelope, what we're going to do is publish the key and the message that we committed to, and then anybody can use this verify call with the commitment that we published previously, the key and message that we just announced, to check the validity of our opening the envelope. Okay. And the property, of course, we want from this is that it behaves like sealing an envelope. And in particular, the two security properties are these. First, given COM, the commitment, the envelope on the table, that someone just looking at the envelope can't figure out what the message is. The second property is that it's binding, that when you commit to what's in the envelope, you can't change your mind later. That is, it's infeasible to find two different messages such that you can commit to one message and then later claim that you committed to another, and the whole thing will verify. Okay, so how do we know that these two properties hold? Well, first we need to talk about how we're going to actually implement commitments. And the way we're going to implement commitments is like this. That in order to commit to a value message, we're going to generate a random 256-bit value and call it the key. And then we're going to, as the commitment, return the hash of the key concatenated together with the message. And as the key value, we're going to return h of this key. And then later, to verify, someone is going to compute this same hash of the key they were given, concatenated with the message, and they're going to check whether that's equal to the commitment that they saw. Okay, so this is a way of using hash functions both in the commitment and in the verification. So now the security properties, if we go down to the security properties that were at the bottom of the previous slide, and we just plug in the definitions of how we're going to implement this here, that is, this used to say COM, given COM, infeasible to find message, we just plug in what COM is. COM is the hash of key concatenated with message. And similarly down here, this is what happens when we take what was written there before and plug in the definition of verify in COM. Okay, so now what these properties become, the first one is given h of key concatenated with message, it's infeasible to find message. Well, it turns out that that's exactly the hiding property that we talked about before. key was chosen as a random 256-bit value, and therefore the hiding property says that if we take the message and we put before it something that was chosen from a very spread out distribution, like I said, a random 256-bit value, then it's infeasible to find the message. So this is exactly the hiding property. And this one down here turns out to be exactly the collision-free property. So that if someone can find two messages which have the same hash like this, well, then they have an input value here and an input value there that are different, and yet those have the same hash. And so because of the two security properties we've talked about for hashes so far, this commitment scheme will work in the sense that it will have the necessary security properties. OK, so that's the second security property of hashes, that they're hiding, and the application of that is commitments. The third security property we're going to need is that they're puzzle friendly. And this is, again, a little bit more complicated, but let me just go through it a bit by bit. That for any possible output value y that you might want from the hash function, we're going to use y as an output value of the hash later, that if k is chosen from a distribution that has high min entropy, that is, k is chosen randomly from some set that's super spread out, then there's no way to find an x such that the hash of k and x is equal to y. So what this means is basically that if someone wants to target the hash function, if they want it to come out to some particular output value y, that if there's part of the input that is chosen in a suitably randomized way, that it's very difficult to find another value that hits exactly that target. So the application we're going to use of this is we're going to build a search puzzle. And what that means is we're going to build a mathematical problem which requires searching a very large space in order to find the solution, and where there's no shortcuts, a way to find a good solution other than searching that large space. That's a search puzzle. To be more specific, the idea is that if we're given a puzzle ID, which is chosen from some high min entropy distribution, that is some very spread out probability distribution, and we're given a target set y, which someone wants to make the hash function fall into, then we want to try to find a solution x, so that if we hash the puzzle ID together with the solution x, we get a result that's in the set y. So the idea is y is a target range or set of hash results that we want. ID specifies a particular puzzle, and x is a solution to the puzzle. And the puzzle-friendly property here implies that there's no solving strategy for this puzzle, which is much better than just trying random values of x. And so if we want to pose a puzzle that's difficult to solve, that we can do it this way, as long as we can generate puzzle IDs in a suitably random way. And we're going to use that later when we talk about Bitcoin mining. That's the sort of computational puzzle we're going to use. OK, so we've talked about three properties of hash functions and one application of each of those. Now let me talk just very briefly about the particular hash function we're going to use. There are lots of hash functions in existence, but this is the one Bitcoin uses, and it's a pretty good one to use. It's called SHA-256, or SHA-256, and it works like this. Basically, it takes the message that you're hashing, and it breaks it up into blocks that are 512 bits in size. The message isn't going to be, in general, necessarily exactly a multiple of the block size, so we're going to add some padding at the end. And the padding is going to consist of, at the end of the padding, a 64-bit length field, which is the length of the message in bits. And then before that, it's going to consist of a 1-bit, followed by some number of 0 bits. And you choose the number of 0 bits so that this comes out exactly to the end of a block. So once you've padded the message so that its length is exactly a multiple of the 512-bit block size, you then chop it up into blocks, and you then execute this computation. You start with a 256-bit value called the IV. That's just a number that you look up in a standards document. And then you take the IV and the first block of the message. You take those 768 total bits, and you run them through this special function C. The compression function, and out comes 256 bits. You now take that with the next 512 bits of the message, run it through C again, and you keep going. Each iteration of C crunches in another 512-bit block of the message and mixes it in sort of logically to the result. And when you get to the very end, you have consumed all of the blocks of the message plus the padding. The result is the hash. That's a 256-bit value. And it's easy to show that if this function C, this compression function, is collision-free, then this entire hash function will also be collision-free. The other properties are a little bit more complicated, so I won't talk about them here. OK, so we've talked about hash functions. We've talked about what hash functions do. We've talked about 3 properties of hash functions and applications of those properties, and the specific hash function that we use in Bitcoin. In the next lecture segment, we'll talk about ways of using hash functions to build more complicated data structures that are used in distributed systems like Bitcoin. In section 1.2, we're going to talk about hash pointers and their application. A hash pointer is a kind of data structure that turns out to be used a lot in the systems that we're talking about. And a hash pointer is basically a simple thing that we're going to take a pointer to where some information is stored, and we're going to, together with that pointer, store a cryptographic hash of the information. So whereas a regular pointer gives you a way to retrieve the information, a hash pointer is going to let us ask to get the information back. And it's also going to let us verify that the information hasn't changed. So a hash pointer tells us where something is and what its value was. Okay, and we're going to draw a hash pointer in diagrams like this. That we're going to have h of and then an arrow that points to something. So anything drawn like this, think of it as being a hash pointer to this thing. It's a pointer to where it's stored, and it's also the hash of the value that this data had when we last saw it. And we can take hash pointers and we can use them to build all kinds of data structures. So a key idea here, take any data structure, a linked list, a binary search tree or something like that, and implement it with hash pointers instead of pointers as we normally would. For example, here's a linked list that we've built with hash pointers. And this is a data structure that we're going to call a blockchain. So just like a regular linked list where you have a series of blocks and each block has data, as well as a pointer to the previous block in the list, here the previous block pointer will be replaced with a hash pointer. So it says where it is and what the value of this entire previous block was. And we're going to remember the head of the list like this, just as a regular hash pointer. Okay. And a use case for this, for a blockchain like this, is a tamper-evident log. That is, if we want to build a log data structure that stores a bunch of data so that we can add data onto the end of the log, but if somebody goes later and messes with data that is earlier in the log, we're going to detect it. That's what the tamper evidence means. So to understand why a blockchain gives us this tamper evident property, let's ask what happens if an adversary wants to go back and tamper with data later that's in the middle of the chain. Okay, so let's assume that an adversary wants to tamper with this block down here. He wants to change the data here, and he wants to do it in such a way that we, the holders of the hash pointer at the head here, won't be able to detect it. All right, so the adversary changed the contents of this block, and therefore the hash here, which is a hash of this entire block, is not going to match up. Because the hash function is collision-free, it must be the case that the hash of this block is now different. And so we could detect the inconsistency between this data and the hash pointer that we remembered before. Or we could do that unless the adversary also tampers with the hash pointer. If he tampers with this hash pointer, then he makes these two match up. But now he's changed the content of this block. And what that means is that when we come back later and hash the contents of this block, it's not going to match the hash that we remembered before because the contents of the block has changed. And so we're going to detect the inconsistency between the contents of this block and this hash, unless the adversary also tampers with the block over here on the right. But now when he does that, the hash of this block is not going to match the hash that we remembered up here and the hash that we're holding on to. And this the adversary can't tamper with because this is the value that we remembered as being the head of the list. And so the upshot of this is that if the adversary wants to tamper with data anywhere in this entire chain, in order to keep the story consistent, he's going to have to tamper with hash pointers all the way back to the beginning, and he's ultimately going to run into a roadblock because he won't be able to tamper with the head of the list. And so what this means is that just by remembering this hash pointer, we've essentially remembered a kind of hash, a tamper-evident hash of the entire list all the way back to the beginning. And so we can build a blockchain like this containing as many blocks as we want, going back to some special block at the beginning of the list, which we might call the genesis block. And that's a tamper-evident log built out of a blockchain. Now, another useful data structure that we can build using hash pointers is a binary tree. We can build a binary tree with hash pointers, and this is called, in the jargon, a Merkle tree, after Ralph Merkle, who invented it. And the idea is this. Suppose we have a bunch of data blocks which we'll draw across the bottom down here. We're going to take pairs, consecutive pairs of these data blocks, and for these two data blocks we're going to build a data structure here that has two hash pointers, one to each of these blocks. And similarly all the way across. We'll then go another level up, and this block here will contain a hash pointer of these two children down here, and so on all the way back up to the root of the tree. And then just like before, we're going to remember just the hash pointer up here at the head of the tree. And we can then, if we want, traverse down through the hash pointers to any point in the list, and we can make sure that the data hasn't been tampered with. Because just like I showed you with the blockchain, if an adversary tampers with some block down here at the bottom with the data, that will cause the hash pointer that's one level up to not match, so he'll have to tamper with that. And therefore, he'll have to tamper with the hash pointer one level up from there. And therefore, he'll have to tamper with the hash pointer one level up from there. And eventually, he'll get up to the top where he won't be able to tamper with the hash pointer that we've remembered. So again, any attempt to tamper with any piece of data across the bottom will be insured against by just remembering the hash pointer at the top. Now, another nice feature about Merkle trees is that unlike the blockchain that we built before, that if someone wants to prove to us that a particular data block is a member of this Merkle tree, all they need to show us is this amount of data. So if we remember just the root, and someone wants to convince us that this block is in the Merkle tree, they need to show us this block, and we can verify that the hash matches up. And then they need to show us this block, and we can verify that the hash of this matches that. They can show us this block, we verify that the hash of this block matches this hash pointer, and then they show us the data. And just by verifying the hashes up to the root, we can verify that this data block was in the Merkle tree. So that takes about log n items that we need to be shown, and it takes about log n time for us to verify it. And so with a very large number of data blocks in the Merkle tree, we can still prove membership in a relatively short time. Okay, so Merkle trees have various advantages. One advantage, of course, is the tree holds many items, but we just need to remember the one root hash, which is only 256 bits. We can verify membership in a Merkle tree in logarithmic time and logarithmic space. That's nice. And there's a variant, which is a sorted Merkle tree. That's just a Merkle tree where we take the blocks at the bottom and we sort them into some order, say alphabetical, lexicographic order, or numerical order, or some order that we agree on. Now, having done that, once we've sorted the Merkle tree, now it's possible to verify non-membership in a Merkle tree. That is, we can prove that a particular block is not in the Merkle tree. And the way we do that is simply by showing a path to the item that's just before where that item would be and just after where it would be. And then we can say, look, both of these items are in the Merkle tree, they're consecutive, and therefore there's no space in between them. There's nothing in between them, and so the thing that we're trying to prove non-membership of can't be there. All right, so a Merkle tree is a binary search tree built with hash pointers. We can do logarithmic time membership proofs, non-membership proofs if we sort the tree, and it's very efficient. More generally, it turns out that we can use hash pointers in any pointer-based data structure, as long as the data structure doesn't have cycles. If there are cycles in the data structure, then we won't be able to make all the hashes match up. If you think about it, in an acyclic data structure, we can sort of start near the leaves or near the things that don't have any pointers coming out of them, compute the hashes of those, and then work our way back sort of toward the beginning. But in a structure with cycles, there's no end that we can start with and compute back from. So for example, a directed acyclic graph out of hash pointers, and we'll be able to verify membership in that DAG very efficiently, and it will be easy to compute. So this is a general trick that you'll see over and over throughout the distributed data structures and throughout the algorithms that we talk about later in this lecture and in subsequent lectures. In segment 1.3, we're going to talk about digital signatures. This is the second cryptographic primitive along with hash functions that we need as building blocks for the cryptocurrency discussion later on. So a digital signature is supposed to be just like a signature on paper, only in digital form. And what that means is this. What we want from signatures is two things. First, that just like an idealized paper signature, only you can make your signature. but anyone who sees your signature can verify that it's valid. And then the second thing you want is that the signature is tied to a particular document, so that somebody can't take your signature and snip it off one document and glue it onto the bottom of another one. Because the signature is not just a signature, it signifies your agreement or endorsement of a particular document. Okay, so the question is, how can we build this in a digital form using cryptography? So let's get into the nuts and bolts. Here's an API for digital signatures. There are three operations that we need to be able to do. The first one is we need, in the beginning, to be able to generate keys. And so we have a generate keys operation, and we tell it a key size. How big in bits should the keys be? And this produces two keys, SK and PK. SK will be a secret signing key. This is information you keep secret that you use for making your signature. And PK is a public verification key that you're going to give to everybody and that anybody can use to verify your signature when they see it. Okay. The second operation is the sign operation. So the sign operation, you take your secret signing key and you take some message that you want to put your signature on, and it returns SIG, which is a signature. It's just some string of bits that represents your signature. And then the third operation is a verify that takes something that claims to be a valid signature and verifies that it's correct. It takes the public key of the signer, it takes the message that the signature is supposedly on, and it takes the supposed signature. And it just says yes or no, is this a valid signature? Okay, so these three operations, these three algorithms constitute a signature scheme. And I'll note that the first two can be randomized algorithms. The verification won't be, it will always be deterministic. And in fact, if you think about it, generate keys had better be randomized because it ought to be generating different keys for different people. Okay, so the requirements for the signatures at a slightly more technical level are the following two requirements. First of all, that if a signature is, that valid signatures will verify. If a signature is valid, that is, if I sign a message with SK, with my secret key, that if someone then later tries to validate that using my public key and the same message, that will validate correctly. So this says that that signatures are useful at all. But then the second thing you want is that it's impossible to forge signatures. That is, an adversary who knows your public key, who knows your verification key, and gets to see signatures on some other messages, can't forge your signature on some message that he wants to forge it on. And in order to explain this property in a little bit more detail, it's normally formulated in terms of a sort of game that we play with an adversary. So the game, I'll depict it here with this diagram. So over here on the left, you have the challenger, who's a TV judge. And the challenger is going to test a claim by an attacker. The attacker claims that he can forge signatures, and we're going to test that claim, and the judge will pass judgment on it. The attacker here, this guy is actually Whit Diffie, who is one of the inventors of digital signatures, of the concept of digital signatures, and a distinguished cryptographer, so I thought I'd let him play the attacker role here. Okay, so the game works like this. The first thing we do is we use generate keys to generate a secret key, a secret signing key, and a public verification key that match up. Now we give the secret key to the challenger, to the judge, and we give the public key to both parties, both to the challenger and to the attacker. So the attacker only knows information that's public. He only knows the public key. And his mission is going to be to try to forge a message. The challenger knows the secret key, so he can make signatures. Right? Now, if you think about a real-life application, and a real-life attacker would be able to see valid signatures from their would-be victim on a number of different documents. And maybe the attacker could even manipulate the victim into signing innocuous-looking documents, if that's useful to the attacker. So in our game, we're going to allow the attacker to get signatures on some documents of his choice. And we see that in the diagram like this. The attacker is going to send over a message M0 to the challenger, and the challenger is going to sign that message and send the signature back. The attacker can look at that, scratch his head a little bit, and send over another message, M1. The challenger will sign that. And we do that for as long as the attacker wants. The attacker can send over any sequence of messages he wants and get signatures on them. Once the attacker is satisfied that he's seen enough signatures, and we're going to let him see only a plausible number, then he's going to pick some message M that he wants to forge a signature on, and he's going to try to forge a signature. And of course, there's a rule that says that this M, this message that he's trying to forge a signature on, isn't one of the messages that he's already seen. Because it would be really easy for him to send over a valid signature on M0. I mean, we sent him a valid signature on M0 earlier. So he's going to pick some other message that he hasn't seen a signature for already, and he's going to send over what he claims is a signature on that message. And then the question is, can he succeed? So the challenger is going to run the verify algorithm, use the public verification key and on that message and the signature that the attacker provided, and is going to check whether it verifies. And if it does verify, if this returns true, then the attacker wins. The attacker has forged a message. And so this game is what we use to define what it means for a digital signature scheme to have the unforgeability property. And if we want to get really precise, what we say is that the attacker's probability of winning this game is negligible, and that that's true no matter what algorithm the attacker is using. In other words, we're going to say that the signature scheme is unforgeable if, no matter what algorithm the attacker is using, the attacker has only a negligible chance of successfully forging a message. And if we have that property together with the much easier property that valid messages verify, then we have a digital signature scheme that is suitable. Okay. Now, there's a bunch of practical things that we need to do to turn that algorithmic idea into a more practically implementable signature mechanism. For example, the algorithms we talk about are randomized, at least some of them will be, and so we need a good source of randomness. And the importance of this really can't be underestimated. Band randomness will sink you, your algorithm will be insecure. And I'll just point out here that attacks on the source of randomness are a favorite trick of intelligence agencies, and those are the people who know what kinds of attacks are likely to be successful. In practice, there's a limit on the message size that you're able to sign because real schemes are going to operate on bit strings of limited length. The fix to that is simply to use the hash of the message rather than the message itself. That way the message can be really big, but the hash will be only 256 bits. And because hash functions are collision-free, it's safe to use the hash of the message as the input to the digital signature scheme rather than the message. And by the way, a fun trick, which we'll see used later, is that you can sign a hash pointer. And if you sign a hash pointer, then the signature covers or protects the whole structure. Not just the hash pointer itself, but everything it points to and everything it points to. For example, if you were to sign the hash pointer that was at the end of a blockchain, the result is that you would effectively be digitally signing the entire contents of that blockchain. That's a useful trick that we'll see used later. Okay, now let's get into the nuts and bolts. Bitcoin uses a particular digital signature scheme that's called ECDSA. That's the elliptic curve digital signature algorithm, and it's a US government standard. And we won't go into all the details of how ECDSA works. It relies on some extremely hairy math. And trust me, you don't want to see all the details of how that works. You can look it up if you're interested. So we'll skip that. One thing I'll note, though, is with ECDSA, good randomness. I said this before, but I'll say it again because it's really essential. Good randomness is especially essential with ECDSA. If you use bad randomness in generating keys or even in signing, you probably leaked your private key. It stands to reason that if you use bad randomness in generating a key, that the key that you generate is maybe not secure. But it's a quirk of ECDSA that even if you use bad randomness just in making a signature using your perfectly good key, that also will leak your private key, and then it's game over. So we need to be especially careful about this in practice. This is a common mistake. So that completes the discussion of digital signatures as a cryptographic primitive. And then in the next segment, we'll move on and talk about some applications of digital signatures that will turn out to be useful in building cryptocurrencies. In segment 1.4, we'll move on, having covered digital signatures, and talk about a nice trick that we can use that goes along with digital signatures. And the useful trick is this. The idea is to take a public key, one of those public verification keys from a digital signature scheme, and equate that to an identity. That is an identity of a person or an actor in a system. So if you see a signature that verifies correctly, that is, if you see a signature such that you can verify with someone's public key that that is a signature on a particular message, then you can think of that as that public key saying the message. You can literally think of a public key as kind of like an actor or a party in a system, and that they can make statements by signing those statements. And so if you think in that mindset, then this public key is like an identity. It's an actor who can do stuff in the system. And if you think about it then, for someone to speak for PK, that is for someone to be able to make statements that will be seen as coming out of PK's mouth, you have to know the matching secret key, SK. And so if you know the secret key that corresponds to the public key, PK, then you can sign messages with that secret key. And what you're doing essentially is making statements on behalf of that public key. And that means that there is an identity in the system which only you can speak for. And of course, that's what you want an identity to be. Something that one person can speak for or on behalf of that everybody can see. All right. So if we're going to treat public keys as identities, one of the consequences of that is that you can make a new identity whenever you want. If you want to make a new identity, you just do this. You create a new random key pair, SK and PK, by doing the generate keys operation in our digital signature scheme. And we get out SK and PK. PK is then the public name that you can use. That's the name of that identity, what it's called. Although in practice, you'd probably use the hash of PK because public keys are big. But again, we'll leave that aside as a detail. So PK, or the hash of it, is the public name that you use to talk about the identity. And SK, the secret key, is the information that lets you, the person who generated this identity, speak for the identity. You control the identity because only you know the secret key. And if you generated this in such a way that the public key PK looks random, then nobody needs to know who you are. You can generate a fresh identity that looks random, that looks like a face in the crowd, that only you can control. This brings us to the idea of decentralized identity management. That rather than having a central place that you have to go in order to register as a user in a system, you don't need to get a username, you don't need to inform someone that you're going to be using a particular name. If you want a new identity, just make one. Anybody can make a new identity at any time, and you can make as many as you want. If you prefer to be known by 5 different names, no problem, just make 5 identities. If you want to be somewhat anonymous for a while, you can make a new identity, use it just for a little while, then throw it away. All of these things are possible with decentralized identity management, and there's no central point of control, so that you don't have to have anyone who's in charge of it. The system operates in an entirely decentralized way. And this is the way Bitcoin, in fact, does identity. These identities are called addresses in Bitcoin jargon. And so you'll hear the term address used in talking about Bitcoin and cryptocurrencies. But what that really is just a public key or a hash of a public key. It's an identity that someone made up out of thin air as part of this decentralized identity management scheme. Now, the obvious question that arises when you're talking about decentralized identity management and people making up these identities is, how private is this? And the answer is, it's complicated. On the one hand, the addresses that are made up this way are not connected to your real-world identity. You can execute a randomized algorithm. It will make some kind of PK that looks kind of random, and nothing exists initially to connect that to who you are. You can do that in the privacy of your own home. So that's good news if you want to be able to act privately. But the bad news if you want to act privately is that if that address, if that identity is making a series of statements over time, if it's engaging in a series of acts over time, that people can see that whoever this is has done a certain series of actions. And they can start to connect the dots. Gee, this person is acting a lot like Joe. Maybe this person is Joe. And so an observer can link together these things over time and make inferences. And so this balance between, on the one hand, there being no initial tie to real-world identity, and on the other hand, that a pattern of behavior of an address emerging over time, and the question of what can be inferred and which dots can be connected, that gets pretty complicated. And that's really the question of privacy in a cryptocurrency like Bitcoin. And there's a whole lecture about that later on. And so I'm not going to steal the thunder of that lecture. I just want to give you an idea of how decentralized identity makes privacy a complicated question. In segment 1.5, we're going to move from talking about cryptography, and we're going to move on to cryptocurrencies. Now, I know that many of you showed up here for the cryptocurrency stuff, and trust me, there will be a lot more cryptocurrency material in future lectures. Unfortunately, we needed to eat some of our cryptographic vegetables in order to have the background to talk about cryptocurrencies. And now you'll see, when I start talking about cryptocurrencies, how these pieces fit together and why the cryptographic operations like hash functions and digital signatures are actually useful. All right, so in this section, I want to talk about some simplified cryptocurrencies that give us ideas about how systems like Bitcoin work. Of course, it's going to require about 10 more lectures in order to really spill out all of the implications of how Bitcoin works and what that means. But let me talk about some very simple cryptocurrencies to get the discussion started. And first, let's talk about Goofy Coin. Goofy Coin is about the simplest cryptocurrency we can imagine. And it works kind of like this. There are just a couple rules of Goofy Coin. The first rule is that Goofy can create new coins. Goofy can make a new coin whenever he wants, and when he makes a new coin, it belongs to him. So when Goofy makes a coin, it's represented by a data structure like this. Here you have the create coin operation, and there's a unique coin ID that Goofy generated, and then there's a digital signature that was put on it by Goofy, which anyone can verify. So anyone being given this can verify that the signature is valid and that it's a signature of this statement. And new coins belong to Goofy by definition because those are the rules that Goofy made. So that's the first rule. Goofy can create new coins. The second rule of Goofy Coin is that whoever owns a coin can pass it on to someone else. They can spend it. So for example, here we have the coin that I showed you before that Goofy created. And now we're going to take a hash pointer to that coin. And then we're going to create a statement. Goofy's going to make a statement that says, pay this to Alice. Alice is being named by a public key here. Pay to public key Alice the coin that's represented by this hash pointer. And this is also signed by Goofy. Now, Goofy is the one who owned that coin, and so Goofy has to sign any transaction that spends the coin. And once this has happened, now Alice owns the coin. Alice owns the coin, and Alice can prove that she owns the coin because she can present this data structure here, which is validly signed by Goofy and points to a coin that was validly owned by Goofy. And so the correctness of this coin is self-evident in the system. Now Alice can move on, and she can spend the coin as well. So here we have the coin we had before. This is down here at the bottom. We have the creation of the coin signed by Goofy. Now Goofy paid the coin to Alice via this hash pointer, and he signed that. Now Alice is the owner of the coin. Now she can create a statement like this that says, pay this coin to Bob's public key, and here's a hash pointer to the coin. And now Alice signs that. So because Alice was the valid owner of the coin, which we could verify by walking this chain, now we know that this is valid and the coin belongs to Bob. So Bob is now the owner of this coin. So those are all the rules of Goofy Coin. Goofy can create new coins by simply signing a statement that he's making a new coin with a unique coin ID. And then whoever owns a coin can pass it on to someone else by signing a statement saying, pass on this coin to person X. And you can verify the validity of a coin by simply following the chain and verifying all of the signatures along the way. That's Goofy Coin. All right. Now, there's a problem, though. There's a big security problem with Goofy Coin, and we can see it in this structure here. So look at this coin here. This is the coin that Goofy made and then paid to Alice. Alice was the owner of that coin, and there's a problem. Alice paid this coin on to Bob, but now Alice makes another data structure like this, which pays to Chuck the very same coin. And this is signed by Alice. Now, if Chuck doesn't know about this thing up in the upper left, this data structure, let's say Alice just gave that to Bob and didn't tell Chuck. Now, Chuck will look at this and he'll think that this is perfectly valid, and now he's the owner of the coin. Chuck has a valid-looking claim to be the owner of this coin, and Bob has an equally valid-looking claim to be an owner of this coin, and that's a problem because coins are not supposed to work that way. This is called a double spending attack. It's called double spending because Alice is spending the same coin twice. And double spending attacks are one of the key problems that a cryptocurrency has to solve. Goofy Coin does not solve the double spending attack, and therefore Goofy Coin is not secure. So although Goofy Coin is simple and we understand its rules, it won't cut it as a cryptocurrency because it allows double spending. So in order to build a cryptocurrency that is going to be workable, we need to have some solution to the double spending problem. And indeed, the double spending problem is the main design challenge that we face in designing a cryptocurrency. So we need to somehow improve on Goofy Coin, and we'll do that by designing another coin, which I'll call Scrooge Coin. Scrooge Coin is going to be rather like Goofy Coin, except it will solve the double spending problem in a particular way. And this coin was created by Scrooge. Okay, so this is a little bit more complicated in terms of data structures, but here's one of the key ideas, that Scrooge is going to publish a history of all the transactions that have happened. This will be a blockchain, that data structure we talked about before, and it will be digitally signed by Scrooge. So anyone can, and it looks like this, of course. It's a series of blocks, data blocks. Each block will have one transaction in it. This block has the transaction with transaction ID number 73. And it has the contents of this transaction, and then there's a hash pointer to the previous block in the history. Okay, and then Scrooge will take the hash pointer, which represents this entire structure, and he'll digitally sign it and publish it. Now anybody can verify that Scrooge really did sign this hash pointer, and then they can follow this chain all the way back and see what is the entire history of all the transactions in the history of Scrooge Coin as endorsed by Scrooge. Okay. Now I said here that we put one transaction in each block. We do that for simplicity of explanation, but in practice, as an optimization, we'd really put multiple transactions into the same block, as Bitcoin does. So you can bear in mind as I talk about Scrooge Coin that that's the way we'd really do it in practice. So Scrooge publishes this history. What does the history do? Well, the thing the history does for us is it allows us to detect double spending. Because assume Alice owns a coin, and she's going to pay that coin on to Bob. And she's then later going to try to pay that coin on to Charlie. Charlie's going to notice that something is wrong because Charlie will be able to look into the history and see that Alice already paid that coin to Bob. In fact, everyone will be able to see that Alice already paid that coin to Bob. So if she tries to pay that coin to Chuck, then everyone can see that that's a double spend and they'll be able to reject it. Scrooge will reject it, and everyone else will reject it and know that they really shouldn't trust Alice. All right. So in Scrooge Coin, there are two kinds of transactions. The first kind is a create coins transaction, and what it does is create new coins. That's like the operation Goofy could do in Goofy Coin that makes a new coin. But here, we're going to allow multiple coins to be created in one transaction. So here's what a create coins transaction looks like. It has transaction ID number 73, let's say in this case. Its transaction type is create coins, and then down here there's a list of which coins are created. Each coin is going to have a serial number within this transaction, 0, 1, 2, etc. Each coin has a value. It's worth a certain number of Scrooge coins. And each coin has a recipient, which is going to be a public key who gets that coin as it's created. So this transaction type creates a bunch of new coins and assigns them to people as initial owners. Now we're going to have a concept in Scrooge Coin of a coin ID. That refers to a particular coin. So this particular coin here is coin ID 73(0) because it was created in transaction 73 and it was number 0 within that transaction. Similarly, we have 73(1), 73(2), and so on. So every coin in Scrooge Coin has a coin ID that we can use to refer to it. A create coins transaction is always valid. Why is it valid? Well, because Scrooge said so, and they call it Scrooge Coin for a reason. If Scrooge puts this into the history which he signs, then it's valid by definition. We don't need to worry about whether Scrooge is entitled to create coins, just like we didn't need to worry in Goofy Coin about whether Goofy is entitled to create coins. The rules of the system, which were created by Scrooge, simply say that if Scrooge wants to make coins, then that's valid. So anything he puts into the history is valid. The second kind of transaction we're going to talk about is a pay coins transaction. And this is a transaction that consumes some coins and destroys them and creates new coins of the same total value, but which might belong to different people. So over here on the left, we have an example of what a pay coins transaction looks like. This is transaction ID number 73, let's say. Its type is pay coins. We have here a list of the coins that this one consumes. All of these coins are being consumed and destroyed by this pay coins transaction. So we're going to add up the value of all of those coins, and then we're going to create a bunch of new coins, down here 0, 1, and 2, etc., just like before in the create coins transaction. Each one has a value. Each one will belong to a certain recipient. And those new coins had better add up to the same total value as the coins that we consumed. And then at the bottom, we have a set of digital signatures. This transaction has to be signed by everyone who's paying in a coin. So if you're the owner of one of the coins that's going to be consumed in this transaction, then you need to digitally sign the transaction to say that you're really okay with spending this coin. The rules of Scrooge coins say that a paycoins transaction is valid if 4 things are true. First, if the consumed coins are valid, that is, they really were created in previous transactions. Second, that the consumed coins were not already consumed in some previous transaction. That is, that this is not a double spend. Third, that the total value of the coins that come out of this transaction is equal to the total value of the coins that went in. And finally, that the transaction is validly signed by the owners of all of the consumed coins. If all of those things are true, then this paycoins transaction is valid. Scrooge will accept it. He'll write it into the history, into the blockchain, and everyone will see that this transaction has happened. One thing to note about this scheme is that coins are immutable. Coins are never changed, they're never subdivided, they're never combined. All they are is created once in one transaction and then later consumed in some other transaction. But you can get the same effect as being able to subdivide or pay on or combine coins by using transactions. For example, if you want to subdivide a coin, you can just create a new transaction that consumes that one coin and then produces 2 new coins of the same total value. And if you want, you can give those 2 new coins back to yourself. That's a way that you can subdivide a coin that you own. Similarly, you can combine coins or you can pay on a coin, in effect, by just creating a chain of transactions, each of which pass that value on in the form of a new coin to someone else. So although coins are immutable in this system, it has all of the flexibility of a system that didn't have immutable coins. Okay, now we come to the core problem with Scrooge coin. Scrooge coin will work. People can see which coins are valid. It prevents double spending because everyone can look into the blockchain and see that all of the transactions are valid and that every coin is consumed only once. But the problem is Scrooge. Scrooge thinks this is fine, right? Scrooge says, don't worry, I'm honest. But the fact is, if Scrooge starts misbehaving, then we're going to have a problem. Or if Scrooge just gets bored of the whole Scrooge coin scheme and stops doing the things that he's supposed to do, then the system won't operate anymore. And so the problem we have here is centralization. That although Scrooge is happy with this system, we as users of it might not be. So the central technical challenge that we need to solve in order to improve on Scrooge coin is, can we de-Scroogify the system? That is, can we get rid of that centralized Scrooge figure? Can we have a cryptocurrency that operates like Scrooge coin in many ways, but doesn't have any central trusted authority? In order to do that, we're going to need to figure out how to provide the services that Scrooge provides, but do it in a decentralized way, in a way in which no particular party is particularly trusted. That means we're going to need to figure out how everyone can agree upon a single published blockchain that is the agreed upon history of which transactions have happened. We need to figure out how people can agree which transactions are valid and which transactions have actually occurred. And we need to figure out how we can assign IDs to things in a decentralized way. If we can solve all of those problems, then we can build a currency that is very much like Bitcoin, which is like Scrooge coin, but without a centralized party. But in order to do that, it's going to take a few more lectures, and we hope you'll stick around and watch them. Thanks.
Hello, and welcome to the second lecture, which is going to be all about decentralization in Bitcoin. Now, in the first lecture, you saw a lot of the crypto basics that underlie Bitcoin, and we ended with a simple currency that we called Scrooge coin that seems to achieve a lot of what we want in a ledger-based cryptocurrency, except for one big glaring problem, which is that it relies upon the centralized authority called Scrooge. And we ended with the question of, how do we de-Scroogify this currency? How do we go to a decentralized version of this? That's what we're going to see today. What I find cool about this is that the way in which Bitcoin achieves decentralization is not purely technical, but it's a combination of technical and clever incentive engineering. And at the end of this lecture, you should have a really good appreciation for how this happens, and a lot of the magic or the mystery of Bitcoin should become clear to you, and how it works, and why it's secure, and what makes it tick. So it turns out that decentralization is an important concept, not just for Bitcoin, but in fact, this notion of competing paradigms of centralization versus decentralization plays out in a variety of different digital technologies. To understand Bitcoin's decentralization, I want to start with the caveat that decentralization almost always is not all or nothing. Almost no system is purely decentralized or purely centralized. And a good example of this is email, which is a decentralized system fundamentally, I would say. It's based on a standards-based protocol, SMTP, but what has happened, especially in the last decade or so, is that we see a dominance of a few different webmail providers, which are sort of centralized service providers, and this might be a good model for understanding what might be happening to Bitcoin. So with that, let's delve into some of the technical aspects of Bitcoin's decentralization, and I would break this down into at least 5 different questions. Questions like, who maintains this ledger of transactions? Who has authority over which transactions are valid? Who creates new Bitcoins? And in fact, other questions like, who determines how the rules of the system change, and how do Bitcoins acquire exchange value? So these are all components of decentralization of the Bitcoin protocol, more or less. And the first 3 of these are going to be the questions that we will consider in this lecture. And when I say, how is Bitcoin decentralized, what I mean encompasses the first 3 of these meanings. And I want to emphasize that there are aspects to decentralization beyond the protocol. That includes things like Bitcoin exchanges, where you can convert Bitcoin into other currencies. It includes things like wallet software and a variety of other service providers. And so even though the underlying protocol is decentralized, these services that develop on top of it may be centralized or decentralized to varying degrees. And just to drive home this point, let me show you 3 different aspects of Bitcoin and where they fall on the centralization-decentralization spectrum. First, there's the peer-to-peer network. And this aspect of Bitcoin, I would say, is the closest thing to purely decentralized. Why is that? Because anybody can run a Bitcoin node, and there's a fairly low barrier to entry. You can go online, you can download a Bitcoin client yourself. It requires a lot of disk consumption on your computer, but basically you can run that on your laptop or your PC yourself. And currently there are several thousand Bitcoin nodes, and so this really resembles a peer-to-peer decentralized system. But that's not the only component of Bitcoin. There's also Bitcoin mining, which we'll study later in this lecture. And Bitcoin mining is technically also open to anyone, but it turns out that it requires a very high capital cost. It's a consequence of how the system happens to have evolved. And because of this, there has been a high centralization or a concentration of power in the Bitcoin mining ecosystem. And the community frequently sees this as quite undesirable. So this aspect of Bitcoin is not quite as decentralized as one might want it to be. And here's a third aspect, updates to the software. And this really gets to how and when the rules of the system change. And once again here, one can conceptually imagine that everybody running a Bitcoin node will look at the Bitcoin specification and maybe even create their own software. And again, you have a purely decentralized system. But of course, that's not how it works in practice. The core developers are really trusted by the community, and they have a lot of power when it comes to determining what Bitcoin software each of these nodes will run on their computer. So we've talked in a generic manner about centralization and decentralization. Let's now talk at a bit more technical level about Bitcoin and decentralization. And a key word that's going to come up again and again here is consensus, specifically distributed consensus. So what am I talking about here? At a technical level, the key challenge that you have to solve to build a distributed eCash system is called distributed consensus. And this is a class of protocols that's been studied for decades in the computer science literature. But intuitively, you can think of it as our goal being to decentralize Scrooge coin, which is the hypothetical currency that we saw in the first lecture. So as I said, there's decades of research in computer science on these consensus protocols, and the traditional motivating application for this is reliability in distributed systems. What do I mean by that? Imagine you're in charge of the backend for a company like Google or Facebook. These companies typically have thousands or even millions of servers, which form a massive distributed database that records all of the actions that happen on the system, like users' comments and likes and posts and so on. So when a new commit, let's say, comes in, the way it'll be recorded is that there might be 10 or 15 different nodes in that massive backend that might contain copies of this action. Now, what the server needs to make sure is that that commit either gets recorded in all copies of that database or none of them. If for some reason, because some of these nodes might be faulty, the action gets recorded in none of the databases, it's okay. You can go back to the user and say, there was a problem saving your post, would you please try again? On the other hand, if some of the copies of the database saved it and others didn't, then you'd be in a lot of trouble because you'd have an inconsistent database. So this is the key problem that motivated the traditional research on distributed consensus. And you can sort of see the similarities to Bitcoin here, but we're going to talk in a bit more detail about the similarities and differences. So that was the traditional motivating application, but we can also imagine that if we achieved a distributed consensus protocol, and we were able to use that to build a massive global scale distributed key value store that maps arbitrary keys or names to arbitrary values, then that will enable a lot of applications. For example, a distributed domain name system, which is simply a mapping between human understandable domain names to IP addresses. Or a public key directory, which is a mapping between user email addresses, let's say, to their public keys. Or even things like stock trades, because this distributed database, instead of keeping track of who's paid whom how much money, would keep track of who's transferred what units of which stock to whom. And the cool thing about this is that now that Bitcoin has solved the distributed consensus problem in a certain sense that we'll try to understand in this lecture, we can also go ahead and try to think about solutions to all of these other related problems. And in fact, there are many altcoins. And altcoins, we'll have several more lectures about altcoins, but very briefly, altcoins are systems built on Bitcoin-like principles to achieve perhaps slightly different goals. Sometimes currency systems, sometimes not currency systems, such as one of these applications. And so, given that we can solve distributed consensus now, and given that we can build a global distributed key value store, it enables a lot of these other cool applications. Okay, let's go to a technical definition now. The technical definition of distributed consensus is really quite simple. Imagine that there is a fixed number n of nodes or processes, and each of these nodes has some input value. And then a consensus protocol happens, and the two requirements on this consensus protocol are that the protocol should terminate, and all correct nodes should decide on some value, the consensus value. Right? And I say correct nodes because some of the nodes might be faulty or even outright malicious. And the second requirement is that this value that they agree upon cannot be an arbitrary value, but it should be a value that was proposed as input by at least one of these correct nodes. So it's really that simple, but let's try to see what this might mean in the context of Bitcoin. So to understand how distributed consensus could work in Bitcoin, let's start with the reminder that Bitcoin is a peer-to-peer system, right? So what I mean when I say that Bitcoin is a peer-to-peer system is that when Alice wants to pay Bob, what she does is she's going to broadcast a transaction to all of the Bitcoin nodes that comprise the peer-to-peer network. And you can see here the structure of the transaction. This is similar to Goofy Coin that we saw in the first lecture. And what a transaction is going to have is it's going to have Alice's signature, which the other nodes need in order to know that it really in fact came from Alice. It's going to have Bob's public key, which also acts as his address at which he wants to receive Bitcoins. And further, it contains a hash. What is this hash? Recall this notion of hash pointers that we saw in the first lecture. So this hash is a way for Alice to link together this transaction or this coin to her receipt of this coin from someone else previously. Right? So those are the things that are contained in this data structure that we call a transaction, and she's going to broadcast that to all of the Bitcoin peer-to-peer nodes. And notice something funny here. Bob's computer is nowhere in this picture. Now Bob, if he wants to be notified that this transaction did in fact happen and that he got paid, he might want to run a Bitcoin node that's one of these peer-to-peer nodes in order to listen in on the network and be sure that he's received that transaction, but his listening is not in fact necessary for him to receive the funds. The Bitcoins will be his whether or not he's running a node on the network. So given this peer-to-peer system, what is it exactly that the nodes might want to reach consensus on? Well, given that a variety of users are broadcasting these transactions to the network, what everybody wants to reach consensus on is exactly which transactions were broadcasted and the order in which these transactions happened, right? So what does that mean specifically? How consensus could work in Bitcoin is that at any given time, all the nodes in the peer-to-peer network would have a sequence of blocks of transactions that they've reached consensus on. So recall that in Scrooge coin, for optimization purposes, for efficiency, we put transactions into blocks and we link these blocks together on a blockchain. So we're utilizing a similar principle here. We could do consensus on transactions one by one. That would be okay. It would just be inefficient. So instead, we do consensus on a block by block basis. So at any given point, all these nodes in the peer-to-peer network would have the sequence of blocks that they've agreed upon already. And each node would then have a set of outstanding transactions that it has heard about. So recall that for these transactions, consensus has not yet happened. And so almost by definition, each node might have a slightly different version of the outstanding transactions that it's heard about. The peer-to-peer network is not perfect, so some node may have heard about a transaction, but not other nodes. So given that we have the setup, what could happen is that you have the sequence of blocks that everybody has agreed upon. A block is just a series of transactions. And now there are these, let's say, these three nodes in the system, each of whom proposes, each of whom has an input, the set of outstanding transactions that it's heard about. And they execute together some consensus protocol. And for the consensus protocol to succeed, you can select any valid block, even if it's a block that was proposed by only one node. And for a block to be valid, all of these transactions have to have the right crypto signatures and so on. So you could select any of these valid blocks and the consensus protocol would still be okay. If some transaction somehow didn't make it into this particular block that gets chosen as the result of a consensus protocol, it could just wait and get into the next block. Right? So maybe this green block gets selected, it now gets added to the consensus blockchain, and then the protocol proceeds in rounds. So if you took the traditional theory of distributed consensus and applied that to Bitcoin, this is the sort of system that you might end up with. Now this has some similarities to how Bitcoin works, but it's not exactly how Bitcoin works. And why is that? And the reason for this is simple. Doing things this way is a really hard technical problem for a variety of reasons. There are some obvious ones. Nodes might crash and nodes might outright be malicious. But also because the network is highly imperfect. It's a peer-to-peer system. Not all pairs of nodes are connected to each other. There could be faults in the network because of poor internet connectivity and so on. And finally, there's going to be a lot of latency in the system because all of these things happen over the internet. They're not even within a single data center or something like that. And one particular consequence of this high latency is that there is no notion of global time. What does this mean and why is this important? It means that not all nodes can agree to a common ordering of events simply based on observing timestamps. It just doesn't work like that. So you can't possibly design your protocol by saying things like, take the node that sent the first message in step 1 and have that node do something in step 2. You just can't work like that because not all nodes will agree on which message was sent first in the first step of the protocol. So this really puts serious constraints on what sorts of algorithms you can really put into your consensus protocols. And in fact, because of these constraints, a lot of the literature on distributed consensus is somewhat pessimistic, and many impossibility results have been proved. I'm just going to name a couple of these in case you want to look them up, but I won't go into too much detail. One impossibility result that's very well known and pretty simple to understand is called the Byzantine generals problem. And a much more subtle one, known for the names of the authors who first proved it, is called the Fisher-Lynch-Patterson impossibility result. Under some conditions, which include the nodes acting in a deterministic manner, what they proved is that consensus is impossible even with a single faulty process. So despite these impossibility results, there are a few well-known protocols, and Paxos is probably one of the better known. And what Paxos does is it makes certain compromises. What it gives you is that it never produces an inconsistent result, which would be really bad, but it accepts the trade-off that under certain conditions, albeit rare ones, the protocol can get stuck and fail to make any progress. But here's the interesting thing. These impossibility results were, they were proved in a different model. They were intended to study distributed databases. And this model doesn't carry over that well to this is a setting that Bitcoin operates under. So what these results really tell us more about the model than about the problem, in fact. And What Bitcoin does is that it violates a lot of the assumptions that go into these models, and because of that, consensus in Bitcoin ironically works better in practice than in theory. And what this really means is that the theory that was developed for a different set of problems needs to catch up in order to be able to say really interesting things about Bitcoin. But nevertheless, that theory is quite important because, for example, it can help us predict unforeseen attacks and really be able to come to strong guarantees on the nature of consensus and security in Bitcoin. So what are these different assumptions? What are some things that Bitcoin does differently? Well, first of all, it introduces the idea of incentives. And this is very different from any previous system for distributed consensus. And this is only possible in Bitcoin because it is a currency and you can use that currency to give incentives to the participants for acting honestly. And so Bitcoin doesn't quite solve the distributed consensus problem in a general sense, but it solves it in the context of a currency system. And the other thing that it does differently is that it really embraces the notion of randomness. And what I mean by that is one of the things it does is it does away with the notion of a specific starting point and ending point for consensus. Instead, consensus happens over a long period of time, about an hour in the practical system, but even at the end of that time, you're not 100% sure that a transaction or a block that you're interested in has made it into the consensus blockchain. Instead, as time goes on, your probability goes up higher and higher, and the probability that you're wrong in making an assumption about a transaction goes down exponentially. So that's the kind of inherently probabilistic guarantee that Bitcoin gives you, and that's why it's able to completely get around these traditional impossibility results on distributed consensus protocols. So let's now dig into the technical details of Bitcoin's consensus algorithm. And while we're looking at that, we should keep in mind that Bitcoin does all of this without nodes having any persistent long-term identities. And this is yet again a difference from how traditional distributed consensus algorithms operated. And if nodes did have identities, it would make things a lot easier for a couple of reasons. One is a pragmatic reason. It would allow you to put into your protocol things like, now the node with the lowest numerical ID should take some step or something like that. So that's a simple pragmatic reason, which already, if nodes are completely anonymous, becomes harder to do. But a much more serious reason for nodes to have identities is for security, because if nodes were identified and it weren't trivial to create new node identities, then we could make assumptions like, let's say that less than 50% of the nodes are malicious, and we could derive security properties out of that. So for both of these reasons, the consensus protocol in Bitcoin is a bit harder. But why is it exactly that Bitcoin nodes don't have identities? Well, it's for a couple of reasons. One is that if you're in a decentralized model, in a peer-to-peer system, there is no central authority to give identities to nodes and verify that they're not creating new nodes at will. And in fact, the technical term for this is a Sybil attack. Sybils are just copies of nodes that a malicious adversary can create to look like there are a lot of different participants, when in fact all those pseudo-participants are really controlled by the same adversary. The other reason is that pseudonymity is inherently a goal of Bitcoin. Even if it were possible or easy to establish identities for all nodes or all participants, we wouldn't necessarily want to do that. So Bitcoin doesn't give you strong anonymity guarantees out of the box, in that the different transactions that you make can probably be linked together, but at the same time, nobody is forcing you to put your real-life identity, like your name or IP address or anything like that, in order to participate in the peer-to-peer network and in the blockchain, and that's an important property. So what we can do instead is we can make a weaker assumption. And I kind of want you to take a leap of faith with me here, that this weaker assumption is something that is going to be feasible. And I'm going to make this assumption here and later show you how this is actually accomplished. And what this weaker assumption is that we're going to assume that there is some ability somehow to pick a random node in the system. And a good motivating analogy for this is a lottery or a raffle or any number of real-life systems where tracking and verifying people and giving them identities and verifying those identities is pretty hard. And so what we do in those contexts is we might give them tokens or tickets or something of that sort, and that then enables us to later pick a random token ID and call upon that person. So we're going to do something similar with respect to these Bitcoin nodes and further assume for the moment that this token generation and distribution algorithm has enough smarts so that if the adversary is going to try to create a lot of Sybil nodes, together all of those Sybils just get one token, so the adversary is not able to multiply his power that way. So let's make this assumption for now, and let's see what becomes possible if we make this assumption. Here's the key idea. What becomes possible under this assumption of random node selection is something called implicit consensus. So what is implicit consensus? In each round, and there are going to be multiple rounds, each round corresponding to a different block in the blockchain. In each round, a random node is somehow selected, magically for the moment, and this node gets to propose the next block in the chain. There is no consensus algorithm, there is no voting. This node simply unilaterally proposes what the next block in the blockchain is going to be. But what if that node is malicious? Well, there is a process for this, but it is an implicit one. Other nodes will implicitly accept or reject that block. And how will they do that? If they accept that block, they will signal that acceptance by extending the blockchain starting from that block, or if they reject that block, they will extend the chain by ignoring that block and starting from whatever was the previous latest block in the blockchain. And technically, how is that implemented? Recall that each block contains a hash of the block that it extends, and this is the technical mechanism that allows nodes to signal which block it is that they're extending. So given this is what the overall consensus algorithm in Bitcoin is going to look like. Now, this is a little bit simplified, and the reason it's simplified is, again, that I'm assuming sort of this magic random node selection process. But except for that simplification, this is pretty close to how Bitcoin actually works. So whenever Alice wants to pay Bob, she will create a transaction, and she will broadcast it to all of the nodes. And any one of these nodes is constantly listening to the network and collecting a list of outstanding transactions that have not yet made it into the blockchain. At some point, one of these nodes is going to be randomly called upon to propose the next block. It's going to round up all of the outstanding transactions that it's heard about and propose that block. Now, presumably that node was honest, but it could also be a malicious node or a faulty node and propose a block that contains some invalid transactions. Invalid transactions are those that don't have the right crypto signature or where the transaction is already spent. In other words, an attempt to double spend. So if that happens, other nodes are going to signal their acceptance or rejection of the block, as we saw on the last slide, by either including the hash of this latest block in their next block, or ignoring this block and including the hash of whatever was the previous block that they considered to be valid. Right. So now let's try to understand why this consensus algorithm works. And the way I like to understand this is, instead of asking why this works, let's try to ask, how can a malicious adversary try to subvert this process? So let's look at that for a second. So here we have a couple of blocks in the blockchain. Assume that this extends to the left a long way back, all the way to what is called the genesis block. But here I'm only showing you a couple of blocks in the blockchain. And that pointer that you see over there is a block referring to what is the previous block that it extends by including a hash of that previous block within its own contents. So a malicious attacker, let's call her Alice. What might she try to do? Can she simply steal Bitcoins belonging to another user at a different address that she doesn't control? Now, even if it is now Alice's turn to propose the next block in this chain, she cannot steal other users' Bitcoins. Why? Because she cannot forge their signatures. So as long as the underlying crypto is solid, she's not able to simply steal Bitcoins. Another thing she might try to do is, if she really, really hates some other user, Bob, then she can look at Bob's address and she can decide that any transactions originating from Bob's address, she will simply not include them in any block that she proposes to get onto the blockchain. In other words, she's denying service to Bob. So this is a valid attack that she can try to mount. But luckily, it's nothing more than a little annoyance, because if Bob's block doesn't make it into the next block that Alice proposes, he will just wait another block until an honest node gets the chance to propose a block, and then his transaction will get into that block. So that's not really a good attack either. So the only one that we're really left with for what a malicious node can try to do here is called a double spending attack. So how might a double spending attack work? To understand that, let's assume that Alice is a customer of some online merchant or a website run by Bob who provides some online service in exchange for payment in Bitcoins. Let's say he allows the download of some software. So here's how a double spending attack might work. Alice goes to Bob's website and decides to buy this item, pays for it with Bitcoins, and what that means in technical terms is that she's going to create a Bitcoin transaction from her address to Bob's address. She broadcasts it to the network, and let's say that some honest node creates the next block, listens to this transaction, and includes it in that block. So what is going on here? So there is this block that was created by an honest node that contains a transaction that represents a payment from Alice to the merchant Bob. By C subscript A, I mean a coin belonging to Alice, and that is now being sent to Bob's address. Let's zoom into this in a little bit more technical detail. A transaction, as we saw earlier, is a data structure that contains Alice's signature here and an instruction to pay to Bob's public key, and also a hash. What is this hash? This hash represents a pointer to the transaction where Alice in fact received that coin from somebody else, and that must be a pointer to a transaction that was included in some previous block in the consensus chain, so visually it's going to look something like this. Let's pause for a second here because there's something subtle going on. There are at least two different types of pointers in this diagram that I've showed you. There's in fact a third one corresponding to Merkle trees, but we're not going to look at that at the present moment. But these two types of pointers that I refer to are blocks that include a hash of the previous block that they're extending, and transactions that include a pointer to whatever the previous transaction where the coin came from. Right, so this is the situation, and this block was now generated by an honest node, and now let's assume that the next time a random node is called, that node is a malicious node controlled by Alice. Right, so this is the blockchain as it stands right now. Bob has already looked at this blockchain, decided that Alice has paid him, and has allowed Alice to download the software or whatever it is that she was buying on his website. Right. So as far as Bob is concerned, he's satisfied, the transaction is completed. Alice has now received her goods in exchange for the payment. Now what might happen is if Alice now gets to propose the next block, she could propose a block that looks like this. Ignores altogether this valid block over here, and instead contains a pointer to the previous block. And furthermore, it's going to contain a transaction that contains a transfer of coins, of Alice's coins, to another address, A prime, that's also controlled by Alice. So this is a classic double spend pattern. What is going on here is Alice now creates a new transaction that transfers that coin instead of to Bob's address to another address owned by her. And visually it's going to look like this. This is a completely different transaction, also with a hash pointer going back to the same transaction referred to earlier. Right? So this is what an attempt at a double spend looked like. And how do we know if this double spend attempt is going to succeed or not? Well, that depends on whether this green transaction here or this red transaction is going to ultimately end up in the long-term consensus chain. So what determines that? That is determined by the fact that honest nodes are always following the policy of extending the longest valid branch. So now, which of these is the longest valid branch? You might look at this and say, aha, the first one is the longest valid branch, not the second one, because it's a double spend attempt. But here's a very subtle point that I want you to appreciate. From sort of a moral point of view, this transaction in green and the transaction in red might look very different because based on the explanation that I've given you, the first one is an attempt by Alice to pay Bob, whereas the second one is an attempt by Alice to defraud Bob and pay coins back to herself. But from a technological point of view, these two transactions are completely identical. The nodes that are looking at this really have no way to tell which one is the legitimate transaction. I'm putting legitimate in air quotes because it's a moral judgment that we apply to it. It's not a technical distinction. Versus which one is the attempted double spend. It could easily be the other way around. Now, nodes often follow a heuristic of extending the block that they first heard about on the peer-to-peer network, but it's not a solid rule, and in any case, because of network latency, that could easily be the other way around. So now there is at least some chance that the next node that gets to propose a block will extend this block instead of this one. Or it could be that even if it's an honest node, Alice could try to bribe that node or try to subvert the process in a variety of ways. So for whatever reason, without going too much into the details, let's say that the next node extends the block with the red transaction instead of the green one. What this means is that at this point, the next honest node is much more likely to extend this block instead of this one because now this has become the longest valid chain. So let's say that after one more block, the situation looks like this. Now it's starting to look pretty likely that this double spend has succeeded. In fact, what might happen is that this ends up the long-term consensus chain, and this block gets completely ignored by the network, and this is now called an orphan block, and this is an example of a successful double spend. So now let's look at this whole situation from Bob the merchant's point of view. And understanding how Bob can protect himself from this double spending attack is really going to be a key part of understanding Bitcoin security. So let's look at what happened here again. We have a couple of blocks in the blockchain. And at this point, Alice broadcasts a transaction that represents her payment to Bob. And so Bob is going to hear about it on the peer-to-peer network right here, even before the next block gets created. And so Bob can do something even more foolhardy than what he did in the previous slide, which is that as soon as he hears about the transaction on the peer-to-peer network, he can complete the transaction on the website and allow Alice to download whatever she's downloading. That's called a zero confirmation transaction. Or he could wait until the transaction gets one confirmation in the blockchain, which means that at least some node has created a block and has proposed this transaction, and that has gone into the blockchain. But as we saw earlier, even after one confirmation, there could be an attempt at a double spend. So let's say that this actually happens. If, as in the previous slide, the double spend attempt succeeds, what Bob should do is to realize that the block that he thought represented Alice paying him has now been orphaned, and so he should abandon the transaction. Instead, if it so happens that despite this double spend attempt, the next block that's generated turns out to extend the block that he's interested in. Now he sees that his transaction has two confirmations in the blockchain. Now he gets a little bit more confidence that his transaction is going to end up on the long-term consensus chain. So let's say there's one more, and now there are three confirmations. In general, the more confirmations your transaction gets, the higher the probability that it is going to end up on the long-term consensus chain. Because if you recall the honest node's behavior, that they will always extend the longest valid branch that they see, the chance that this one is going to catch up to this longer branch is now very minuscule, especially if only a minority of the nodes are malicious. Right? Because typically, the only reason that this double spend attempt block would be extended at this point is if the next node to be picked randomly was a malicious node, and then you'd need another malicious node and then another for this shorter branch to then become the longer branch. In general, the double spend probability decreases exponentially with the number of confirmations. So if the transaction you're interested in has received k confirmations, then the probability that this other transaction is going to end up on the long-term consensus chain goes down exponentially as a function of k. And the most common heuristic that's used in the Bitcoin ecosystem is that you wait for 6 confirmations. There is nothing really special about the number 6. It's just a good trade-off between the amount of time you have to wait and your guarantee that the transaction you're interested in ends up on the consensus blockchain. So let's recap what we saw here. Protection against invalid transactions, that is, protection against a malicious node simply making up a transaction to steal someone's bitcoins, is entirely cryptographic, but it is enforced by consensus, which means that if a node does attempt that, then the only reason that that transaction won't end up in the long-term consensus chain is because a majority of the nodes are honest and will treat that transaction as invalid. On the other hand, protection against double spending is purely by consensus. Cryptography has nothing to say about this, and true transactions that represent a double spending attempt kind of look identical from the perspective of signatures and so on, but it's the consensus that determines which one will end up on the long-term consensus chain. And finally, you're never 100% sure that a transaction you're interested in is on the consensus branch, but this exponential probability guarantee is pretty good. After about 6 transactions, there's virtually no chance that, that you're going to go wrong. So in the previous section, we got a basic look at Bitcoin's consensus algorithm and a good intuition for why we believe that it's secure. But recall that at the beginning of the lecture, I told you that Bitcoin's decentralization is partly a technical mechanism and partly clever incentive engineering. So far, we've mostly looked at the technical mechanism. Now let's talk about the incentive engineering that happens in Bitcoin. I asked you to take a leap of faith with me earlier in assuming that we're able to pick a random node, and perhaps more problematically, that at least 50% of the time this process will pick an honest node. But of course, this assumption of honesty is quite problematic, especially if there are financial incentives for participants to subvert this. Then why would we expect any node to be honest, really? So what we want to ask is, can we give nodes an incentive for behaving honestly? Let's look at this with respect to the picture we've been looking at. This is the long-term consensus chain, and this block contains an attempt to double spend. We can ask, can we penalize somehow the node that created this block? But this is problematic for a number of reasons, including the fact that nodes don't have identities, and so there's no way to go after them to penalize them. So instead, let's flip the question around and ask, can we reward the nodes that created all these blocks that did end up on the long-term consensus chain? Well, again, sort of the same problem. We don't have node identities, so we can't mail them cash to their home addresses. If only there were some sort of digital currency that we can use to incentivize them, a decentralized one perhaps. You probably see where I'm getting at. In other words, we're going to use Bitcoins in order to incentivize the nodes that created these blocks. So how are we going to do that? Well, so far, everything that I've said is just an abstract algorithm for achieving distributed consensus. Now we're going to break out of that model. What I'm going to say now is specific to the fact that what we're achieving through this distributed consensus process is in fact a currency. And we're going to incentivize these nodes by paying them in units of this currency. So how do we do that? There are in fact two separate incentive mechanisms in Bitcoin. And the first one is called the block reward. So what is the block reward? It's just this. According to the rules of Bitcoin, the node that creates each block gets to include a special transaction in that block, and that special transaction is a coin creation transaction. And this node can also choose the recipient address of this transaction. So of course that node will typically choose an address belonging to itself as the recipient of this coin creation transaction, thereby paying itself. It's sort of, you can think of it as a payment in exchange for the service of creating that block to go onto the consensus chain. In fact, the value of this coin creation transaction has an interesting property. It's currently fixed at 25 Bitcoins, but it actually halves every 4 years. We're now in the second period. For the first 4 years of Bitcoin's existence, it was 50 Bitcoins. Now it's 25, and it's going to keep halving. This has some interesting consequences. We'll come back to that in the next slide. But let me ask you this. It appears, based on what I've said here, that this node gets the block reward regardless of whether it proposes a block with only valid transactions or it behaves maliciously. So how are we actually providing any incentives for honest behavior via this block reward? But think about this. Well, how will this node sort of get to collect its reward? That will only happen if this block ends up on the long-term consensus branch, because that's the only case in which this coin creation transaction will be considered valid, because the coin creation transaction is not special. It's just like every other transaction. It's only valid if it ends up on the consensus chain. So that's the incentive mechanism here. It's very subtle, but it's a very neat trick. And so it incentivizes nodes to behave honestly, or at the very minimum, it incentivizes nodes to behave in a way that they think other nodes are going to agree with in creating the next blocks of the blockchain. So that's the first incentive mechanism. Let's come back to this point now, this weird sort of halving phenomenon that we see here. And this can be best illustrated graphically. Here I'm going to show you a graph of time on the x-axis versus the total number of Bitcoins in circulation. And this over here was the first period where each block resulted in 50 new Bitcoins being created. And roughly at the end of last year, that block reward halved from 50 to 25. And you can see that every 4 years, extending well into the future, the slope of this curve is going to keep halving. And this is a geometric series, and you might know that it means that there is a finite sum. And in fact, there is a total finite supply of Bitcoins. And if you add up all these numbers, it works out to 21 million based on the rate of new block creation, which I'm going to get to in a second. Also worth noting is that this is the only way in which new Bitcoins are created. There is no other coin generation mechanism, and that's why this is a final and total number, as the rules stand now at least, for how many Bitcoins there can ever be. And this new block creation reward is actually going to run out. So that sounds a bit weird. Does that mean that the system will stop working and become insecure because nodes no longer have the incentive to behave honestly? Well, not quite, because this is only the first of two incentive mechanisms. There is quite another incentive mechanism called the transaction fee. And what is a transaction fee? So the creator of any transaction, not the creator of a block, but the creator of a transaction, when Alice is paying Bob, what she can do is she can choose to make the output value of that coin less than the input value. And the way that all the nodes interpret this difference, according to the rules of Bitcoin, is that it's a transaction fee. And whoever creates the block that first puts that transaction into the blockchain gets to collect that transaction fee. So if you're a node that's creating a block that contains, say, 200 transactions, then the sum of all those 200 transaction fees accrues to you and to the address that you put into that block. Of course, this transaction fee is purely voluntary, like a tip, but we expect, based on our understanding of the system, that as the block reward starts to run out, it'll become more and more important, almost mandatory, for nodes to put a transaction fee into their transactions in order to get a reasonable quality of service. And to a certain degree, this is already starting to happen now. But precisely how the system will evolve, it really depends on a lot of game theory, which hasn't been fully worked out yet. So that's an interesting area of open research in Bitcoin. So now we've acquired an understanding of how the nodes that create these blocks are incentivized to act honestly or follow the protocol. And so if we address a few more of these remaining problems, we'll be all set to have a really good understanding of how Bitcoin achieves decentralization. What are these remaining problems? Well, one of them, the first major one, is the leap of faith that I asked you to take, which is that somehow we can pick a random node. And the second is that we've created a new problem by giving nodes these block rewards and incentives, which is that you could easily get into a free-for-all where everybody wants to run a Bitcoin node in the hope of capturing some of these rewards. And a third one is an even trickier version of this problem, which is that an adversary might create a whole different number of Sybil nodes in order to really try to subvert this consensus process. So number 3 is sort of a trickier version of number 2. It turns out that all of these problems are related, and all of them have the same solution. And that solution is called proof of work. So what is proof of work? Here's the key idea. Instead of picking a random node, we do something a little bit different, which is we approximate selecting a random node by instead selecting nodes in proportion to a resource that we hope that nobody can monopolize. What does that mean? Well, if that resource that we're talking about is computing power, then it's a proof of work system where we somehow select nodes in proportion to their computing power. Alternately, it could be in proportion to ownership of the currency, and this is a legitimate alternate model. It's not used in Bitcoin, but it's been proposed and it's used in a lot of alternatives to Bitcoin, and that's called proof of stake, which we'll see in a later lecture. But let's come back to proof of work. Let's try to get a better idea of what this means. Selecting nodes in proportion to their computing power, another way to understand this is that we're allowing nodes to compete with each other by using their computing power. And that will result in nodes automatically being picked in that proportion. So those are two equivalent ways to view proof of work. You can also think of a third way, which is that we're making it moderately hard through proof of work to create new identities. So it's sort of a tax on identity creation and on the Sybil attack. This may all appear a bit vague, so let me actually go ahead and show you what is the exact proof of work system that's used in Bitcoin, and that's going to make things a lot clearer. So here it is. It's called hash puzzles, and what this means is that in order to create a block, the node that proposes that block is required to find a number, a nonce, such that when you put together in the block the nonce, the previous hash, and the list of transactions that comprise that block, and take the hash of this whole long string, then that hash output should be a number that is very small, that falls into this small target space here in relation to this very large space that is the output space of that hash function. Let's look at it one more time. As we looked at it earlier, normally a block contains a series of transactions that you're proposing. In addition, a block also contains a pointer to the previous block, as we saw, and a pointer is just a string in this context. But in addition here, we're requiring that a block also contain a nonce. And why is this? And the idea is that we want to make it moderately difficult to, in fact, find a nonce that satisfies this required property, which is that hashing the whole block together, including that nonce, is going to result in a particular type of output. And so we believe that if the hash function is secure, then the only way to succeed in solving this hash puzzle is to just try enough nonces one by one until you get lucky. So specifically, if this target space were just 1% of the overall output space, you would have to try about 100 nonces before you got lucky. And if this hash function were to behave essentially randomly, only 1 in 100 nonces will result in an output that falls within this target space. In fact, the size of this target space is not nearly as high as 1% of the output space. It's much, much smaller than that, which we'll get to in a second. But fundamentally, this is the computational problem that a node is required to solve in order to produce the block. Now, this notion of hash puzzles and proof of work completely does away with the requirement for somebody somehow to pick a random node. Instead, nodes are simply all the time independently competing to solve these hash puzzles. And once in a while, one of them will get lucky and will find a random nonce that satisfies this property. And that node then gets to propose the next block. That's how it's completely decentralized. There is nobody deciding which node it is that gets to propose the next block. So let's look at it in a little bit more detail now. There are 3 properties that I want to show you, essential properties of this proof of work function, of this hash puzzle. And the first is that it needs to be quite difficult to compute. I said moderately difficult, but what I mean by moderately difficult, as of today, and you'll see why it varies with time, it's about 10 to the 20 hashes per block that you need to compute. So the size of the target space is only 1 over 10 to the 20 of the size of the output space of this hash function. Right, so if you look at it in terms of the amount of computing that your laptop needs to do, for example, this is simply a humongous and infeasible number. And because of this, only some nodes even bother to compete in this block creation process. And this is what is known as Bitcoin mining, basically the process of repeatedly trying and solving these hash puzzles. And we call these nodes miners. And because of how capital intensive this process is, this goes back to what I said at the beginning, that even though technically anybody can be a miner, there's been a lot of concentration of power or concentration of participation in the mining ecosystem. So that's the first property of these proof of work puzzles. The second property is that we want this cost to be parameterizable. It's not a cost that is fixed over all time. And the way that that's accomplished is that all the nodes in the Bitcoin peer-to-peer network will automatically recalculate the target, that is the size of the target space as a fraction of the output space, every 2 weeks. And they do it in such a way that they maintain this invariant, which is that the average time between any 2 successive blocks produced globally in the overall Bitcoin network is about 10 minutes. So let's think about what this means. What this means is that if you're a miner and you've invested a certain fixed amount of hardware into Bitcoin mining, but the overall mining ecosystem is growing, more miners are coming in or they're deploying faster and faster hardware, that means that over a 2-week period, slightly more blocks are going to be found than expected. And so nodes will automatically readjust the target. And so the amount of work that you have to do to be able to find a block is going to increase. So if you put in a fixed amount of hardware investment, the rate at which you find blocks is actually dependent upon what other miners are doing. So there's a very nice formula to capture this, which is that the probability that any given miner, Alice, is going to win the next block is equivalent to the fraction of global hash power that she controls. Which means that if she has mining hardware that's about 0.1% of total hash power, she will compute roughly 1 in every 1,000 blocks. So why does this readjustment happen? Why do we want to maintain this 10-minute invariant? Well, the reason is simple. If blocks were to come very close together, then there would be a lot of inefficiency, and we would lose the optimization benefits of being able to put a lot of transactions, as it currently stands, several hundred transactions in a single block. If you went down from 10 minutes to 5 minutes, it would probably be okay. And there are a lot of discussions about if we're doing an altcoin now, what is the block latency that we should have? But everybody agrees that the block latency should be a fixed amount. It cannot be allowed to go down without limit. And that's why you have this automatic target recalculation property. Now, because of the way that this cost function and proof of work is set up, it allows us to reformulate our security assumption. Here's where we finally depart from the leap of faith that I asked you to take several slides ago. Instead of saying that somehow the majority of nodes are honest, in a context where nodes don't even have identities and not being clear about what that means, we can now state crisply that a lot of attacks on Bitcoin are infeasible if the majority of miners weighted by hash power are following the protocol or are honest. And the reason for that is if a majority of miners weighted by hash power are honest, because of this competition for proposing the next block, this will automatically ensure that there is at least a 50% chance that the next block to be proposed at any point is coming from an honest node instead of a malicious one. Let's now look at the consequences of the fact that solving hash puzzles is probabilistic. Why is it probabilistic? Because nobody can predict which nonce is going to result in solving the hash puzzle. The only way to do it is to try nonces one by one and hope that one succeeds, right? And so this process is called mathematically Bernoulli trials. I won't go into detail on that, but you can look it up. But typically nodes try so many nonces that a discrete probability process called Bernoulli trials can be well approximated by a continuous probability process called a Poisson process. And the end result of all of that is that the distribution, the probability density function of the time to find the next block by any node in the network globally looks something like this. It's called an exponential distribution, but really the upshot is that there is some small probability that if a block has been found now, the next block is going to be found very soon, or within a few seconds, or within a minute. And there's also some small probability that it will take a long time, maybe an hour, to find the next block. But overall, the network automatically adjusts the difficulty so that the interblock time is maintained at an average long term of 10 minutes. Right. So this is a graph that shows how frequently blocks are going to be created by the entire network, not caring about which miner this is coming from. If you're a miner specifically interested in how quickly you're finding blocks, what does this probability density function look like? Well, it's going to have the same shape, but it's just going to have a different scale on the x-axis. Again, it can be represented by a nice equation. For a specific miner, the mean time to find a block, given that you've just found a block, is going to be 10 minutes divided by the fraction of hash power that you control. So again, if you have 0.1% of the total network hash power, you're going to find blocks once every 10,000 minutes, which is several days. And so not only is your mean time between blocks going to be very high, the variance of the time between blocks found by you is also going to be very high. And this has some important consequences that we're going to be looking at in later lectures. So now let's turn to the third important probability of this proof of work function, which is that it's actually trivial to verify that a node has computed proof of work correctly. What does that mean? Even if it takes a node on average 10 to the 20 tries to find a nonce that succeeds in finding the right property of the hash function, that nonce must be published as part of the block, so it's trivial for any other node to look at the block contents, hash them all together, and verify that the output is less than the target. So this is an important property because, once again, it allows you to get rid of centralization. You don't need any centralized authority verifying that miners are doing their job correctly. Any node or any miner can instantly verify that a block found by another miner satisfies this proof of work property, and thereby they can be sure that this miner put in a lot of computing power into finding that block. Let's now look at mining economics, because we've said that it's quite expensive for miners to be in operation because finding a single block takes computing about 10 to the 20 hashes. At the same time, we've also seen that the block reward is about 25 bitcoins, which is quite a lot of money. So it really boils down to an economics question of whether or not it's profitable for a miner to mine. But we can write down a simple equation that represents what the inputs into this decision are. Fundamentally, the mining reward that the miner gets is in terms of the block reward and transaction fees. The miner asks himself whether that's bigger than or less than their total expenditure, which is the hardware and electricity cost. In fact, Bitcoin mining is so expensive in terms of electricity that that becomes a significant portion of the cost and not just the upfront cost of the hardware. And if the rewards are greater than the costs, then the miner profits. If not, the miner incurs a loss. But there are some complications to this simple equation. The first is that, as you may have noticed, the hardware cost is a fixed cost. It's an upfront cost, whereas the electricity cost is a variable cost that is incurred over time. Another complication is that remember that a reward that the miner gets depends upon the rate at which they find blocks, which depends on not just the power of their hardware, but in fact, more accurately, as the ratio of the power of their hardware as a fraction of the total global hash rate. So that makes it more complicated as well. Another complication is note that the costs that the miner incurs are in terms of dollars or whatever currency that they're using, whereas they're rewarded in terms of bitcoins that are created or bitcoins that are transaction fees. So this equation is really going to depend on what the exchange rate of Bitcoin is doing at any given time. And finally, so far we've assumed that the miner is interested in honestly following the protocol, but it could be the case that the miner could deploy some other mining strategy instead of always finding the next block that extends the longest valid branch. And so this equation doesn't capture all the nuances of the different strategies that the miner can employ. So even though we can write down the simple equation, actually analyzing what it makes sense for miners to do is a complicated game theory problem, and we don't have simple answers to that. Okay, so now we've obtained a pretty good understanding of how Bitcoin achieves decentralization. Let's put it all together now and do a little bit of a recap and understand some high-level points in order to get an even better understanding. So what I'm going to do is I'm going to do a very quick recap of several of the major aspects of Bitcoin that we've learned so far. Let's start from identities. As we've learned, there are no real-world identities required to participate in the Bitcoin protocol. Any user can create a pseudonymous key pair at any moment, any number of them. And when Alice and Bob want to make a transaction, when Alice, for example, wants to know what address Bob wants to get paid at, that's not part of the Bitcoin protocol. That needs to be through some other process, for example, on Bob the merchant's website. So given these pseudonymous key pairs as identities, transactions are basically messages that are broadcast to the Bitcoin peer-to-peer network that are instructions to transfer a coin from one address to another. And a coin really is just a chain of transactions to the extent that we can call anything in Bitcoin an actual coin, and this is something we'll see in much more detail in future lectures. And so this peer-to-peer network that we've looked at, its goal is to propagate all new transactions to all the Bitcoin peer nodes, as well as new blocks to the Bitcoin peer nodes, but it's just going to do sort of the best effort that it can. The real security of the system doesn't come from the perfection of the peer-to-peer network. In fact, the underlying assumption that the network is in fact quite unreliable. But instead, where the security comes from is from the blockchain and the consensus protocol that we spent a lot of time looking at. So what it means for your transaction to be in the blockchain is that it achieves a lot of confirmations. It's not a fixed number. 6 is a commonly used heuristic, but the more confirmations your transaction has received, the more blocks are found that extend the block that contained your transaction, the more certain you can be that your transaction was part of the consensus chain. And now, often there are going to be a variety of orphan blocks. These are blocks that don't make it into the consensus chain. This could represent an invalid transaction or a double spend attempt. It could simply represent the fact that there is latency in the network, and two miners competing to solve this proof of work puzzle simply ended up finding new blocks within just a few seconds of each other. And so both of these blocks were broadcast nearly simultaneously onto the network. So another subtle point here is that if Alice and Bob are two different miners, and Alice has 100 times as much computing power as Bob, what that means is not that Alice will always win the race against Bob to find the next block, but instead, Alice and Bob have a probability ratio of finding the next block in the proportion 100 to 1. So in the long term, Bob will find, on average, 1% of the blocks that Alice does. So those are some of the basics of blockchain and consensus and where the security of the system really comes from. And finally, we looked at hash puzzles and mining. Miners are a special type of nodes that bother to compete in this game of creating new blocks, and they're rewarded for their efforts in terms of bitcoins. And we expect that miners are going to be typically somewhere near the economic equilibrium of the expenditure that they incur in terms of hardware and electricity being somewhere equal to the rewards that they obtain in terms of the new block creation reward and the transaction fee-based rewards. So that's a broad recap of the system. Let me show you in a pointed way how deeply this notion of distributed consensus permeates Bitcoin. Now, in a traditional currency, consensus does come into play in a certain limited extent, which is we have a consensus process around what is the exchange rate of the currency. You can make a rough analogy to consensus in distributed systems. And that is certainly true in Bitcoin as well. We need consensus around the value, the exchange rate of Bitcoin, but consensus goes much deeper in Bitcoin than in other, say, fiat currencies. In fact, you need consensus around state, which is what the blockchain accomplishes, that is a record of which transactions are valid or which transactions have even happened. So even the idea of how many Bitcoins you own is subject to consensus. What it means when I say I own a certain amount or number of Bitcoins is that I mean that the Bitcoin peer-to-peer network, as recorded in the blockchain, considers me, the sum total of all my addresses, to own a certain number of Bitcoins. That is sort of the ultimate nature of truth in Bitcoin. So ownership of Bitcoins is nothing more than other nodes thinking that I own a certain number of Bitcoins. And finally, we need consensus about the rules of the system, because occasionally the rules of the system have to change. There are things called soft forks and hard forks, and we're going to see a little bit more detail of this in later lectures. Now, I want to show you another subtle idea, which is very tricky. And it's this very neat idea of bootstrapping that I really found intriguing the first time I encountered it. And so I want to share this with you. So what do I mean by bootstrapping? I mean the tricky interplay between three things in Bitcoin. And what are these three things? Let's start from the notion of security of the blockchain. So obviously, we want the blockchain to be secure for Bitcoin to have to be a viable currency. But what is necessary for the blockchain to be secure? What this means is that an adversary shouldn't be able to overwhelm the consensus process, shouldn't be able to create a lot of nodes and take over 50% or more of the new block creation. But when will that be true? What is a prerequisite for that? A prerequisite for that is having a healthy mining ecosystem made up of largely honest protocol-following nodes. So that's a prerequisite for security of the blockchain. But what's a prerequisite for that? When can we be sure that a lot of miners will put a lot of computing power into participating in this hash puzzle solving competition? Well, they're only going to do that if the exchange rate of Bitcoin is pretty high. Why is that? Because they receive rewards denominated in Bitcoins, whereas their expenditure is in dollars. So the more the value of the currency goes up, the more incentivized these miners are going to be. But what ensures a high and stable value of the currency? That can only happen if users in general, people who want to buy Bitcoins, have trust in the security of the blockchain. Because if they believe that the network could be overwhelmed at any moment by an attacker, then Bitcoin is not going to have a lot of value as a currency. So you have this interlocking interdependence between these three things. Right? So the existence of each of these is predicated on the existence of another. So one might flip that around and imagine at the beginning, during Bitcoin's creation, when none of these three things existed, when there were no miners other than what we believe to be Nakamoto himself or whoever the creator was running the mining software, and when Bitcoin didn't have a lot of value as a currency, and when the blockchain was in fact insecure because there was not a lot of mining going on, and so anybody could easily overwhelm this process. How do you go from there, not having any of these three properties, to having all three of them. And that is what I mean by bootstrapping. And it's this very tricky process of how all of these three characteristics were acquired by the Bitcoin system in an interdependent manner with each other. And this was, of course, fueled by a lot of media attention as well, because the more people hear about Bitcoin, the more they're going to get interested in mining. And the more they get interested in mining, the more confidence people will have in the security of the blockchain, because there's now more mining activity going on, and so on and so forth. And so Bitcoin went from having none of these properties to now having, in some large measure, all three of these properties. And that's the interesting bootstrapping feature of Bitcoin. And every new altcoin that wants to succeed also has to somehow solve this problem of pulling itself up by its bootstraps. Okay. Let me leave you now with one final thing, which is that in order to understand consensus and what it's responsible for and what it's not responsible for, a good way to do that is to ask ourselves what would happen if consensus failed and there were in fact a 51% attacker somehow who controls 51% or more of the mining power in the Bitcoin network. So let's see what happens in that case, and let's list a whole variety of things, possible bad things that we think might happen. And let's ask ourselves, which of these are possible for a 51% attacker? First of all, can this attacker steal coins from an existing address? Well, you might guess that the answer is no, because stealing from an existing address is not possible unless you subvert the cryptography. It's not enough to subvert the consensus process. This is a bit tricky. Let's follow through this line of argument. Let's say that this 51% attacker creates an invalid block that contains an invalid transaction that represents stealing bitcoins from an existing address that the attacker doesn't control and transferring them to his own address. Now this attacker can pretend that that's a valid transaction and pretend that that's a valid block and keep building upon this block and even succeed in making that the longest branch, but the other honest nodes are simply not going to accept this invalid block and are going to keep mining based on the last valid block that they found in the network. So what will happen is that there will be what we call a fork in the chain. Now imagine this from the point of view of the attacker trying to spend these invalid coins and send them to some merchant Bob and buy something in exchange. Now Bob will presumably be running a Bitcoin node himself, and that will be an honest node, and that node is going to say, oh, this might be the longest branch, but it's not a valid branch, because it contains an invalid transaction because the signatures didn't check out. And so it's going to simply ignore this longest branch because it's an invalid branch. And because of that, subverting consensus is not enough. You have to subvert cryptography to steal coins from an existing address. So we conclude that this attack is not possible for a 51% attacker. By the way, in saying all of this, I should note that this is all somewhat hypothetical, somewhat a thought experiment, because if there were, in fact, actual signs of a 51% attack, what will probably happen is that the developers will notice this and will try to react to it, and will update the Bitcoin software, and we might expect that the rules of the system of the P2P network might change in some form to make this attack more difficult to launch, but we can't quite predict that, so we're working in a simplified model where a 51% attack happens, but other than that, there are no changes or tweaks to the rules of the system. Okay, let's move on. Can the attacker suppress some transactions? Let's say there is some user, say Carol, whom the attacker really doesn't like, and the attacker knows some of Carol's addresses and wants to make sure that no coins belonging to any of those addresses can possibly be spent. Is that possible? Well, let's think about this. The attacker, since he controls the consensus process of the blockchain, can simply refuse to create any new blocks that contain transactions from one of Carol's addresses, and can in fact also refuse to build upon blocks that contain such transactions. And the attacker will be successful at that. However, the attacker cannot prevent these transactions from even being broadcast to the peer-to-peer network, because the peer-to-peer network doesn't depend on the blockchain, doesn't depend on consensus, and we're assuming that the attacker doesn't fully control the network. So the transactions are still going to find a way to reach the majority of nodes. So even if the attacker tries this attack, it will be very clear that that attack is happening because the peer-to-peer network will still receive these transactions. Okay, what about this one? Can the attacker change the block reward? Can the attacker start pretending that the block reward is, instead of 25 bitcoins, 100 bitcoins or something like that? Well, this sort of corresponds to changing the rules of the system, and because of a reasoning similar to what we applied for stealing bitcoins from an existing address, this is also not possible because the attacker doesn't control the copies of the Bitcoin software that all of the honest nodes are running. So that's also not possible. Finally, let's ask ourselves if the attacker can somehow destroy confidence in Bitcoin. Well, let's imagine what would happen if there were a variety of double spend attempts and a behavior of not extending the longest valid branch and other such attempted attacks. Then people are going to look at this and decide that Bitcoin is no longer acting as a decentralized ledger that they can trust. And so people will simply lose confidence in the currency, and we might expect that the exchange rate of Bitcoin is going to plummet. In fact, if there is a 51% attacker, and this is known, even if the attacker is not necessarily trying to launch any attacks, it's possible that this might happen. So this we can classify as not only possible, but in fact likely that a 51% attack of any sort will simply destroy confidence in the currency. And this last one is in fact the main practical threat if a 51% attack were ever to materialize. None of these others really, considering the amount of expenditure that the adversary would have to put into attacking Bitcoin and achieving a 51% majority, really makes sense from a financial point of view to try any of these other attacks. Great. So now, hopefully, you've obtained a really good understanding of how decentralization is achieved in Bitcoin, and understood identities, understood transactions, understood the peer-to-peer network, understood the blockchain and consensus, understood hash puzzles and mining. So you should be at a really good point now, and a good launching point for understanding a lot more of the subtle details and nuances of Bitcoin, which we're going to start seeing in the next few lectures. So the next lecture is going to be by Joe Bonneau, where he will address a lot of questions that take off from the point where we've left off in this lecture. The first is, how do we get from consensus to currency? So this is an assumption that I've already made in this lecture. Not only are we solving a distributed consensus problem, but also we're treating the result of distributed consensus as a currency in order to incentivize participants. But a lot of details are missing. What exactly does it mean to be paid in Bitcoin? How does that happen? How are those transactions represented, and so on? We're going to look at that. We're going to look at what else can we do with consensus. I hinted at this a little bit, but it turns out that Bitcoin offers a lot in addition to just doing consensus. It has a whole scripting language, so there are a lot of interesting things to see there. And so Joe is going to take it from there in the next lecture. Thank you.
Welcome to the third lecture in our series on Bitcoin. This lecture is going to be all about the mechanics of Bitcoin at a fairly low level. So whereas in the first two lectures we've talked at a relatively high level, in this lecture we're going to be trying to give it to you as real as possible. So look at real data structures, real scripts, try to learn the details and language of Bitcoin in a precise way to set up everything that we want to talk about for the remainder of the course. So in some ways this will be the most challenging lecture because a lot of details are going to be flying at you. It's also one of the most real where you're really learning the specifics and the quirks that make Bitcoin what it is. So to recap where we left off last time, the Bitcoin consensus mechanism gives us an append-only ledger. So a data structure that we can only write to, and once data is written, it's there forever. And there's a decentralized protocol for establishing consensus about the value of that ledger. And the miners who perform that protocol are validating transactions, so making sure that transactions are well formed, that there aren't double spends, and that this thing can function as a currency. Although it's kind of funny because we assumed that a currency existed to motivate these miners. So in this lecture we'll be looking at the details of how we actually build that currency to make the miners make this whole process happen. All right, so we'll start by looking at transactions in Bitcoin. Transactions are really the fundamental building block which the whole currency is going to be based on. So remember, we have this ledger. The ledger is append only, so as time goes on, we just add more and more units to it. We're going to take a simplified model here, where instead of having blocks, we just have individual transactions being added to the ledger one at a time. So how can we build a currency this way? So the first model you might think of, which is actually a lot of people's mental model for how Bitcoin works that we'll look at first, is that you'd have an account-based system. So you can add some transactions that create new coins and credit them to somebody. And then later you can transfer them and you just have a transaction that would say, we're moving 17 coins from Alice to Bob. That will be signed by Alice to authorize the transaction. And that's all the information that would be contained. Now backing this up, there would be some state that says that after Alice received 25 coins in the first transaction and then transferred 17 coins to Bob in the second transaction, Alice would have an account that is left with 8 Bitcoins. So now after that transfer from Alice to Bob, we can add some more transactions to the ledger. We'll say that Bob pays some Bitcoins to Charlie, Charlie pays some coins to Alice. And at this point, each participant, Alice, Bob, and Charlie, has an account with a different value in it, and those values are going to mutate each time we add a new transaction. Now the downside of this system, if we add a new transaction at the bottom here, is that we have to remember what the account balance is for each participant to figure out if this transaction is valid or not. Does Alice have the 15 coins that she's trying to transfer to David here? So sure enough, looking at this just with your naked eye, it's fairly hard to tell to do the mental arithmetic to figure out if Alice has enough money to transfer to David here. And in fact, to figure this out, you'd have to look backwards in time forever to see every transaction affecting Alice and whether or not her net balance at the time that she tries to transfer 15 coins to David is greater than 15 coins. Okay, so to tell if this transaction is valid or not, we have to figure out whether or not Alice has the 15 coins that she's trying to transfer to David. And to figure that out, we might have to look backwards forever to the beginning of time at every transaction that's ever involved Alice. Every time Alice has sent or received coins, we need to find all of those transactions and add them up to see if she really has the 15 coins that she's trying to transfer to David. And of course, we can make this a little bit more efficient with some data structures that track Alice's balance after each transaction. But that's going to require a lot of extra housekeeping besides the blockchain itself. And that's why Bitcoin isn't based on an account-based model like this. Instead, Bitcoin uses a ledger that just keeps track of transactions. So how does that work? So this is a transaction-based ledger, which is very close to Bitcoin. So now transactions explicitly specify a number of inputs and a number of outputs. And transactions also each have a unique identifier. So we'll start with transaction 1, which has no inputs, because this is new currency being created, and an output of 25 coins going to Alice. And again, since this is a transaction where new coins are being created, there's no signature required here. Now, let's say that Alice wants to send some of those coins over to Bob. Well, now she has to explicitly refer to the previous transaction where these coins are coming from. So the input to this transaction will be output index 0 from transaction 1, which we can see from the very previous transaction in the log was a transaction that assigned 25 Bitcoins to Alice. And now there are two outputs of this transaction. One of them is 17 coins to Bob, and one of them is 8 coins to Alice. And of course, this whole thing is signed by Alice so that we know that Alice actually wants to do this transaction. And now you might ask, why does Alice have to send money to herself here? She's taken the 25 coins that were assigned to her in transaction 1. She only wanted to pay 17 to Bob, and she has to have a new output where 8 coins are sent back to herself, possibly to a different key, but to herself. So this is what's called a change address. And the design here is that you always completely consume the output of a previous transaction. So there's no way to say I only need 17 coins from that previous output. You have to say I'm using all 25 coins from the previous output, but since you want to keep some, you just have a second output that sends some of the coins back to yourself, which is called a change address. Now, let's say that we keep going with this system, and now we add a new transaction, and we ask ourselves again, is this new transaction valid? Now it's much easier to look at the blockchain and figure out whether or not this transaction is valid, because we know exactly which input to look at. So we just need to go to transaction 2, output 1, and verify that there's enough money there and that it hasn't been sent already. And of course, we can look back and say, yes, that second output of transaction 2 went to Alice with 8 coins. Therefore, it's enough to cover the outputs of this transaction. It's a finite backward scan to check for the validity. And we implement this with hash pointers. So again, each transaction has a unique ID. In reality, they're not serial numbers like this. It's the hash of the block. And each transaction actually gets its specific ID as well, which is the hash of the transaction. And now it's basically just following one pointer to figure out whether or not there's enough money to cover the desired outputs in the new transaction. Now conceptually, you could say maybe this isn't that much different than just maintaining a separate data structure which tracked account values for each person. But the nice thing is that now this data structure is embedded within the data in the blockchain itself. So some other things that we can do quite easily here, we can merge value. So let's say there's 2 different transactions that send some money to Bob, 17 coins in transaction 1 and 2 coins in transaction 2. Bob might say, I'd like to have one transaction I can spend later where I have all 19 coins. So this is pretty easy. You just create a new transaction that has 2 inputs now and only 1 output, so all of those coins go to Bob. And you've combined the 2 previous transactions into one that Bob can then spend later. Similarly, we can do joint payments pretty easily. So let's say that Carol and Bob both want to pay David. We can have a transaction with 2 inputs that are actually owned by 2 different people and combine the value and pay all 8 coins to David. And the only extra thing here is that since the 2 outputs that are being claimed here are owned by 2 different people, we're going to need 2 separate signatures, one by Carol and one by Bob. So conceptually, that's really all there is to it, to a Bitcoin transaction. And let's look at what it looks like at the low level. So again, one of the goals of this lecture is going to be to show you the real data structure, the real deal of what Bitcoin looks like. And here it is. Now, this isn't exactly what a Bitcoin transaction looks like. This is a representation of it that is pretty printed. It looks kind of like JSON. In reality, there's a compact binary format that this gets compiled down to that's not human readable, but this is very, very close to the actual low-level transaction. So there's 3 parts. There's some metadata, there's a series of inputs, and a series of outputs. So we'll start with the metadata. So there's some housekeeping information, which is the size of the transaction, the number of inputs, and the number of outputs. Pretty straightforward stuff. There's the hash of the entire transaction, which, as I said, will serve as a unique ID for the transaction to let us do hash pointers. And then there's this funny lock time parameter, which I'll come back to later. The transaction inputs is just an array of inputs that all have the same form. The inputs specify a previous transaction specifically, so they have the hash of the previous transaction or a hash pointer to it, and the index of which output from that transaction you're actually claiming. And then there's a signature. So remember that we have to sign to show that we actually have the ability to claim those previous transaction outputs. And now the outputs have just 2 things. They have a value, so each output can have a different value. The sum of all the outputs has to be less than the sum of all the inputs. And then there's this funny thing that looks like what we want to be the recipient address. So each output is supposed to go to a specific person or to a specific public key. And there is some stuff in there that looks like it's the hash of a public key. But there's also some other stuff that looks like a script. And in fact, it is a script, and we'll talk more about that very soon. Okay, so like we said, each transaction output doesn't just specify a simple public key, it actually specifies a script. So what do I mean by that? What is a script and why do we use scripts? In this section we're going to talk about what the Bitcoin scripting language is and why script is used instead of simply assigning a public key. Okay, so to understand scripts, I think the easiest way is by an example. And we'll take as an example the most common script in Bitcoin, which is to redeem a previous transaction by signing with the correct public key. So this is what the output address would look like in that case. The output address is really a script. And in this case, the script is going to have 4 instructions. So what happens to this script? Who runs it? How does this script indicate who has the ability to spend these coins? The secret is that the input address is also a script. So that's a bit of script that you combine with the output address. You simply concatenate them, and that gets you one script that has to run successfully in order to claim a Bitcoin. So traditionally, these two scripts are called script sig and script pub key, and that's because in the simplest case, the output script just specifies a public key, and the input script specifies a signature with that public key. When a transaction is being validated, the two scripts get pasted together, they get run, and if the concatenated script can run without any errors, this is considered a valid transaction. So where did this scripting language come from? It doesn't really have a proper name. It's just called script, or the Bitcoin scripting language, and it was built specifically for Bitcoin. It was probably most inspired by a language called Forth, which is an old stack-based simple programming language. But you don't need to understand Forth to understand Bitcoin scripting. The key design properties here were to have something that was quite simple, quite compact, but yet had support for pretty sophisticated cryptography. So there are special purpose instructions to compute hash functions and to compute signatures and verify signatures. And this is a stack-based language. And you may have never seen a stack-based language before in your life, but I'll explain on the next slide what that means and why that was chosen. So there are a lot of limits here that are important to keep in mind. In particular, there are no loops in the Bitcoin scripting language. Every instruction is executed exactly once in a linear manner. So if you look at a script, just based on the number of instructions in the script, you know exactly how long it might take to run and how much memory it could use. So this is not a Turing-complete language. It doesn't have the ability to compute arbitrarily powerful functions, and this is by design because the miners have to run these scripts, which are submitted by arbitrary participants in the network, so you don't want to give them the power to submit a script that might have an infinite loop or might run forever. And since it's not a Turing-complete language, we don't have the halting problem. You can look at any Bitcoin script and be sure that it's going to terminate within a finite number of steps, which is just the number of instructions that are in that script. Okay, now the fun part. We're going to look at a specific Bitcoin script and exactly how it's executed. This is the same example as before. This is the most common script in Bitcoin. A script where the sender of coins simply specifies the public key of the recipient, and the recipient of the coins, to redeem them, has to specify a signature using that specified public key. So the first two instructions in this script are simply data instructions, like I said, and these are the signature and the public key used to generate that signature. And these were specified by the recipient in that script sig component or the input script. So executing data instructions is easy in a stack-based language. If you see data, you just push it onto the stack. And that's the only interaction with memory that you have in a stack-based programming language. There's no variables, there's only a stack, so the only thing you can do to write data to memory is to push it onto the stack. So after we've pushed those two values onto the stack, we're going to start executing the second half of the script, which was specified by the sender of the coins. So this is the script pub key component of the script. And now we're going to start to actually manipulate some of those values on the stack. So this duplicate instruction, opdup, says simply take the value that's on the top of the stack, pop it off, and then write 2 copies back to the stack. So we're just going to duplicate that public key. The next instruction, hash 160, says take the top value on the stack and compute a cryptographic hash of it. So this top value is going to be converted from the public key into a hash of the public key. Now we're going to do one more push of data onto the stack. And this data, remember, was specified by the sender of the coins. So this is the public key that the sender specified had to be used to generate the signature to redeem these coins. So now at the top of the stack we have two values. We have the hash of the public key as specified by the sender, and the hash of the public key that was actually used by the recipient when trying to claim the coins. And we'll just run this equal verify command, which just says, are the two values at the top of the stack equal? If they aren't, an error is going to be thrown and the script will stop executing. But we'll assume that they are. We'll assume that the recipient of the coins actually did use the correct public key. That instruction will consume those two data items that are at the top of the stack. So now we're left with two data items on the stack, a signature and a public key. And we've already checked that the public key was the right public key that was specified by the sender of these coins. And now we want to check that the signature is actually valid. So this is where the power of the Bitcoin scripting language really comes into play. There's one instruction here that lets you verify a signature. So it's easy to write scripts that do signature verification without calling any special library to check the signatures. That's all built into the Bitcoin scripting language. Now, one thing I haven't told you is what is this actually a signature of? What was the input to the signature function? And it turns out there's only one thing you can sign in Bitcoin, which is an entire transaction. So this check sig instruction is going to verify that the entire transaction was successfully signed. So in just one go, hopefully the check sig instruction will pop those remaining two items off of the stack, check that the signature is valid. And now we've executed every instruction in the script. There's nothing left on the stack. And if we haven't had any errors, the output of this script will be a simple yes. So every Bitcoin script can only produce two outcomes. It can either execute successfully with no errors, in which case the transaction is valid. If there's any error while the script is executing, the whole transaction will be invalid and shouldn't be accepted into the blockchain. So a little bit more about the Bitcoin scripting language. It's very small. There's only room for 256 instructions because each one is given 1 byte. And of those, 15 of them are currently disabled, so you can't use them at all. And 75 of them are reserved, so haven't been assigned any specific meaning yet, but might be instructions that are added later in time. So there's a lot of the basic instructions that you'd expect in any programming language are going to be there. There's basic arithmetic, basic logic like if and then, throwing errors, not throwing errors, returning early. And finally, there are crypto instructions, like I said. So there are hash functions, instructions for signature verification, and there's a special, very important instruction for multi-signature verification. That's called check multi-sig. So this, even more powerful than checking just a single signature with one instruction, Bitcoin actually lets you check multiple signatures with one instruction. So with multi-sig, you specify n public keys, and you specify a parameter t, or a threshold. And for this instruction to execute validly, there have to be at least t signatures, t out of n of those public keys that are valid. So we'll show some examples of what you'd use multi-sig for in a second, but this is quite a powerful primitive that in a compact way in the Bitcoin scripting language, you can express the concept that t out of n of these public keys must sign in order for this transaction to be valid. So there's an important bug here. There's a gotcha, which has been there since the beginning of time, which is that in the original implementation of this, the check multi-sig instruction actually pops an extra data value off the stack and ignores it. So this is just a quirk of the Bitcoin language. It's something that in programming you have to deal with by putting an extra dummy variable onto the stack. And at this point, it's considered a feature in Bitcoin in that it's not going away. The costs of removing it are much higher than the damage it causes. So this is just a fun bug that everybody in the Bitcoin community gets to live with. So, like I've said, we have this whole scripting language that lets us specify, in some sense, arbitrary conditions that must be met in order to spend coins. But as of today, this isn't used very heavily. So if you look at the history of Bitcoin and look at what scripts have actually been used, the vast majority, 99.9%, are exactly the same script, which is in fact the script I showed you in our example of a script execution, a script that just specifies one public key and requires a signature for that public key in order to spend the coins. There's a few other things that have some use. So multisig gets used a little bit, and there's a special type of script called pay-to-script hash that I'll talk about in just a minute. But other than that, there hasn't been too much creativity in terms of what scripts people actually use. And one reason for that is that Bitcoin nodes by default have a whitelist of scripts, and they refuse to accept scripts that they consider not standard. This doesn't mean that those scripts can't be used at all, it just makes them harder to use. And I'll talk about exactly what that means a little bit later when we talk about the Bitcoin peer-to-peer network. Okay, so I mentioned that some of the scripts are what we call proof of burn. So proof of burn is actually a script that can never be redeemed. So if you have a proof of burn script, it's provable that those coins have been destroyed. There's no possible way for them to be spent. This is quite simple to implement. You just use this code op_return, which throws an error if it's ever reached. And no matter what values you put before then, that instruction will get executed eventually, in which case this program will crash. The data that comes after op_return is never going to be looked at, so this is an opportunity for people to specify arbitrary data in a script. So what is the point of proof of burn? Well, there's two main things that this gets used for. The first is to write arbitrary data into the blockchain. If for some reason you want to write your name, or if you want to timestamp and prove that you knew some data at a specific time, you can create a very low value Bitcoin transaction that's proof of burn. So you can destroy a very small amount of currency, and in exchange you can write whatever you want into the blockchain, which should be kept around forever. The other example of proof of burn we'll talk about in a later lecture on alternate currencies, but it can be a way to bootstrap an alternative to Bitcoin by forcing people to destroy Bitcoin in order to gain coins in the new system. So one thing that's funny about this is that the sender of coins has to specify the script exactly. So this might be funny if you're a consumer, you're shopping online, you're about to order something, and you say, all right, I'm ready to check out, I'm ready to pay, tell me the address where I should send my coins. And the retailer came back and said, oh, well, we're doing something fancy now. We're using multisig. We're going to ask you to send the coins to some complicated script. You might say, I don't know how to do that. That's too complicated. As a consumer, I just want to send to a very simple address. So in response to that problem, there's a really clever hack in Bitcoin, which is that instead of having the sender specify the entire script, the sender can specify just a hash of the script that is going to be needed to redeem those coins. So this looks like the sender specifying a very simple script, which just hashes the top value on the stack and checks to see if it's equal to the required redemption script. So the receiver of those coins, all they have to do, it looks like, is just specify the right script, and then this transaction will verify. So the basic script is very easy to satisfy here. The receiver just has to specify as a data value the value of the script that whose hash the sender specified. But after this happens, a special second step of validation is going to occur, where that top data value from the stack is going to be reinterpreted as instructions, and then it's going to be executed a second time as a script. So we see there were two stages that happened here. First, there was this traditional script which checked that the redemption script had the right hash, and then the redemption script will be deserialized and run as a script itself, and here's where the actual signature check is going to happen. So this is called pay-to-script hash in Bitcoin as an alternative to the normal mode of operation, which is pay to a public key. And the reason this was so complicated is that this was added to Bitcoin after the fact. This wasn't part of the initial design specification. This is probably the most notable feature that's been added to Bitcoin that wasn't there in the original specification. And it solves a couple of important problems. It removes complexity from the sender, so the recipient can just specify a hash that the sender sends money to. And it actually has a nice efficiency gain, as we'll talk about later, since miners have to track the set of output scripts that haven't been redeemed yet. The output scripts are now as small as possible with pay-to-script hash, because they just specify a hash, and all of the complexity is pushed to the input scripts. So we've just invested the effort to understand Bitcoin scripts a little bit, but I haven't really shown you what's so cool about Bitcoin scripts yet. It turns out you can do quite a lot of neat things that will justify the complexity of having a scripting language instead of just specifying public keys. So one of them is to do an escrow transaction. So this is a classic situation online. Alice and Bob want to do business with each other. Maybe Alice has just won some online auction and is ready to buy some things from Bob. Now Alice wants to pay Bob in Bitcoin for Bob to send some physical goods back to Alice. But we get into this problem where Alice doesn't want to pay until after she's received the goods, but Bob doesn't want to send the goods until after Bob has been paid. So what can we do about that? There's quite a nice solution in Bitcoin that's actually used quite heavily in practice, which is to introduce a third party and do escrow transactions. So how does this work? Well, Alice is going to send the money not directly to Bob, but create a multi-sig transaction that requires 2 of 3 people to sign in order to redeem the coins. And those 3 people are going to be Alice, Bob, and Judy, who's a judge who's going to come into play in case there's any dispute. So Alice will create this transaction for the desired amount with that 2 out of 3 multi-sig between Alice, Bob, and Judy. Alice signs the transaction, redeeming some coins that she owns, and this will get published in the blockchain. So at this point, these coins are held in escrow between Alice, Bob, and Judy, and any 2 of them can specify where the coin should go. So Bob will be satisfied after that happens that he's safe sending the goods over to Alice. So he'll mail them or deliver them physically. Now what we hope happens in the normal case is that Alice and Bob are both honest, in which case the goods arrive on time. They're what Alice was expecting, and she wants to actually release the money from escrow so that Bob can spend it. So if this happens, Alice and Bob can both sign a transaction redeeming the funds from escrow and sending them to Bob. And the great thing here is that Judy never had to get involved at all. There was no dispute, and so Alice and Bob were able to sign, and that represents 2 out of the 3 people required by the multi-sig transaction. So in the normal case, this isn't that much less efficient than Alice just sending Bob the money. It requires just 1 extra transaction on the blockchain. Now, what would have happened if Bob didn't actually send the goods? Or if he tried to send them and they were lost in the mail? Maybe he sent the wrong size. Alice now doesn't want to pay Bob because she thinks that she got cheated and she wants to get her money back. So Alice and Bob are definitely not both going to sign a transaction that releases the money to Bob, but Bob's also not going to sign a transaction that releases the money back to Alice because he may be denying Alice's claim of fraud here. So now we're going to have to get Judy involved. Judy's going to have to decide which of these 2 people was honest, which one doesn't deserve the money. And if Judy decides that Bob cheated, Judy will be willing to sign a transaction along with Alice, sending the money from escrow back to Alice. So Alice and Judy can get together. That's 2 of the 3 required signatures, and Alice can get her money back. And of course, Judy would have the opportunity to rule in the other direction. If Judy thinks that Alice is at fault here and Alice is simply refusing to pay when she should, Judy can sign a transaction with Bob, sending the money to Bob. So Judy essentially has full control here, but the nice thing is that she won't have to be involved unless there's a dispute. Another cool application is what are called green addresses. So the problem here is that Alice wants to pay Bob, and Bob's offline. So Bob can't go and look at the blockchain to see if a transaction that Alice is sending is actually there. Maybe Bob simply doesn't have the time to go and look at the blockchain and wait for the transaction to be confirmed. Remember that normally we want a transaction to be in the blockchain and be confirmed by 6 blocks, which takes up to an hour before we trust that it's really in the blockchain. Or maybe Bob is just in a Faraday cage and doesn't have any connection to the internet at all, so Bob is never going to be able to check the blockchain. This would be the case, say, if Bob is a person selling food on the street. So to solve this problem of being able to send money using Bitcoin without the recipient being able to access the blockchain, we have to introduce another third party, which is the bank. So Alice is going to talk to her bank and say, hey, it's me, Alice. I'm your loyal customer. Here's my card or my identification. And I'd really like to pay Bob here. Could you help me out? And the bank will say, sure, I'm going to deduct some money out of your account and draw up a transaction from one of my green addresses over to Bob. So notice that this money is coming directly from the bank to Bob. Some of the money, of course, in a change address is going back to the bank, maybe. But essentially, the bank is paying Bob here from a bank-controlled address. That bank-controlled address comes with a guarantee that that money will never be double spent. So as soon as Bob sees that this transaction is signed by the bank, if he trusts the bank, if he trusts the bank's guarantee not to double spend the money, he can accept that that money will eventually be his when it's confirmed in the blockchain. Now notice that this is not a Bitcoin enforced guarantee. This is a real-world guarantee. So Bob has to trust that the bank in the real world is doing a business and cares about their reputation and won't double spend for that reason. And the bank will be able to say, you can look at my history. I've been using this green address for a long time and I've never double spent. Therefore, I'm very unlikely to do so in the future. Of course, if the bank ever does double spend, trust in this whole system is going to collapse pretty quickly. And in fact, the two most prominent online services that implemented green addresses, which were InstaWallet and Mt. Gox, both ended up collapsing. So for that reason, green addresses aren't used as much in Bitcoin as when they were first proposed. People were really excited and thought this was a great idea and a way to do payments more quickly and without accessing the blockchain. Now people are actually quite nervous about this idea. And they're worried that this puts too much trust in the bank. As a result, this isn't used that much in practice, even though it's a cool protocol. A third example I'd like to show you is a way to do efficient micropayments. So the setup here is that Alice is a customer who wants to pay Bob a low amount of money for some service that she's going to use. So maybe in this case, Bob is really Alice's wireless service provider, and Alice wants to pay a small amount of money for every minute that she talks on her phone. Now you can see why a solution that won't work here is to simply create a Bitcoin transaction every minute that Alice speaks on the phone. That's going to create too many transactions, there will be too many transaction fees, and nobody's happy about that. The simple solution here is to create a new low-value transaction every minute that Alice talks on the phone. So if she talks for 2 hours, you might need over 100 transactions. The problem that you're going to get into in that system is that those transactions might be all very low value, and the transaction fees might really kill you. So if the value of each one of these transactions is on the order of what the transaction fees are, you're going to be paying quite a high cost to do this. So what we would like is if you can combine all these small payments into one big payment at the end. And there's actually a neat way to do this with serial micropayments. So how is this going to work? So we start with a multi-sig transaction that pays the maximum amount Alice would ever need to spend to a multi-sig transaction requiring both Alice and Bob to sign to release the coins. Now, after the first minute that Alice has used the service, or the first time Alice needs to make a micropayment, she signs a transaction spending those coins that were sent to the multi-sig address, sending one coin to Bob and returning the rest to Alice. After the next minute of using the service, Alice signs another transaction, and this time she's paying 2 coins to Bob and sending the rest to herself. And notice that these are just signed by Alice. They haven't been signed by Bob yet. Alice is going to keep sending these transactions to Bob every minute that she uses the service. Notice that these aren't getting published in the blockchain. They're just getting sent from Alice to Bob. Eventually, Alice is going to finish using the service, in which case she'll tell Bob, I'm done. You can cut off the service. I'm not going to pay you anymore. And Bob's going to say, great, I'll disconnect your service. And I'm going to take that last transaction that you sent me, and I'm also going to sign that and publish that to the blockchain. So since each transaction was paying Bob a little bit more and Alice a little bit less, whatever the final one is what Bob is going to choose to actually redeem, paying him for the service that he was provided and giving the rest of the money back to Alice. And the great thing is that all those transactions that Alice signed along the way won't make it to the blockchain. Bob doesn't have to sign them. They'll just get discarded. So technically, all of these transactions are double spends. So unlike the case with green addresses, where we were specifically trying to avoid double spends with a strong guarantee, with this micropayment protocol, we're actually generating a huge amount of potential double spends. Although in practice, if both parties are operating normally, Bob will never sign any transaction but the last one, in which case the blockchain won't actually see any attempt at a double spend. Now there's one more detail here, if you stop and think for a second, which is somewhat tricky to deal with. What if Bob never signs the last transaction? He may just say, I'm happy to let the coins sit there in escrow forever, in which case maybe the coins won't move, but Alice will be out the full value that she paid at the beginning. So there's a very clever way to avoid this problem using a feature that I described earlier but haven't explained yet, which I'll need to introduce now. And that feature is called lock time. So to avoid this problem, before the micropayment protocol can even start, Alice and Bob will both sign a transaction which refunds all of Alice's money back to her, but is locked until some time in the future. So before Alice signs the first transaction paying for the first minute of service, she's going to want to get this refund transaction from Bob and be able to hold that in her hand. And know that if she makes it to time t and Bob hasn't signed any of the small transactions that Alice has sent, Alice can publish this transaction which refunds all of the money directly to her. So what does it mean when I said it's locked until time t? How do we do that? Well, you'll remember when we looked at the metadata in Bitcoin transactions that there was this lock time parameter, which I had left unexplained. It's quite simple, actually. If you specify any value other than 0 for the lock time, that tells miners, don't publish this transaction until this point in time. The transaction is invalid and can't be published until either a specific block number or a specific point in time based on the timestamps that are being put into blocks. So this is a way of preparing a transaction that can only be spent in the future if something else doesn't happen. And it works quite nicely in that micropayments protocol as a safety valve for Alice to know that if Bob never signs, eventually she'll be able to get her money back. So hopefully those examples have shown you that you can do some pretty neat stuff with Bitcoin scripts. Those are just 3 examples that are the most practical and simple to explain, but there are a lot of other things that people have looked into doing. One of them is multiplayer lotteries, which is a very complicated multi-step protocol with a lot of transactions with different lock times. There are escrows in case people cheat, but you can actually run a fair multi-party lottery over Bitcoin using just the scripting language, which is really neat. There are other things, like you can pay someone if they know the pre-image of a hash, so you can try to pay somebody to do some brute force work for you. And there are a couple of neat protocols for different people to get their coins together and mix them so that it's harder to trace who owns which coin. And we'll talk about that a lot more in our lecture on anonymity. So the general term for contracts like this is smart contracts, which means that the contracts actually have some technical enforcement of something that used to be enforced through things like laws or courts of arbitration. So it's a really cool feature of Bitcoin that we can use scripts and we can use the miners and we can use transaction validation to enforce things like escrow or the micropayment protocol. And you don't have to rely on any centralized authority to actually enforce these contracts. Now the whole field of smart contracts goes quite deep. There's a lot more smart contracts people would like to apply, a lot of which you unfortunately can't build with the Bitcoin script today. So the Bitcoin script is fairly limited in the types of things that you can address. There's a lot of smart contracts people wish they could build that either are impossible or nobody has come up with a way to do it yet. But you can do quite a few interesting smart contracts with the Bitcoin script. So now let's talk about how Bitcoin blocks get put together. So we've been talking about the blockchain and the fact that transactions are actually grouped by blocks, but everything in this lecture so far we've been talking about just individual transactions getting published. So why do we group transactions together into blocks? Well, a couple reasons. One is that creates a nice single unit of work for miners that's bigger than the individual transaction size. So if the miners had to do work and do hashing and add metadata for every transaction in the system, that would provide too much overhead. It also makes the hash chain of blocks shorter because we only need one block for a large number of transactions. And that's going to make it easier for us to verify the blockchain data structure. So what does the blockchain data structure look like? It's a pretty clever combination of two different hash-based data structures. So on the top here, we have a hash chain of blocks. Each one has a block header and then a pointer to some transaction data, as well as a pointer to the previous block in the sequence. And remember, these are hash pointers. And then we have a tree of all of the transactions that are included in each block. So this is a hash tree, or what's called a Merkle tree, which commits to all of the transactions in the block in quite an efficient way. So it's easy to provide just the path through the tree, which will be logarithmic in size, to prove that that transaction is included in a specific block. So that's the high-level idea behind a block. What does it look like in practice at the low level? So we'll do another deep dive into the actual data here. So this is what a Bitcoin block looks like. There's what's called the block header, which has all of the metadata for that block. And then there's that Merkle tree of transactions. So basically a long list of transactions. All of the hashes are arranged in this tree structure, which gives you the ability to efficiently prove which transactions are included in a block. The most important part, of course, is the header, which mostly has information related to the mining puzzle, which was talked about in the lecture on consensus, and we'll revisit in the lecture on mining. But recall that the most important thing here is that the hash of the block header has to start with a large number of zeros for the block to be valid. And then there's some other data to make that happen. There's a nonce that miners can change. There's a timestamp. There's a indication of how difficult this block was to find. That's all stored in the header. And the important thing is that the header is the only thing that's hashed during mining. So to verify that chain of blocks, all you need to do is look at the headers. And the only transaction data that's included in the header is that one root of the transaction tree. So that's this Merkle root parameter. The other thing that's interesting about blocks is that they have one special transaction in the Merkle tree, which is unlike all the other transactions we looked at before. And this is the coin-based transaction. So this is where the creation of new coins in Bitcoin happens. It mostly looks like a normal transaction with a few exceptions. So the value of this transaction is going to be equal to currently a little over 25 Bitcoins. As we discussed, this is a flat mining reward, which is set by the system and which is halving every 4 years. In practice, it will be a little bit more than 25 Bitcoin because it also gets to include the transaction fees collected from every transaction included in the block. So the pointer to the output transaction that this coin-based transaction is receiving is a null pointer. It's a hash of all zeros. And this is an indication that since this is the creation of new coins, there is no antecedent. There's no previous transaction that's being consumed to create these coins. And there's also this special Coinbase parameter. And the Coinbase parameter is completely arbitrary. The miners can put whatever they want in there. So famously, in the very first block ever mined in Bitcoin, the Coinbase parameter had a quote from the newspaper. It had a quote from the Times of London describing a story involving the Chancellor bailing out banks, which was both a political commentary on the motivation for starting Bitcoin and served as a commitment that Bitcoin, the first block, was obviously mined after this newspaper came out. But since then, miners are free to put whatever they want in the Coinbase parameter. It's been used as a place to put some arbitrary data for different reasons, to signal support by miners for different new features, but there's no actual limits on what miners can put in there. So with both the block format and the transaction format that we described earlier, the best way to learn it is to just see for yourself. So there's a lot of websites that make this data accessible. This is a screenshot from blockchain.info, which I found very helpful myself in understanding and exploring what's going on at a low level in Bitcoin. There are a lot of other websites that do a great job of making this information accessible. So you can look at the graph of transactions, see which transactions redeem which other transactions, look for transactions with complicated scripts. You can look at the block structure and see how blocks refer to other blocks. It's all available online because, again, the Bitcoin is a public data structure, so a lot of different people have put very pretty wrappers around this to explore it graphically. So we've been talking about the ability for participants to publish a transaction and get it into the blockchain as if this happens by magic. Of course, it doesn't happen by magic in the real world. It happens through the Bitcoin network. So what is a Bitcoin network? It's a peer-to-peer network, so it inherits a lot of ideas from peer-to-peer networks that have been proposed for all sorts of other purposes. It's a peer-to-peer network where all nodes are equal. There's no hierarchy, there's no centralized special nodes, no master nodes. Every node on Bitcoin is an equal peer. It runs over TCP, it has a random topology, so there's random nodes are paired with random other nodes. And new nodes can come at any time. So you can download the Bitcoin client today, you can spin your computer app as a node, and you'll be a participating Bitcoin node with equal rights and capabilities as every other node on the Bitcoin network. Now the network is very dynamic, it changes over time, nodes are coming and going all the time, although there's actually no explicit way to leave the network. Instead, if you don't hear from a node for a while, 3 hours is the amount that's hard-coded into the common clients. People eventually start to forget you, so it gracefully handles nodes going offline. So what does that mean that you can simply join the Bitcoin peer-to-peer network at any time? Well, if this is a picture of the network at one moment in time, obviously scaled down quite a bit with just 7 nodes, but this is a picture of what it might look like, 7 nodes with all random connections to each other. And notice that the numbers are scattered around here because there's no geographic topology here. Networks connect to other nodes in a random fashion by design. Now, if you launch a new node and say you want to join the network, you start with a simple message to one node that you know about. So all you need to know is how to get to one node that's already on the network. This is usually called your seed node, and there's a few different ways you can look up lists of seed nodes to try connecting to. But you find your seed node, and you send a special message saying, tell me all the peers that you have. Tell me the addresses of all the other nodes in the network that you know about. And that node will respond and say, well, I'm paired with nodes 1 and 7, you can try them. And then you might go talk to 1 and 7 and say, hey, tell me everybody on the network that you know about. And they'll send you the nodes that they know about, and you can iterate as many times as you want until you have a list of peers to make connections with. And then you can choose which ones to peer with, and you'll be a fully functioning member of the Bitcoin network. And again, there's a few steps of randomness here, so depending on which seed node you used or which of the peers of the seed node you decided to go and talk to, you'll end up with a random set of nodes that you're connected to, but that's perfectly fine. So now that you're a member of the network, what is the network good for? Well, the network maintains the blockchain, so if you want to publish a transaction, you want to get the entire network to hear about it. And there's a simple flooding algorithm to make this happen. So let's say that node 4 here hears about a new transaction. So Alice wants to pay Bob some money. Alice creates a Bitcoin transaction and submits it to node 4. or maybe her wallet software or her exchange does that on her behalf. But somehow this transaction gets to node 4. Now node 4 says, great, I've got a new transaction. Alice wants to pay Bob. Let's tell everybody about it. Sometimes this is called a gossip protocol because it's very simple. If you have news, you try to tell as many people as you can, and they try to tell as many people as they can, much like people gossiping in the real world. Great, so node 4 is going to talk to its neighbors, node 3 and node 2, and say, hey, check out this new transaction. Alice wants to pay Bob. And those nodes will add it to their own pool of pending transactions. So each node maintains a list of all the transactions they've heard about that haven't been put into the blockchain yet. And then they can decide to forward that onto other nodes. So 3 is going to talk to its neighbors and say, new transaction for you. Alice wants to pay Bob. That'll end up in their transaction pools and so on. And we want to make sure that this process doesn't go on forever. So let's say that node 2 comes along later and tries to tell node 7, hey, new transaction, Alice wants to pay Bob. Node 7 is going to say, that's all right, node 2, I've already heard about that. I already got it in my memory pool. I don't need to forward it further. So eventually this thing has to stop because every node will have heard about the new transaction and they won't forward it anymore. And remember, every transaction is identified uniquely by its hash. So each node can tell they've seen that hash before and that they don't need to keep forwarding that transaction, so it won't loop around the network forever. So how do nodes decide when they hear about a new transaction whether or not they should propagate it? The most important thing they do is they check to see, given their view of the blockchain, whether or not this transaction is valid. So they do all the transaction validation we talked about earlier. They run the script, they see that the script checks out, they see that the coins that are being redeemed here haven't already been spent. And if all of that checks out, then this looks like a valid transaction that they should try to relay. With a couple of other caveats, by default, nodes won't relay the transaction if it's a non-standard script. If the script has any weird features, if it doesn't match a fairly simple whitelist of scripts that nodes know about, even though it's a valid transaction, the nodes won't relay it. They'll also make sure that they haven't seen the transaction before. That's that condition to avoid infinite loops. And there's another property, which is that they won't relay the transaction if it looks like a double spend. So if they've seen a transaction where Alice tries to send some specific coins to Bob, and then later they see a second transaction where Alice tries to send those same coins to Charlie, the node shouldn't relay the second transaction. Even though either transaction could be valid because those coins still haven't been spent, they'll only relay the first one they hear. And that's an extra guard against double spending. But it's important to keep in mind that all of these checks are just sanity checks. So well-behaving nodes all implement these to try to keep the network healthy and running properly. But there's no rule that says that nodes have to follow these specific steps. So since it's a peer-to-peer network and anybody can join, there's always the possibility of a node not following this exact protocol, forwarding double spends, forwarding transactions that aren't standard, forwarding transactions that aren't valid. And that's why it's important that every node do the checking for itself. So it's possible that nodes will end up with a different view of the pending transaction pool based on what they've seen. So let's go back to this example where node 4 originally relayed a transaction where Alice was trying to pay Bob. And let's say that this transaction hasn't yet flooded to the entire network, and before it gets to everybody, node 1 is going to announce a new transaction and say, hey, I just heard Alice is trying to pay Charlie. Now from node 1's perspective, this is a valid transaction, and they haven't seen the other transaction where Alice is trying to pay Bob. So node 1 is going to implement the protocol normally and is going to tell all of her neighbors about it. Now the neighbors that haven't heard the conflicting transaction yet will add it to their transaction pool. Whereas other neighbors like node 6 in this example, they've already received a transaction where Alice is trying to pay Bob. So node 6 is going to say, I don't want to hold two conflicting transactions in my pool. I'll just keep the one I already have. The network may end up in a divided state here, where different nodes have a different view of what the pending transaction pool is. But that's fine. These transactions haven't been published in the blockchain yet, so this is just a temporary state where nodes disagree on which transaction should be put into the next block. In practice, this is a race condition. If nodes have a different perspective on which transactions are pending or which blocks have been accepted, that's okay in a temporary state, and eventually they'll sort it out. So in the case of transactions, if different nodes have a different view of the pending transaction pool, depending on who mines the next block, they'll essentially break the tie or the race condition and decide which of those two pending transactions should end up being put permanently into a block. And once one of those two transactions has been put into a block, other nodes will see that the transaction that they're holding onto in their pool is now never going to make it into a block because it would be a double spend, and they'll just drop it. So if the transaction where Alice tried to pay Bob successfully makes it into a block first, the nodes who heard the transaction where Alice tried to pay Charlie will just say, that's not a valid transaction anymore, so I can forget it. So the default behavior is for nodes to just hang on to whatever they hear first, which means that network position matters. If two conflicting transactions or two conflicting blocks get announced at two different positions in the network, they'll both flood in opposite directions, and the nodes which end up with one transaction or the other will depend on which side of the network they started out closer to. Of course, this assumes that every miner implements this logic where they keep whatever they hear first, but there's no central authority enforcing this. So every node is free to do whatever logic they want. So if for some reason, if any node wants to, they can choose to implement any other logic they want for choosing which blocks or which transactions to forward. We'll talk about that more in our lecture on mining, why miners might want to implement some different logic other than the default. Now, I've been talking mostly about transactions here. The logic for announcing new blocks whenever miners find a new block is almost exactly the same as propagating a new transaction. So the same algorithm is used to announce new blocks around the network. It's the same flooding algorithm, the same gossip process. And in this case, instead of verifying that the transaction is valid by running a script, the nodes are going to verify that the new block is valid by computing the hash and making sure that it starts with a sufficient number of zeros to meet the difficulty target. Now, validating a block is also much more in-depth because in addition to validating the header and seeing that the hash value is correct, nodes are asked to validate every transaction included in the block to make sure that the block contains only valid new transactions. And the other check, which is this really important critical part that makes Bitcoin consensus what it is that nodes shouldn't forward a block unless it builds on their perspective of the current longest chain. So they have a view of the blockchain, and they should only forward new blocks if they come at the very end of the chain, not at some earlier point. And this avoids forks building up. So just like with transactions, nodes can implement different logic if they want. They're free to relay blocks that aren't valid, or to relay blocks that build off of an earlier point in the blockchain. So some nodes may be trying to relay a block that doesn't extend the current longest chain, that actually builds a fork. And that's okay, the protocol is designed to withstand that. So how long does this flooding algorithm actually take? How much latency is imposed here? This is a graph showing the average time for new blocks to propagate to every node in the network. And the three lines show the 25th, the 50th, and the 75th percentile of how long it takes for a new block to reach every node in the network. And if you look at the 75th percentile there for some of the larger blocks, and this is heavily dependent on size because of bandwidth constraints that some nodes have, you'll see that the average propagation time is over 30 seconds. So this shows that this isn't a particularly efficient protocol. On the internet, 30 seconds is a pretty long time for people to hear about something. The reason it takes so long is because the protocol is not very efficient. It wasn't designed to be efficient, it was designed to be simple and to have no structure so that every node is equal and they can come and go at every time. And as a result, the topology may not be optimized for fast communication. A block may need to go through many nodes before it reaches some of the most distant nodes in the network. Whereas if you design the network top-down for efficiency, you would design it to make sure that the path between any two nodes was very short. For Bitcoin, it's more important to have a decentralized structure where all nodes are equal, even if that means that the propagation time can be over 30 seconds in some cases. So how big is a Bitcoin network? Well, there's no official statistics anywhere because, again, there's no central authority overseeing it. It's simply whatever the nodes participating, they are the Bitcoin network. So it's impossible to measure exactly, and it's changing all the time. But a number of researchers have looked into this and tried to come up with estimates. On the high end, some researchers have said that over 1 million IP addresses in a given month will at some point be running the Bitcoin protocol and acting at least temporarily as a Bitcoin node. But if you look at full nodes that are actually permanently connected and are fully validating every transaction they hear and running the full protocol, it's only about 5 or 10,000, which may be a surprisingly low number. And in fact, that number may be dropping. There's no evidence that the number of fully validating nodes is going up, and there's some concern that the number of fully validating nodes is actually going down. So to be a fully validating node, you want to stay permanently connected so that you hear about all data. The longer you're offline, the more catch-up you're going to have to do to hear about all the transactions you missed. And you're going to have to store the entire blockchain. You'll also need a pretty active network connection so that you can hear every new transaction and forward it to your peers. So you can see the growth over time here. And currently it takes about 20 gigabytes to store the entire blockchain, which isn't too bad. If you have a few years old PC with an active network connection, you have what it takes to be a fully validating node. Although you basically need to dedicate that machine to doing that and not much else. Fully validating nodes maintain the entire set of unspent transaction outputs. So every coin that's available to be spent, and remember, those are just unspent output transactions, ideally you'd like to store this in RAM so that when you hear a new proposed transaction on the network, you can quickly check the transaction that it's attempting to claim, run the script, and see if the signature is valid. So currently there are about 12 million unspent transactions, and that's out of 44 million transactions that have ever been proposed. So fortunately, that's still small enough to fit in less than a gigabyte of RAM in an efficient data structure, so that if you're running a fully validating node, every time you hear about a new transaction, you can quickly check, run the redemption script, and see that this is a valid transaction that you should put in your pending transaction pool. So in contrast to being a fully validating node, there are lightweight nodes, also called thin clients or simple payment verification clients. This is actually the vast majority of nodes on the Bitcoin network. And the difference here is that these nodes aren't attempting to store the entire blockchain. They only store the pieces that they need to verify some specific transactions that they care about. So for example, if you run a wallet, your wallet might want to be a simple payment verification node. And if somebody sends money to you, you'll act as a node. You'll download the bits of the blockchain that you need to verify that the person sending you the money actually owned it and that the transaction sending it to you actually gets included in the blockchain, but you won't care about the thousands of other transactions going on that don't affect you. Now, an SPV client like this won't have the full security level of being a fully validating node. And the reason is that when they hear a new block, the only thing they can check is the block header. They can check to see that the block was difficult to mine, but they can't check to see that every transaction included in that block is actually valid because they don't have the entire previous blockchain. They don't know the entire unspent transaction output set. They can only validate the transactions that actually affect them. So they're essentially trusting the fully validating nodes to have validated all the other transactions that are out there. So this isn't a bad security trade-off. You're assuming there are fully validating nodes out there that are doing the hard work, and that if miners went through the trouble to mine this block, which is a really expensive process, they probably also did some validation to make sure that this block wouldn't be rejected. And the cost savings of being an SPV node are huge. It's about 1,000 times smaller to just store block headers than to store all of the previous transactions. So instead of storing about 20 gigabytes of data, you're down to about 20 megabytes, which is something that almost anybody on a PC or even on a phone can store and act as a limited node in the Bitcoin network. So finally, we'll talk about some built-in limitations to the Bitcoin protocol and why it's challenging to actually improve them. There are a lot of hard-coded constants that are implemented into the Bitcoin protocol, which were chosen when Bitcoin was proposed in 2009, before we really had any idea that it might grow into this globally important currency. So the most important limits are probably the limits on the average time per block, the size of blocks, the number of signature operations in a block, and the divisibility of the currency. The limitations on the total number of Bitcoins in existence, as well as the structure of the mining rewards, are very likely to never be changed because the economic implications of changing them are too great. Miners have invested a lot of real-world resources into becoming miners, assuming that Bitcoin rewards would take a certain shape and that the limited supply of Bitcoins would remain the way it's been planned. So if you change that, that would have large financial implications for people. So for that reason, the community has basically agreed that those values, whether or not they were wisely chosen, we're basically stuck with. Some other changes you'd like to make seem like they would make everybody better off. Things about Bitcoin that just weren't quite properly designed at the beginning, but are also hard to change. The main aspect of Bitcoin that people are worried about and would probably like to change if they had time to design it over again are limits that affect the throughput of the system. How many transactions can the Bitcoin network process per second? So this limitation comes from the hard-coded limit on the size of blocks. Each block is limited to 1,000,000 bytes. And each transaction has to be at least 250 bytes. So if you divide through and the fact that blocks are found every 10 minutes, you're left with about 7 transactions per second, which is all that the Bitcoin network can handle. And it seems like tweaking those numbers would be very easy. It's just one constant in a file somewhere that you'd have to change. It would actually be very hard to change this in practice for reasons that will become clear in a few seconds. So how does 7 transactions per second compare? Well, if you went down to the offices of Visa and told them, I'm proposing a new payment system that can handle 7 transactions per second, they would probably tell you, that's terrible, and then they would laugh and throw you out the door. They've been working for a long time to build a payment network that goes way bigger than this. So it's said that Visa handles on average about 2,000 transactions per second around the world. And on the busiest times, so think the Saturday before Christmas when everybody's out shopping and swiping a credit card, the Visa network can handle about 10,000 transactions per second. And other payment card networks are similarly big. You can also look at PayPal, which is not as big or as old as Visa, but even PayPal can handle 100 transactions per second at peak times, so an order of magnitude more than Bitcoin. Another limitation that people are worried about in the long term is that the cryptography in Bitcoin is fixed. There's only a couple of hash algorithms, and there's only one signature algorithm, which is elliptic curve DSA, over a specific elliptic curve called SEC-P256. And there's some concern that over the lifetime of Bitcoin, which people would like to be for a long time, this algorithm might be broken. Cryptographers might come up with a clever new attack that we haven't foreseen, which makes this an insecure algorithm. And the same is true of the hash functions. Hash functions in the last decade have actually seen steady progress in cryptanalysis, with SHA-1, which is included in Bitcoin, already having some known cryptographic weaknesses. So to change this, we would have to extend the Bitcoin scripting language to support new cryptographic algorithms. So what would it look like to make a change like this, where we just said, we had a problem in Bitcoin, we're going to release a new version of the software, and everybody is going to have to switch? This is what we would call a hard forking change. So in practice, it's impossible to assume that every node would upgrade. Some nodes in the network would fail to get the new software or fail to get it in time. And what would be the implications of that? Well, let's take a look at a network here where most of the nodes have upgraded, but there are a few that haven't. And now let's say one of the new nodes says, hey, I found this nifty, great new block. Maybe it has some new signature algorithm in one of the transactions using the new features that we've added to Bitcoin. So block 4 has found this and says, OK, I'm going to update and say that's now the newest block. So I'm at block index 24. The rest of the network is at 23. but I'm going to propagate that to all of my peers using the normal block flooding algorithm. So node 4 is going to send block 24 out to its neighbors, nodes 3 and 2. Node 3 is going to get it and say, great, I got that one. I'll update my version of the blockchain to have that as the newest block. Whereas node 2 is going to say, that's crazy. You have some operation code that's disabled or reserved. I have to reject this block. I don't understand it. I can't accept it. And similarly, when it gets over to node 6 is also going to say, nope, I can't accept that block either. And now you're going to end up in a state where the new nodes have one picture of the blockchain, and the old nodes have all refused to accept this latest block. So the new nodes will go off and work on a version of the blockchain, including this new block with the new fancy feature. And the old nodes will all be stuck on an old version of the blockchain. And unfortunately, they're never going to catch up, because until they upgrade their software, they'll keep rejecting all of the blocks that are proposed by the nodes in the network that have upgraded to the new version of the protocol. So the reason it's called a hard fork is that the blockchain will split. Every node in the network will be on one side of it based on which version of the protocol it's running, and they'll never join together again. And this is considered unacceptable by the community, that old nodes would effectively be cut out of the Bitcoin network if they don't upgrade their software. So by contrast, there's an approach called soft forking, which tries to avoid creating a permanent fork like this. The observation is that we can add new features to the Bitcoin protocol if they only restrict the set of valid transactions or the set of valid blocks. Because we want to avoid this hard fork situation, we can try to add new features in a way that will cause only a soft fork. So the key to making this happen is that the new features can only make validation rules stricter. They can only limit the set of blocks or the set of transactions that are considered valid. So the new nodes in the network will be enforcing some new, tighter set of rules. So we're relying on enough nodes switching to the new version of the protocol that they'll be able to enforce the new rules, knowing that the old nodes won't be able to enforce the new rules because they haven't heard of them yet. There is a risk here, which is that old nodes might be mining an invalid block because they include some transaction which used to be valid, but according to the new, more strict rules, is not valid anymore. So that could be bad. Those nodes could waste a lot of time mining a block that the new nodes will reject. But when they try to announce that new block, the new nodes will reject it. The old nodes will at least figure out that for some reason, even though I don't understand the reason, the rest of the network has rejected my new block. Therefore, I should move on to the version of the blockchain that all of my peers have, and it won't be a hard fork. They'll have a temporary fork by virtue of the new block they tried to mine that was rejected by the network, but they'll recover and get back onto the main chain. So the classic example of a change that was made via soft fork was pay-to-script hash, which we introduced earlier in the section discussing the scripting language. So the view of pay-to-script hash from old nodes, and again, pay-to-script hash was not present in the first version of the Bitcoin protocol. They see this script as really simple. All it's doing is hashing this one data value and checking to see if it's equal to the value specified in the output script. The old nodes never do that second step of verification in pay-to-script hash, where they then check to see that that value before being hashed runs as a valid script. So what could we possibly add with a soft fork? Pay-to-script hash was successful. It's also possible that new cryptographic schemes could be added by a soft fork, or that we could add some extra metadata in blocks that had some meaning. And the place you'd add this is in the Coinbase parameter. So today, any value is accepted in the Coinbase parameter, but we could in the future say that the Coinbase has to have some specific example. One idea that's been proposed is that in each new block, Coinbase contains a Merkle root of the entire set of unspent transactions. It would only result in a soft fork because old nodes might mine a block that didn't have the required new Coinbase parameter that got rejected by the network, but they would catch up and join the main chain that the network is mining. Other changes might require a hard fork. That would be if we wanted to add new opcodes to Bitcoin, change the limits on block or transaction size, or do a lot of bug fixes. So for example, the bug I showed earlier, where the multisig instruction pops an extra value off the stack, that would actually require a hard fork. And that's the reason why, even though it's an annoying bug that people wish wasn't there anymore, it's much easier to just leave the bug in the protocol and have people work around it, rather than have a hard fork change to Bitcoin. So all of these hard forking changes, even though they would be nice, are very unlikely to happen, at least within the current climate of Bitcoin. But a lot of these ideas have been tested out and proved to be successful in alternative currencies, which start over from scratch, and we'll be talking about those in a lot more detail in our lecture on altcoins. So I spent a lot of time talking about details today. I know this has been a long lecture with a lot of technical detail, very hard to absorb it all at once, so like I said, I would certainly recommend you can go online and see some of this stuff in practice, see what blocks and transactions look like. It took me a couple of times looking at them before I really had a good sense of what was going on, but I think the practical examples do really help. In the next lecture, given all these mechanics we've introduced, we're going to look at the human side of things. Because after all, human beings aren't Bitcoin nodes, and you're never going to run a Bitcoin node in your head. So how do you as a human actually interact with this network to get it to be usable as a currency? How do you find a node to tell about your transaction? How do you get Bitcoins in exchange for cash? How do you store your Bitcoins? So all of these questions are crucial for making a currency that will actually work for people as opposed to just software.
Welcome to Lecture 4, where we'll talk about how we store and use Bitcoins in practice. In section 4.1, we'll talk about the simplest way of storing Bitcoins, and that is simply putting them on a local device. Now, just to review, in order to spend a Bitcoin, you need to know two kinds of things. First of all, you need to know some information that's stored on the public blockchain. You need to know what the identity of the coin is and how much it's worth, for example. And along with that, you also need to know the secret key of the owner of the Bitcoin. Presumably, that's you. Now, if you think about it, the first piece of information, being on the public blockchain, you don't need to worry too much about how to store it because you can always get it back when you need it. But the secret signing key is the thing that you'd better keep track of. So in practice, when we talk about how you store your Bitcoins, what we're really talking about is how you store and manage your keys. And that's going to be the main topic when we talk about how to store Bitcoins. So really, this lecture, which we titled How to Store and Use Bitcoins, might as well be called How to Store and Use Secret Keys, because that's really what it's about. Okay, now, when figuring out how we're going to store and manage our keys, there are three goals that we have in mind. The first goal is availability. You want to be sure that you can actually spend your coins when you want to. The second goal is security, and that is that nobody else can spend your coins. If someone gets the power to spend your coins, they could just send your coins to themselves, and then you don't have the coins anymore. And the third goal is convenience, just that whatever you do, it's relatively easy to use. Okay, so the simplest approach to managing your keys, what to do with them, is just to take the key and store it in a file and put that file on your own local device, on your computer, on your phone, or on some other kind of gadget that you carry or own or control. And evaluating that method against our three goals, well, for convenience, it's great. Nothing could be better than to have, say, an app on your phone where you can push a button or swipe something and spend your Bitcoins. So for convenience, it wins. But when it comes to availability and security, storing things on a local device in a simple way is not such a great idea. And the reason is, first, when you get to availability, that your key, your coins, are no more available than your device. That means if you lose the device, if the device crashes and you have to wipe the disk, if your file gets corrupted or something like that, you're out of luck. The key is lost, therefore your coins are lost. Similarly, for security, your keys, therefore your coins, are just as secure as your device. If somebody managed to break into your device to compromise it, if they can put malware on your device, a virus or something like that, then they can get the key, leak the key to themselves, and they can then send all of your coins to themselves. So although storing things locally is very convenient and very simple, it really isn't up to the task for availability and security. And the way to think about this is a lot like carrying around money in your wallet or your purse or in your pocket. It's useful to have some spending money, but you don't want to carry around your life savings because you worry that you might lose it or that somebody might steal it. And so what you typically do is store a little bit of information, a little bit of money in your wallet, and keep most of your money somewhere else. Now, in order to do all of this, we typically, if we're going to follow the local storage approach, we typically use wallet software. And that's just software that manages all the details of keys and makes things convenient. It keeps track of your coins. It gives you a nice user interface. If you want to send $4.25 worth of Bitcoins to your local Starbucks, the wallet software will give you some easy way to do that. And by the way, if you're using wallet software, once you're using software to manage keys and such, it's a nice trick, it's a useful trick to use a whole bunch of different addresses, a whole bunch of different keys. So rather than taking all of your coins and paying them to one address and controlling them with one key, you can have a separate address, a separate Bitcoin address, and a separate key for each coin. That keeps things separated so that you get a maximum degree of anonymity or privacy. And you don't need, as an individual, to worry about the management of all these different keys and addresses. Your wallet software takes care of it for you and just gives you a very simple interface that says how much is in the wallet and lets you spend it. The wallet software figures out all the details of which keys need to be used and how to generate new addresses and all of that stuff. So one thing you need to do if you're going to be able to receive Bitcoins in payment into your wallet or spend them to somebody else is you need to have a way of exchanging an address with somebody. So you can give them an address or receive an address so that payments can happen. And there are two main ways that addresses are encoded or conveyed in this way. The first one is as a text string, and the second is as a QR code. So as a text string, what we do is we take the bits of the key and we encode it as a number in base 58 notation, and then we use these 58 characters to encode the digits in our base 58 notation. So what this is basically is it's all of the digits and capital letters and small letters, except that they've taken out a few that might be confusing or might look like each other. For example, capital O and 0 are both taken out because they look too much alike. But other than that, most of the characters are here, and you can encode first in base 58 notation and then using this alphabet. The second method for encoding a Bitcoin address is as a QR code, something like this. This is a simple 2D barcode. And you can do something like point your phone at this, take a picture, and your phone can scan it and recover the bits of the address. And so this is the sort of thing you might use, for example, in a store, or if you want to have a phone-to-phone communication. My phone might display a barcode like this, which is my address on it, and your phone might take a picture of it in order to get the address. So this down here actually is an active address, and if you'd like to give me some Bitcoins, feel free to do so. In segment 4.2, we'll talk about hot storage and cold storage. Recall that in 4.1, we talked about how to store Bitcoins on your local computer, the equivalent of carrying money around in your wallet or your pocket. Now, the idea of hot and cold storage is that you're going to have some storage which is hot or online, as on your phone or in your local computer. And as we covered before, storing Bitcoins in that way is convenient, but it's also somewhat risky. You keep some money in hot storage, and you keep some money in cold storage. Cold storage is offline. It's locked away somewhere. It's not connected to the internet. And it's archival. It's more secure. It's safer, but of course, it's not as convenient. So this is similar to how you carry some money around on your person, but you don't keep your life savings on your person. You put that somewhere safer. And so when we're using this strategy of hot and cold storage, we're going to have separate keys and separate addresses for the coins that are stored either on the hot side or the cold side. And so the main topic of discussion here, the main thing we need to go over, is how you move coins back and forth between the hot and cold sides and what the relationship is between the sides. Okay, so obviously you're going to have separate secret keys to control the coins on the hot side and the cold side. The whole point of cold storage is that the coins that are in cold storage are not vulnerable to attack or loss if the hot storage is compromised. And so you need to have separate private keys for hot versus cold storage. And of course, each side needs to know the addresses that the other side is using, because you want to be able to transfer money back and forth between the different sides, between the hot side and the cold side. And so each side knows its own secret keys, and it also knows the addresses at which the other side will accept transfers. And that lets you do transfers back and forth. Now, in practice, of course, the cold storage is not online. And so the hot storage and the cold storage won't be able to connect to each other across any network. So you can think of the cold storage as being locked up somewhere while the hot storage is operating. Now, the good news here is that even if the cold storage is offline and not connected to anything, the hot storage still knows the addresses at which the cold storage is willing to accept coins. And that means that the hot storage can send coins across to the cold storage even while the cold storage is offline. And that's very nice. At any time, if the amount of money in your wallet, in your hot wallet, becomes uncomfortably large, you can just transfer a chunk of it over into cold storage, and you don't need to put your cold storage at risk by connecting it in order to receive that money on the cold side. Next time the cold storage connects, it will be able to receive from the blockchain information about those transfers to it, and then the cold storage will be able to do what it wants with those coins. Okay, but now we have a little bit of a problem if you think about it, which is how we manage these addresses. On the one hand, as I said in segment 4.1, we want, for privacy reasons and for other reasons, to be able to receive each coin at a separate address and to be able to manage the different secret keys that are used at that address. And so whenever we transfer a coin from the hot side to the cold side, we'd like to use a fresh cold address for that purpose. But because the cold side is not online, we have to have some way for the hot side to find out about those addresses. And that's the problem that we need to solve. Now, there's a kind of awkward solution to this, which would work, but we'd prefer not to use. And that is this, that we have the cold side generate a big batch of addresses all at once. We transfer those addresses over to the hot side, and then we use them up one by one. And the drawback of that is that we're periodically going to have to reconnect the cold side in order to transfer more addresses. And we might worry that while we're out and about, spending our bitcoins in a night on the town, that the hot wallet will run out of these addresses, and that could be a problem. So that's an awkward solution, generating them in batches. What's a better solution, a more effective solution, is to use a hierarchical wallet, but that requires a little bit of cryptographic trickery. So let me explain the trick behind hierarchical wallets. So just to review, previously when we talked about key generation, when we talked about digital signatures back in lecture 1, we talked about an API operation called generate keys, which generates a public key and a secret key. The public key in a Bitcoin context corresponds to the Bitcoin address that can receive coins, and the private key we still call a private key, and that's the key that allows us to spend or control the coins that are sent to the corresponding address. So this is how things normally would work if we generated keys in the standard way. But with hierarchical key generation, we do things a little bit differently. Rather than just doing generate keys, we do a hierarchical key generation operation. And this generates two things. It generates, rather than an address, it generates what we'll call address generation info. And rather than generating a private key, it generates what we'll call private key generation info. And now we can take this information and generate multiple keys. For example, given the address generation info, we can apply a gen address operation and give it the address generation info and some integer I. And that will generate the ith address in a whole series of addresses. And we can do this for any integer I. Any integer I, we can generate the ith address in the sequence given only that integer and the address generation info. Similarly, on the private key side, we can take this private key generating info and use it to generate a key, again using any integer I. And what we get is the ith key in the sequence. Right. Now, what makes this useful is that it has two important properties. First, that the ith address and the ith key match up and correspond to each other, just as if they were generated the old-fashioned way. And what I mean by that is that a coin that's transferred to the ith address will be spendable and controllable by somebody who knows the ith key. So these behave just like a regular address and a regular key. The other thing that's important is that we have a security property, and the security property is this, that the address generation info doesn't leak keys. That is, it doesn't leak any information about what the keys might be. And that means that it's safe to give the address generation info to anybody, and so that anybody can be enabled to generate the ith key. Now, not all digital signature schemes that exist can be modified in a way like this to support hierarchical key generation. Some can and some can't. But the good news is that the digital signature scheme used by Bitcoin, which is called ECDSA, does support hierarchical key generation, and so we can do this trick. And the reason this is useful for hot and cold storage is that we can take this operation and split it up between the hot side and cold side of our storage, like this. Everything that has a blue background here is done on the cold side, and everything that has a red background is done on the hot side. And so what we do is at the very beginning, on the cold side, we do the generate keys hierarchical operation. We then take the private key generation info that makes and keep it on the cold side. And we take the address generation info that makes and pass it across to the hot side. Then, once we've done that, the hot side can generate the entire sequence of addresses on its own without needing any further communication with the cold side. We can generate an arbitrarily long string of addresses, or at least long enough that we'd never have to worry about running out. And on the private side, we can generate the corresponding keys, again, without needing to communicate. We can generate that later. So if we do things this way, there's only one passage of information from the cold side to the hot side about keys and addresses. That happens once at the very beginning of the situation. And once that's done, then no further connection is required. And so this lets us use separate keys and separate addresses for every coin that's passed across to the cold side, but without requiring a lot of back and forth communication, and critically for security, without requiring the cold side to connect to the net or pass information out in any way, except once at the beginning. Okay, so with that in place, we can talk about the different ways in which cold information can be stored. I said earlier that information on the cold side, whether it's a key or key generation info or something else, is stored offline. But let's get more specific about exactly how it is stored. The first way we can store it is to store the information in some kind of a device and just put that device in a safe. It might be a laptop computer, it might be a mobile phone or tablet, or it might just be a thumb drive. But whatever it is, we store the information on that device, we turn the device off, we lock the device up. And now, obviously, if somebody wants to steal this, they have to get into our locked storage and get that device away from us. The second method we can use is called a brain wallet. And in a brain wallet, what we're doing is we are taking the information that we want to protect and we're encrypting it under some kind of passphrase or password that a user remembers. Then, in order to get the information back later, we're going to ask the user to give us the passphrase, and then we'll be able to decrypt. If we do this, and if the crypto is done correctly, and if the user picked a good passphrase, then the security of this will be as good as the security of the passphrase. And as long as the user isn't tricked or coerced into giving up the passphrase, and as long as the adversary can't guess the passphrase, then our data is going to be secure. But this, of course, is subject to the same kind of attacks that passwords typically are. The third thing we can do to protect information offline is what's called a paper wallet. We can take the information and we can print it out onto paper, and then we can put that paper in some safe or secure place. We can lock it in a safe deposit box or something like that. Now, the benefit of doing that, obviously, is that, again, just like with a device, the security of this is just as good as the physical security of the paper that we're using. This is a Bitcoin paper wallet. They come in different shapes and sizes, but this is one example. What you see over here is the public address, the address of this wallet. And this is shown in two ways. First, as a 2D barcode, as a QR code. And then second, down here, you see it as a character string in the base 58 notation. Now, originally, this side over here was sealed because it has the private key within it, and you don't want to give away the private key too easily. We can open this up. Originally, we would have broken a seal. And we have this stuff here that's designed to frustrate scanners and people looking through and so on. And eventually we open it up and we see over here this, which is a 2D barcode which contains the private key that controls access to this wallet. Now this particular wallet doesn't have any coins in it. I wouldn't be showing you the private key if it had any coins of mine in it. But this is the experience that you would have. And this is a thing that you can hand out to someone. And in fact, this was handed out at a conference as an example. So this shows how you can take a Bitcoin wallet and encode it as a paper artifact. You could take this thing, I could seal it up, put it in an envelope, and put it in a safe deposit box, and it would be relatively safe there. The fourth way that we can store offline information is to put it in some kind of tamper-proof device, some sort of device that resists tampering. The idea is that we either put the key into the device or the device generates the key, and then the device is designed so that there's no way it will output or divulge the key. The device might sign a statement with the key when we say press a button or give it some kind of password, but the device is designed so that it doesn't give out the key. And the advantage of that is that, again, the security of the key is, we hope, as good as the security of the device. And in particular, if we lose the device or if it's stolen, we'll know it. Unlike the theft of information about a key, where we might not know that someone has learned our key, if the key is built into a device and the device can never divulge the key, then if someone has stolen the key, they will necessarily have stolen the device, and we'll know that the device is missing. So this has some advantages as well. Now, in general, people may use a combination of all four of these methods in order to secure their keys. For hot storage, and especially for hot storage holding large amounts of Bitcoins, people are willing to work pretty hard and come up with novel security schemes in order to protect them. And we'll talk a little bit about one of those more advanced schemes in the next segment. In segment 4.3, we'll talk about how to share and split keys. Up to now, we've talked about different ways of storing and managing the secret keys that control Bitcoins, but we've always put a key in a single place. Whether that's locked in a safe or in software or on paper, it's in one place. And storing the key in one place leaves us with a single point of failure, so that if something goes wrong with that single storage place, then we're in trouble. So here what we'd like to do now is be able to take a key and split it up into pieces and share those pieces around so that we avoid the single point of failure problem. And so we're going to introduce a cryptographic trick called secret sharing. The idea is we're going to take some secret, in our case a secret key, and we're going to divide it up into some number n of pieces. And we're going to do that in such a way that if we're given any k of those pieces, then we'll be able to reconstruct the original secret. But if we're given fewer than k pieces, then we won't be able to learn anything about the original secret. So for example, we might have n equals 2 and k equals 2. That means we're dividing the secret into two pieces, and you need both pieces to put them together. And a specific way of getting n equals 2, k equals 2 secret sharing like this is as illustrated here. That first we're going to generate a number p, which is a large prime number. It doesn't need to be secret or anything, just really big. S is going to be the secret, and the secret has to be between 0 and p minus 1 inclusive. And then we're going to generate a random value r secretly, which is also within the range between 0 and p minus 1. And now we're going to split our secret into two pieces, x1 and x2. Piece x1 is going to be s plus r modulo p. And remember that modulo is the operation that's sometimes written with the % sign in programming languages. It just means take this value s plus r and divide it by p and keep the remainder when we do that division. That's s plus r modulo p. So that'll be x1, our first share. And the other share, x2, is going to be s plus 2r modulo p. Okay. And now if we have both of these shares, x1 and x2, we can combine them to reconstruct the secret s. What we do is we compute 2 times x1 minus x2 modulo p. So 2 times x1 is 2s plus 2r, and x2, which we're subtracting off, is s plus 2r. And so we have 2s minus s. That leaves us with an s. We have 2r minus 2r. And so the 2r's cancel out, and we're left just with s mod p, which is equal to s, because s is less than p. And so we can reconstruct the secret in this way. So given two shares, we can reconstruct. But given only one of the shares, it turns out we don't learn anything. And to see why that is, consider x1. We took s, which is the secret, but we added to it a random number which could take on any value between 0 and p minus 1 with equal likelihood. And if you think about it, you can convince yourself that the result then of s plus r modulo p is equally likely to take on any value between 0 and p minus 1, and that's true regardless of what s was. And so this share by itself just looks like a purely random number and doesn't convey anything about what the value of s might have been. Similarly, this share by itself is also equally likely to take on any value between 0 and p minus 1, and therefore doesn't convey any information about s. So that's n equals 2, k equals 2. Given both shares, we can get back the secret. Given one share, we can't. Okay. Now, in general, we can talk about how to get higher values of n and k. For example, let's talk about how to get higher values of n where k equals 2. That is, we're going to want to require 2 shares to be put together to reconstruct the secret, but we're going to make more than 2 shares that are eligible for use in this way. And so the way we'll do that is to draw our standard x and y axis here, and we're going to add a point here at 0, comma s, where s is the secret. And so obviously, if somebody can learn what this point is, then they will have reconstructed the secret. Okay. Now we're going to draw a line, and we're going to draw a line that has a random slope r. R is going to be generated randomly, and so we get a line like this. And now we can give out shares. The first share is this point here at x equals 1, and y is s plus r. The second share is here at x equals 2, and y turns out to be s plus 2r. The third share is here, x equals 3, and y is s plus 3r, and so on. We can go as far up this line as we want and generate as many shares as we want. Okay. Now, if you think about it, you can convince yourself that given any 2 points, you can interpolate and find s, right? That's a property of a line. Given any 2 points on a line, you can interpolate the line. Imagine setting down a ruler that exactly touches, say, these 2 points, and then you can just draw a straight line along that ruler. So given any 2 points, you can reconstruct what this line is. You can see where the line crosses the y-axis. That will be 0, comma s, and that will give you back the secret. But given just 1 point, you don't really know anything. Because if you have, say, this point, well, the line might be sloped like this, but equally likely it might be sloped like this. It could be sloped any way at all. And so given just this point, you don't really know anything about where this line might cross the y-axis, so you don't know anything about s. And in fact, you can prove that if you do this arithmetic modulo a large prime p, like we did before in the previous slide, that in fact you can prove that any 2 points are sufficient to interpolate and find s, and fewer than 2 points don't tell you anything about s. And so this gives us n equals any value and k equals 2. All right, but now what if we wanted to require more than 2 points? Well, for 2 points we drew a line because any 2 points are sufficient to uniquely specify a line. If we want to require 3 points, what we're going to do is use a quadratic function because any 3 points are sufficient to reconstruct a quadratic function. And so we can use this table to understand what's going on. So if we use the equation s plus rx mod p with the random parameter r, that's the slope that we saw in the previous slide, then you need 2 points to recover s because you need 2 points to interpolate a line. If, on the other hand, if then you use a quadratic, that is s plus some random value r1 times x plus some other random value r2 times x squared, then there are 2 random parameters r1 and r2, and with any 3 points you can uniquely interpolate a quadratic and get back s. And we can just go up the ladder here. If we use a cubic function, there are 3 random parameters. We need 4 points. And in any case, you can generate as many points as you want on the line or the quadratic or the cubic. And therefore, you can get any value of n. And you see how you can get any value of k by just going to higher and higher order polynomials. And so this scheme will let you take any secret and split it into n shares, such that k shares or more are needed to reconstruct. And that turns out to be a really useful thing, because now you can take a secret key or other secret information and split it up in this way. Support k out of n splitting for any k and n. So let's talk about the good and bad that we get out of this process. The good part is that we can store the shares separately, and the adversary needs to be able to recover k shares in order to get back what the secret was. And that's a good news, right? That means that if we use, say, k equals 3, n equals 4, the adversary needs to get break into 3 separate places. And if we're clever about storing those separate shares in places that are far apart and independently secured, then we can make the adversary's job much more difficult. And indeed, if we notice that the adversary has compromised one of those places, we can then race out and try to recover the other shares and address the problem. The other thing that's good about this is that we can afford to lose some of the shares. If we do 3 out of 4 secret splitting, then we can lose 1 share and we'll still have 3 left. And so we can put those 3 remaining ones together and still get back the key. So even though we're spreading out the information, there are more places where information might be lost. We can also tolerate the loss of some of those. In general, we can tolerate the loss of n minus k of them. Now that's the good news. The bad news is that if we take a key and we split it up in this way, and we then want to go back and use the key to sign something, we still need to bring the shares together and recalculate the initial secret in order to be able to sign with that key. And that point where we bring all the shares together and recombine them is still a single point of vulnerability where an adversary might be able to attack us. And that's the bad news. So although this is useful, it's not a panacea, and there's something else that we'd like, which is the ability to generate separate shares and use those shares separately in order to sign. And that's what's behind the concept of multisig that we saw earlier in Lecture 3. So if you recall multisig in Lecture 3, it lets you keep the shares or the different pieces that need to sign a particular transaction apart, and to allow them to approve the transaction separately without needing to reassemble the key at any point. So just as an example of application of that, suppose that Andrew, Arvind, Ed, and Joseph are co-workers. Let's say they're co-founders of a company, and the company has a lot of bitcoins. Hey, we can dream. Now, what we might want to do is use multisig to protect our large store of bitcoins. So what we're going to do is have each of the 4 of us generate a key pair, and we're going to, for our company's cold storage, store the coins so that we require multisig with 3 out of the 4 keys signing. Now the result of that is that we know that we're relatively secure if the 4 of us keep our keys separately and secure them differently, that someone would have to compromise 3 out of the 4 keys, that if some employee or even 2 employees go rogue, those rogue employees can't steal all of the company's coins because you would need a conspiracy of 3 out of 4 to do that. And we also know that if something goes wrong, if one of us loses our key, or if one of us gets run over by a bus and our brain wallet is lost, the others can still get the coins back and transfer them over to a new place. And so multisig allows you or helps you to manage large bodies of cold stored coins in a way that's relatively secure and that requires action by multiple people before anything drastic happens. In segment 4.4, we'll move on to talk about online wallets and exchanges. Thus far, we've talked about ways in which you could store and manage your bitcoins yourself. Now we'll talk about ways in which you can use other people's services to help you do that. So the first thing you could do is to use an online wallet. An online wallet is kind of like a local wallet that you might manage yourself, except that the information is stored in the cloud. And so you have some kind of, say, web-based interface like this. This is from one called Blockchain, but there are plenty of other online wallet services. You might have a website that you use on your computer. You might have an app that you use on your phone. So it's like a local wallet, but it's in the cloud. It might typically run in your browser, which means the site sends the code that does all of the operations. The site will store your keys. At least it will have the ability to access your keys. Ideally, the site will encrypt those keys under a password that only you know. But of course, you have to trust them to do that. You have to trust their code to not leak that key or leak that password. And then, of course, you would log in order to access the wallet. Okay. So an online wallet has certain trade-offs compared to doing things yourself. One of the big advantages is that it's convenient. You don't have to install anything on your computer in order to be able to use an online wallet in your browser. On your phone, you maybe just have to install an app once. It'll work across multiple devices. You can have one wallet that you access on your desktop and on your phone, and it will just work because the real wallet lives in the cloud. But there are security worries. If the site or the people who operate the site turn out to be malicious or are compromised somehow, now you have to worry about the information of yours that they're storing. You have to worry about the fact that they're supplying code that has its grubby fingers on your bitcoins. And there are things that can go wrong if there's a compromise or malice at the service provider. Ideally, you would hope that the site or the service is run by security professionals who are better trained or perhaps more diligent than you in protecting the security of things. And so you hope that they do a better job and that your coins are actually more secure. But at the end of the day, you have to trust them and you have to rely that they won't be compromised. Now, another approach, instead of an online wallet, is something that functions rather more like a bank in the real world. And to set context for this, let's talk about how banks or bank-like services operate in the traditional economy. So this is pretty simple, right? You give the bank some money, that's a deposit, and then the bank in exchange promises to give you back that money later. And of course, crucially, the bank doesn't actually just take your money and put it in a box in the back room. All the bank does is promise that if you show up and ask for the money, they'll give it back. The bank will typically take that money, put it somewhere else. They'll invest it or something else like that. The bank will probably keep some money around in reserve in order to make sure that they can pay out the demand for withdrawals that they'll face on a typical day or maybe even an unusual day. And many banks typically use something called fractional reserve, where they keep a certain fraction of all of the demand deposits on reserve just in case. Now, Bitcoin exchanges are businesses that, at least from a user interface standpoint, function in a way that's similar to banks. That is, they accept deposits of Bitcoins. You can transfer your Bitcoins to an exchange, and they will, just like a bank, promise you that they will give them back on demand later. You can also transfer fiat currency, that is, traditional currencies like dollars or euros or similar, into an exchange by doing a transfer from your bank account. And so you can make deposits of both of these sorts of things, and they promise to pay back either or both of them on demand. And what they then let you do is, again, various banking-like things. They let you make and receive Bitcoin payments. You can direct the exchange to pay out some Bitcoins to a particular party, or you can ask someone else to deposit funds into a particular exchange on your behalf, put them into your account. And they also let you exchange Bitcoins for fiat currency or vice versa. And typically the way they do that is they find some customer who wants to buy Bitcoins with dollars and some other customer who wants to sell Bitcoins for dollars, and they try to match them up. That is, they try to find customers who are willing to take opposite positions in a transaction so that there's a mutually acceptable price, and then they will consummate that transaction. Now, it's important to understand what happens if you buy or sell Bitcoins in an exchange. So suppose my account at some exchange starts holding $5,000 and 3 Bitcoins. And I use the exchange, I put in an order to buy 2 Bitcoins for $580 each. And eventually the exchange finds someone who's willing to take the other side of that transaction, and the transaction happens. So the result of that is that my account is different. Now I have 5 Bitcoins instead of 3, and I also have $3,840. That's my $5,000 initial dollars minus $580 each times 2 Bitcoins. That's $3,840. So now that's what's in my account. But the important thing to note here is that when this transaction happened involving me and another customer of the same exchange, that no transaction actually happened on the Bitcoin blockchain. Because the exchange didn't need to go to the blockchain in order to transfer from my account into that other person's account some dollars, or in the other direction some Bitcoins. So all that happens in this transaction is that the exchange is now making a different promise to me than they were making before. Before they said, we'll give you $5,000 and 3 Bitcoins. Now they're saying, we'll give you $3,840 and 5 Bitcoins. It's just a change in their promise, no actual movement of money through the dollar economy or through the Bitcoin blockchain. And of course, the other person has had the exchange's promise to them change in the corresponding opposite way. Now, there are pros and cons to using exchanges. One of the big pros is that exchanges help to connect the Bitcoin economy and the flows of Bitcoins with the fiat currency economy, the dollar and euro and other national currency economy, so that it's easy to transfer value back and forth. If I have an account in an exchange and I have a bunch of dollars and a bunch of Bitcoins, I can trade back and forth between dollars and Bitcoins pretty easily. And that's really helpful. The con is risk, that because an exchange functions in some ways like a bank, that is, that it is accepting demand deposits, that it's accepting payments of money to it in exchange for a promise to pay money back later, that you have the same kinds of risks that you face with banks. And those risks really fall into three categories. The first risk is the risk of a bank run. This, of course, is a famous scene from the movie It's a Wonderful Life. Jimmy Stewart is running a credit union, another bank-like business, and all of these people have shown up and they want their money back. This is a bank run. And Jimmy Stewart explains to them, I don't have your money in the back room. I lent out your money to Fred so he could open his hardware store and so on. So one of the risks is that even if the bank is solvent on paper, that you might show up and want your money back, and the bank might be unable to produce it. And there's a danger of a kind of panic behavior where once the rumor starts to get around that a bank or exchange might be in trouble, and they might be getting close to not honoring withdrawals, then people stampede in to try to withdraw their money ahead of the crowd, and you get a kind of avalanche. And that's what Jimmy Stewart was able to stave off with his eloquence in the movie. The second risk is that the owners of the banks might just be crooks. This is Charles Ponzi, inventor of the Ponzi scheme. A Ponzi scheme is a scheme where he would get people to give him money in exchange for wonderful, wonderful profits in the future, only he would actually take their money and use them to pay out the wonderful, wonderful profits to people who bought previously. And so his schemes were always insolvent and were doomed to eventually fail and lose a lot of people a lot of money, which is why he went to prison. And so there's the risk that the people who run the exchange are just crooks. The third risk is the risk of a cyber attack. The risk that someone will manage to penetrate the security of the exchange. Exchanges have large numbers of bitcoins. That means that they store key information that controls large numbers of bitcoins, and they need to be really careful about their procedures and how they manage their cold and hot storage and all of that. And if something goes wrong, if that key information is compromised, if a suitable quorum of employees is compromised, then your money could get stolen from the exchange. And all of these things have happened. We have seen exchanges that failed due to the equivalent of a bank run. We've seen exchanges that fail due to the operators of the exchange being crooks, and we've seen exchanges that fail due to break-ins. And in fact, the studies on this are not encouraging. The best study I think shows that at least as of the time of the study, something like 45% of Bitcoin exchanges had ended up closing due to some failure, some inability to pay out the money that the exchange had promised to pay out. The most famous example of this, of course, is Mt. Gox. Mt. Gox was at one time the largest Bitcoin exchange, and it eventually found itself insolvent. That is, unable to pay out the money that it owed. And Mt. Gox was a Japanese company, and it ended up declaring bankruptcy, leaving a lot of people wondering where their money had gone. Right now, Mt. Gox and the bankruptcy of Mt. Gox is tangled up in the Japanese and American courts, and it's going to be a while, I think, before we know exactly where the money went. The one thing we know is that there's a lot of it, and Mt. Gox doesn't have it anymore. So this is a cautionary tale about the use of exchanges. Now, connecting this back to banks, we don't see a 45% failure rate for banks in most developed countries. And the reason for that partly is because of regulation. For traditional banks, government regulates in various ways. The first thing that governments do is they often impose a minimum reserve requirement. In the US, this is typically 3 to 10% of demand deposits a bank is required to have in liquid form so that it can deal with a surge of withdrawals if that happens. Second, the regulators often regulate the types of investments and money management methods that banks can use to make sure that the bank's assets are invested in places that are relatively low risk, because those are really the assets of the depositors in some sense. Now, in exchange for these forms of regulation, governments typically do things to help banks or at least protect their depositors. First, governments will issue deposit insurance. That is, that they'll tell depositors that if you deposit your money in a bank that follows these rules, then we, the government, guarantee that if the bank goes under, we will make good on at least part of those deposits for you. And the other thing that governments sometimes do is act as a lender of last resort. And what that means is that if a bank gets itself into a tough spot, but it's basically solvent, that the government may step in and loan that bank money in order to tide it over until it can move money around as necessary to get itself out of the woods. So traditional banks are regulated in this way. Bitcoin exchanges are not. The question of whether or how Bitcoin exchanges or other Bitcoin businesses should be regulated is a topic that we'll come back to in Lecture 7. Now, there is one interesting thing that a Bitcoin exchange or somebody else who holds Bitcoins can do, which relies on some cryptographic tricks to give users or customers some amount of comfort about where the money went or where the money is that those people deposited into the Bitcoin business. And that's what's called a proof of reserve. So let me explain how that works. The goal here is that a Bitcoin exchange or some other business that's holding Bitcoins can prove that it has a fractional reserve. It can prove that we have at least, let's say, 25%, or maybe that we have 100% of the deposits that people have made with us available and under our control if need be. And so the way that proof of reserve works is you break the problem into two pieces. First, you prove how much reserve you're holding. That's the relatively easy part. So the company publishes a valid payment to self transaction of that amount. That is, if they claim to have 100,000 Bitcoins, they create a transaction in which they pay 100,000 Bitcoins to themselves and show that that transaction is valid. Then they sign some challenge string, that is some random string of bits that was generated by some impartial party, and they sign that challenge string with the very same private key that was used to validate that payment to self transaction. That proves that someone who knew that private key was participating in this proof of reserve. Now, strictly speaking, that's not a proof that the party who's claiming to own the reserve owns it. All this proves is that whoever does own that 100,000 Bitcoins is willing to cooperate in this process. But nonetheless, this looks like a proof. This looks something like a proof that somebody controls or knows someone who controls the given amount of money. So the first piece is to prove how much reserve you have. And the second piece is to prove how many demand deposits the group holds. And if you can prove those two things, then somebody can simply divide those two numbers, and that's what your fractional reserve is. One more thing to note before we go on and talk about how you prove how many demand deposits you hold, that's the tricky part, is that in proving how much reserve you're holding, you could underclaim. That is, the organization might have 150,000 Bitcoins, but choose to make a payment to self of only 100,000. And so this proof of reserve doesn't prove that this is all you have, but it proves that you have at least that much. Okay. Now, how do you prove how many demand deposits you hold? In order to do that, we're going to use a trick that relates to the Merkle trees that we talked about in Lecture 1. And if you recall, a Merkle tree is a binary tree that's built with hash pointers, so that each one of these pointers not only says where we can get a piece of information, but also what the cryptographic hash of that information is. Now we're going to add to each one of these hash pointers another field or attribute. So we're going to add to each hash pointer a total value, that is a total monetary value in Bitcoins of all of the things that are underneath that hash pointer in the tree. So for example, this hash pointer here would be tagged with the total value in this entire left subtree. Right? Now down here at the bottom, we're going to have one item for each user's or customer's account. And we're going to combine these up the tree so that each node, the hash pointer coming out of it, will be labeled with the sum of the values on the two hash pointers down below. So that will be a valid total for the subtree. So we can construct that structure, and then the exchange that wants to do the proof of reserve can cryptographically sign the root hash pointer here, which is making a claim that this is a valid tree and that everybody is down here. Okay. Now each customer can then go to the organization and they say, okay, prove it to me. If this is prove that my account is included in your tree. And so I can go to the exchange, I can make that demand, and they can show me this partial tree. I can see that up here that the hash pointer is the same hash pointer that they signed. I can see that the hash pointers are consistent all the way down, and that is that the hash stored in this hash pointer actually is the hash of the cryptographic hash of this node, and so on for each hash pointer all the way down. And so just like with the Merkle tree, that proves that my account here was in the tree that they initially committed to. I also am going to verify that the amounts in the hash pointers add up all the way down. So for example, the total value in this hash pointer adds up to the same total as this hash pointer plus this hash pointer, which is included in this node. And I make sure that on this path down to my account, that the totals add up all the way. Now, if you think about it, if everybody does this, if everybody makes a demand to see their own account, then every branch of this tree is going to get explored, and someone is going to verify that for every node in the tree, that the value of the hash pointer pointing to that node is equal to the sum of the value on these two children. And so if everyone does this, then they will collectively prove over the whole tree that, that the values are added correctly going up the tree. Okay, so this is the scheme that first the exchange builds a tree like this that includes all their customers' accounts at the bottom and sums the total values going up the top. Then all customers, or really realistically those customers who are willing to go to the trouble, demand to see the partial subtree that includes their account and verify that everything adds up. And if that works, then we can believe that the organization is correctly reporting all of the accounts that they have. Or actually, to be a little bit more precise, they can claim to have more accounts than they really have. All they're proving is that every actual account appears somewhere in the tree. Now let's review. So first they've proven that they have at least X amount of reserve currency by doing a self-transaction of X amount. Then they've proven that their customers have at most an amount Y deposited. And of course they can claim that in the other direction as well. So what that means is that the reserve fraction is, if they report it exactly accurately, it's X over Y. If in fact X is larger, then the reserve fraction is larger than they're claiming. Or if Y is smaller, then the reserve fraction also, because this is in the denominator, is also larger than they're claiming. And so when they prove an X and prove a Y this way, you can guarantee that the actual reserve fraction they're holding is at least as big as what they're claiming. And therefore they can prove a reserve to you. And what that means is that if a Bitcoin exchange wants to prove that they hold 25% reserves on all deposits, or 100%, they can do that in a way that's independently verifiable by anybody. And no central regulator is required. So that's an aspect of regulation that Bitcoin exchanges can prove voluntarily, but other aspects of regulation, as we'll see in a later lecture, are harder to guarantee. In segment 4.5, we'll talk about payment services. Thus far, we've talked about how you can store and manage your Bitcoins. Now we're going to talk about how a merchant can accept payment in Bitcoins in a practical way. So the scenario here is that we have a merchant. Maybe it's an online seller of some kind of goods or services. Maybe it's a local retail merchant, and they want to be able to receive payments in Bitcoins. Now the reason they want to be able to receive payments in Bitcoins, let's say, is not that the merchant is so excited about Bitcoins, but simply because their customers want to be able to pay in Bitcoins. What the merchant wants is to receive dollars or local fiat currency, whatever that is, at the end of the day. They want to have some way of receiving payments in Bitcoins which is easy for them to deploy, so they don't have to worry a lot about technology, changing their website, or building some kind of point of sale technology. And they also want low risk. There are various risks associated with receiving payments in Bitcoins, and the merchant doesn't want to have to worry about those. So they don't want to have to worry about technology risk. That is, the risk that by changing their technology, something will go wrong, their website will go down, something will malfunction, and that will cost them money. They don't want to deal with the security risks of handling Bitcoins, the possibility that someone will break into their hot wallet, or some employee will make off with their Bitcoins. And they don't want to deal with the exchange rate risk, that the value of a Bitcoin in dollars may fluctuate from time to time, and the merchant who might want to sell a pizza for $12 wants to know that they're going to get $12 or something close to it, and that the value of the Bitcoins that they received in exchange for that pizza won't drop drastically before they can get it, before they can exchange those Bitcoins for dollars. So the merchant wants to be isolated from all of that. And so the reason that we have payment services is fundamentally to allow both of these parties to be happy and get what they want, while someone else takes care of bridging the gap between these different desires. So the process by which a merchant might arrange to accept Bitcoin payments on their site through a payment service would work something like this. The merchant would first go to the payment service's website, and they'd fill out a form that looks something like this. This particular form comes from a service called Coinbase. And so the merchant says, all right, I want to display a button on my web page. I want it to be a buy now button. I want the button to look like this. Here's the name of the item that is being bought. Here's the sale price amount, which can be in either bitcoins or dollars or some other currency. And then here's where the funds should be sent when the customer buys. The merchant then, having filled that out, presses this button to generate button code, and out will come a bunch of HTML code that the merchant can just drop into their website. The merchant will put that into their website, and what will appear on the website to the customer will be a button that looks like whatever they chose. When the customer pushes that button, then a bunch of payment magic will happen, and the merchant will eventually get a confirmation saying that, yeah, a payment was made by this customer for alpaca socks in such and such amount. So the way that that actually works, or one typical way that the mechanism might work for a payment is illustrated here. Here we have down at the bottom a user who wants to buy something from the merchant who's up here. And we have over here the payment service. Okay, so the user goes to the merchant's website, they shop, they pick out an item they want to buy, and when it comes time to pay, the merchant will deliver a web page which will contain the Pay with Bitcoin button, and it will contain some other information. It will contain a transaction ID, that is some identifier that is meaningful to the merchant in their own accounting system, along with an amount that they want to be paid. And this will basically be the magic HTML code that was provided earlier by the payment service. The user, if they want to pay with Bitcoins, will click that button. That will cause information to be sent to the payment service as an HTTP or HTTPS, ideally, request, which says that that button was clicked. Here's the transaction ID from the merchant. Here's the amount. And of course, the identity of the merchant is implicit here. When that happens, now the payment service knows that this customer, whoever they are, wants to pay a certain amount of Bitcoins. And so the payment service will pop up some kind of a box or do some kind of an interaction with the user, in which the user will receive information about how to pay, and the user will then initiate a Bitcoin transfer to the payment service. Once the user has created that payment, then the payment service will send back information. Might be a redirect of some kind, maybe an HTTP redirect or something else that comes back to the user's browser and causes the user's browser to send a message on to the merchant from the payment service saying, it looks okay so far. And then later, the payment service will directly send a confirmation saying that yes, in correspondence with this transaction ID that you, the merchant, created, the following amount was spent, that this is fully confirmed in the Bitcoin blockchain, and the payment service will confirm that it's giving you the money at the end of the day. So once that happens, now the merchant knows that the payment is confirmed, and they can go ahead and allow whatever the item is that this user bought to be shipped out to the user. And then the user will eventually get the item, and everyone is happy. So this is a typical kind of flow. The details of the flow might work a little differently depending on which payment service you're using, but that's the idea. From the merchant standpoint, what happens is they include this blob of HTML in their website, that eventually they get this tentative okay, things are going ahead, and eventually a firm confirmation from the payment service. They use this transaction ID to match up the purchase of this particular Snuggie by this particular user in their accounting system, and they use the confirmation to know they got paid. And now the final step is the one in which the payment service actually gives money to the merchant. Okay, so the end result of this whole process is the following: that the customer pays Bitcoins, some number of Bitcoins, that the merchant gets dollars. That's what the merchant wanted. They wanted to sell that item for a particular number of dollars or whatever their local fiat currency is. The merchant gets the number of dollars they asked for minus a small percentage. The payment service is going to take a small percentage as a fee, maybe a couple of percent. And the payment service does everything else. The payment service receives the Bitcoins that the customer paid. It pays out the dollars, maybe at the end of every day. It makes a deposit into the merchant's bank account of all of the payments that came in that day. And of course, it keeps a small percentage, and that's how it makes its profit. And the payment service absorbs all of the risks involved in this process. It absorbs the security risk, so it has to have good management of the Bitcoins, of its cold storage and all of that. It absorbs the exchange rate risk because it's receiving Bitcoins and paying out dollars. If the price of dollars against Bitcoins fluctuates wildly, the payment service might be unhappy. Then again, if it fluctuates wildly in the other direction, the payment service might be happy. But that risk, that uncertainty is part of, and absorbing it is part of what the payment service does. One thing to note here is that the payment service, if it's operating at large scale, is receiving large numbers of Bitcoins and paying out large numbers of dollars. And therefore, it's going to have a constant need to exchange the Bitcoins it's receiving for more dollars so that it can keep this whole cycle going. And so a payment service is going to be an active participant in the exchange markets that link together, in this case, the dollar economy and the Bitcoin economy. And that's another thing that they need to worry about, not just what is the price of exchange, but how can we manage to exchange currency in this large volume. But in exchange for doing all of this stuff, the payment service gets their fee. And so this is potentially a lucrative business because it solves the mismatch between the customer's desire to pay Bitcoins and the merchant's desire to just get dollars and concentrate on selling goods. In segment 4.6, we'll talk about transaction fees. This is a topic that has come up before in a previous lecture, and it will come up again later in a later lecture. And transaction fees are one of the bits of how the engine room of Bitcoin works, if you will. And it touches a bunch of different topics. So what I want to talk about here today is the practical details of how transaction fees are set in Bitcoin today. We've talked about storage in this lecture. We've talked about payment services. We've talked about exchanges. But bottom line is, whenever a transaction is put into the Bitcoin blockchain, that transaction might pay transaction fees. Now recall from a previous lecture that a transaction fee is just defined to be the difference between the total value of coins that go into a transaction minus the total value of coins that come out. The inputs have to be always at least as big as the outputs because a regular transaction can't create coins. But if the inputs are a little bigger than the outputs, then the difference is deemed to be a transaction fee. And that transaction fee goes to the miner who recorded this transaction, the miner who made the block that records this transaction. The economics of transaction fees are interesting, and we'll come back to this in a later lecture. But what I want to talk about today is how transaction fees are actually set in Bitcoin as it operates as of the time of this filming. These things do change from time to time, but we'll give you a snapshot of what's going on right now. Okay, so why are transaction fees exist at all? Well, the reason is that there's some cost that someone has to incur in order to relay your transaction. The nodes in the Bitcoin peer-to-peer network need to relay your transaction, and ultimately a miner needs to build your transaction into their block, and it costs them a little bit of computational effort to do that. And the time that they spend calculating a block that's slightly larger because it contains your transaction is time that they could otherwise have spent trying to make a block and get a block reward. So there is a cost both to the peers in the peer-to-peer network and to the miners of incorporating your transaction. So the idea of a transaction fee is to somehow compensate people for those costs that they incur because your transaction exists. Generally, you're free to set the transaction fee to whatever you want it to be. You can pay no fee or you can pay a high fee. But as a general matter, if you pay a higher transaction fee, it's natural that your transaction will be relayed and recorded more quickly and more reliably. Okay. So the current consensus transaction fees are as follows. First of all, no fee is charged if the transaction is less than 1,000 bytes in size, in total size, if all of the outputs of the transaction are 1/100th of a Bitcoin or larger. That's currently worth about $5 or $6 US, and if the priority of the transaction, according to a certain formula, is large enough. The priority formula works like this. You look at all of the inputs to the transaction, and for each one you add up the product of the age of that input times the value of that input in Bitcoins. You add that up over all the inputs, then you divide by the transaction size. So if you meet these three requirements, then no fee will typically be charged, and your transaction will be relayed, and it will be recorded in the blockchain without a fee. Otherwise, a fee is charged, and that fee is about 0.0001 Bitcoins per 1,000 bytes. And that's a fraction of a US penny per 1,000 bytes. Now, just as an aside, the approximate size of a transaction based on the number of inputs and the number of outputs is about 148 bytes per each input, plus about 34 bytes for each output, plus about 10 bytes for other information. And so a transaction that's of small size has maybe 2 inputs and 2 outputs. Its size would be 400 to 500 bytes. All right. Now, the current status quo is that most miners enforce the consensus fee structure, which means that they will either not service or will service last transactions that don't meet the consensus fee structure. So if you don't pay the consensus fee, your transactions will typically take longer to be recorded. It's worth noting that if you pay a small fee, that because of the way the priority calculation works, the priority includes age of your Bitcoins, the longer your transaction sits without being recorded, the higher its priority will get because its Bitcoins get slowly older. But in any case, if you haven't paid the consensus fee, your transactions will probably take longer to find their way into the blockchain. Maybe that's okay with you. Most miners prioritize transaction based on the fees that are paid and based on the priority formula. And I'm not going to go into the details of how that works, but if you pay more or if your priority is higher, according to the formula, then your transaction probably gets memorialized first. Now finally, I said this was the consensus and that most miners do it. But in fact, there are other miners who don't enforce these rules and who will record and operate on a transaction even if it pays a smaller fee or no fee at all. So if you make a transaction that doesn't meet the fee requirements, it will probably find its way into the blockchain anyway. But the way to get your transaction recorded more quickly and more reliably is to pay the consensus fee. And that's why most wallet software and most payment services include the consensus fee structure in the payments that go on. And so you'll see a little bit of money raked off for transaction fees when you engage in everyday Bitcoin business. In segment 4.7, we're going to look at currency exchange markets. That is, markets on which you can trade Bitcoins against fiat currencies like dollars and euros, etc. We've talked earlier about Bitcoin exchanges and other types of businesses that are involved in trading between Bitcoins and fiat currencies. But now we want to look at this as a market. We want to look at the size of it, the extent of it, and how it operates, and we'll look a little bit at the economics of this market. The first thing to understand about this, if you're new to it, is that it operates in many ways like the market between two fiat currencies, like the market between dollars and euros. The price will fluctuate back and forth depending on how badly people want to buy euros versus how badly people want to buy dollars on a particular day. So in the Bitcoin markets, we can look at data. And in fact, there are sites like Bitcoin Charts. This is the Bitcoin markets page on Bitcoin Charts, which shows exchanges that trade dollars against Bitcoins. And you can see there's a list of different exchanges or different places where you can trade dollars against Bitcoins here, from top to bottom. Up here at the top, we have Bitstamp, which on this particular day had the highest volume. For each one, there's the current price. For Bitstamp, on the day I took this screenshot, it was $582.54. You can get graphs, you can look at the average, the volume, etc. You can look, the 24-hour average price was $585. The volume was about 6,100 Bitcoins, or about $3.6 million over the previous 24 hours. So you can see there's a lot of trading here. And if you go to this site live, you can see the prices move in real time as trades get made. So this is an active market, it's a liquid market, and there are plenty of places you can go to buy or sell Bitcoins. Another place you can go besides an online exchange, if you want to buy or sell Bitcoins, is that you can use sites that help you meet people to trade Bitcoins in real life. So here I went to localbitcoins.com. It's an example. I said I want to buy Bitcoins in Princeton, New Jersey, United States, and it gave me a bunch of results. A bunch of people who on this particular day were willing to sell me Bitcoins for what price and for how many. And so I could then contact these people. I could arrange to meet them at a coffee shop somewhere or in a park or wherever it is, and I could give them dollars, and in exchange they would give me Bitcoins. And so this is another way to do it. You can just find a person near you, or you can find somebody you know. The very first Bitcoins I bought from one of my students who owned some Bitcoins. I just gave him some dollars, and he paid some Bitcoins into my digital wallet. Another thing you can do is you can go to a physical place. There are some places in the world, or some regular meetups, where it's known that people go to trade Bitcoins. And so you can go to a certain park, a certain street corner on a particular day, and you know that there will be people standing around wanting to buy or sell Bitcoins, and you can do business with them. And here you see a bunch of people at one of these meetups looking at their phones with their apps to transfer or verify transfer of Bitcoins. And so these are all the ways that you can trade, or the popular ways that you can trade Bitcoins against dollars. Okay, now this is a market, as I said. And the market matches buyers who want to do one thing with sellers who are willing to do the opposite thing. It's a relatively large market, meaning millions of US dollars per day pass through it. It's not like the New York Stock Exchange, or it's not like the dollars to euros market, which is vastly larger. But it's relatively large so that there is a notion of a consensus price, and that a person who wants to come into this market to buy or sell a modest amount at least will always be able to find a counterparty. The price of this market, this consensus price, like the price of anything in a liquid market, will be set by supply and demand. That is, what is the supply of Bitcoins that might potentially be sold, and what is the demand for Bitcoins by people who have dollars. The price through this market mechanism will be set to the level that matches supply and demand. But let's dig into that a little bit more. First of all, let's talk about what is the supply of Bitcoins. The supply of Bitcoins, that is the Bitcoins that you might possibly buy in one of these markets, is first of all equal to the supply of Bitcoins that are in circulation. Currently, of course, there's a fixed number of Bitcoins in circulation. At the time of this filming, it's about 13.1 million. And the rules of Bitcoin as they currently stand say that this number will slowly go up and hit a limit of 21 million eventually. But you might also sometimes include demand deposits of Bitcoins. That is, if someone has put money into their account in a Bitcoin exchange, and the account doesn't keep a full reserve to meet every single deposit, then you'll have demand deposits at that exchange that are larger than the number of coins that the exchange is holding. And depending on exactly what question you're asking about the market, it might or might not be correct to include demand deposits in the supply. So when should you include demand deposits? Well, basically, you should include demand deposits in a market analysis when demand deposited money can be sold in that market. So for example, if you're talking about exchange of dollars for Bitcoins that can happen in an exchange, if I have Bitcoins demand deposited in an exchange, I can trade those for dollars. And so if that's the scenario you're looking at, it would make sense to include demand deposits in that exchange as part of the supply. It's worth noting as well that when economists conventionally talk about the supply of a fiat currency, they typically include in the money supply not only the currency that's in circulation, that is the actual paper and metal money, but also the total amount of demand deposits. And that's for the logical reason that people can actually spend their demand deposited money to buy stuff. And so although it's tempting to say that the supply of Bitcoins is fixed at 13.1 million currently or 21 million eventually, for some purposes we have to include demand deposits, where those demand deposits function like money. And so the supply might not be fixed in the way that some Bitcoin advocates claim. And we need to look at the circumstances of the particular market we're talking about in order to understand what the proper money supply is. But let's assume we've agreed on what supply we're using based on what market we're analyzing. Let's now look at demand. There are really two main sources of demand for Bitcoins. There's demand for Bitcoins as a way of mediating fiat currency transactions, and there's demand for Bitcoins as an investment. So first, let's look at mediating fiat currency transactions. So here's the scenario. Imagine that Alice wants to buy something from Bob or wants to pay some money to Bob. And Alice and Bob want to transfer, let's say, a certain number of dollars. But they find it convenient to use Bitcoin to do this transfer. Perhaps they're at a distance. Alice wants to be able to email the money to Bob. Perhaps they like the fact that they can have very low transaction fees in Bitcoin and lower than some other service. Whatever the reason, they want to use Bitcoins to mediate this transaction. So the way that works is this, that first Alice buys Bitcoins for dollars. Alice then sends those Bitcoins to Bob as a Bitcoin transaction. Once that transaction is recorded in the blockchain and it's confirmed to Bob's satisfaction, Bob will sell those Bitcoins for dollars and get the dollars back. So Alice starts by putting in dollars, Bob ends by getting out dollars. But the key thing for the purpose of Bitcoin demand is that the Bitcoins that are mediating this transaction that are bought by Alice in step 1 and sold by Bob in step 3 have to be taken out of circulation, and they're devoted to serving this transaction during the time that the transaction is going on. And that creates a demand for those Bitcoins. If there are a lot of people who want to mediate transactions like this, whether those are fiat currency transactions or other transactions, if they want to mediate transactions, that will generate demand for Bitcoin. So that's the first source of demand. The second source of demand is that Bitcoin is sometimes demanded as an investment. That is, somebody wants to buy Bitcoins and hold them, in the hope that the price of Bitcoins will go up in the future and that they'll be able to sell them. So to the extent that people are buying and holding those Bitcoins are out of circulation, but there's a demand to buy Bitcoins, at least depending on the price. When the price is low, you might expect a lot of people to want to buy Bitcoins as an investment. But if the price goes up very high, then the demand for Bitcoins as an investment won't be as high. So that's the second source of demand. Now, we can do some simple economic modeling to understand how these markets will behave. And I'm not going to do a full model here, although that's an interesting exercise. What I want to do is look specifically at the market at the effect of this transaction mediation demand and what effect that might have on the price of Bitcoins. And we can build a simple model for doing that. So here's a simple model of the demand that's driven by transactions, by transaction mediation, and what it tells us about what the price should be. So we're going to assume some parameters here. First, we're going to say T is equal to the total transaction value that's going to be mediated via Bitcoins by everyone who's participating in the market. And that's going to be measured in dollars per second. We're going to assume for simplicity that the people who want to mediate these transactions have in mind a certain dollar value of the transactions. Or if it's some other fiat currency, we'll translate it into dollars for simplicity. So there's a certain number of dollars per second of transactions that need to be mediated. We're going to say D is equal to the duration of time that Bitcoins need to be held out of circulation in order to mediate a transaction. That's the time from when the payer buys the Bitcoins to when the receiver is able to sell them back into the market, and we'll measure that in seconds. And then S is going to be the supply of Bitcoins that are available for this purchase. And so that's going to be all the Bitcoins that exist. That is all of the hard currency Bitcoins, all of the 13.1 million or eventually up to 21 million Bitcoins, not including those that are held out by people as long-term investments. So at any point in time, there's some supply of Bitcoins that are sloshing around and available for this purpose. Okay, and now we can do some calculations. The first thing we'll do is we'll calculate how many Bitcoins become available in order to service transactions per second. Well, there are S Bitcoins in total that are used, and because they're taken out of circulation for a time of D seconds, then every second about 1 over D fraction of those Bitcoins will become newly available because they'll emerge from that out of circulation state. And so on average, S over D Bitcoins will become available for mediating transactions every second. That's the supply side. On the demand side, the number of Bitcoins per second that are needed to mediate transactions, well, we have T dollars worth of transactions to mediate. And in order to mediate $1 worth of transaction, we need 1 over P Bitcoins. That is, we need to take this T, which is measured in dollars per second, and divide it by the price in dollars per Bitcoin, and the result we get is Bitcoins per second. These are the number of Bitcoins per second that are needed in order to serve all the transactions that people want to serve. Okay, so if you look at a particular second of time, for that second, there's a supply of Bitcoins of S over D, and there is a demand of T over P. And now, if you think about the dynamics of this market, it behaves like many markets, in that the price will fluctuate in order to bring supply into line with demand. If the supply is higher than the demand, then there are Bitcoins that are going unsold. And so the people who are selling Bitcoins will be willing to lower their price to try to sell those Bitcoins. And so the price will come down if supply is higher than demand. And when the price comes down, that will cause demand actually to go up because P, the price, is in the denominator of demand. So if supply is bigger than demand, then demand will be pulled up. On the other hand, if demand is higher than supply, that means that there are people who want to get Bitcoins to mediate a transaction who can't get them because there aren't enough Bitcoins around. And so those people will bid more in order to get their Bitcoins. They'll have to bid more because there'll be a lot of competition for the limited supply of Bitcoins. And so if the demand is higher than the supply, the result is that price will go up. And when price goes up, then because price is in the denominator of the demand, that means demand will come back down. Demand for Bitcoins will come back down as the price goes up. So if you have supply here and demand here, then the demand will be pulled down toward the supply. Right? And so if the supply is at some point, that the demand, we've argued, will always be pulled toward the supply. And in fact, the two will come into equilibrium. And so the equilibrium condition, the point where you'll end up in this market, is where this supply, S over D, is equal to the demand, T over P. And so if you set those two expressions equal to each other, and then you solve for P, the price, what you get is this, that in equilibrium, the price should be equal to T times D divided by S. All right, so what does this mean? Well, one thing we can conclude about this is that if you think of D as being, D, the duration, as not changing, because probably the duration that you need to hold a Bitcoin to do a transaction is not going to change. So if D doesn't change, and if S, the supply, is not changing, then what this tells us is that the price is going to be proportional to the demand for transaction mediation as measured in dollars. And so if the demand for transaction mediation in dollars doubles, then the price of Bitcoins should double. And we could in fact graph the price against some estimate of the demand for transaction mediation and see whether they match up. And when economists do this, they do tend to match up pretty well. So we could graph the price of Bitcoins against the demand for transaction mediation as you can best estimate it in dollars per second. And those things should tend to be proportional over time. And when economists do that, they do tend to match up pretty well. The other thing we can note is that supply is in the denominator here, and that supply includes only the Bitcoins that aren't being held as investments. And so what that tells us is if more people are buying Bitcoin as an investment, the result will be that coins are withdrawn from this status where they're available to mediate transactions. And so the S that we're using here will go down. So that if investors are buying a lot of Bitcoins, it will drive down S, and therefore P will go up. And so that makes sense. If there's more demand on the investment side, then the price that you need to pay to mediate a transaction will go up. Right? Now, this is not a full model of the market. In order to have a full model, we need to take into account the activities of investors. We need to bear in mind that investors will demand Bitcoins when they believe that the price will be higher in the future. And so we need to think about investors' expectations. And investors' expectations, of course, have something to do with what is the expected total transaction value demand in the future. And we could build a model that's more complex. I'm not going to do that here, but you get a flavor of the kind of thing that you can do. So the bottom line here is that there is a market between Bitcoins and dollars, or Bitcoins and other fiat currencies, that market has enough liquidity that you can buy or sell in modest quantities in a reliable way, although the price does go up and down, and that it's possible to do economic modeling and get some idea of how supply and demand interact in this market and predict what the market might do, as long as you understand unknowable things like how much are people going to want to use Bitcoin to mediate transactions in the future. That kind of economic modeling is important to do and very informative, and I'm sure that there are people who are doing it in some detail today. But a detailed economic model of this market is beyond the scope of this course.
All right, welcome to the 5th lecture on Bitcoin. Today is going to be all about mining. So to recap, what have we learned about the miners so far? Well, we've heard about the miners quite a bit, and we know that Bitcoin depends on the miners pretty heavily to perform a couple of important roles. Of course, they validate every transaction, they build all the blocks, and we know that the miners earn some reward. Who are the miners? How did they get into this? How do they operate? What's the business model like for miners? What impact are they having on the environment? We're going to get to all those questions in today's lecture. So we'll start by talking about what Bitcoin miners actually have to do in order to be miners. And maybe before we get into that, we'll talk about some historical miners. So if you're thinking about becoming a Bitcoin miner, I wouldn't want to completely discourage you, but I'd be remiss not to tell you that this is not a get-rich-quick scheme. This is a very long haul. So looking back at some historical gold rushes, they're full of stories of young people rushing off hoping to find fortune, a lot of them losing everything that they have, some of them making it really striking it rich, but a lot of hardship along the way. This is probably my favorite example from the Klondike Gold Rush in Alaska in 1898. This gold rush all happened within a matter of 6 months, so there was a huge rush to get there for the one summer mining season. And all of these people are trudging up this snowy mountain pass with all of their equipment at the same time. Doesn't look like the easiest way to get rich. And I'll argue that Bitcoin mining is starting to look like a similar proposition. So what do you have to do to be a Bitcoin miner? In 6 easy steps? Well, you join the network, you become a Bitcoin node, you listen for all of the transactions that people are broadcasting. Of course, you have to validate them. You listen for new blocks that people have found. You maintain a view of the current blockchain. Of course, you want to validate all the blocks and all the transactions that are in those blocks. You start to assemble new valid blocks based on the transactions that you're hearing. Then you have to work really hard in step 4 here to find a nonce that will make your block considered valid. That's the really difficult computational step where all of the difficulty really happens for the miners. Finally, if you're lucky enough to find a block, you have to hope that all of the other miners accept your block, that they validated and start mining on top of it, and that they don't accept some competitor's block instead. And if all of that happens, in step 6 you finally get to profit, currently to the tune of over 25 Bitcoins per block, worth about $15,000 US. And so a couple of these steps, all of the validation in particular, are what's actually useful to the Bitcoin network. So that's why we have mining at all. Miners perform this validation step. The rest of it, the profit and the race to find blocks, that's all just incentive to encourage the miners to do the validation which is necessary for Bitcoin to function as a currency. So what does the process look like for finding a valid block? Well, we'll have to look back to the data structure that we introduced 2 lectures ago and recall that there are 2 main hash-based data structures here. There's the blockchain, where each block header points to the previous block header in the chain. And then within each block, there's this Merkle tree, this hash-based binary tree of all of the transactions included within that block. So the first thing that you do as a miner is you assemble all of the transactions that you have from your pending transaction pool into this tree. You create a block with the right header that points to the previous block. And then you have to start searching over this nonce field to try to have the hash of the block header start with the required number of zeros. So you may start with a nonce of all zeros. That's a 32-bit integer. And when you try that, you'll get a hash that's incorrect. So you'll say, OK, let's move on to the next nonce, nonce number 1. The hash is also incorrect. Step forward one more time, try hash 2, also incorrect. So you can see where this is going. And in a lot of cases, you'll try every single possible value for that 32-bit integer, and in no case will the hash be correct. So at this point, you're going to have to make further changes. And you'll notice that there's this parameter in the Coinbase transaction. And remember that the Coinbase transaction is where the miners are actually minting new coins and claiming them for themselves. There's also this extra nonce parameter in there. So after you've exhausted all possible nonces in the block header for the extra nonce in the Coinbase transaction of all zeros, you'll step the extra nonce in the Coinbase transaction up to 1, and then you'll start searching nonces in the block header once again. And it's important to realize that when you change that one parameter in the Coinbase transaction, the entire Merkle tree of transactions has to change. So that change will propagate all the way up. Changing the extra nonce in the Coinbase transaction is much more expensive than changing the nonce in the header for that reason. So you do that as the outer loop, and the inner loop where you're really working hard is changing the nonce in the block header. Okay, but once again, our first try didn't work here, so we'll have to keep stepping that nonce. And again, this is a really difficult computation, so the vast majority of nonces that you try aren't going to work. But eventually, if you stay at it long enough, you'll find the right combination of the extra nonce in the Coinbase transaction and the nonce in the header, and you'll find a block with a hash that starts with enough zeros to be considered valid. And this is when you want to announce it as quickly as you can and hope that you can profit from it. So I said it was difficult. Exactly how difficult is it? Well, as of today, this is the mining difficulty target. So the hash of any valid block has to be below this value here. And this is a 256-bit hash output. We're using SHA-256, the hash function, which is appropriately named. It's 256 bits. Currently, at least the first 64 bits of the hash of any valid block have to be set to 0. Overall, the current difficulty is about 2 to the 66, which is a really huge number. If we try to write it out in decimal, that's what we get. That's 84 quintillion. And this number is so big, it's difficult to even imagine. One approximation for it that you can think about is it's about the population of the Earth squared. So basically, if every person on Earth was themselves their own planet Earth with 7 billion people on it, the total number of people would be close to this number. Or another way to think about it is that if all 7 billion people on Earth shook hands with each other, fewer than 2 to the 66 total handshakes would have to take place. So this is an incomprehensibly huge number. So where did this number come from? How is the mining difficulty set? It's actually chosen again every 2 weeks based on how efficient the miners were over the previous 2 weeks. So you simply take the amount of time that it took the miners to find the previous 2016 blocks, and you divide that amount of time by 2 weeks, and then you multiply that ratio by whatever the previous difficulty value was to get the next difficulty value. So you're just scaling it to keep a constant property true, which is that blocks should be found by the network on average about once every 10 minutes. That's the fixed constant that was chosen at the beginning of time for Bitcoin, and every 2 weeks the difficulty is reset to ensure that that property is maintained. So you can see that over time, the mining difficulty keeps increasing. It's not necessarily a steady linear increase or an exponential increase. It depends on activity in the market, how many new miners are getting into the game, which may be affected by the current exchange rate of Bitcoin. But generally, more and more hash power comes online, more people are hashing, blocks are found faster, and the difficulty is adjusted up so that it again takes 10 minutes to find blocks. And you can see that in the red line on the graph here, there's a step function of difficulty. Even though the overall network hash rate is growing smoothly, because you only reset every 2 weeks, the difficulty steps up. Another way to view this is to look at how long it takes to find a block on average. So here you can see a graph of over time how many seconds elapse between consecutive blocks in the blockchain. And you can see that this gradually goes down, and then it jumps up again, and then gradually goes down. And of course, what's happening there is that every 2 weeks the difficulty resets, and the average block time goes back up to about 10 minutes, and then more and more power goes online. The difficulty stays the same, so the miners are finding blocks faster and faster. And then 2 weeks pass, the difficulty resets back up to 10 minutes, and the process starts all over again. So in actuality, even though the goal was for a block to be found every 10 minutes, on average it's more close to about every 9 minutes, and at the end of the 2 week cycle it will get down to about every 8 minutes. All right. Now we're going to talk about what hardware miners use to achieve this computation, which I've just spent time telling you is really, really difficult to do. So first of all, what exactly is this computation? So we've mentioned hash functions and we've mentioned SHA-256 in particular. What exactly is SHA-256? Well, it's a general purpose cryptographic hash function. It's actually part of a bigger family of functions that was standardized in 2001. It did come out of the NSA, which has led to a couple of interesting conspiracy theories by some people about its relationship to Bitcoin. But it's generally considered a fairly strong hash function. It's not broken cryptographically, although there are some theoretical weaknesses that are starting to show up. As a result, the replacement, the SHA-3 family, has already been picked, actually, and it's in the final stages of standardization today, but it wasn't available at the time Bitcoin was designed. This was a good choice. This was the strongest general purpose cryptographic hash function available at the time. It is possible that it will become less secure over the lifetime of Bitcoin, but for now it's pretty good. So what does it look like? This is a diagram of what the SHA-256 state looks like. And we don't need to know all of the details of this to understand how Bitcoin works, but I'll just give a high-level overview to give an idea of the task that needs to be solved by the miners. So there's a 256-bit state in SHA-256. It's split up into 8 32-bit words. So this is very much optimized for 32-bit platforms. And in each round, some of those words are taken. There's 4 different tweaks that are applied to those words that are at the bit level. So each one of these is 2 or 3 bits being flipped or anded together, basic logic operations. And then a number of words in the state are taken, some with these tweaks applied, and added together mod 32 in a pipeline here. And then the result of all of these additions is wired over to the first word of the state, and the entire state shifts over. So some of the design here, some of the design ideas date back to classic linear feedback shift registers, which was one of the earliest approaches to cryptographic design. So all of this happens. This is just one round of the SHA compression function. And a complete computation of SHA-256 does this 80 times for 80 iterations. And in each iteration, there are slightly different constants applied at that one step there so that every iteration isn't exactly the same. So this is the task ahead of miners, to compute this specific function, only this, as fast as possible. And so you can see that to do this, you need to be able to deal with 32-bit words, you need to be able to do 32-bit addition, and you need to also be able to do some bitwise logic. So the first generation of mining, when Bitcoin was originally proposed, was all done on general purpose computers, general purpose CPUs. In fact, it was as simple as this code here that simply searched over nonces in a linear fashion, computed SHA-256 in software, and checked if the result was a valid block. And one quirk, which I haven't mentioned yet, this is probably a good time to mention it if there ever was one, is that for reasons that aren't completely specified, you actually compute the SHA-256 function twice. So it's just doubled up. That's a fact of life that miners have to live with. So how fast will this run on a general purpose computer? Well, if you're doing pretty well, if you have a high-end desktop PC, you might be able to do this at about 2 to the 24 hashes per second, which would be, about 20 megahertz. Remember that even though hertz often are applied for processor speed, the basic idea of hertz is it just means something that you're doing that many times per second. Okay, so if you're hashing at a rate of 20 megahertz, what does that get you with today's difficulty? Well, it would actually take you over 100,000 years at this rate to find a block. So we talked about how mining was going to be a difficult slog. If you're mining on a general purpose PC today, it's a really, really big hill to get up because it's going to take you that 140,000 years. So as a result, today, and even for the last few years, anybody trying to do mining on a CPU probably didn't understand how Bitcoin worked, and were probably pretty disappointed that they never made any money doing it. So CPU mining was the first generation of mining. The second generation, when people started to get frustrated with how slow their CPUs were, was to try to use their graphics card, their graphics processing unit, or GPU. So what is a GPU? Almost every computer now has a GPU built in for high performance graphics. They're designed to have high parallelism, which does help with Bitcoin mining because you can parallelize and compute multiple hashes at the same time for different nonces that you want to try. And they're also designed for high throughput, so there's a highly pipeline design in graphics cards. And around 2010, the first implementation came out written in a language called OpenCL, which is a general purpose language to do things other than graphics on a GPU. And it's a high-level language, so it took a little while before people started tweaking the code even further to run quickly on specific graphics cards. So what's the advantage of using a graphics card? Well, for one thing, they're easily available and they're easy for amateurs to set up. You can order graphics cards online. You can buy them now at most big consumer electronics stores. So they're just the most accessible high-end hardware that's available to most people. They also have some properties that make them specifically nice for Bitcoin. They're designed for parallelism, so they have a lot of arithmetic logic units, ALUs, that you can use in parallel to do different SHA-256 computations. And some of them also have some specific instructions to do bit fiddling that work out quite nicely for SHA-256. They also have the property that you can drive many graphics cards from one motherboard and CPU, so you could take your one computer and attach multiple graphics cards to it if you want. Most graphics cards can also be overclocked, which is a property that gamers demand, so you can run them faster than they're actually designed for if you want to take the risk on. And with Bitcoin mining, it might be a good idea to run the chip much faster than it was designed for, even if you introduce some errors into the process. So there's a measure of mining success called goodput, which is the throughput, how quickly you're finding blocks, times the success rate. How often does the computation actually have errors? An interesting observation is that it may be worthwhile to go much faster even if you make a large number of errors if it leads you to find valid blocks more quickly. So if you can tweak one knob and run your graphics card 50% faster, even if you have an error in the SHA-256 computation 30% of the time, you just multiply 1.5 times 0.7 and you're still finding blocks faster than running the chip at normal speed with no error. So this is something that people spent a long time optimizing, exactly how much should they overclock the chip and what errors it would introduce. So people started trying to scale this up. They said, aha, I have a graphics card, I'm mining faster than I was on my CPU. What's better than one graphics card? Lots of graphics cards. And you started to see these really interesting homebrew setups like this one here, where people hand-built their own racks. They had their own custom cooling setup, which was often as simple as buying a bunch of fans or a bunch of air conditioning units, and trying to run as many GPUs as possible in their basement or whatever other room was available to them. So this was obviously in the early days of Bitcoin, when it was still mostly hobbyists who didn't know a lot about running a modern data center, but they came up with some quite ingenious designs to pack a lot of graphics cards into a small place and try to keep them cool. Now, what are the disadvantages of doing this? Well, GPUs actually have a lot of other hardware specifically for doing video. Specifically, they have floating point units that you don't use at all on SHA-256. So you're actually wasting a lot of the hardware from what the factory built. They also don't have the greatest cooling characteristics when you put a lot of graphics cards next to one another. They're not designed to be run all in a row like I showed on the previous slide. They're designed to be run one graphics card in one box doing graphics for one computer. They can also have a fairly large power draw, so a lot of electricity is being used by these relative to a computer. And initially there was the problem that you had to build your own board or buy expensive boards to actually house multiple graphics cards. So what's the upshot of this? What kind of performance can you get? Well, on a good card, a really high-end graphics card with a lot of aggressive tuning, you might get as high as 200 megahertz, which is about 2 to the 27 hashes per second. So that's up to an order of magnitude better than you would be doing in the CPU case. But even with that improved performance, and even if you're really aggressive and you say, I want to get 100 graphics cards together for my mining rig, that setup would still take you 174 years to find a block at the current difficulty. So it was a fun era while it lasted, but graphics cards for Bitcoin mining is basically dead. So what replaced graphics cards? Well, around 2011, people started to use FPGAs, or field programmable gate arrays. That was around the time that the first implementation of Bitcoin mining came out in Verilog, which is the hardware design language that's used to program FPGAs. And FPGAs are something that maybe you've programmed before if you've taken a hardware design course. They're designed to have hardware-like performance, but to have customers or the owner of the card being able to customize it or reconfigure it in the field, unlike a chip which is made in a factory and does the same thing forever. So they do offer better performance than graphics cards, particularly on some of the bit fiddling operations. That kind of stuff is very easy to spec out in an FPGA. And if you know what you're doing, you can get the cooling to work out better with an FPGA. You're wasting a little bit less of the card than you would be with a graphics card. And you can pack more of these together and drive them from one central unit. So just like with the graphics cards, people said, once I have the FPGA working, why don't I try getting a lot of FPGAs? And now this doesn't look quite as messy as the graphics card setup looked. This is a relatively neat rack with neat wires. You don't see the cooling setup here. You still needed a cooling setup with air conditioning or with fans. But it was possible to build a big array of FPGAs a little bit more neatly and cleanly than you could with graphics cards. The disadvantages of using FPGAs are that they were being driven harder for Bitcoin mining by being on all the time and working as hard as possible than a lot of consumer-grade FPGAs were really designed for. So a lot of people found a number of errors and malfunctions in their FPGAs as they were doing Bitcoin mining. It turned out to be difficult to optimize the 32-bit add step, which, as we said, is critical for doing SHA-256. They were also just less accessible for people. It's harder to buy an FPGA. You can't buy one at most stores. There are fewer people who know how to program FPGAs or know how to set them up. And it turned out that the cost, even though the performance on FPGAs went up, the cost per performance was only an incremental, very marginal gain over using graphics cards. So it was a pretty short-lived reign, whereas people were mining on graphics cards and graphics cards were king for maybe a year or so. It was a much shorter matter of months where FPGAs were a popular solution for Bitcoin mining. But if you were using an FPGA and using it well, you might get up to about 1 gigahertz. And now it sounds like we're making some real progress. We're doing 1 billion hashes per second. But even with a 1 gigahertz setup on an FPGA, and even if you had 100 boards, so again, even if you bought a lot of FPGAs and shoved them all into your amateur mining rig, it would still take you 25 years to find a Bitcoin block at that rate. So this is still not looking like a really attractive thing to jump into. And you might be asking, if all of these solutions are so intractable today, what are people actually doing? Well, mining today is essentially dominated by Bitcoin ASICs, or application-specific integrated circuits. So these are chips that were designed and built from scratch to do nothing except mine Bitcoins. They were fabbed out at a factory, packaged up, and sold to a consumer solely to be Bitcoin miners. And if you go online today, you can find a lot of people willing to sell you Bitcoin mining ASICs. There's a couple of big vendors that now do this as a full-time product. So these companies have sprung up in the last 2 years, and the main product, in some cases the only product that they sell as a business, is Bitcoin mining ASICs. And now you'll notice when you're buying an ASIC, you have a lot of options. You can choose between slightly bigger and more expensive models, more compact models, and they'll throw a lot of numbers at you in terms of what the performance is going to be, the cost, how much power it's going to use. But the most important thing to look at in a lot of these cases is how quickly they're going to ship to you. So a lot of ASICs have a pretty strong disclaimer that you have to pre-order them before they're even available, and they don't make any firm guarantees on when they're going to be delivered. So again, since these are new companies selling the ASICs, they've had to be funded as they went, which means they need to essentially pay for the production run of ASICs with consumers' pre-orders. And that means there's a lot of pressure on consumers to pay before the chip is ready. In a lot of cases, the chips have been shipped late, and this has caused considerable consternation and heartache for customers. There are a lot of dramatic complaints and stories and tales of woe of people who spent good money on a Bitcoin ASIC and were hoping to really strike it rich when the thing came in the mail, only it came in the mail later than they were expected. Like I said, these are special purpose. They're designed to be run at full speed constantly for life to do nothing other than mine Bitcoins. They require a lot of expertise and a long lead time to design, so much more complicated to actually tape out a chip than to just write an implementation in OpenCL or in Verilog. But the amazing thing about Bitcoin ASICs is that as hard as they were to design, analysts who've looked at this have said this may be the fastest turnaround time essentially in the history of integrated circuits for specifying a problem, which was mining Bitcoins, and turning it around to have a working chip in people's hands. So this was really a rush job. People realized the need to have Bitcoin mining ASICs and the fact that they could sell them for a lot of money. They designed them extremely quickly and started shipping them to consumers. And as a result, you can probably expect there were a lot of bugs in the first few generations of these things. Some of them didn't deliver. In fact, most of them probably didn't deliver quite the performance that they were promising. Some of them, in fact, were quite buggy. But it's evolved a lot over the past year, and there are now fairly reliable ASICs being shipped. So what does it look like if you actually want to buy one of these things? So here's just a case study of something that's been available for about 6 months now, so it's already a little bit out of date. But this TerraMiner 4 is this nice big fancy box you see here. And this hashes at about 2 terahertz, so it's 1,000 times faster than that hypothetical array of 100 really good FPGAs that we were talking about previously. So you'd have to pay about $6,000 for this. And even with this incredible performance, it would still take 14 months on average to find a block. So even if you think that you're investing in a fairly nice piece of hardware, it's still extremely difficult to mine a block. And the market dynamics are really interesting here. So most boards that have been coming on the market since ASICs came out have been effectively obsolete in maybe 6 months. And on top of being obsolete within 6 months, the bulk of the profits are made upfront. Often in the first 6 weeks is when you'll make half of the expected profits in the lifetime of a mining rig. The fact that such a high proportion of the profits are made in the first 6 months means that there's an incredible premium on shipping speed. If your thing ships a week late, you may have lost 1/6 of that optimum time. In fact, you'll have lost the most valuable week in the lifetime of the ASIC because its value is only going to go down over time as mining gets more and more difficult. And this is really the motivation for why so many companies require pre-orders. The fact that there's so much competition to get the ASICs first. And there's a lot of speculation that some companies have actually manufactured the ASICs, tried to run them themselves for a couple of weeks before shipping them, and then ship them off to consumers. So the dynamics of this are still very unfavorable to the small miner who wants to go online, order an ASIC, and start making money. And in fact, in almost all cases, people who've placed orders for mining hardware should have lost money based on the calculation that they made at the time. Except for one thing, which is that the price of Bitcoin has been rising for most of the history of Bitcoin. It has leveled off a lot in the last 6 months or so. But during the period when prices were rising, the rising prices often bailed out miners who would have lost money if prices had stayed constant. So in effect, buying Bitcoin ASICs has been an expensive and convoluted way to simply bet that the price of Bitcoin would rise. And a lot of miners, even though they've made money mining Bitcoins, would have been better off if they had just taken the money that they were going to spend on mining equipment, invested it in Bitcoins, held them while they appreciated in value, and then sold the Bitcoins at the end. And now we're firmly in the era of professional mining. So the details are often pretty scant because companies doing this don't want to share exactly what their setup is. But it is known that there are some professional mining centers popping up around the world now. And here's just one picture that's been made available of one that came online in the last couple months in the Republic of Georgia. So if you want to open a professional Bitcoin mining center, where should you go? You basically need 3 things. You need cheap electricity. You need good network connectivity so that you can hear about new blocks as they're announced and not miss out. And ideally, you'd like a cool climate so that you don't have to pay too much in your cooling bill to cool all this equipment down. So in addition to Georgia, places like Iceland have been popular destinations for people to try to start their Bitcoin mining data center. So if we zoom out a little bit and we think about the evolution of mining, we can see really interesting parallels between Bitcoin mining and gold mining, or really any other kind of mining, but especially gold mining, because it's led to the same kind of gold rush mentality when initially a lot of young amateur folks wanted to get into the business. So whereas with Bitcoin mining, we've seen the slow evolution from CPUs to GPUs to FPGAs to now ASICs, with gold mining, we saw the evolution from individual people with a gold pan to maybe a small team of people with a sluice box, to placer mining, which was a big group of people blowing away hillsides with water, to modern gold mining, which is a giant open pit extracting tons and tons of raw material from the earth. And in both cases, the friendliness to small people trying to jump into this has gone down, and there's been a consolidation with large companies owning most of the action over time. So a couple of questions for the future are small miners out of Bitcoin mining forever? Is there any way to make it as a small miner in this game? And does that violate the original spirit of Bitcoin? Does the existence of these ASICs and these large mining centers go against the original vision of Satoshi Nakamoto, which was to have every individual in the network being a miner running on their own computer? So some people who think that this has been a violation of the original vision wonder, would we be better off if there were no mining ASICs? If the only way to mine Bitcoin was using your CPU like in the good old days? Well, we're going to have a lecture later on in the series, which I'll point forward to a number of times in this lecture, where we look at alternative formulations of mining that might be possible. So I won't say anything more about how we could design mining to be less friendly for ASICs here, but that will be a topic that will come up in the future that will be quite interesting. So in the last section, we ended by showing how large professional mining data centers have taken over the business of Bitcoin mining. And we showed the parallel to traditional mining with those open pit mines on the bottom, which you may know have been a huge source of concern for environmentalists over the years, asking how much damage are these pit mines doing to the environment. Now, Bitcoin is not quite at that level yet, but as I said, it is a very difficult computation with a lot of large players interested in competing now. And it is starting to use a significant amount of energy, which has become a topic of discussion. So in this section, we'll talk about how much energy Bitcoin is using and what that might mean for the currency and for the planet. So to start with, we'll talk about why computation inherently requires some energy. So there's a principle developed by Rolf Landauer in the 1960s that any non-reversible computation must use a minimum amount of energy. So this is derived from basic physics. And we're not going to go through the derivation here, except to say that every time you flip one bit in a non-reversible computation, there's a minimum number of joules that you have to use. And of course, if you remember some fundamental theorems of physics, energy is never destroyed, it's only converted from one form into another. In the case of computation, it's mostly that energy is transformed from electricity, which is very high-grade energy, into heat, which is dissipated into the environment. Now, of course, SHA-256, being a hash function, which is the basis of Bitcoin, is not a reversible computation. And if you remember all the way back to lecture 1, this was a basic requirement of hash functions that they're not reversible. So since I told you that any non-reversible computation has to use some energy, and SHA-256 is not reversible, energy consumption is an inevitable fact of doing Bitcoin mining. And it is worth saying that the limits provided by Landauer's principle are far, far below the amount of electricity that's being used today, by over a factor of 1,000. So we're nowhere close to the theoretical optimum efficiency of computing, But even if we did get to the theoretical optimum, we would still be using some energy to perform Bitcoin mining. So why does Bitcoin mining require energy? There are 3 steps in the process that require energy. First, you have to manufacture your Bitcoin mining equipment. So that requires both physical mining, digging up things out of the ground, especially rare earth metals and copper that go into integrated circuits. And then you have to manufacture it into a Bitcoin mining ASIC. So it takes a lot of energy to run fabs and to tune out chips. So all of that energy is called the embodied energy. As soon as you receive a Bitcoin mining ASIC in the mail that you order, you've already consumed a lot of energy, including the shipping energy, of course, just to get that to you before you've even turned it on and tried to mine Bitcoins. Then you'll plug it into the wall and turn it on. And of course, it will be drawing electricity constantly while it's on, and that's the electrical energy consumed in mining. And that's a step that, no matter what happens, has to be consumed because of Landauer's principle. So hopefully, over time, the embodied energy will go down as less and less new capacity comes online. Fewer people are going out to buy new mining ASICs. They're being obsoleted less quickly. The existing fleet can last a long time. The embodied energy will be amortized over years and years of mining. But the electricity consumption, even though it will go down a little bit because rigs will get more efficient, that will be a fact of life forever. The other thing about both electricity and embodied energy is that both are probably less if you're operating at a large scale. If you're running a huge mining data center, you can do it more efficiently. It's cheaper to build chips that are designed to run in a large data center, and you can deliver the power more efficiently because you don't need as many power supplies. You can deliver all of the electricity to one place, and so on. But there's a third important component, which is cooling off your equipment to make sure that it doesn't malfunction. So if you're operating your equipment in Antarctica, maybe your cooling budget is very small, but almost anywhere else you're going to have to pay extra, usually electricity, to cool off your equipment from all the waste heat that it's generating. And the interesting aspect about cooling is that cooling actually costs more the bigger your scale is. So if you want to run a very large operation and have a lot of Bitcoin mining equipment all in one place, your cooling budget is going to increase because cooling that big mass is going to be much more difficult. There's less air for the heat to dissipate into surrounding your equipment. So how much energy is the entire Bitcoin network using? There are 2 basic approaches to trying to estimate how much energy the Bitcoin network is using. Of course, we can't compute this precisely because it's a decentralized network with miners operating all over the place who haven't documented exactly what they're doing. But we'll start with a really simple approximation strategy, which is to take the fact that about $15,000, and again that's 25 Bitcoin, of reward are created with every block, which is found every 10 minutes. So if we convert that to revenue per second, we get about $25 per second that are being minted and given to the mining community. Now, if the miners are turning all of those $25 per second into electricity, how much can they get? Well, at US industrial electricity prices, and this will vary from state to state or certainly from country to country, but we'll go with about 10 cents US per kilowatt hour. And kilowatt hour is kind of a funny marketing unit, so we'll go to the more standard scientific unit of the megajoule. So if the miners took those $25 that they earn every second and converted it purely into electricity, they would get about 900 megajoules every second. And of course, joules per second are just watts, so those 900 megajoules per second are 900 megawatts, or 900 million watts. A second way to estimate the same figure is to do a bottom-up approach, and to say, let's look at how many hashes the miners are actually computing, which we know by observing the difficulty of each block, and what is the best hardware that miners might be using. So if you look online at mining rigs that are being sold commercially today, one of the best performance figures that you'll see is rigs that are able to turn 1 watt of electricity into about 1 gigahertz of hashing. So they perform 1 billion hashes per second while consuming about 1 watt of power. And the total network hash rate is about 150 million gigahertz, or 150 petahertz. Of course, that excludes all of the cooling energy and all of the embodied energy that's in those chips, but we're doing an optimal calculation here. So if the entire network was running at about the efficiency of generally the better chips on the market, what would we get? If we just multiply these two together, we would get about 150 megawatts to produce that many hashes per second at that efficiency. So again, last slide I said at a high end, using the top-down approach, we estimated about 900 megawatt. And using the bottom-up approach, this is a lower bound, about 150 megawatt. So maybe for the whole network today, somewhere between 100 megawatts and a gigawatt of electricity are being consumed. In reality, of course, it's probably somewhere in the middle, and it's going to evolve over time, but that's a useful ballpark to think about right now. So how much is a megawatt? Well, we can look at what big power plants produce. So one of the largest power plants in the world, the Three Gorges Dam in China, is a 10,000 megawatt power plant. It actually has slightly higher capacity than that, but that's the average rate of power that's being produced. Whereas a typical large hydro plant is more like 1,000 megawatts. If you're interested in nuclear power, we can look at the largest nuclear plant in Japan, and that's about a 7,000 megawatt plant, whereas the average nuclear power plant is more like 4,000 megawatt. Or back in the carbon-heavy way of producing electricity, we can look at a major large coal-fired plant, and you might get 1,000 to 2,000 megawatts. So again, our high-end estimate was still that Bitcoin is consuming less than 1,000 megawatts. So the whole Bitcoin network is consuming less than a large power plant's worth of electricity. So it's not nothing. It still means that we have to essentially run a large power plant purely to power Bitcoin and not any of the other things that we need electricity for in the world. But it's not yet to the point where it's a large amount of electricity compared to all the other things that people are using electricity for on the planet. And it's certainly worth pointing out that any payment system is going to require energy and electricity. So when we look at traditional currency, a lot of energy is consumed moving gold bullion around, guarding the gold bullion, running ATM machines, running coin sorting machines, running cash registers, transporting the money around in armored cars. All of that is energy consumed by the traditional money system. So sometimes people have a tendency to think that Bitcoin is wasting energy because the energy is being expended in this SHA-256 computation that doesn't serve any apparent purpose. But you could also look at all of the energy used in a traditional currency system and say that it's also wasted and that it doesn't serve any other purpose besides maintaining the currency system. So that's a really important disclaimer, I think, that just because Bitcoin uses electricity, it's not necessarily wasted. If Bitcoin is a useful currency system, then the electricity is essentially being used for that purpose. But we still might think, is there something better that we could do with this electricity, rather than just heating up air which is sent off into the atmosphere? And one pretty interesting idea is, what if we tried to capture the heat that we're turning that electricity used in Bitcoin mining and use it for practical purposes? So this is called the data furnaces model. And the basic idea is that you would go down to your local hardware store, and instead of buying a traditional electric heater to heat your home or to heat water in your home, you would buy a Bitcoin mining rig that you would plug in both to the electricity outlet and also to your internet connection. And your heater would essentially be doing Bitcoin mining and using the heat produced as a byproduct of that computation to heat your water or to heat your home, which is hopefully useful. And it turns out that the efficiency of doing this isn't actually that much worse than just buying an electric heater. So this seems to be a great idea, and maybe it's a promising avenue to explore for the future. There's a couple of challenges here. For one, electric heaters are still much less efficient than gas heaters. So if you're in a really cold climate where people really need heat, hopefully they'll have gas heating in their home anyway. It's also not clear what the ownership model is here. If you buy the Bitcoin data furnace, do you own the Bitcoin mining rewards that you get? Or does the company that sold them to you? Most people don't have any interest in Bitcoin mining and probably never will, so it might make more sense to buy this as an appliance and have the company that sold it to you keep the rewards. And then there's the really basic question of what happens if everybody turns off their Bitcoin mining rig in summer? Will the capacity of the Bitcoin network go way down seasonally based on how much heat people need? Will it go way down on days that happen to be warmer than average? This would be really interesting if the data furnace model actually caught on. So a couple of open questions related to Bitcoin's energy consumption. Does the fact that Bitcoin provides such a good way to turn electricity into cash mean that countries that have strong electricity subsidies will have to rethink that model? So right now in many countries around the world, the government actually subsidizes electricity, particularly industrial electricity. And one of the reasons they do so is to try and encourage industry to be located in their country as opposed to other countries. Now, if one of the main things that Bitcoin miners need to be successful is cheap energy, and you can mine Bitcoins basically anywhere, it may not be stable to have countries subsidizing electricity heavily, because all that will mean is that you're paying for a lot of Bitcoin miners to move into your country. There's also the interesting question of, will the fact that you can turn electricity into money easily with Bitcoin mean that people have to start guarding their power outlets, particularly around universities and corporations, large buildings with a lot of power outlets? Will they need security cameras to make sure that employees or students aren't trying to mine Bitcoins by plugging into unmonitored power outlets and just letting them run? And you might ask, would we be better off if we didn't have this electricity consumption? Could we make a currency that didn't have proof of work and didn't have to use so much electricity? And again, I'm not going to talk about that directly today, but that's going to be a topic that we'll talk about quite a bit in our future lecture on alternative mining. Now we're going to talk about mining pools. So what is a mining pool? Well, let's look at the economics of being a small miner. So say you're an individual who spent $6,000 of your hard-earned money to buy a nice shiny new Bitcoin mining rig. Now, you expect that you'll find a block in about 14 months with this fancy new rig. And remember that a block is worth about $15,000 at today's prices. So if you amortize that, you could say that the expected revenue of this box is about $1,000 per month. And now maybe once you factor in electricity and your other costs of operating it, if you actually got a check in the mail every month for $1,000, that would make it worth it for you to buy this $6,000 mining rig. But remember that mining is a random process. You don't know when you're going to find the next block. It's a completely random search, and you could find your next block at any time. So if we look at the distribution of how many blocks you're likely to find in the first year with that hypothetical 1 terahertz box, the variance is pretty high because the expected number of blocks you're going to find is so low. So if we just look at the distribution, and this is a Poisson distribution, there's over a 40% chance that you won't find any blocks in the first year, in which case you might really be in trouble if you haven't earned any revenue in an entire year of running that $6,000 box that costs a lot of electricity to run. There's about a 36% chance that you'll find one block in the first year, in which case maybe you're barely scraping by. And then there's a slightly smaller chance that you'll find 2 or more blocks, in which case you'll really be making a profit with this thing. So again, on expectation, you might be just doing okay, enough to make a return on your money, but there's a big chance that you'll make nothing at all. So that means that for a small miner, mining is essentially a big game of roulette. Now, historically, when small business people faced a lot of risk and they wanted to lower the risk, they got together and formed mutual insurance companies. So farmers would get together and agree that if any individual farmer's barn burned down, they would share profits with that farmer so that that farmer wouldn't go bankrupt. And the question is, can we have a mutual insurance model that works for small Bitcoin miners? So that's what a mining pool is. Now, the goal of a mining pool is that a group of miners will get together, form a pool, and they'll all attempt to mine a block which pays the Coinbase, the newly minted coins, to the same recipient. That recipient is going to be called the pool manager. So no matter who actually finds the block, the pool manager will control the rewards. And then the pool manager will take that revenue and distribute it to all of the participants in the pool based on how much work each participant actually output. Of course, the pool manager will also probably take some kind of cut for their service of managing the pool. So this sounds like a great idea. You can see why it would be attractive to Bitcoin miners to join a pool to lower their variance. But how does the pool manager know how much work each of the members of the pool is actually performing? Obviously, the pool manager doesn't want to just take everybody's word for it, because everybody would say that they're performing more work than they actually did. So there's a really powerful idea, which is that miners can prove probabilistically how much work they're doing by outputting shares. And shares are blocks that are almost valid. So whereas it's pretty rare to find an actually valid block that starts with all 66 required zeros at the beginning of the output hash, there will be a lot more almost blocks that start with a lot of zeros, but not quite the 66 necessary to make it a valid block. So a common choice might be, say, 40 bits or maybe 50 bits, depending on what size the pool is designed for. Now, if miners participating in the pool send in a bunch of these near-valid blocks, the rate at which you're finding those near-valid blocks should give the pool manager a very good statistical idea of who's doing how much work. And the other nice property of this is that there's no way to fake it. Because of the properties of the hash function, there's no way to find almost blocks without also finding actual blocks at the expected rate. So how does this whole setup look? So to start with, in each round, after the previous block is discovered, the pool manager, which will be collecting transactions and assembling a block, will tell all of the participants, here's the next block that we're all going to work on. So they'll assemble the block header, they'll assemble a Merkle tree of transactions to be included in that block, and in particular, they'll make sure to put into that Merkle root of transactions the Coinbase transaction, which creates new coins and assigns ownership to the pool itself. And now this block header will be sent to all of the participants in the pool, and this is what they're asked to work on. And they have to prove that they've been working on it by sending in shares showing that they've been hashing this block. Now once that gets sent out, all of the miners go about and do their work, and they'll all slowly find almost valid blocks or shares until finally one of the miners, hopefully in the pool, finds a valid block that will then be published. Now, after this happens, all of the participants will send in all of the shares that they found to the pool manager, which should be pretty efficient for the pool manager to verify are valid shares that they found. And then the pool manager will take all of the revenue earned from that block that was published and distribute it back to the participants based on how much work they actually did. Now notice that this miner all the way on the right here, who did happen to find the block, actually receives less revenue than that miner on the left there, who didn't find the ultimately valid block, but they did find more shares. So there's no bonus for this miner on the right here that they actually found a valid share. They would have been better off if they just mined as an individual, because they would have gotten to keep all of the revenue from that block. But of course, for the miner on the left, they're sure going to be glad that they joined this pool, because they would have gotten nothing if they just mined on their own, because they happened to not find a valid block. So there are a bunch of variations on this model of exactly how you determine, based on shares submitted, how much money each miner should get in mining rewards. So a couple of common ones. There's the pay per share model, where the pool manager just announces, I'll pay a flat fee for every share above a certain difficulty that you're willing to send me based on this block. In some ways, that's the best for miners because that's a guarantee. Every time they find a share, they'll get a certain amount of money. The pool manager is essentially absorbing all of the risk in that scheme. Of course, as a result, usually with pay per share, you pay the highest transaction fee to the pool manager. Another way to do it is a proportional model, where instead of paying a flat fee per share, the amount per share depends on whether or not the pool actually found a valid block. So every time a valid block is found, the rewards from that block are distributed to the members proportional to how much work they actually did. So in this case, the miners still bear some risk proportional to the risk of the pool in general. So if the pool is large enough, the variance of how often the pool finds blocks will be fairly low. Proportional can still be a good approach, and it will provide lower risk for the pool manager. And it gets around a problem that's inherent to pay per share, which is that with pay per share, the miners actually don't have any motivation to send in valid blocks. They don't have any motivation not to, but miners have the option when they find a valid block of just keeping it a secret. Now they're hurting the pool by doing that, so this is purely an act of vandalism, but they have no real motivation since they get a flat reward per share to actually send in the valid blocks. Whereas with a proportional scheme, the miners certainly want to send in the valid blocks because that triggers revenue coming back to them. And a final variation that I think is interesting and was popular for a while is that the pool owner actually collects no fee, but miners can't receive any revenue out until their balance is over 1 Bitcoin. So basically, this means that new entrants to the pool don't make any money for a while, and then they make money at an even rate without paying any fee to the mining pool manager. So essentially, once you're established in a pool with this approach, it's a great place to be, but they're harder to break into. So this has become pretty advanced now. There are quite a few protocols to run mining pools, and it's even been suggested that these mining pool protocols should be standardized as part of Bitcoin itself. So just like there's a Bitcoin protocol for running the peer-to-peer network, these protocols are an API for communicating from the pool manager to all of the members when to work on a new block, what that block should be, and for the miners to send back to the pool manager the shares that they're finding. Another reason why this is so important is that some mining hardware actually supports these protocols at the hardware level. Now this makes it very simple to buy a piece of mining hardware, plug it into the wall, both the electricity and your network connection, choose a pool, and then it will start immediately getting instructions from the pool, mining and converting your electricity, hopefully, into money. So mining pools first started around 2010, actually way back in the graphics card era of Bitcoin mining, which is several generations ago. And they were instantly very popular for obvious reasons because they lowered the variance for the participating miners. So by 2014, the vast majority of all miners are mining through pools. Very few miners mine on their own anymore. And a very interesting thing happened in June of this year, where the largest pool, called ghash.io, got so big it actually had over 50% of the entire capacity of the Bitcoin network. Now this is something that people had feared for a long time, but essentially ghash offered such a good deal to all the participating miners that everybody wanted to join. Now since then, ghash has gone down a little bit, partly by design. They've made their fees a little bit less attractive to try to get smaller. But you can see in this pie chart of the largest mining pools, they still have about 1/3 of the power. And it's basically only 2 mining pools today that control about half of the power in the network. And then there's a nice smattering of other pools thrown in there. So are mining pools a good thing? Well, the advantages of mining pools are that they make mining more predictable for the participants, and they make it much easier for smaller miners to get involved in the game. Whereas the variance would simply make mining infeasible for economic reasons if you didn't have mining pools, you can operate a much smaller mining rig profitably if you're part of a pool. Another advantage of mining pools is that since there's one central pool manager who's sitting on the network and assembling blocks, it actually makes it easier to upgrade the network, because by upgrading the software that the mining pool manager is running, that effectively updates the software that all of the pool members are running. The disadvantages of mining pools, of course, is that this leads to centralization. It's an open question how much power the operators of a large mining pool actually have. Of course, miners are fairly free in theory to move between pools as much as they like. If you're making profit on one pool, you'll likely make very similar profit in another pool because the fees that they pay out have converged. They all offer about the same deal today. But in practice, miners don't switch very often, simply because they're lazy and it's easier to keep using the pool that they've already signed up for. And another disadvantage of mining pools is that it lowers the population of people actually running a fully validated Bitcoin node. So previously, small miners all had to run their own fully validating node. They all had to store the entire blockchain and validate every transaction. Now, most miners offload that task to their pool manager. And this is one reason why a couple of lectures ago I said the number of fully validating nodes may actually be going down in the Bitcoin network. So if you're concerned about this level of centralization, you might ask, could we redesign the mining process so that we don't have any pools, so that everybody has to mine for themselves? And once again, that's going to be a very interesting topic that we'll talk about in our lecture on alternative mining approaches. So the last topic in this lecture about mining will be mining incentives and strategies. So what do I mean by mining strategies? I've spent most of this lecture talking about how the main challenge of being a miner is to get some good hardware, get some cheap electricity, run as fast as you can, and hope for some good luck. But it turns out there's also some interesting strategic considerations that every miner has to make before they pick which blocks to work on. So in particular, miners get to choose which transactions they want to include in a block. The default strategy is to include any transaction that includes higher than some minimum transaction fee. Miners get to decide which block they want to mine on top of, and the default behavior there is to choose whatever the longest current chain is that's been announced. Miners have to choose how to decide between two colliding blocks when they get announced. So if two people find blocks around the same time, miners have to decide which block to extend because both will be the longest chain in history. And miners have to decide when to announce new blocks. They can choose to find a block and wait before actually announcing it to others. So in each case, there's a default strategy, which is what most miners are currently doing because they run the default Bitcoin client. Remember, it's about 90% of fully validating nodes run the default client. It's not clear what proportion of mining power that represents, but it's safe to assume that it's probably a majority. So most miners are doing this default strategy. So what if you want to change some of those decisions? Can you make more money as a miner if you implement some other strategy besides the default one? Well, it's all going to depend on how much mining power you actually have, and we'll express that with the parameter alpha from 0 to 1, which is the proportion of all the mining capacity in the world that you actually control. Now, it turns out that for some alpha, yes, you can make more money by implementing a non-default strategy, although the analysis is still ongoing. So this is very much new, under development stuff. So the simplest attack is a forking attack. And the idea here is to perform a double spend. So we have a valid state of the blockchain here, and the miner will send money to some victim, Bob. So it may look as if that transaction sending money to Bob is in the valid longest chain. Now this forking miner is going to then work on an earlier block, and to do this in practice it would need to be about 6 blocks earlier based on the standard number of confirmations that people usually wait before accepting that a payment is final. And then the miner will insert an alternate payment where they keep the money for themselves by transferring it to a different address. Now at this point, that block won't be valid since it builds on an earlier point in the blockchain. It doesn't represent the longest possible chain of blocks. But if you have a majority of hash power, if alpha is greater than 0.5, eventually your alternate chain will be longer than what was previously the longest chain. And at this point, your longest chain now becomes the valid blockchain. So you've rewritten history, you've removed that payment that you made to Bob, and you've now kept that money for yourself. And if your target had given you something in exchange for those bitcoins, preferably real currency or some kind of goods in the real world that they can't easily take back, then you've swindled them. And this is a way that you could profit if you have a majority of power in the network. So like I said, this attack is certainly possible if alpha is greater than 1/2, if you have the majority of the mining power. It might be possible in practice with a little bit less because of things like network overhead and the fact that as one mining pool, you shouldn't be working on colliding blocks in your alternate chain. So sometimes people talk about a 51% attacker in Bitcoin, but it's a mistake to think that that's a magical threshold where as soon as you cross it, all of a sudden you can do this attack. In reality, it's more of a gradient where the attack gets easier the further over 50% you go. It's important to realize that this attack is detectable, and it's possible that if you were doing it on a large scale, that the community would decide to reverse it by refusing to accept your alternate chain, even if it was longer. So it's not clear in practice that this would actually work, and it is also possible that doing this would completely crash the exchange rate of Bitcoin. So it might be that once a miner started trying to do this, people would lose so much confidence in the system that they would not want to buy into it, and the amount of dollars that Bitcoins were worth would go way down. In fact, if this was done on a large scale, it's possible it could destroy the currency completely by a dramatic loss of confidence. So who would want to do this? The conceivable scenario where people are worried about an attack like this has been referred to as a Goldfinger attack, named after the famous villain in the James Bond movie, of course, whose goal in the movie was to irradiate all of the gold that the US government held at Fort Knox to make it valueless. So if your goal was to destroy Bitcoin, then you might be willing to do this forking attack in order to specifically to tank the market, make Bitcoins worth less, and possibly profit because you'd either shorted Bitcoin or because you had significant holdings in some competing currency. So beyond that threat model, it's not clear in which scenarios we would have to worry about a large-scale forking attack. Although it's possible that the attack is easier than achieving that alpha greater than 0.5, all that hash power, by simply buying it. So whereas it would be really expensive to buy enough mining capacity to have more than everybody else in the world, it might be possible to just bribe the people who do control that capacity to work on behalf of you. So there's a couple of ways you could pay the bribe to them. You could try to do it out of band. You could hand them an envelope full of cash, say. You could declare yourself to be a new mining pool and run it at a loss. You could say, I'll pay out 1.01 or something that clearly wasn't sustainable, but enough to get miners to join your pool at the expense of all other pools. Maybe that would push you over 50%. And there's some other subtle ways you could try to get people to work on your alternate chain, say by leaving big tips in the blockchain. But the idea is that instead of actually acquiring all the mining capacity yourself, you just pay the people who already have it to work on your fork. Now, it might be a bad idea for those miners to actually participate, because by doing so, they would be hurting the currency that they've invested so much money in mining equipment, hoping will stay sustainable. So why would anybody be subject to such bribery? Well, it would be an incentive problem. All of the miners together have an incentive in keeping the Bitcoin currency solvent, but individual miners would have the incentive to defect and accept a bribe if they thought they could make more money in the short term. So this would be a classic tragedy of the commons from an economic perspective. Now, this hasn't happened. This is pure speculation, but it's an open problem if a bribery attack like this could actually be viable. So one defense that does exist in Bitcoin against forking attacks is checkpointing. So since 2010, each version of the default Bitcoin client ships with a specific checkpoint and will refuse to accept versions of the blockchain that don't date back to that version. And it's usually several hundred blocks before whatever the current longest chain is. So there's some questions about the implications for this in terms of how decentralized this is, because this now means that essentially a central party, the developers who maintain the core Bitcoin client, are deciding something about the value of the valid blockchain. But this does serve as a good practical mitigation against the risk of a deep fork in the blockchain. Another type of attack that's quite interesting is a block withholding attack. So the idea here is that you don't want to announce your blocks right away as soon as you find them. Instead, you're going to want to try to get ahead. What do I mean by get ahead? Well, you'll want to do a little bit of mining and hopefully find 2 blocks in a row before the rest of the network finds even one. And you keep these blocks to yourself as a secret. Now, why would you want to do that? What would you gain from keeping blocks secret? Well, as long as you have those 2 blocks that are being held secret in your back pocket, the rest of the network is going to be trying to extend what they think is the current longest blockchain, and all of that effort is going to be a waste for them. So while you're ahead by 2 blocks, all of the mining that you're doing is essentially unopposed. And the reason is that as soon as the rest of the network actually found a valid block, they would publish it and everybody would accept it, but then immediately, boom, you can drop the 2 blocks that you had in reserve, and that would instantly be the new longest valid blockchain, and that block that the rest of the network worked so hard to find would immediately be orphaned and cut off from the longest chain. So this approach has been called selfish mining, which I think is a little bit of a misnomer because all mining is inherently selfish. At least at this point, now that the hobbyist interest in mining has largely died down, mining is a business and people are in it to try to make money. So we should say that it's all in the game for miners to do this if they think that they'll make more profit. So what happens if you're trying this block withholding strategy and you're ahead by 1 when the rest of the network finds the next block? So instead of being 2 blocks ahead, you just have 1 secret block held in your back pocket. And then the rest of the network announces what they think will be the next valid block. Well, if this happens, you're going to want to immediately push your secret block out the door. And now there's 2 versions of potentially the longest chain, and every other miner is going to have to decide which version they want to work on, and we're in that race condition. So you basically have to race as soon as you hear somebody else finding a valid block to get your secret block out the door and hopefully get more miners to hear about your block first. So the viability of this block withholding approach is going to depend really heavily on your ability to win these races. So when is it a good idea to do a block withholding attack? Well, if you assume that you can win every race, every time there's competition for the next valid block, the rest of the network is going to accept yours, then no matter what alpha, no matter how much mining capacity you have, it's better to try selfish mining. By selfish mining, I mean this block withholding strategy that I've just described. So how would you try to win every race? Well, you could just fight really hard to have a good network position. You could try to peer with every node so that you'll announce to more nodes ahead of the legitimate flooding algorithm. Or you could try bribing people. And again, you could bribe by including small tips in your block so that it makes it more attractive for people to mine on top of you rather than the competing block. So if you assume that you only have a 50% chance of winning these races, which is about what the natural chances would be if you're competing fairly, then this block withholding strategy is an improvement if alpha is greater than 0.25. And again, this is a theoretical attack, which is very interesting, but it hasn't actually been observed yet in practice, and it should be something that you'd be able to tell by monitoring the blockchain and when miners are announcing new blocks. But even though it hasn't been observed in practice, it's very surprising that this is possible, and it's contrary to the original idea of Bitcoin that without alpha over 0.5, without a majority of the network, there was no better mining strategy than the default. So the very existence of this attack shows that it's not safe to assume that a miner who doesn't control 50% of the network doesn't have anything to gain by switching to an alternate strategy. Another interesting case is if miners want to do punitive forking. So specifically, if miners want to blacklist transactions from a specific address, which would freeze the money held by that address forever, they could announce that they'll refuse to mine on any chain with a transaction originating from address X. So the reason this is an extreme strategy is that if you have less than a majority of the network, by announcing that you'll refuse to mine on any chain that has the transaction from X, as soon as a chain exists that the majority of the network accepts that has that transaction from X, then you will have cut yourself off from the longest chain forever, and all of the mining that you're doing is essentially wasted. So you could do this strategy, but very quickly you would just be mining on an orphaned fork, and it would be a waste of all of your time and electricity. But there's a much more clever way to do punitive forking, which is called feather forking. And the idea here is that instead of announcing that you're going to fork forever as soon as you see a block that has a transaction from address X, you announce very publicly that you're going to fork, you're going to try to mine an alternate longest chain if you see a block that has a transaction from address X, but you will give up after a while. Typically after 1 or 2 blocks confirm the transaction from address X, you'll go back to the longest chain. So your chance of actually pruning that block or orphaning that block that has the transaction from address X, if you give up after 1 confirmation, is alpha squared. And the reason is because you'll have to find 2 consecutive blocks to get rid of the block with the transaction from address X before the rest of the network can find the next valid block. So alpha squared might not be very good. Say you're a 20% miner, alpha squared is going to be quite low. It's going to be only a 4% chance of actually getting rid of that transaction that you don't want to see in the blockchain. But you might motivate other miners to join you. Now, why is that? As long as you've been very public about this, other miners know that if they include a transaction from address X, they have an alpha squared chance that the block that they find will end up being orphaned because of your feather forking attack. And if they don't have any strong motivation to include that transaction from address X, and it only has a very low transaction fee, that alpha squared chance of losing their mining reward might be a much bigger incentive than including the transaction. So those other miners might rationally say, we have this person, this miner doing feather forking. It's in our interest to join them and just do the blacklist that they're demanding rather than run the risk that they'll feather fork away from the new block that we've just found. And the cool thing is that you can now enforce a blacklist even if alpha is less than 0.5, if you have less than a majority of the mining capacity. And your success in doing this is going to depend really heavily on how convincing you are to the other miners that you're definitely going to fork. So ideally, what you would want to do is say, I've burned this into hardware. I have no choice. I have to do this. So no matter what you do, I'm going to be feather forking. In which case the miners would say, well, this miner really is going to go through with it, so maybe we should just give them what they want and do this blacklist. So why would you want to have a blacklist? Well, like I said, there's the ability to freeze money held by an individual, and if you're blacklisting successfully, you can keep them from ever spending that money. So maybe you could profit off of this by some sort of ransom or extortion, demanding that the person you're blacklisting pay you in order to be taken off of your blacklist. It also might be something that you might want to do for legal reasons. Maybe certain addresses are designated by law enforcement as being bad. Those assets are demanded to be frozen, in which case some proportion of miners, say those operating in the jurisdiction where the asset freezing has legal authority, will say, well, we really have to enforce this blacklist we're being demanded to by the government, therefore maybe we should feather fork to try to make it happen. But a much more interesting case is if miners do this to try to enforce a minimum transaction fee. So instead of a blacklist against a specific address, you want a blacklist against any transaction that doesn't include some minimum transaction fee that you think is fair to you as a miner for your hard work. So we haven't talked a lot about transaction fees in practice yet. We've said that they exist, and we've said that there's the capacity in Bitcoin to pay transaction fees. But what are transaction fees? So this is the default policy for transaction fees, taken essentially right out of the Bitcoin code. Transactions are assigned a priority, which sums over all the inputs, the value of that input times how old the transaction is, how long ago that input was put on the blockchain, divided by the size of the transaction. So this basically means transactions that are larger, transactions that are spending older coins that haven't been moved in a while, and transactions that are smaller have higher priority. And by smaller, I mean smaller in size of the transaction, which means they don't have a long, complicated script. So the idea is to prioritize large transactions, people who don't move their coins very often and who do it in a simple way. Whereas if you want to move money quickly, if you want to move small amounts, or if you want to do complicated scripts, you have to pay a higher transaction fee. And currently, by default, there's a magic number where miners accept with no transaction fee if the priority is higher than 0.576. And if you're sitting there thinking that seems pretty random, where did that number come from? I'd say you're right. It's a very arbitrary choice, but it's in the default client. So that's basically what you need to pay if you want to move Bitcoin. So currently, transaction fees don't matter that much. And the reason is that block rewards provide the vast majority, well over 99% of all the revenue that miners are making. But keep in mind, we mentioned earlier, that the size of mining rewards is going down constantly over time. So every 4 years, it's halving. So eventually, in the distant future, the mining rewards, the fixed rewards by creating new coins, are going to be much lower, and transaction fees are going to be the main game for miners. It's going to be where they're making all of their revenue. So it's an open question in that new world where transaction fees are everything for the miners. They really depend on transaction fees for their revenue. Are miners going to be more aggressive about enforcing minimum transaction fees? And how are they going to enforce that? Will they need to form a cartel to enforce minimum transaction fees? Is that something that market concentration provided by mining pools will make easier to happen? These are really interesting long-term open questions about how Bitcoin will evolve. So in summary, miners are free to implement any strategy that they want, although in practice, in the wild, we've seen very little behavior of anything but implementing the default strategy. And I should stress that there's no complete model for miner behavior that says that the default strategy is optimal. We've seen that in a world where most miners do choose the default strategy, Bitcoin seems to work fairly well. So it seems to work fairly well in practice. We're not sure if it works in theory yet. But even though it works in practice so far, the facts on the ground are going to change for Bitcoin. They're changing slowly because of more network hashing capacity. The miners are getting better and better. There's more centralization and professionalization of the miners. But even beyond those trends, they have to change in the long run because of the transition from fixed mining rewards to transaction fees. So overall, I'd say you should stay tuned to this space. Things might be about to get a lot more interesting for Bitcoin mining. And currently, it's a very interesting research topic to try to play out using what we know from game theory. How is this going to evolve in the long term? So that's all on Bitcoin mining for now. A few lectures from now, we'll have another lecture about mining, but about alternative models for mining. How could we redesign Bitcoin mining to have different properties? But before we get to that, in the immediate next lecture, we're going to look at anonymity in Bitcoin. How much anonymity does Bitcoin provide? If I use Bitcoin, will people be able to link my Bitcoin transactions to my real name? And what technologies are there to try to either strengthen anonymity in Bitcoin or design an alternate currency with more anonymity? That's all coming your way in the next lecture.
Hello, and welcome to the 6th lecture. By now you've seen a lot of the basics of Bitcoin, how the system works, how mining works, and how to use Bitcoin as a currency. Now let's get to what has been one of the most controversial aspects of Bitcoin, which is the anonymity properties of Bitcoin. And in fact, there's a lot about Bitcoin and anonymity that you'll hear different opinions on. Is Bitcoin anonymous, first of all? Are anonymous cryptocurrencies even a good thing? Is it good for people who have a stake in Bitcoin? Is it good for society? And what of the various proposals that have been made to improve Bitcoin's anonymity? How well do those work? Which of those should we adopt? And so on. So in this lecture, what we're going to do is help cut through all of that confusion, and we're going to discuss where things are, what are the options, and where things seem to be going. So let's start like this. Let's start with a basic understanding of what we even mean when we say anonymity in Bitcoin, and some of the overall concepts like how does anonymity tie into privacy? Is that a good thing or a bad thing? Can we only have the good aspects of anonymity without the bad? A variety of questions like that. And then we'll see a variety of proposals, some already existing and some that may be implemented someday, for improving Bitcoin's anonymity or creating different anonymous cryptocurrencies altogether. And what's interesting about them is that they offer a variety of increasing levels of cryptographic sophistication as we go down this list, and we'll learn to see what the trade-offs are and analyze the anonymity properties, how deployable these are, and so on. All right, let's get started. If you look online, you'll see there are a number of people in groups saying that Bitcoin is anonymous. There's no shortage of opinions on this. Let me just pull out one quote in particular. This is the WikiLeaks donation page. It says, in plain and simple terms, Bitcoin is a secure and anonymous currency. Is that actually true? Well, you'll also find a variety of opinions to the contrary. Again, I'm just pulling out one example. This is the Wired UK saying Bitcoin won't hide you from the NSA's prying eyes. So how can we resolve this confusion? Let's look at what the word anonymous means. At quite a literal level, anonymous means without a name. And so what does that mean exactly? Well, there's two ways to interpret it. We know that in Bitcoin, addresses are public keys. You don't need to put in your real name in order to interact with the system. Or public key hashes instead of real identities. But we can interpret this property of being without a name in two different ways. We can interpret it as interacting without your real name, or we can interpret it as interacting without any name at all. Now, if you interpret it as interacting without your real name, then certainly Bitcoin is anonymous in that sense. But we do have these public key hashes that act as some sort of pseudo-identities. And so when computer scientists look at this situation, they don't use the term anonymous to describe this. They call this pseudonymity. And there's a very clear difference between the two, and it's an important one, and we'll see why in a second. You might wonder, yeah, even though you're using a pseudonym, which is your public key hash, you can create any number of them. You can have as many pseudonyms as you want. Does that make it anonymous? Well, the answer is not quite, and we'll get into that as well. Okay, so if computer scientists call this pseudonymity, what is anonymity then? Is there a clear definition of what it would take for something to be called anonymous? At a conceptual level, the answer is very simple. Anonymity in computer science is just pseudonymity together with unlinkability. So what is this property called unlinkability? At an intuitive level, we'll get into better definitions in a little bit, but at an intuitive level, what unlinkability means is that as a user interacts with a system repeatedly, these different interactions should not be able to be tied to each other from the point of view of some adversary. So you have to be talking about a specific adversary for this to even make sense. Now, This distinction here between full anonymity and mere pseudonymity is something that you might be familiar with from a variety of other contexts. And one good way that I like to explain this is to look at online forums. And again here, the distinction between a mere pseudonymous interaction and anonymous interaction comes up in different forums. And Reddit is a good example of a forum where you pick a long-term pseudonym and interact over a period of time with that pseudonym. You could create different pseudonyms, but it's going to be practically infeasible to create a new pseudonym every single time you want to post a comment, and it's not even very meaningful. So Reddit offers pseudonymous interaction. The opposite of that, fully anonymous interaction, where you can make posts with no attribution at all, is the model that you typically have in 4chan. And there's a similar difference in Bitcoin as well, and Bitcoin is in the pseudonymous model more than the anonymous model. Okay, but let's talk about why this difference is important in Bitcoin. Why is mere pseudonymity not sufficient if you want privacy? After all, if you have pseudonymity, it seems like even if somebody can create a pseudonymous profile of all of your interactions on the system, they can't tie it back to your real identity. Well, here's the answer to that. It turns out that if you have this pseudonymous profile, it's pretty fragile. It's very easy for it to get linked back to your real identity at some point. And if that happens at any point, then of course, all of your transactions, past, present, and future, have been linked to your identity. So here are a couple of different ways in which that can happen. One is that a variety of Bitcoin businesses, online wallet services, exchanges, and others, even vendors in a lot of cases, are going to want your real-life identity in order to let you transact with them. Consider this analogy. You go to a coffee shop, you pay for your coffee with Bitcoins, and of course, if you're there in the store, then the person who's giving you your coffee sort of knows who you are, even if they don't actually ask for your real name. And so your physical identity does get tied to one of your Bitcoin transactions. And if that Bitcoin transaction then gets tied to all of your Bitcoin transactions, then that is a complete violation of anonymity. So this notion of a pseudonymous profile is very fragile. It could easily get compromised in a variety of ways. And also, even if such a direct linkage doesn't happen, these linked profiles can be de-anonymized due to side channels. What do I mean by side channels? Well, here's something that I find intriguing that might seem like a tall claim, but in fact such things have been known to happen. Maybe somebody looks at a profile of your pseudonymous Bitcoin transactions and finds that you interact at certain times of day, and they're able to correlate the times of day when you're active online with the times of day when your Twitter account is posting tweets, and so they're able to find a connection between your Twitter identity and your transactions on Bitcoin. Similar attacks have been known to happen, so this is why this notion of a pseudonymous profile is considered quite fragile, and for real anonymity, we want the stronger notion of unlinkability. So let's try to define it in a little bit more concrete sense, what unlinkability means in the context of Bitcoin. And we can do that in a variety of different ways. One is that it should be hard to link together different addresses of the same user. Another is that it should be hard to link together different transactions made by the same user. Both of these seem intuitive. Look at this one though. It should be hard to link the sender of a payment to its recipient. This one might sound a little confusing at first, because if you interpret a payment as a Bitcoin transaction, then of course that transaction has inputs and outputs. And these inputs and outputs are inevitably going to be in the blockchain publicly and linked together. And so you might think that this is impossible to achieve. But if we interpret this notion of payment in a different way, not as a single direct Bitcoin transaction, but perhaps an indirect sort of payment that goes through a circuitous route of transactions, then one might imagine that the ultimate sender and the ultimate recipient of that payment might not immediately be linkable looking at the Bitcoin blockchain. So these are all somewhat more concrete, but still at an intuitive level, varieties of unlinkability that one might want to shoot for. But if you look at this last definition, it might still be not entirely convincing. Let's say that you pay for a particular product and it costs a certain amount of Bitcoin, and then maybe you send that payment through a circuitous route of transactions, but still you might think somebody looking at the blockchain must be able to infer something, specifically that Bitcoins left some address, a certain number of Bitcoins, and Bitcoins showed up at some other address. And these two might be slightly different because of transaction fees and so on, but roughly equal. and also roughly in the same time period, because there can't be too much of a lag between the sending and the receiving of a payment. And so clearly, even if we try to achieve this kind of unlinkability, it can be unlinkability between all possible transactions, but some smaller subset of transactions that look like each other. So let's make this a little bit more concrete now. And this is how we quantify anonymity. We usually don't try to achieve complete unlinkability, which is unlinkability among all possible transactions or addresses in the system. But instead, we go for something more measured. We try to maximize the size of our anonymity set. The anonymity set is the size of the crowd of other addresses or transactions that we're trying to hide in. So if I can be reasonably sure that with respect to some adversary, there are these 1,000 other transactions that look just like mine, and the adversary can't tell which one was mine, then that we might consider it to be a pretty good level of anonymity. And to calculate this anonymity set, it's not trivial at all. It takes a few steps. You have to first define concretely what your adversary model is. And you have to reason carefully about what that adversary knows, what they don't know, and what they cannot know. And there's no general formula for doing this. It requires carefully analyzing each protocol and system and doing it on a case-by-case basis. I want to point out that in the Bitcoin community, often people carry out intuitive analyses of anonymity services, for example, mixing services that we're going to see later in this lecture, and often they come up with ways like taint analysis. This is an intuitive way that tracks the flow between a particular sending address and a particular receiving address. And intuitively, it might make a lot of sense, but if we consider it from the point of view of how we actually should calculate anonymity, taint analysis is not a very good measure of how much anonymity you get from a system. And the reason for that is that it assumes a particular type of attack the adversary might carry out, a rather naive attack looking directly for quantities of flow between a sending and a receiving address. And if your adversary were a little bit cleverer than that, then you might carry out taint analysis and think that you have a lot of anonymity in a certain situation, but in fact you might not. So the bottom line from this slide is that quantifying anonymity must be done in terms of the anonymity set, and in some cases probability distributions on top of that anonymity set, and it requires a careful analysis of the protocol in the system. You can't apply a simple formula. Okay, let's switch gears a little bit and talk about the ethics of anonymity. Why do people want anonymity? We've already seen a little bit the connection between anonymity and privacy, but let's make that very concrete. Now, in blockchain-based currencies, because all transactions are recorded on the ledger, they're totally and publicly and permanently traceable. And so if your identity ever gets linked to these transactions, you're in a situation where your privacy level is much worse than you get with traditional banking. Why? Because anybody might be able to carry out this type of de-anonymization attack, not specifically a company or a government that you might be worried about, any member of the public. And your transactions, since they're permanent, your loss of anonymity years down the line could affect all your transactions today and vice versa. So we really want anonymity to even get the privacy level of cryptocurrencies to the level that we enjoy with the traditional system. But also people hope that it can give us a new level of privacy. Of course, we have to acknowledge the concerns as well, and one of the major concerns is money laundering and all of the bad things that that can enable. So let's talk about that. This is definitely a legitimate worry. I wouldn't be in favor of studying anonymity in cryptocurrencies and ignoring the ethical aspects and saying, oh, that's not something I'm going to worry about. I'm only interested in the technology. I think it's important to consider the ethical aspects. There's one item of comfort that I will offer, though. If you look at how things stand currently in Bitcoin, the difficulty of things like money laundering is not necessarily because the blockchain is not so anonymous and so it's easy to trace flows, but instead the difficulty stems much more from the fact that moving large flows into and out of the currency rather than within Bitcoin is what is really hard. In other words, cashing out is hard. And so anti-money laundering efforts have great promise if they're focused in this part of the system. And the good news is that all of these attempts to improve anonymity in Bitcoin don't affect this part of the equation in any way. And so I would recommend that Bitcoin researchers and developers coordinate efforts with anti-money laundering efforts by law enforcement and others so that the technical aspect of Bitcoin anonymity can be relatively separate from law enforcement and legal aspects and so on. Nevertheless, one could try to ask, can't we design the technology in such a way that only the good uses of Bitcoin anonymity are allowed and the bad uses are somehow permitted? Well, this turns out to be a quite common conundrum in computer security and privacy. In a lot of scenarios, we want something like this, but it never turns out to be possible. Why? Because these different uses that we're talking about that we perceive as being very different morally are going to be almost identical technologically. And if we want to encode some sort of moral rules into the technical rules of the system that are going to be automatically enforced by miners, it's not even clear how to do that. And so hence my recommendation of separating out the technical anonymity properties of the system with the legal principles that we put on top of it in terms of how people use that currency. It's not a completely satisfactory solution, but it's perhaps the best way we have of trading off the good with the bad. I do want to point out that this is far from the first time that we're considering this dilemma. It's come up in the context of Tor, an anonymous communication network. And anonymous communication enables bad actions at least as much as anonymous moving of funds does. And so Tor has really had to grapple with this problem. In a very simple and single picture, Tor is a communication network that routes messages between a sender and a receiver through a network of nodes. But further, through some clever encryption, ensures that as long as at least some of the nodes in that network are honest, then the adversary is not going to be able to link the sender to the receiver. So that's what Tor does, and you can see how it can enable a lot of bad activities. Let's look at some activities, good and bad, that do happen on the Tor network. It's used, first of all, by normal people who want to protect themselves from being tracked online by marketers or various other privacy properties online when they're browsing websites. It's used by journalists and activists and dissidents and so on, and so that's clearly an important use case. It's also used by law enforcement, because if they wanted to do an electronic sting operation, then you want to be able to visit websites without revealing that your IP address is coming from a law enforcement block. So clearly a lot of activities that we might approve of, but it's also used by botnets, for example, for spreading malware between nodes in the network. And unfortunately, there is also child pornography in the network. So distinguishing between these uses at a technical level is essentially impossible. And so Tor has grappled with this issue, and as a society, we have grappled with it. And by and large, we've concluded that it's better for the world that the technology exists than it doesn't. And in fact, one of the main funders of Tor is the US State Department. They're interested in it because Tor helps dissidents in other countries who might be fighting oppressive governments and so on. And in fact, recently there was a news story about the FBI having a successful string of sting operations against people using Tor for child pornography. And so, of course, we have to remember there is a level above the technology that law enforcement can exploit, a variety of ways to get to people who are using these systems for bad purposes, and so it preserves a sense of balance. So let's switch gears a little bit once more. Let's look at the history of anonymous eCash. Even though with Bitcoin these questions are quite controversial and there are debates about how anonymous exactly Bitcoin is and what are the options and so on, this is not the first time that we've thought about anonymous cryptocurrencies at a technical level. These efforts have quite a long history. In fact, all the way back in 1982, more than 2 decades ago, cryptographer David Chaum proposed something called blind signatures that helped him develop anonymous electronic cash. So what are blind signatures? Blind signatures are a two-party protocol. Two parties communicate with each other, and at the end of that, one party has produced a digital signature of some input without actually knowing what that input is. I know it sounds a little bit like magic, but I encourage you to look it up. It's not that sophisticated at a technical level. It's quite simple to understand if you work through the details, but since I'm not actually going to go into the details now, let's for the moment assume that this works by magic. So assuming that we have blind signatures, how can that help us achieve an electronic cash protocol? That's what David Chaum did. And as we go through this protocol, try to see if you can spot any other flaws with it other than the anonymity properties or lack thereof. It's quite a simple protocol. I'm going to show it to you in just one slide. Now, imagine that there is a bank, and this is a protocol for anonymous eCash through blind signatures. Imagine that there is a bank, and the bank stores various things in its database. In particular, it stores these two tables. The first table has a mapping of users with the balance that they have in their bank account. These balances don't refer to any sort of cryptographic currency. It's just a plain old number sitting in a database, just like your actual bank account or PayPal or something like that. In addition, it has another table called spent coins, and you'll see in a moment what this means. Let's say that a user now wants to withdraw an anonymous coin from the system. And now this is where the crypto magic is going to come in. So the user wishes to withdraw an anonymous coin of a standard denomination. Let's say that that's $1 denomination, and all of these values refer to dollars. So the first thing that the bank is going to do on receiving this request is deduct this user's balance. It's gone down from 10 to 9 in this example. The next thing the user and the bank are going to do together is execute a two-party protocol, a blind signature protocol, at the end of which the user, having picked a random serial number of a coin, that's what's being depicted here. This is a serial number for an anonymous coin, and the user was completely at liberty to pick that number. She did, and then they executed a protocol, at the end of which the user has received a signature of this serial number, but in such a way that the bank did not in fact learn this serial number. The bank had no idea what number it was signing. It just knew that it was some number that it signed. Right? And now this signed number represents an anonymous token. This is a token that the user can pass around to another user. So let's say that she wants to make a payment to another user. What she'll do is send to that user not only the signed token, but also the plain text value of the token of the serial number. And what the receiving user will do immediately is the following. She will immediately contact the bank and try to deposit this anonymous coin. Because without actually trying to deposit it, this red user here cannot be sure that this blue user is not trying to double spend. The blue user could be sending that same anonymous coin to 100 different users. How can they know that they're not being tricked into accepting a double spent coin? The way they're sure is when the red user receives the coin, they have to immediately contact the bank to verify if it's valid or not. And only if the coin turns out to be valid will the red user proceed to complete the rest of whatever transaction she was having with the blue user. So the bank now receives the message to deposit the coin, and note that it now gets finally the plain text serial number as well as its own signature. The bank looks at the signature, verifies that it's a valid signature, and here's the key thing. It also verifies that the serial number that it received is not on the list of spent coins. That's how it knows that this is not a double spend attempt. This is the legitimate first spend of a coin that the bank signed before. So it's a legitimate anonymous token. And since the bank didn't see the serial number the first time around, the bank does not know which user initially withdrew this anonymous coin. And that's the key anonymity property. In the period of time between the blue user withdrawing this coin and then perhaps much later sending it to the red user who immediately deposits the coin, many other pairs of users might have deposited and withdrawn coins, and the bank has no way to tell them apart. So coming back to this part of the protocol, the bank verifies that this is a new serial number that it's seeing for the first time. It puts that serial number into its list of spent coins so that it cannot be spent anymore, and adds $1 or whatever the denomination is to Red's account, and then sends back a message saying this is okay. And now the Red user has verified that they received a legitimate anonymous coin from the blue user and can now proceed to complete the transaction. Right? So this is the entirety of a very simple anonymous electronic cash scheme, and the key property here is that the bank cannot link the two users. So I asked you to think about whether this has any drawbacks other than anonymity. And of course, the glaring thing that you probably noticed is that all of this depends upon trusting this bank. I mean, look at this part of the system. This is simply the bank keeping numbers in its database of who owns how much money. Right. So this seems to be a trust model that's very, very different from the model that Bitcoin operates under. So a lot of the traditional cryptography research on anonymous eCash was in this model where you were willing to trust a bank for many things, including keeping your money, but you were not willing to trust a bank with anonymity. You wanted to be sure that the bank didn't know who was interacting with whom. Okay, it's an interesting model, it's a valid model, and many such schemes were developed under this model. But in retrospect, it seems to have been that the decentralization problem was a much more important one to solve than the anonymity problem in order for anonymous electronic cash to become successful. People were willing to accept a decentralized eCash system with only sort of pseudonymity properties and not real anonymity, and then get to work on maybe improving the anonymity, instead of starting from a fully provably anonymous electronic cash system that relied on a single central authority. But more generally, anonymization and decentralization, as we'll see repeatedly in this lecture, are in conflict with each other. There are at least a couple of reasons for this. One is that, as we saw in the last slide, often for anonymity, you might want to rely on certain interactive protocols with a bank in order to do some blinding, which we saw in blind signatures. That's where you get anonymity from. But how are you going to do that without a central bank to carry out that protocol with? It's not clear. But even if you got rid of this blinding and were willing to accept just pseudonymity instead of true anonymity, you still have the problem that in order to decentralize and still get security properties like resistance to double spending, often the way to go is to record and trace everything in a public ledger, as Bitcoin does. And so you might even further compromise your anonymity and privacy properties. So these are two big challenges to overcome. And as we'll see much later in this lecture, ZeroCoin and ZeroCash are cryptographic, anonymous, decentralized electronic cash schemes that have some similarities to the blind signature-based protocol that I showed you earlier, but some of the giant challenges that they have to tackle involve these two limitations. All right, I said several times earlier that Bitcoin is only pseudonymous, and so all of your transactions or addresses could get linked together. Let's now go in and see how that might actually happen. Let's in fact start from WikiLeaks again. I showed you a quote from them saying Bitcoin is a secure and anonymous digital currency, and this is actually the page that was taken from. This is their donations page. And here you'll see that in addition to this blurb about Bitcoin being secure and anonymous, they have a donation address over here. This is, of course, the hash of a public key. You've seen things like this in previous lectures. But they also have this interesting refresh button right next to that. What do you imagine this refresh button might do? Well, as you might expect, if you click on that refresh button, it'll give you an entirely new donation address. Let's go in and take a look at that. So a totally new address popped up on the page. So what is going on here? What WikiLeaks is doing is it's making sure that each time a person visits the page, each time a person wants to visit the page and make a donation, they send that donation to a totally new public key that WikiLeaks creates just for that purpose. So here, WikiLeaks is taking advantage of the ability to create new pseudonyms, new public keys to the maximum. Every single transaction that they receive, they want to receive it at a new address. And in fact, this is the Bitcoin best practice for anonymity, to always receive new transactions at a fresh address. So you might look at this and think, surely then, these different addresses must be unlinkable. You receive a transaction over here, and then much later you spend it by sending it to somebody else. You receive another transaction at this address, and then you send it to someone else over there. So how might somebody link? Well, here's the key. Let's imagine this scenario. Alice, a customer, goes to a big box store and wants to buy a teapot. So in this scenario, Alice has a few Bitcoins lying around with these different denominations, and the store lists the teapot for a price of 8 Bitcoins. That's a pretty expensive teapot at today's exchange rate, so imagine that's centi Bitcoins or something, if you like. At any rate, Alice has these different addresses and wants to pay for the teapot. How is she going to accomplish this? She doesn't actually have an address with 8 Bitcoins sitting in there. And so what she's going to do is she's going to combine several different input transactions into a single transaction in order to pay 8 Bitcoins to the store. So this reveals something. For somebody who's looking at this transaction that gets recorded permanently in the blockchain, they're going to think, aha, 2 different inputs to this transaction. That could only happen because both of these input addresses are under the control of the same user. They were able to use their wallet software to create a transaction that combined both of them into one. So in other words, shared spending is evidence of joint control of 2 different addresses. And it doesn't stop there. This is not just about linking 2 different addresses that are inputs to a transaction. You can do that transitively, and every time Alice has a whole cluster of addresses that have been linked, and then she creates a new transaction that combines one of those addresses with a new address, you can add this new address to the cluster. Right. So this is the first insight behind being able to link transactions together. And we'll see later on that an anonymity technique called CoinJoin works by violating exactly this assumption. But if you assume that people are just using regular Bitcoin wallet software, not doing anything special on top of it, then this technique tends to be pretty robust. And this has been explored in a variety of research papers. And just a note about this lecture, a lot of what we're going to be discussing today gets into the frontiers of where the research knowledge are. So a lot of this, the state of the art, may have advanced in a few months or a few years. So every time I talk about a technique that we know from a particular research paper, I'll give you a reference to that paper so that you can look it up. You can look up papers that cite it, and you can build up that knowledge on your own. Now, in particular, one of the papers that used this technique used it for a particular purpose. There was a well-publicized Bitcoin theft a few years ago. And what they wanted to do, the authors of this paper decided to see how this thief has been moving Bitcoins around between multiple addresses of his own. And so this is that paper in question. It's called An Analysis of Anonymity in the Bitcoin System. And so this is one of the first major research efforts that did what we call transaction graph analysis. So you can use the techniques that I showed you in previous slides, and you can draw a lot of these pretty graphs and deduce that this represents the thief moving money around between his own different addresses. This is the thief sending money to someone else, and various things like that. I haven't yet shown you anything that allows you to link any of these clusters to real-world identity, but let's defer that question for a bit. Let's defer that question and go back to the scenario of Alice and the teapot. So let's look at it again. Maybe the teapot has gone up in price to 8.5 centibitcoins. So what is Alice going to do now? She can't combine any subset of her transactions or her addresses to produce the exact amount of change necessary for purchasing this teapot. So instead, what she's going to do is exploit the fact that transactions can have any number of inputs and outputs, and create a single transaction that looks like this. It combines these 2 inputs to produce this output that goes over here, and another output that goes to an address that she herself owns. And this is called a change address, which you saw in a previous lecture. This presents a conundrum for an adversary who's looking at this. The adversary might be able to deduce that these 2 addresses belong to the same user. He might suspect that one of these addresses also belongs to that same user, but has no way of knowing which one that is. In this particular example, the change address is a small amount, but it doesn't have to be that way at all. Alice might own an address that has 10,000 Bitcoins and might spend a little bit on the teapot and might send most of the rest of it back to her in her own change address. And these transaction outputs don't have any particular ordering in the blockchain. That order is not meaningful at all, so it's not clear what the adversary might do. It's not clear how the adversary might determine which addresses change in a multi-output transaction. So what is the adversary to do? There's another pretty cool technique for this, again from a research paper, which I'll tell you about. But the technique is this. The authors call this idioms of use, and they exploit idiosyncratic features of different wallet software. For example, one thing they found is that most wallet software use an address as a change address only once. That means that this, in fact, seems to sort of follow Bitcoin best practice for anonymity in a sense. If you have a new transaction where you need to create a new change address, don't use an address that you've already used before as a change address. Create a new address and use it for this purpose. Right? Now, not all addresses that are outputs of transactions might have this property. Going back to the example of the big box store, the store might advertise a long-term address at which it wants to receive Bitcoins instead of receiving Bitcoins at a different address every time. So not every non-change address has this property, that it's used only once as a change address, but every change address does have that property. So they used this, and they found that it works pretty well. On the other hand, this has some limitations. It just happens to be a feature of wallet software. And so there are a lot of false positives that might creep in to these clustering techniques if you use techniques like this. So it required a lot of manual intervention. Nevertheless, they were able to use the technique that I showed you before, which is clustering shared inputs together, as well as a few heuristics for change address detection. And then what they were able to do is they were able to look at the entire Bitcoin transaction graph and create some giant clusters that they hypothesized belonged to various major service providers. And here's what that graph looks like after applying these two heuristics. And this is the paper in question. This is by Sarah Mickeljohn and others as a whole bunch of authors of this paper. Now, this graph looks very interesting here. The sizes of these circles represent the amount of money flowing into those clusters, and the number of edges going out of a cluster represent the number of transactions. Let's try to just stare at this for a second and see if we can guess what some of these major service providers and other clusters of nodes might be. This huge one here that dominates in transaction volume compared to any other cluster, given that this paper was written in 2013, we might guess that it's Mt. Gox, which was a very prominent exchange at the time that later went under. We might also guess that this little one here, that only has a little bit of transaction volume, in spite of having a very large number of transactions, sort of corresponds to the profile of the gambling service, Satoshi Dice, because the way that it works is you send a tiny amount of Bitcoins and you either win that bet or you lose that bet, and so you might get double the Bitcoins or none of the Bitcoins. So that's the gambling service Satoshi Dice. We might guess that it's this one here, we might guess that it's Mt. Gox, and so on. But this kind of guessing is suboptimal. The authors wanted some sort of reliable way of identifying what are the service providers corresponding to each of these clusters. How did they do that? Well, one idea you might have is you might think, oh, why not just go to the Mt. Gox website and see what address they advertise for receiving Bitcoins? Well, that doesn't quite work because they're going to advertise a new address for every single transaction. And if you just go to the website, look at the address, and actually don't complete that transaction, you don't send Bitcoins there, then they're simply going to discard that address. They're not going to reuse that address for another customer. In other words, that address will never get used. You simply won't find it in the blockchain. So what's the way around this? Well, the only way to reliably infer addresses that are associated with a service provider is to actually transact with that service provider, which is exactly what the authors did. They went ahead and bought a variety of things and interacted in a variety of other ways with a bunch of service providers comprising 344 transactions in all. Mining pools, wallet services exchanges, various merchants, even gambling sites, and so on. And they got a bunch of cool things to show for their efforts, and Mickeljohn informs me that in fact the cupcakes were really good. At any rate, the authors used this very clever technique to go ahead and label the major clusters in the graph that I showed you on the previous slide. And so this is what the labeled graph looks like. In fact, this was Mt. Gox, as we might have guessed. This was Satoshi Dice, but a lot of the others would have been very difficult to guess. And by actually transacting with these services, they were able to identify most of these service providers. So already now, we've seen something pretty interesting beyond just clustering and being able to put labels on the clusters. So the next question is, sure, you can do these labels for these major service providers. Can you put labels for individuals? In other words, connect little clusters corresponding to individuals to their real-life identities. Well, there's at least a couple of different ways in which that can happen. One is intuitively what I told you right at the beginning. You could simply interact at a coffee shop or with some other merchant, so they learn some transaction or some address that corresponds to you, and they might use that to tag your cluster. There are at least a couple of other ways in which this might happen. And one is that there's high centralization in these service providers. So the intuition here is that most users, in the course of normal usage of Bitcoin over a period of months or years, are going to interact with at least one of those major service providers that were labeled in the previous graph. So if somebody wants to identify a cluster corresponding to a particular user, there's a very high chance that they're going to be able to identify a transaction that ties that cluster with a known labeled cluster, and then they can go to that service provider, and if they have the appropriate authority, subpoena that service provider, or if they're a hacker, try to hack into that service provider, and so on. And so this is one major avenue in which regular users can get de-anonymized because they eventually inevitably interact with one of these major easily identified service providers. Another one is simply carelessness. A lot of users end up posting address information in forums. They might post one of the Bitcoin addresses that they own, for example, to receive donations when they're posting comments on forums. Now, that might be because these users are not worried about getting de-anonymized. It could also be because they don't realize that posting one of their addresses is almost going to inevitably allow somebody to connect all of their different addresses together. Okay, so hopefully I've convinced you that there are clever ways that an attacker might utilize in order to not only link different addresses or transactions belonging to a user, but go from there to real-world identity. And our experience, our history of these de-anonymization algorithms shows that they only get more powerful with time and more auxiliary information, as we call it, for attackers to utilize in order to link together to get to users' identities. So this is something to worry about if you care about privacy. Before we look at how to make things better for anonymity, let's look at a completely different way in which users can get de-anonymized. So far, what we've looked at is all based on what is available to the attacker in the blockchain, right? The part that is permanently and publicly recorded. But recall that that's not the only part of Bitcoin. There's also a peer-to-peer network in which a lot of messages are sent around that don't necessarily get permanently recorded in the blockchain. So the blockchain in networking terminology is called the application layer, and the peer-to-peer network is, of course, the networking layer. And so de-anonymization can happen at this totally different layer, at the networking layer. Well, how could that happen? Here's an example. This was first pointed out by Dan Kaminsky a few years ago in a talk at Black Hat. Here's the peer-to-peer network. What he noticed is that when a node creates a transaction and wants to broadcast it, it's going to connect to a lot of nodes at once and broadcast that transaction. And so if a few nodes on the network put their heads together, they can figure out that, hey, this new transaction, this is the first we heard of it, and all of us first heard of it from this particular node. So this must be the node, this must be the IP address corresponding to the user who created this transaction. So here you have a linkage not between a transaction or a cluster and a real-world identity. Instead, you have a linkage between a transaction and IP address. And of course, IP address is something that's very close to real-world identity. There are a lot of ways to go from there to the next level of finding identity. So this is already a serious problem. Luckily, though, this is not a very hard problem to solve. Why? Because this is now a problem of communications anonymity. And communicating anonymously is a problem that has received a lot of attention from the research community. And as we already saw in the introduction, there is a good system called Tor that you can use for communicating anonymously. Now, there's one little caveat. Tor is intended for what is called low latency activities, such as web browsing, where there is a large volume of flow, and you don't want to sit around waiting for too long, and you get the response immediately. So it makes some compromises in anonymity in order to achieve low latency. Bitcoin is inherently a high latency system. right? Because it takes a while for transactions to propagate through the network, and especially to get confirmed in the blockchain. So we don't have this low latency constraint. So it's possible that we could come up with a more specific, fine-tuned sort of anonymity network for this particular purpose. And there are such things called mixed nets. The only problem is that Tor is the system that's most widely deployed and analyzed and robust and functional today. But it's possible that somebody might develop a mixed-net solution for anonymizing your Bitcoin communications. And if that happens, that would be something to switch to. So let's summarize what we've learned so far. We've seen that based on the information in the blockchain, different addresses could get linked together, could also get linked to identity. We've also seen that based on the information at the network layer, a transaction or address could get linked to your IP address. Luckily, this latter problem is simple to solve. If you care about your anonymity and privacy when using Bitcoin, it's a good idea to do it through Tor. But the former problem is much trickier, and that's what we're going to spend the rest of this lecture talking about. So there are a variety of solutions to inhibit what we've been calling transaction graph anonymization, or transaction graph analysis, pardon me. And the first of them is called mixing. So what is mixing? Well, the intuition behind this is very, very simple. It's the same intuition that comes up in a lot of contexts, which is that if you want anonymity, use an intermediary to route your communications or your funds or whatnot. So let's look at what that might look like visually. Here's an intermediary, and in a second we'll get to who these intermediaries might be. But assume that there is some intermediary, some service, that allows users to put in Bitcoins. But the key property that it gives you is that after these Bitcoins have been put in, it forgets who put them in and treats its entire store of Bitcoins as indistinguishable from each other. And in fact, it might further combine them all into one giant transaction, or it might further mix them or split them and merge them in different ways, whatever. But the key property is that when users later come in to withdraw their Bitcoins, it's not tied to the coin that they put in. They're going to get some other, say, randomly picked deposit that the intermediary received. So when these three users come back, they're going to withdraw these coins in a random order. And so somebody looking at this in the blockchain who doesn't have the records that the intermediary might or might not store, just from the publicly available information in the blockchain, is not going to be able to link the ultimate input addresses to the ultimate output addresses corresponding to the same user. So that's the intuition behind intermediaries. Now, looking at this, does that strike a chord? Have we seen in previous lectures something that offers services that are similar to this, that allows you to deposit Bitcoins and then withdraw them later at a later time? You might recall that this is exactly what online wallets do. There are services where you can just store your Bitcoins online until you need them. And so you might wonder, well, is that the solution to our problems? Do online wallets provide anonymity? Let's think about that. The answer to this is not obvious, but I will start by mentioning that it's taken well-known researchers by surprise. Here was a post on the New York Times Bits blog reporting on a preprint of a paper released by two Israeli researchers saying that there was a link between Dread Pirate Roberts, the pseudonymous creator of Silk Road, which we're going to see more about, and Satoshi Nakamoto. This was, of course, very surprising. But as it turned out, all that had happened was that they had mistook this link that went through an intermediary, and that intermediary just turned out to be Mt. Gox, which you can think of sort of as an online wallet service. And so a few days later, this other post was published at the same venue. See if you can spot the difference. They had to retract their study, and I think they had made a very simple mistake of not accounting for the presence of this intermediary. So it's clear that at least in some sense, online wallets provide some sort of anonymity because at least somebody tried to make a connection between an input and an output address and completely failed at that. So let's try to understand exactly the sense in which online wallets provide anonymity And I think a good way to do that would be to, in fact, contrast online wallets with the online services that exist specifically for the purpose of acting as these intermediaries for anonymity. And those are going to be dedicated mixing services. We'll talk about mixing services in much more detail, but very briefly, the two things that they promise that you won't get simply by putting your Bitcoins into an online wallet and retrieving that again is that they promise not to keep records. It's not just that as a side effect, they sort of randomly give you Bitcoins that came from some other address, but they specifically say that they won't keep records, and so even if they tried to, they wouldn't know which Bitcoins were the ones you put in, and so with a high probability, you're going to get some other Bitcoins back. And furthermore, even if someone came knocking for their records, or if they got hacked and so on, there would be nothing to find. There would be no records. So that's something that a mixing service promises. And the other thing is that you don't need your real-life identity in order to interact with these services. And this is in contrast to most of these online wallets. Why? Because online wallets are typically reputable and in fact often regulated businesses. And this fact has two consequences. One is that they'll typically require your identity. In banking, there is the know your customer principle, which essentially at a technical level translates to learn the customer's identity and store those records. And in fact, they will keep records if they receive a deposit. They will keep the link between the identity and the Bitcoin address. If they move money around internally, they will probably keep records of all of that. And just because when you withdraw your Bitcoins, they come from a different address, does not mean that the online wallet does not know the link. That link probably does exist in their records and will exist for all eternity. Even if they don't explicitly ask for your identity, think about this. To even interact with an online wallet, you do need a persistent long-term identity. You can't possibly use a different pseudonym every time, because if you did, they'd have no way of associating an account with you, of knowing how many Bitcoins they owed you. Right? So because of that, even if they didn't ask for your identity, at the very least, the online wallet knows the address of every single deposit that you made of the Bitcoins that you put into the system, and more importantly, every single withdrawal that you made. And so when you make a series of withdrawals from an online wallet and proceed to spend those Bitcoins, the wallet service can now connect all of those together in a profile. And of course, it's not just the wallet service. People who care about anonymity are also worried about those records getting hacked, insider attacks, somebody who has a subpoena for getting those records, and so on and so forth. So with respect to the wallet service itself and whoever they might be cooperating with, you have no anonymity in this context. On the other hand, there is something cool about this. If you are willing to trust them with your Bitcoins, then what's going to happen is you're going to keep them in the wallet service for much longer than you typically would with a mixed service. Why? Because you don't trust a mixed service as much. You want to put in your Bitcoins and you want to receive it back immediately from some other address at an address of your choosing. Right? So unlike that, for an online wallet service, you're going to have a bigger anonymity set. Why? Because your anonymity set, from the point of view of someone with no privileged information, from the point of view of someone who's merely looking at the blockchain, your withdrawal could look indistinguishable from every single withdrawal ever made from that service provider. So with respect to the wallet service, you have no anonymity. With respect to everybody else, you have a bigger anonymity set than you possibly would with using a mixing service, or at least with using a single mixing service. So if we look at this, this looks suspiciously similar to the kind of privacy properties that you have with the traditional banking system. There are these centralized intermediaries that know a lot about our transactions. But from the point of view of a stranger with no privileged information, we have a pretty good amount of privacy. So even if this gives you some sort of anonymity, it's almost at best what you get with the traditional system. And so those are not the kind of people who are typically looking for anonymity in Bitcoin anyway. If they were happy with the anonymity properties of the traditional system, they would have probably stayed with that system. And so generally, people who are looking for anonymity properties in Bitcoin simply do not want to accept the trust requirements that these online services, online wallet services require. And they don't want the sort of anonymity properties that it gives you. They don't want to have to trust that service with their anonymity. And in fact, we've seen that there have been a lot of closures of these exchanges and services, and so there's good reason for believing that if you put all your trust in an online service, you might simply lose your money. Okay, so having rejected online wallets as an anonymity solution, let's turn to these dedicated mixing services that I told you a little bit about. Before looking at their details, let's talk about the terminology a little bit. I like to call it a mix. Some people call it a mixer. These are really the same thing. Some people also call them laundries. I don't like this term at all. And the reason for this is that it needlessly attaches moral meaning to something that's a purely technical term. As we've seen earlier, there are very good reasons why you might want to protect your privacy in Bitcoin and use mixes for entirely good reasons for everyday privacy. Of course, we must also acknowledge the bad uses, but it seems a little bit weird to me to use the term laundry that implies that your coins are dirty and you need to clean them, and attaching a negative moral value to the whole thing, and for that reason, I'm not going to use that term in this lecture. We'll go with the technically neutral term, which is mixing. So, in talking about mixing, there are several of us, about 6 of us, who got together, researchers at Princeton, Concordia, and Maryland, including all 4 of us who are doing this online lecture series, and analyzed the existing mix ecosystem and proposed a series of changes for improving the way that mixes operate, both in terms of anonymity and the trustworthiness of mixes. So let's look at those principles. Before I show you those principles, as a quick reminder, at a very fundamental level, how does a mix operate? It asks for an address at which you want to receive Bitcoins, and it gives you an address to send Bitcoins to the mix, and then you both execute that transaction. It's a swap, basically. In a second, I'll show you what that looks like visually. But what were our principles for running these mixes properly? Well, the very first one is that you might want to use a series of mixes instead of just a single mix. And this is a very well-known principle. Using a series of routers is the same principle in the anonymous communication system Tor. And it's a good idea because it allows you to not have to trust a single mix, but instead be sure that as long as any one of these mixes is promising to delete its records, then you have a good guarantee of anonymity. And in particular, mixes should implement a standard API so that this can be very easy for clients to accomplish. And right now, this is not quite the case. And this is our paper for your reference. So now let's go in and look at what a series of mixes would look like visually. So here it is. Here is a user who starts with a coin or an input address that we assume that the adversary has managed to link to this particular user. They're going to send it to the mix at this address and get back a Bitcoin at this other output address that they provide. They freshly generate this output address and provide that address to the mix. The mix will hopefully return the same amount of Bitcoins at this output address. There's no way for the user to force the mix to do that. The user has to trust the mix. And this is, as we'll see, a recurring problem with the whole notion of mixes. And either immediately or after a time gap, it doesn't matter, the user will take the Bitcoin or Bitcoins of whatever value they've received at this address and send it to a different mix, which is hopefully not cooperating with the first mix, and repeat this process over and over again. So from an adversary's point of view, looking at the public blockchain, they're merely going to see, along with all of these transactions, a variety of other mixed transactions that other users are executing. And hopefully, the adversary will have no way to tell apart which of those transactions correspond to this particular user and which one corresponds to some other users. So that's the first principle. And the second one, if you think about what I've just said, in order to make that possible, you want to make these transactions as uniform as possible so that this linkability is minimized. And what does it mean to make these transactions as uniform as possible? One important consequence is that all of these mixed transactions, not only from a particular mix, but all of the mixes in this mix ecosystem should have the same value. So we think that all mixes out there providing service should agree upon a chunk size, a standard chunk size. And of course, there can be multiple denominations, but there can't be too many, and you can't simply allow the users to put in whatever amount of Bitcoins they wish to. That wouldn't work. So you need this kind of standardization. In addition to this, we found that there are a variety of possible attacks in which a clever adversary might infer various things, not just the amount. Even if you remove the amount, some other properties, including timing, for example, in order to try to link users' input addresses and output addresses together. This type of linking can be avoided, but human users, if they interact with the mix, are not going to be able to take into account all of those possible linking attacks. So instead, what needs to be done is this client-side software must be automated and built into desktop wallet software, so that this desktop wallet software automatically knows how to interact with these mixes in order to preserve the user's anonymity. So that was our third principle. Our fourth principle is a subtle one. Now, these mixes, why do they provide this service? Typically, it's because they're a business. And if they're a business, they want to be paid. How are they going to get paid? Well, it turns out that pretty much the only way for these mixes to get paid is to take a cut of the transaction that the user is sending to the mix. That seems a bit weird because if a mix takes a standard percentage, then an adversary might be able to use that to link the input transaction and the output transaction. So some current mixes try to randomize the transaction fee. They might say, we take a random cut between 1% and 3%. We found that this is not a good idea either, because if you put that through a chain of mixes, then the amount of the value in the chunk is going to dwindle in a predictable way, and this is an important side channel for the adversary. So what is a way to avoid this? We proposed that these mix fees should be all or nothing. In other words, the mix should either swallow the whole chunk with a small probability, or should return the whole chunk. So if the mix wants to charge a 0.1% mixing fee, this is, by the way, very different from the transaction fee that mining nodes charge. This is a mixing fee on top of that. So if the mix wants to charge a 0.1% mixing fee, then 1 out of 1,000 times, the mix should swallow the entire chunk. And 999 times out of 1,000, the mix should return the entire chunk without taking any mixing fee. This is a tricky property to accomplish, which means that the mix should generate a random number in a way that can convince the user that the mix is not cheated in generating this random number, and has genuinely flipped a coin which has a 99.9% chance of coming up one way versus the other. But we do show how to do this using cryptography in a way that both parties can be satisfied has worked correctly. We think that really all four of these principles are necessary to have anything approaching mathematical confidence in having a large anonymity set and in our ability to resist clever inferential attacks by an adversary that looks at the blockchain to try to link input to output. The sad news is that virtually none of the current mixes follow these principles. They're in a very different model where each mix operates completely independently, and they have a web interface, and the user interacts with them totally manually instead of automatically through their wallet software. And will manually put in the amount. Instead of a standard chunk size, it's whatever amount the user chooses typically. And the mix will take some cut of that as a mixing fee and send the rest to the user. So we don't think this is a situation that gives mix users a lot of anonymity, but we think that by moving to a slightly different model based on these four principles, the anonymity properties of the mix ecosystem can be dramatically improved. All right, so through these four principles, we've seen how the anonymity properties of mixing can be improved, but there is still one major problem, which is that users still have to trust these mixes. So again, we had a few ways that we talked about in our paper for what to do about this. Mixes can do several things to improve their trustworthiness. One is that simply by staying in business for a long time and not stealing users' money, they can build up a reputation. You might wonder, does this reputation count for anything? Because it's simply a matter of he said, she said. In fact, a mix operator can claim that a competing mix operator stole all their money, even if that did not in fact happen. Well, generally, reputation systems in the real world manage to operate even though there can be conflicting claims that are made. In this context, for example, users might learn to only trust the word of prominent members of the Bitcoin community who they think have the best interests of the ecosystem at heart. Another way is that in the system that we proposed, the chunk sizes are going to be so small that in the regular course of mixing, users are going to mix a pretty huge number of chunks. Or at least the system can be configured in that way so that the chunk sizes are relatively small. So in that context, if a mix has even a 1% probability of stealing a user's chunk, then after 100 or so interactions with small chunk sizes with a particular mix, the user is going to know, the user is going to detect the theft, and so the user will learn to never use this mix again. And so the system might sort of correct itself by users testing mixes for themselves for trustworthiness. An important thing to keep in mind here is that the chunks that users are sending to mixes have typically already been through other mixes. So the mix itself can't know which user the chunk is coming from. And so the only thing the mix can do is to essentially steal randomly from users. The mix can't steal from a particular user. So from the user point of view, on average, they won't suffer losses that are more than the average rate at which the mix steals. So they don't have to worry that a mix might particularly have it in it for that particular user and steal all of their money. There's no way that that can happen. So that's what I mean when I say users can test this for themselves. And finally, we proposed a cryptographic mechanism where the mix can issue sort of a promissory statement to the user that once it receives a chunk at a particular address, it will send a chunk back at some other address that the user provides. And so if the mix fails to keep this promise, our idea is that the user can publicize this warranty and everybody will know that a particular mix is cheated. And so everybody will stop using this mix and the mix will lose business. And in combination, all of these three mechanisms provide incentives for mixes to act honestly. So these were our calculations anyway in our proposal. We haven't proved that this will work in practice. That remains to be seen. All right, on that note, let's quickly look at how things are in practice right now. It doesn't seem that there are any reputable services providing dedicated mixing that users have learned to trust, or at least enough to use on a regular basis. In fact, this is from the Bitcoin wiki, where the original is also highlighted in red, so I took the liberty of doing that myself. Mixing services may themselves be operating with anonymity, and so if your funds are not delivered, you have no recourse, use at your own discretion. So we're proposing moving to a different model where mixes stay in business, become reputable entities, and so on. That hasn't quite happened yet. And note that there is sort of a bootstrapping problem here. If mixes were reputable entities, they would have a big volume of transactions. And so by interacting with them, you'd get a pretty good anonymity set. And so users would be more confident in interacting with them, and mixes would realize that they're making more money by staying in business and taking a small cut than by trying to steal the small amount of money that they're controlling at any given time. And so mixes would be further incentivized to stay in business. So you can imagine that once a mix ecosystem gets going, it will be self-sustaining. But whether or not that can eventually happen, we can say for sure that it hasn't quite happened yet. So the fact that this mix ecosystem currently doesn't exist is a big part of the reason why many people have proposed decentralized mixing. And there are a variety of reasons for decentralized mixing, some of which we've talked about, in that there is no bootstrapping problem. So the reason there's no bootstrapping problem is that in decentralized mixing, you don't go through a particular dedicated mix service. Instead, you find a community of peers who all want to do mixing. And somehow, without any central coordination, or at least a central service that collects your funds, you manage to mix with each other. So that avoids the bootstrapping problem, because as long as there is enough interest from Bitcoin users, they can meet with each other and start mixing. How to do that, we'll see in a second. Also, theft is impossible, and this is enforced through technical means because nobody is explicitly sending Bitcoins to another user. Again, we'll see how this is accomplished. It could possibly provide better anonymity, and we'll look into more details on that as well. And finally, I just want to point out that this is just more philosophically aligned with Bitcoin. If you can get rid of having to have a centralized service for some purpose, then there are a lot of users who are Bitcoin users who find that appealing. So how might this work? The main proposal for decentralized mixing is called a coin join, and this is something that was proposed by Greg Maxwell, who's a core Bitcoin developer, who will meet again in the next lecture, actually. So what he proposed is different users coming together to create a single Bitcoin transaction. And what are the outputs of this transaction? We'll see in a second. But somehow create a single Bitcoin transaction that combines all of their inputs, presumably of equal value. Now let's think about this for a second. What is necessary in order for these three users to create a single transaction? Well, one way of thinking about it, we might imagine that in order to produce a signature, somebody has to collect all three private keys. That's not actually how it works, though. In Bitcoin, all the signatures corresponding to the different inputs are totally separate. So each input signature is entirely separate. So what it allows the users to easily do is create different inputs that correspond to different users and also different output addresses that correspond to different users and randomize the order between them. So in this situation, maybe the users participating in the protocol might necessarily have to know which input address corresponds to which output address, although we'll see in a second if we can avoid that as well. But certainly someone looking at the blockchain, looking at only this single transaction, even if they realize that this is a coin join transaction, will not be able to find the mapping between the input and the output. It's that simple. That's the essence of coin join. Of course, this is just one round of mixing. On top of this, you have to apply the same principles that we talked about before. So the principles that I discussed, they're not only for centralized mixes, they apply essentially with very few modifications even to the coin join scenario. So you want to do a sequence of coin joins. You want to make sure that these chunk sizes are standardized so that you don't introduce new side channels, etc., etc. Okay, but let's look into this single transaction though. Exactly how would this work? There are a lot of details that are still not clear. So let's look at this in algorithmic form. So if we write it out like this, what needs to happen is that a group of peers who all want to mix somehow need to find each other. That's the first difficulty. And then they have to exchange their input and output addresses with each other. And one of these users, it doesn't matter who, will construct this transaction, not yet a signed transaction, but just the transaction that corresponds to these different inputs going to these different outputs. And then they'll pass it around to collect signatures from each of the peers. Now, if the peer who constructed the transaction were disruptive and, for example, left out one of the peer's outputs, then the whole thing will collapse, because when that particular peer gets the transaction in order to sign it, they will simply refuse to sign. And the process will not be able to go forward. But if everything's okay, everybody acts honestly, then the transaction is constructed. And now any peer, again, doesn't matter who, can broadcast the transaction to the network. Two of them could do it independently. It doesn't matter. The transaction will, of course, be counted only once. So that's it. That's the whole protocol. The entire security property comes from each peer checking that their output address is represented and that their output, of course, receives at least as much value as went in from their input. So that seems simple enough. But what are the remaining problems here? Well, there are three problems. One is, how did this group of peers find each other? Right? And the second is that, as I described in the previous slide, this protocol involves each of these peers finding out the mapping between inputs and outputs, or at least one of those peers. So that seems like a problem. In fact, I want to point out that this is a worse problem for decentralized mixes than for centralized mixes. And why is that? In the centralized mixing case, you could hope that these different mixes are run by entirely different entities who are not colluding with each other. And at least in some cases, these will be reputable real-life entities who you would imagine have incentives not to collude with each other because they have different goals or for whatever reason. Again, the reasoning is similar to Tor. You have a variety of different types of people who are running Tor nodes. They don't all have the same incentives, so we imagine that they're not all going to collude with each other, and also that they're not all going to get compromised by the same attacker. A similar principle holds for decentralized mixes, and that only works because you know something about the identities of these mixes. So these mixes, having known identities and being reputable entities, helps anonymity in this case. We don't have that luxury with decentralized mixes because we have no idea who any of these peers are. Right? So it could be a single attacker creating lots of Sybil accounts and accounts in the sense of just creating lots of Sybils, and trying to get into every single coin join transaction that's ever carried out in order to learn these input-output mappings. And so even if you do a series of coin joins, it might be the case that in each of those coin joins, at least one of the participants was an attacker or was controlled by the same attacker, in which case your entire anonymity is lost. So that seems like a problem. And a third problem, and kind of a tricky one, is denial of service. What does this mean? Well, it could happen that after providing the input-output pairs, one of the nodes disappears and refuses to sign the resulting transaction. So the transaction is not able to proceed forward. And secondly, even after creating the signature, before the transaction can get broadcast to the network and confirmed in the blockchain, one of the nodes who might be malicious might take this input and spend it in some other transaction that's unrelated to this coin join. And so this coin join will look like a double spend attempt and will be rejected by the Bitcoin network. So that's another way in which you can launch denial of service against coin join. So now let's look at what are some possible solutions to each of these three problems. Well, the first one, how to find peers, is a very simple solution. It's not a perfect solution, but people consider this to be somewhat okay. You simply use an untrusted server. It's sort of like a watering hole where different users can connect and find each other, but the server is not necessarily involved in any way that the users have to trust in running the protocol. Right. And as we're going to see, each of these steps for solving these problems introduces a little bit of engineering complexity. So this already requires a whole peer-to-peer protocol for finding these coin join peers on top of the Bitcoin protocol. And we're going to see similar factors that introduce engineering complexity for solving each of the other problems. So the next one, how do we solve the anonymity problem? Well, there's a simple straw man solution. You can frame the anonymity problem in this way. You need to communicate the set of inputs to all the peers, and also you need to communicate the set of outputs, but break the linkage between the input and the output. Now this becomes a communications anonymity problem instead of a Bitcoin anonymity problem, right? Because it's simply the matter of communicating these output addresses that needs to be unlinked from communication of the input addresses. So a straw man solution to that, since we already have seen Tor a little bit, is simply this. These peers come together, they exchange input addresses, and they disconnect and then reconnect over Tor after a while, and then exchange the output addresses. So this is pretty simple, but it may not be very robust in practice. A better solution might be to build a special purpose anonymous routing mechanism for these participants to utilize just for this protocol. And there are things called decryption mixnets that allow you to do exactly that, and such solutions have been proposed. So let's move to the third problem, which is a denial of service attack. Let's think about it this way. What's a traditional solution to a denial of service attack? Well, one possible solution to a denial of service is to make it a little bit expensive for the client to connect to the server and to receive service. Well, this is not a client-server model, it's a peer-to-peer model, but we can still try to adapt the same principles. And that's the principle behind the first two of the proposed solutions for denial of service, either a proof of work or a proof of burn. So what do I mean by this? Proof of work is simply repurposing the algorithm behind Bitcoin's proof of work to require each of these peer nodes to do a little bit of computational work before they can join a coin join protocol. And the rationale is that if the adversary is going to disrupt every coin join that exists out there, they're going to be burning a lot of computing power, which will make it very expensive for them. Proof of burn is a similar concept. It's also called fidelity bonds in Bitcoin. It allows you to irreversibly destroy some Bitcoins that you own by sending it to an unspendable address, thereby proving that you've made a little bit of an expensive signal in order to get into this system. So that's the rationale between the first two solutions. The second two solutions, next to the third and fourth, also have a similar rationale, which is to identify the malicious participant, one or more malicious participants who launched the denial of service, to kick them out and to run the coin join with the remaining participants. And that could be done if you trust the server a little bit to carry it out. It could also be done in a purely decentralized manner, like this paper called Coin Shuffle proposed. And they came up with a cryptographic blaming protocol for doing this. And it involves something called zero knowledge, where you learn at least one of the players who misbehaved without necessarily learning much more about what happened. And then the rest of the peers can then redo the protocol. At various points, I've talked about side channels, so let's look at an example of that. And I want to point out that these side channels can be very tricky. Not all the mixing in the world can save you from what I call high-level flows that could be identifying. And here's a neat example of this. Let's say user Alice receives a very specific amount of bitcoins, let's say on a weekly basis as income, and has the habit of always automatically and immediately transferring, let's say 5% of that to her retirement amount. Right? So think about the patterns that will be visible on the blockchain here. No matter what she does to obscure the link between the address at which she receives her income and the address to which she transfers to her retirement account, the patterns here are going to be uniquely identifying because this is a very specific value. And the 5% of that is also going to be a specific value. And there's also a timing pattern. Every time money appears here, every time money goes to this address as well. So this is a problem. How do we protect ourselves from this? Well, one suggestion that has been proposed is not only in the context of mixing, but even in the context of regular Bitcoin wallets where users are not even trying to do any mixing, is by Mike Hearn. And he calls this merge avoidance. Merge avoidance is a very simple idea. When users want to do payments, the proposal is that instead of creating a giant transaction that combines as many inputs as necessary in order to pay the entire payment to a single address, why not have a protocol by which the receiver can provide multiple output addresses, as many as necessary, and the sender and receiver can agree upon denominations, and the sender can avoid combining different inputs and can make a variety of different transactions that send money from different input addresses to different output addresses. Right? So this avoids a lot of the problems both of high-level flows, because even these multiple input and output addresses cannot be linked to each other, so an adversary might not even be able to observe the fact that this is a high-level flow that's happening, but also avoids problems like clustering addresses together because of evidence of shared spending. And this is a proposal that one could think about incorporating right now into Bitcoin-based payment flows in order to improve anonymity for everyone. Now let's turn to zero coin and zero cash, which are a completely different approach to Bitcoin anonymity. The approach is sort of to bake it in at the protocol level, and these are cryptographic heavyweights. And so Azure Coin was first developed by cryptographers at Johns Hopkins, and later on they started collaborating with other researchers around the world who had been developing a very efficient cryptographic technique that would enable making some of the cryptographic operations in Zero Coin more efficient, and that resulted in zero cash. As you'll see, these techniques provide a qualitatively different level of anonymity than mixing solutions that sit on top of Bitcoin. But what's the catch? The problem is that this is not quite backward compatible with Bitcoin. Zero coin and zero cash are going to require altcoins. Technically, it's possible that zero coin can be deployed as what is known as a soft fork of Bitcoin, but the practical difficulties are high enough that this is not really considered feasible. And in fact, the zero coin developers intend to deploy it as an altcoin themselves instead of trying to be compatible with Bitcoin directly. Let's start talking about the details here. Let's review some of the things that I've just said. So zero coin brings protocol level mixing. And being baked into the protocol, what it gives you is a cryptographic guarantee of mixing. What does that mean? You don't need to trust a single mix or even a set of mixes or a set of peers or anybody at all to ensure your anonymity. You just need to rely on the underlying crypto being solid. You don't even need to rely on the miners enforcing this in order to achieve anonymity. It's purely a cryptographic guarantee. So that's really great. That's qualitatively better than what we have so far. And of course, it's not currently compatible with Bitcoin. And here's the paper if you want to look it up. So how does zero coin work? I'm going to introduce a concept called base coin, and I'm taking a few liberties with the presentation here in order to simplify and clarify the concepts. I'm going to do that by mixing some concepts from zero coin and zero cash, but toward the end I'll make very clear what the differences are between the two. So like I said, zero coin is an altcoin, and I'm going to call that altcoin base coin. I'm not calling it zero coin because zero coin is something else. It's an extension of this base coin. It's something that sort of sits on top of this altcoin. And the key property that gives you anonymity is that these base coins can be converted into zero coins and back again. And when you do that, it breaks the link between the original base coin and the new base coin. So think of this as a cryptographic mixing system that's provided by the protocol itself. So how might this work? Another way of looking at a zero coin is that it's a cryptographic proof that you owned a base coin, not anymore, but you owned it, and then you made it unspendable. A zero coin is something that allows you to assert that to, say, any miner who might care. And miners can verify these proofs, and that's what gives you the right to later redeem a new base coin in exchange for the zero coin. And the analogy is a little bit like poker chips. So how could that work, and what properties do these proofs need to have in order to enable this? So one challenge is how to construct these proofs, and the other trick is how do you make sure that each proof can be spent only once, can be used only once to redeem a base coin, because if you don't have that property, then it's going to lead to double spending. So let's see how to do that. It crucially involves a concept called zero-knowledge proofs. What are zero-knowledge proofs? I'm going to tell you at a little bit of an intuitive level, so I'm calling it crypto magic again. But what it is it's a way for somebody to prove a statement without revealing any other information that leads to that statement being true. A couple of examples are going to make this really clear. You might be able to prove a statement like, I know an input that hashes to this particular value. And notice that if the input that you had picked were long and random, you could, if you did a proof in such a way that you don't actually reveal the input, it won't necessarily allow somebody else to infer what that input is. A more complex version of this is you could say, I know an input that hashes to some hash in a following set of several different possible outputs. And the zero-knowledge proofs that zero coin is going to use is something that's very similar to the second category here. Okay. Let's dive in a little bit more. So zero coins are minted. They come into existence by minting. And anybody can do this. And zero coins come in standard denominations. Let's assume for the rest of this that zero coins are worth one base coin each. You could also imagine multiple denominations coexisting. How do you make a zero coin? We're going to see that in the next slide. But let me just say for now that minting a zero coin doesn't automatically give it any value. You can't get free money. It only acquires value once you put it onto the blockchain. And so putting it onto the blockchain is going to be about as expensive as the value of that zero coin that you're later going to be able to redeem. So you have some sort of a conservation principle here. Okay. So here's how, specifically in cryptographic terms, we mint a zero coin. It's something called a cryptographic commitment. What a cryptographic commitment is intuitively you can think of it as you're taking a serial number, a random serial number that you generated, and putting it into an envelope. So this intuitive notion of putting it into an envelope, cryptographically, what does that correspond to? What it corresponds to is generating another random secret R, which you're never going to make public, and computing the hash of the coin serial number together with this random secret. Now this is a little bit of a simplification, but it really helps you understand the properties of the system, so let's go with this description. So what just happened here? You generated arbitrarily, just like you generate Bitcoin public keys, a serial number for your zero coin. And if it were long and random, hopefully no one else has ever picked that same serial number before. And you also generated this other random number that you're going to keep secret. And intuitively, generating a commitment to this serial number corresponds to putting it in an envelope and sealing it. And mathematically, it happens by computing the hash of the serial number together with this random value. Okay, once you've generated this commitment, what do you do with that? Well, the next step is to put that commitment onto the blockchain. That's when the zero coin sort of becomes real, and doing this requires, in a sense, burning a base coin and making it unspendable. So in concrete terms, how would that work? You've got the blockchain over here, and one of those transactions might be a mint transaction, and if you zoomed in, it would be a transaction that's signed by Alice, who created this zero coin, who minted this zero coin. And what we saw earlier in the structure of transactions is that over here, you would have the recipient's public key or the recipient's address. Instead of that, here you have this cryptographic commitment. And just like before, just like a transaction having a pointer to a previous transaction, the same structure is carried over for zero coin transactions as well. So what has happened here? We've spent this base coin in order to mint this zero coin. And this commitment, this sealed envelope that we've put into the zero coin, is what is going to allow us to redeem that zero coin later in exchange for a base coin once again. So how does that work? To spend the zero coin later, you will reveal that serial number that you put inside the envelope. And what miners will do, it's their job to verify that the serial number has not been spent before, that the serial number has not been revealed as a number that was put inside some other envelope. That's what prevents double spending in the system. Next, you'll create a zero-knowledge proof that we just talked about. And specifically, the zero-knowledge proof will say, I know a number R such that the hash of the serial number together with R corresponds to one of the zero coins in the blockchain. And we'll make that statement more mathematically precise in a second. But think about what this says. It doesn't reveal that random number R. But somehow you're proving that you are in possession of that number, combined with this serial number that you have just made public, will result in the zero coin that was once in the past put onto the blockchain. Right? So for somebody looking at this proof, this is all they need to know to verify that you earlier spent a base coin in order to get to this point. So this now should give you the right to redeem a base coin. But which base coin? And here's where the anonymity property comes in. You can pick an arbitrary zero coin in the blockchain and use that as an input to a new transaction, out of which comes a base coin, and the miners will allow you to do that. So put a zero coin in, take a zero coin out, but a different zero coin. And all that anybody needs to know is that you have the right to do that because you put in some zero coin in the past. Doesn't matter which zero coin. And you can't do that twice. You can't do a spend twice corresponding to a single mint because the serial number now will become public. And there's only one serial number corresponding to one zero coin. And you only know the serial numbers corresponding to your zero coins and not anyone else's zero coins. Great. So where does the anonymity property come from? Here's the anonymity property. Since you've kept this random number R secret, and this is what is available on the blockchain, there are a number of hashes or commitments corresponding to the different zero coins that have been put on the blockchain. Even though you've revealed the serial number, not knowing this other random input R, nobody can try to brute force this and guess which of these zero coins corresponded to your serial number. So even after the serial number inside an envelope has been revealed, and it's been verified that this serial number was inside one of the envelopes, we still don't know which serial number it is. So this is the sort of magical property that zero-knowledge proofs in cryptography give us that you wouldn't get in a real-world, physical world, envelope-based analogy of this. So the next cool thing about this whole construction is the fact that these proofs are efficient. And I'm putting efficient in quotes here. And the sense in which they're efficient is that compared to what we know of zero-knowledge proofs and have come to expect on them, it's quite an achievement that these proofs are as efficient as they are. However, compared to the efficiency of Bitcoin transactions themselves, these are in fact quite slow. So it occupies a space in between those two. So exactly what I mean by efficient, the reason it's efficient is that it manages to avoid being linear in the number of zero coins on the chain, even though that is what you would expect. Why is that what you would expect? Think about the statement that the spender is proving here. I know a random number R such that Either the hash of the serial number with R corresponds to the first commitment, or the first hash, or the second commitment, or any one of these giant number of commitments that reside on the blockchain. Right? So it's a very long statement that the prover is proving. It's a statement whose length is proportional to the number of zero coins on the blockchain. And yet, the proof is much smaller than that. It's not linear. It's only logarithmic in the value n here. And that's part of the magic of zero coin. That's what makes it possible to even run the system. All right, moving on, let's talk about zero cash now. Zero cash kind of takes the cryptography sort of to the next level. It uses a cryptographic tool called snarks, which we won't get into at all. But the upshot of the use of these more efficient cryptographic constructions for proofs is that the efficiency gets to a point where the authors suggest that you can in fact run the whole system without having any base coin. All transactions can be done in this zero-knowledge manner. You don't need to have separate expensive transactions that are used only for mixing and a set of regular everyday transactions that you use when you don't want special anonymity properties. That distinction is now gone. The claim is that you can run all of these transactions inside these envelopes, and what I mean by that is the following. All transactions are zero coins, and so zero cash becomes untraceable in a sense because there is no base coin. And the reason for that is that splitting and merging of coins are also transactions that are supported in zero cash itself without going to base coin. And in particular, the transaction values, the transaction amounts, you can put those inside the commitments. Those won't be visible on the blockchain anymore. The only thing that the ledger records publicly is the existence of these transactions. You know that Alice put in some transaction. You know much later that Bob redeemed some transaction who might be the same user, might be a different user. But the only people who need to know what the amount is are the sender and receiver of any particular transaction. The miners don't need to know that. If there's a transaction fee, then the miners need to know that fee, but that doesn't really compromise your anonymity property. Right? So the ability to run zero coin in this different configuration where it's not two different coins anymore, it's not a base coin with a mix layer on top, but instead an entirely untraceable system of transactions, puts zero cash sort of in the next level when it comes to anonymity, because a lot of the possible side channel attacks that were true for mixing, that were true to a certain extent at least for zero coin, are no longer true for zero cash because the transaction amounts will no longer be visible in the public ledger. But that almost sounds too good to be true. A completely untraceable electronic cash system. It is ledger-based, but the ledger doesn't record anything that might compromise anonymity or privacy. Well, there is one catch. Here's the catch in zero cash. It requires a certain setup process to even set up the system. Specifically, one needs random and secret inputs in order to generate the public parameters. Think of those as public keys, except that these are giant public keys. They're over a gigabyte in size. And not only that, not only is the size a bit of a problem, these secret inputs for the security of the system then have to be securely destroyed so that nobody knows what those secret inputs were that were used in order to generate these public parameters. That seems like a bit of a problem, and the reason that no one can know them is because if somebody knows them, it doesn't mean that they will be able to compromise anonymity, but they will be able to create new zero coins for themselves, and nobody will be the wiser, which is also an equally bad problem for the currency. So it's kind of an interesting sociological problem here. How could some entity set up the system and then convince everybody that they have securely destroyed the parameters that were, of course, necessary in order to set up the system? So it's not entirely clear how that can be solved. There have been various proposals for it, but at the moment, we don't have a very clear idea of how to go forward on this. So what have we seen so far in all of the different efforts to improve anonymity in Bitcoin? Well, if we put them on a line, as I'll show you in a second, we see that there are 5 clearly different levels of anonymity that we've seen in different proposed solutions. And what are these? So let's look at not only the levels of anonymity that these systems provide, but also the deployability of these systems. Let's start with Bitcoin, which is already here. It's only pseudonymous. It doesn't even aspire to be really anonymous. And we've seen that pretty bad transaction graph analysis are possible. I showed you many beautiful graphs with the clustering of different addresses, and in many cases, how to go from those addresses to identities. So not a lot of anonymity provided by Bitcoin. The next level is simply using a single mix, sort of in a manual way in which people are doing right now with some of these dedicated mix services. And that still allows you transaction graph analysis because, as you might remember from the 4 principles that I gave you, if you don't have this automated system that has uniform chunk sizes and so on, a lot of transaction graph analysis is still possible. In addition, you have to worry that this mix might not be trustworthy, is storing records, and might be sharing them with other people, and again, could get hacked, etc. The third level that we saw is a chain of mixes. And this can be in a centralized model or a decentralized model. It doesn't matter. Both models give you roughly the same level of anonymity. But where really the anonymity improvement comes in for this one compared to a single mix is that you have these standardized chunk sizes, and you have a series of mixes, and you have a variety of other bells and whistles on top of it, like automated clients and so on. And for this, some side channels are still possible, not as bad as before. Transaction graph analysis is no longer that easy. And you still have to worry about an adversary who might collude with multiple mixes, or in the decentralized model, some peers that might be malicious and compromise your anonymity. This is, of course, perfectly backward compatible with Bitcoin, could be deployed and adopted any day. Hasn't quite happened yet in a way that we would consider to be truly anonymous. And then we saw zero coin, which is cryptographic mixing baked into the protocol. Doesn't depend on anybody promising to destroy their records or anything like that. You just need to trust the math. So that's a whole different level of anonymity. In my opinion, it still has some possible side channels, but it's not as bad as the other mixing-based solutions that we saw, where it's not baked into the protocol. And zero coin, of course, as we saw, is an altcoin, so it's not quite Bitcoin compatible in a way that one might hope. And finally, zero cash. The difference between zero cash and zero coin is not so much at a fundamental mathematical level, but because of the fact that you can run zero cash in a configuration where you get rid of the base coin altogether, and the efficiency is not too bad in that configuration. And so what that gives you is untraceability, which is something on top of unlinkability. So that's a new anonymity property. And there really aren't any anonymity attacks that I can think of, at least. But the downside, of course, is that not only is it an altcoin, but it also has this very tricky setup process that we don't necessarily know how to make progress on. So we've talked a lot about Bitcoin's anonymity in this lecture. But Bitcoin's anonymity becomes even more powerful when combined with other technologies, in particular, anonymous communication technologies. We've talked about Tor a little bit, we've alluded to it several times, but now let's go into more detail. Let's first set up the problem of anonymous communication, though. So this is what the system looks like. There are a bunch of senders, there are a bunch of recipients, and messages are routed from senders through recipients through this network over here. And of course, there's going to be an attacker. This attacker, and this is called the threat model, the attacker controls several things. Some of these nodes in red are compromised by the attacker. Some of these edges, some of these links between honest nodes to the network are also controlled by the attacker, even if the nodes themselves are not. Similarly, some of the recipient nodes over here and some of these links from the network to the recipient node are also controlled by the attacker. And finally, some of the internal nodes of the anonymous communication network, all under the control of the attacker. But crucially, not all of the communication network is controlled by the attacker. And we want to achieve anonymity in this hostile environment. And as before, anonymity refers to unlinkability between the sender and the receiver. So how does Tor accomplish this? It's the same old pattern of picking a chain of intermediaries to route your messages through. And here it is in a nice visual form. And I have to thank the Electronic Frontier Foundation for this slide. So what's going on? Alice over here wants to talk to Bob over here. So she pre-selects a path through this set of routers. And that number is fixed in the Tor protocol. It's always 3. But conceptually, you can imagine that it would be any number you want. And the more nodes you route through, the more anonymity you get. Or the harder it is, I should say, to breach anonymity. So these nodes denoted with a plus are all the Tor nodes. And she picks some subset of 3 nodes randomly in order to route her message. And the security property that we get is that as long as at least one of these 3 nodes that she picks is not compromised or colluding with the attacker, then she is sort of safe here, in that Alice cannot be linked to Bob by somebody who's observing some of the nodes in the network. I should say that there are many attacks possible on Tor. One of them, for example, is called an end-to-end traffic correlation attack. So there are going to be timing patterns in the flow of traffic between Alice and whatever Bob is, maybe a website. And so if the attacker controls both of these links, then just by observing the correlation in those timing patterns, he might be able to determine that these 2 nodes are in communication with each other, even if he knows nothing about the route that the message took between them. So one key point here is, how do you hide routing information? What do I mean by that? When a message has gone from Alice to the first router, it has to have the IP address of Bob's computer somewhere in that message. Otherwise, there is no way that this router can appropriately forward that on to reach the right destination. However, we don't want this router to actually learn that IP address, because if the router does learn that IP address, then it knows both Alice's IP because the message came from her, and Bob's IP because that's where the message is eventually going. And now this router has the link between the 2 ends of the communication. And this would be a problem if this router were malicious. So as you might guess, the answer involves encryption. And as you can see in this picture, these links are in green. They're encrypted connections, and this one is an unencrypted connection. Let's look in more detail to see how this encryption works. It's a specific way in which encryption is used. It's called a layered encryption. It resembles an onion, so that's why onion routing is a related concept here. So what is going on here? Alice and router 1 share a symmetric key that's represented in purple. Alice and router 2 share this key that's represented in blue, and Alice and router 3 share the key that's represented in gold. Now, these symmetric keys are not stored long-term by any of these nodes. They're established as necessary using key exchange. The only persistent keys are the long-term public keys of these routers. And these routers do, in fact, have long-lived identities and public keys and so on. Alice, of course, does not need to have any long-term public key. When she picks a path of these routers, she finds their public keys, executes key exchange protocols, and obtains these shared symmetric keys. And what she's going to do is, when she sends the message to R1, it's going to be triply encrypted. The outermost layer of encryption is a symmetric encryption between Alice and R1. And so what this allows R1 to do is peel off that layer of encryption like peeling off an onion. And when router 1 peels off that layer of encryption, inside it's going to find the IP address of router 2 and an encrypted message to send to router 2. And it's going to forward that. Router 2 peels off a further layer of encryption, and then to router 3, further layer of encryption. Now the message is unencrypted, consisting of the plain text message as well as Bob's IP address. And so router 3 now sends that message in plain text to Bob. Of course, what you probably want to do is further layer a protocol like HTTPS or secure web browsing on top of Tor, so that even this message from router 3 to Bob is encrypted, but the Tor protocol itself doesn't guarantee that, has no way of guaranteeing that, because Bob might be a regular web server that doesn't even speak the Tor protocol, and so there's no way that Tor can be responsible for the encryption between R3, which is called the exit node, and the ultimate recipient of the message. I'll leave you to think about why this wouldn't quite work if there were only one layer of encryption. For example, if Alice tried to encrypt the message all the way from her to R3, it wouldn't quite work. The routing would not quite work out. But as it is, the very neat property that you have is that R1 only knows Alice's IP address and R2's address, does not know R3's or Bob's address. And similarly, every node knows only the addresses of the node that was one hop before it and one hop after it. And in fact, when the message gets to this point, the IP address of Alice is not even present anymore, whether or not in encrypted form. So that's really how you get anonymity here. If any one of these, if R2, for example, were compromised, then it would learn R1's and R3's IP addresses, but not Alice's or Bob's. So that's how Tor works. And now let's talk about Silk Road, and in particular, the problem that a site like Silk Road has to overcome is this. Silk Road is what is known as a hidden service. In other words, the Silk Road server wants to hide its address for obvious reasons. If you haven't heard about Silk Road, let me just say a sentence about it briefly. You're going to see it in more detail in the next lecture. Silk Road was a website that operated for a couple of years. It was an anonymous marketplace. It sold a variety of goods, but the thing that it was most known for is selling drugs. And because of the pervasive anonymity, or at least pseudonymity in the system, the idea was that it was very hard for law enforcement to go after. And the story of what happened next I will leave to the next lecture, but let's look at the technology that made something like Silk Road possible and the implications of that. So here is a simplified algorithm by which a server can keep its identity hidden and yet provide services through Tor. What it does is it connects through what is called a rendezvous point, which is one of the Tor routers, through Tor. And then what it's going to do is it's going to publish the mapping between its name, its domain name, and the address of the rendezvous point through directory services that the Tor system offers. And these domain names are not your regular DNS domain names. That wouldn't work because it's this whole parallel system of routing. And so these are called onion addresses, and they're going to look like this long string .onion. And notice that it looks a lot like Bitcoin public keys. And it's for sort of the same reasons. It's because anyone can generate one of these. And now the client will have to learn the onion address of the site that it wants to visit. If when the Silk Road existed, if you wanted to go to Silk Road, you couldn't type in silkroad.com. That wouldn't make any sense because Silk Road is not even available over the regular web. Instead, you would have to, through some manner, and this was a widely known address, you would have to find, this is not Silk Road's address, by the way, this is the onion address of DuckDuckGo, a search engine that offers privacy and anonymity. But you would find a similar address that belonged to Silk Road and put that into your Tor-enabled browser. And what your client would automatically do is look up the mapping for the address of the rendezvous point, connect to that rendezvous point, and through that rendezvous point have an anonymous and encrypted connection to the ultimate server without the server having to publish its actual IP address. So that covers some of the technology behind Silk Road, in particular anonymous communication and how do you do anonymous payments, which is of course with Bitcoin. But still, you need more technology in order to make this whole system work. You need security. In other words, how can you be sure that when you pay someone on Silk Road, they're going to actually sell you the goods? Silk Road had a reputation system for that. And how do you do anonymous shipping? The site pretty much left this to the participants. It advised buyers to provide an anonymous PO box, for example, to ship goods to. So let's take a step back. We've covered a lot of technology in this lecture. Hopefully you've understood that Bitcoin anonymity is a very powerful thing. And it gains in power when combined with other technologies, in particular anonymous communication technologies. And also, anonymity is a deeply morally ambiguous thing. There are many moral distinctions that we would like to make that we're not able to adequately express at the technological level, and so some of this moral ambiguity appears to be inherent. Hopefully, it's also been clear that anonymity is very fragile. One mistake can create a link that you're trying to hide. But also anonymity is an important thing to protect. It's worthwhile protecting. It has a lot of good uses in addition to bad uses. So most of the things that we've talked about today are either at the forefront of research technologically, or they're the topic of serious ethical debates. None of this is really settled. And so this is an ongoing conversation, area of ongoing research. We don't know which anonymity system for Bitcoin, if any, is going to become prominent or mainstream. And so this is a great opportunity for you, either as a developer or in thinking through the ethical implications, to get involved in some of these issues. And hopefully what you've learned in this lecture has given you the right background for that.
Welcome to Lecture 7. In this lecture, we'll talk about all the ways that the world of Bitcoin and the technology touches the world of people. We'll talk about the community, we'll talk about politics within Bitcoin and the way that Bitcoin interacts with politics, and we'll talk about law enforcement and regulation issues. In Lecture 7.1, we'll talk about consensus in Bitcoin, the way that the operation of Bitcoin relies on the formation of consensus among people. Now, there are really three kinds of consensus that have to operate for Bitcoin to be successful. The first kind is a consensus about the rules. This is a consensus about things like, what is it that makes a transaction valid? How can you tell a valid transaction from an invalid one? Second, what makes a block in the blockchain valid? Which block should be accepted and which block should be rejected? Third, how the nodes in the P2P network should behave, how they should interact with each other, and what kind of protocol they should use to discuss with each other, and more generally, all the protocols and data formats that are involved in making Bitcoin work. You need to have a consensus about these things so that all the different participants in the system can talk to each other and agree on what's happening. And so the first form of consensus that goes into Bitcoin is just a consensus about what these rules should be in order for the system to go forward. The second form of consensus in Bitcoin is consensus about the history. That is a consensus about what's in the blockchain and what's not in the blockchain, and therefore a consensus about which transactions have occurred. And once you have a consensus about which transactions have occurred, what follows from that is, of course, a consensus about which coins, which unspent outputs exist, and who owns them. And so this consensus obviously flows from the processes that we've talked about in earlier lectures by which the blockchain is built and by which nodes come to consensus, the processes that we hope push Bitcoin toward a consensus about the contents of the blockchain. So that consensus about what's in the blockchain and therefore what the history is the second important form of consensus that Bitcoin relies on. The third form of consensus that Bitcoin relies on is just the consensus that coins are valuable. That is, the general agreement that Bitcoins are valuable, that Bitcoins are a good thing to have, and in particular, the consensus that if somebody gives you a Bitcoin today, that tomorrow you'll be able to redeem or trade that for something that is of value. Any currency needs this, whether it's a fiat currency like the dollar or a cryptocurrency like Bitcoin. You need a consensus that the thing has value. That is, you need people to generally accept that it's exchangeable for something of value now and in the future. And so that's the third kind of thing that Bitcoin needs. Now this form of consensus, unlike the others, can be viewed as a little bit circular. In other words, my belief that the Bitcoins I'm receiving today are of value depends on my expectation that tomorrow other people will believe the same thing. So consensus on value relies on believing that consensus on value will continue. And this is sometimes called the Tinkerbell effect by analogy to Peter Pan, where it's said that Tinkerbell exists because you believe in her. The same thing is kind of true here, that the consensus that Bitcoins have value exists because of the consensus that Bitcoins have value. So circular or not, it's a thing that seems to exist, and it's important for Bitcoin to operate. Now, what's important about all three forms of consensus is the way that they're intertwined with each other. And this diagram shows a little bit about what I mean when I say that. First of all, the consensus about the rules and the consensus about history go together. Because it's the rules that determine which kinds of transactions can go into a block and which kinds of blocks can come into existence. If you agree on the rules, that is, which blocks are valid, then it's possible to build a consensus about the blockchain and about history. Whereas without a consensus about the rules, then people are going to disagree about what's in the history, and you won't be able to come to consensus in that way. So consensus about rules and consensus about history are tied together. In a similar way, consensus about history and a consensus that coins are valuable are also tied together. Consensus about history means that we agree on who owns which coins, and agreeing on who owns which coins is a necessary prerequisite for believing that the coins have value. Because if there's not a consensus that I own a particular coin, then I'm not going to have any expectation that people will accept that coin from me in payment in the future. So consensus about history is a prerequisite for consensus that coins are valuable. But in the same way, the consensus that coins are valuable is needed to make the consensus about history work. And we heard about this in the earlier lecture when we talked about the incentive arguments, the ways in which the block reward that is built into the mining process creates an incentive for people to follow the expectations about mining. So the consensus that coins are valuable is what creates the incentives that allows us to get to a consensus about history. And so we have all three forms of consensus here, which are tied together, such that if any one of them failed, then the other ones would fall apart as well. And in a sense, the genius of Bitcoin, the genius in Bitcoin's original design, was in recognizing that it would be very difficult to get any one of these forms of consensus by itself. Consensus about the rules in a worldwide decentralized environment where there's no strong notion of identity, that's just not the kind of thing that's likely to happen. Consensus about a history, similarly, that is a very difficult distributed consensus data structure problem, which is not likely to be solvable on its own. And a consensus that some kind of cryptocurrency has value was also a very difficult thing to put together. What the designer of Bitcoin and what the continued operation of Bitcoin shows is that even if you can't build any one of these forms of consensus by itself, you can somehow stand up all three of them together and get them to operate in an interdependent way. And so when we talk about how things operate within the Bitcoin community, we have to bear in mind that Bitcoin relies on consensus, it relies on agreement by the participants, and that consensus is a fragile and interdependent thing. In section 7.2, we'll talk about the Bitcoin core software. This is a piece of open source software which is a focal point for discussion of and debate about Bitcoin's rules. The Bitcoin core software is a body of open source software. It's licensed under the MIT license, which is a very permissive open source license. It allows the software to be used for almost any purpose as long as the source is attributed and the MIT license is not stripped out. The Bitcoin core software comprises the most widely used Bitcoin software. And even those who don't use it tend to look to it to define what the rules are. That is, people who are building alternate Bitcoin software typically try to mimic the rule-defining parts of the Bitcoin core software. That is, they look at the parts that check which transactions are valid, they look at the parts that check which blocks are valid, and they try to behave in the same way as the core software. So this is the focal point for talking about what the rules are. In fact, the Bitcoin core defines the de facto rulebook of Bitcoin. If you want to know what's valid in Bitcoin, if you want to know what the rules are, this is the place to look. This or explanations of it. Another related piece of machinery is Bitcoin improvement protocols, or BIPs. These are formal proposals for a change to Bitcoin. And typically, an improvement proposal will include a technical specification for a proposed change as well as a rationale for it. So if you have an idea about how to improve Bitcoin by making some technical change, you're encouraged to write up one of these documents, you're encouraged to publish it as part of the Bitcoin Improvement Proposal series, and that will then kick off a discussion within the community about what to do. They're published in a numbered series. Each one has a champion, that is sort of an author whose job it is to evangelize in favor of it, to coordinate discussion, and to try to build a consensus within the community in favor of going forward with or implementing a particular proposal. Now, what I've talked about so far are proposals to change the technology. There are also some BIPs that are purely informational, just to tell people about things that they might not otherwise know, or that are process-oriented, that talk about how things should be decided within the Bitcoin community. But nevertheless, if you have an idea about how to improve Bitcoin, typically you would make a Bitcoin improvement proposal, and that would be the process for discussion going forward of proposed rule changes. And so we have a rule book, and we have a process for proposing, specifying, and talking about rule changes. Now, the other group we need to talk about with respect to the Bitcoin core software are the core developers. We have these 6 people, maybe arguably 5. Satoshi Nakamoto, who I'll talk about a little bit later, is not currently active. But the other 5 are currently involved as core developers of the Bitcoin core software. So these are the people who are leading the effort to continue development on the Bitcoin core and who are in charge of which code gets pushed into new versions of the Bitcoin core. So how powerful are these people? Well, on the one hand, they're very powerful in one sense. In another sense, they're not all that powerful at all. On the one hand, you could argue that they're powerful because the rule changes, that is, the changes to the code that get shipped in the Bitcoin core, will be followed by default. These are the people who actually hold the pen that can write things into the de facto rule book of Bitcoin. On the other hand, because it's open source software and anybody can copy it and modify it, anybody can fork the software at any time. And so if the lead developers start behaving in a way that the community doesn't like, strongly rejects, the community can go a different direction. So one way of thinking about this is to say that the lead developers are leading the parade. So they're out in front of the parade marching, and the parade will generally follow them when they turn a corner. But if they try to lead the parade in a direction that's disastrous, well, then the parade members, the marching behind them, might decide to go in a different direction. They can urge people on, and as long as they seem to be behaving reasonably, the group will probably follow them. But they don't have formal power to force people to follow them if they take the system in a technical direction that the community doesn't like. So it's worth, in this respect, thinking about what you as a user of a system can do if you don't like the way the rules are going or the way it's being run, and to compare a centralized currency, like either a fiat currency or a currency that's issued by a central entity, against something like Bitcoin. So in a centralized currency, if you don't like what's going on, you have the right to exit. You can leave the currency, which means that you can stop using it. You can sell any currency you hold or try to sell it, and then you can just stop using it. Just like any business that you do business with, almost any business, you have the ability to just stop dealing with them if you don't like what they're doing. On the other hand, if it's a currency and you've got a lot of business, you've got a lot of assets tied up in it, it might be expensive or difficult to actually exit. But with the centralized currency, that's really your only option. With Bitcoin, because it operates in an open source way, you have the right to fork the rules. That means you and perhaps some of your friends or colleagues can decide that you'd rather live under a different rule set, and you can fork the rules and go a different direction from where the lead developers have gone. The right to fork like this is more empowering for users than the right to exit. You can exit if you want, but you have the right to fork, and that actually gives you more power. And therefore, the community has more power in a system like Bitcoin, which is open source, than it would have with the purely centralized system. So although the lead developers might look like a centralized entity controlling everything, in fact, they don't have the power that a purely centralized manager or software owner would have. Let's look a little bit more at what happens if there's a fork in the rules. And I'm talking here, in a previous lecture, we talked about the distinction between a hard fork and a soft fork. I'm talking about a hard fork here. So what happens is the following. So here we have the blockchain, which is coming along, building up the history. And at some point, there will be a fork in the blockchain if there's a disagreement about the rules. And you get two branches. You get one branch, let's say this one up here, which is valid under rule set A, but invalid under rule set B. And conversely, you have another branch down here, which is valid under rule set B and invalid under rule set A. If there's a hard fork as to what the rules should be, then there will be some transactions that are valid on each side and not the other, and this will eventually happen. And once these branches go apart, they can't come back together because this branch is illegal under the B rules, this branch is illegal under the A rules. They're permanently separate. So if the currency that we had over here on the left we can think of as being Bitcoin, the big happy Bitcoin that everyone agreed on, after the fork, it's as if there are two new currencies, which you can think of as being A coin, corresponding to rule set A, and we'll call this one down here B coin, corresponding to rule set B. And it's as if at this moment where there was a fork, everyone who owned one Bitcoin at the moment of the fork will receive one A coin and one B coin at that time. And from that time on, A coins and B coins will operate separately, as if they were separate currencies. And they might operate independently. The A group and the B group might evolve their rules in different ways, and certainly their blockchains will continue to grow in ways that are probably inconsistent across the two coins. So when this happens, we might say that the currency forked, that it's not just the software or the rules that forked or the software implementing the rules that forked, it's the currency itself that forked. And that's an interesting thing that can happen in a system like Bitcoin that couldn't happen in a traditional currency where the option of forking is not available to users. Okay, so what happens if a fork like this goes on? What do people actually do? How do they respond? Well, after a hard fork like this, there are really two cases. The first case is where the fork was really not intended as a disagreement about the rules, but the fork was designed as a way of starting an altcoin, that is, of starting a new kind of cryptocurrency with different rules. And if somebody just wanted to start their own currency and they found it convenient to start with a rule set that was very close to Bitcoin's, they found it convenient maybe even to start with Bitcoin's blockchain and to fork off as I illustrated on the previous slide, then that's not really a problem. The altcoin goes its separate way. The branches coexist peacefully, and some people prefer to use Bitcoin, some prefer to use the altcoin. The interesting case is what happens if the fork actually reflected a fight between two groups about what the future of Bitcoin should be. If that's the case, then the two branches are rivals, and the branches will fight for market share. After the fork, there's an A coin and there's a B coin, and each branch will try to get more merchants to accept it. Each branch will try to get more people to buy it. The branches will fight for market share. The branches will fight to be seen, to be perceived as being the real Bitcoin. Probably each branch claims to be the real Bitcoin, and there's a public relations fight between them, which goes along with the fight for market share. Each one wants to be seen as the real thing, and the other one to be seen as the weird splinter group. Probably, eventually one branch will win and the other one will melt away. These sorts of competitions tend to tip in one direction. Once one of the two gets seen as more legitimate, gets seen as having a bigger market share, gets perceived more broadly as being the real one, the other one becomes kind of a niche currency and eventually will fall away. So this is the likely future if you had a fork that reflected a fight over the future of Bitcoin. And what this amounts to is a kind of rebellion within the Bitcoin community, where a subgroup decides to break off and say, we think we have a better idea about how this should be run, and you have a competition between the new and the old, which eventually one of them probably wins and becomes seen as the de facto new rule set and the de facto new governance structure. In section 7.3, we'll talk about who are the stakeholders in Bitcoin. Really, the question is who's in charge. We've talked about how Bitcoin relies on consensus and about how the rule book of Bitcoin is written in practice. We've talked about the possibility of a fork or a fight about what the rules should be. So now I want to come to the question of who actually has the power to determine who might win a fight like that. Okay, so who is the power? Well, suppose there's a negotiation about rule setting. There's a discussion within the community. There's a disagreement about which rule set should be used. Who actually controls the outcome? Now, if you think about it, as with any negotiation, one of the most important factors in understanding who has an advantage in the negotiation is to look at what happens if the negotiation fails and it comes down to a fight. And generally speaking, whoever has the best alternative to a negotiated agreement is going to have the advantage in a negotiation. In other words, whoever is likely to win a fight is likely to win the negotiation. It's the long-standing rule that on the playground, the biggest, strongest person is likely to get their way, even if no blows are exchanged. So let's talk about who actually has the power and who would be able to win if there were a fight involving a fork in the rules and a struggle for power over what the future of Bitcoin would be. So we can make a bunch of claims on behalf of a bunch of different stakeholders. The first claim is that the Bitcoin core developers have the power. Whoever it is that develops the core software, they have the power. They write the rule book. They literally have their fingers on the keyboard and have the ability to change the code that gets shipped. Since they write the rule book, since almost everybody does use their code and does follow their rules in practice, you could argue that they have the power because they can actually put a change out there that other people would, at least by default, accept. So the first stakeholder is the developers. A second claim, though, that we might make is that it's the miners who have the power. Why? Because miners are the ones who write the history. The miners are the ones who make the blocks that record the transactions that have happened. And so if the miners decide to follow a certain set of rules, then arguably everybody else has to follow it. We talked in previous lectures about what happens if you have a majority of miners. Certainly if there's a disagreement among the miners, and let's say 80% of them want one rule set, 20% want the other, well, the 80% group is going to be able to build a bigger, more impressive blockchain. And so they have some ability to push push the rules in a particular direction. Now, how much power they have depends maybe on whether the fork is a hard fork or a soft fork. This can get a little bit technical into the details of the dynamics of Bitcoin. But bottom line is, miners have some amount of power because they get to write the history. And the history is going to be consistent with whatever consensus rules the miners end up following in the long run. So the second claim is that the miners have the power. You might also claim, though, that investors have the power. Why? Because investors are the ones who buy a lot and hold a lot of the Bitcoins. And so it's the investors who decide whether Bitcoin has any value. If the miners control the consensus about the history, and the developers control the consensus about the rules, it's the investors who control the consensus that Bitcoin will have value. Or at least that's the way the argument goes. So in the case of a hard fork, the investors, if they all or mostly decide to put their money on one branch, on the A coin or the B coin, then that one will have a lot of perceived legitimacy. And so the investors have a lot of power to decide which way things go if there is a fork. On the other hand, we could claim that merchants and their customers are the ones who have the power. Why? Because merchants and customers are the ones who generate the primary demand for Bitcoin. Yes, investors provide some of the demand that supports the price of the currency, but the primary demand that drives the price of the currency, as we saw in Lecture 4, is driven by a desire to mediate transactions, to use Bitcoin as a transaction technology. And because merchants and their customers drive that demand, they're the ones who drive the long-term price of Bitcoin. Or so this argument goes. Investors, according to this argument, are just guessing where the primary demand will be in the future. So investors are guessing where the merchants and customers will go in the future. And therefore, it's the merchants and their customers who really have the power. On the other hand, we could argue that no, it's the payment services that have the power. They're the ones that really handle transactions. A lot of merchants don't care which currency they follow. They simply want to use a payment service which will give them dollars and ease of use and handle all of the risk. And so to the extent that merchants and customers have power and that those people rely on the payment services to actually handle transactions, well then maybe it's the payment services that have the power because they drive primary demand and merchants, customers, and investors will follow them. Okay, now I've argued for a bunch of different parties, all of whom I've argued should have the power. And there's some merit to all of those arguments. But the fact is all of those entities have some power. In order to succeed, remember, a coin needs all these forms of consensus. It needs a stable rule book written by developers. It needs investment. It needs mining power. And it needs participation by merchants and customers and the payment services that support them. So all of these parties have some power in controlling the outcome of a fight about the future of Bitcoin. And there's no one that we can point to as being the definite winner. It's a big, ugly, messy consensus-building exercise. There's one more player that I want to talk about when I talk about governance of Bitcoin, and that's the Bitcoin Foundation. The Bitcoin Foundation was founded in 2012, and it really does two main things. First of all, it pays the core developers, or at least some of the core developers, it pays them a salary out of the foundation's assets so that they can work full-time on continuing to develop the software. The other thing that the Bitcoin Foundation does is it talks to government, especially the US government, as the voice of Bitcoin. People in the Bitcoin community said that we have a problem, that there's no one to talk to government on our behalf, and so our case is not being made, our arguments are not being heard in government. We need to have an entity that will do that. And the Bitcoin Foundation is one of the things that was set up to do that. And so that's the other function that the Bitcoin Foundation was set up to do. Now, the Bitcoin Foundation is not in charge of Bitcoin any more than any of these other parties are. It has membership from some members of the community, not from other members of the community. And its success, ultimately, like everything else in this kind of open source consensus-based ecosystem, will be driven by how much support it can attract and retain from the community over time. And it's worth discussing the points of controversy that have happened with respect to the Bitcoin Foundation. There have been controversies over the membership in the board, where some members of the Bitcoin Foundation board have gotten into trouble. They've gotten into criminal trouble or they've gotten into financial trouble, and the foundation has had to struggle with dealing with what to do about members of the board that are become liabilities and have to be replaced on short notice. There's been some controversy from those people who believe that Bitcoin should operate outside of and apart from traditional national governments, that Bitcoin shouldn't be in the position of negotiating with the government. Bitcoin should be what it is, be independent of government, and simply operate across borders, not having to explain or justify itself to government at all. People who believe in that point of view don't like the fact that there are people in suits who hand out business cards saying Bitcoin on them and talk to government as the voice of Bitcoin. And finally, there have been controversies over the Bitcoin Foundation and the question of who put these people in charge. There are members of the community who feel that the foundation and the people who set up the foundation aren't really true representatives of the community, and that they are anointing themselves as leaders of something that they have no right to put themselves in charge of. So, although the Bitcoin Foundation is prominent, there are still some questions about what its role is going to be in the long run. I think it's fair to conclude that the Bitcoin Foundation, in its dealings with government, has done a fair amount to smooth the road for understanding of and acceptance of Bitcoin, at least within the US government. But still, the foundation continues to be a somewhat controversial organization and one that's going to be the topic of debate going forward. So when we come down to the question of who's really in charge of Bitcoin, who's in control, the answer is, in one way, nobody. That there is no one entity, no one group that's definitively in control. In another sense, the answer is everybody, because it's really the existence of this consensus about how the system will operate, the three interlocking forms of consensus on rules, on history, and on value, that really is what governs Bitcoin. And any group, any rule set, any structure that can retain that consensus will, in a very real sense, be in charge of Bitcoin. In lecture 7.4, we'll talk about the roots of Bitcoin, how it got started, what were the precursors to it, and we'll talk about the mysterious founder of Bitcoin. There were really two precursors to Bitcoin that are worth talking about. First, Bitcoin arose out of the cypherpunk movement. This was a movement that brought together two trends or arguments. First was libertarianism, and particularly the idea that society would be better off with either no government or with a very minimal government, with government enforcing only the minimum rule set necessary to allow people to coexist at all. So together with that strong libertarian notion, or perhaps even anarchist notion, we had the idea of strong cryptography and public key cryptography, which started in the late 1970s. These two ideas came together in the cypherpunk movement, and this was a group of people who believed that with strong online privacy and strong cryptography, you could re-architect the way that people interacted with each other into a world in which people could protect themselves and their interests more effectively, and could do so with much less activity, action, or, as they would say, interference from government. So that was the cypherpunk movement. One of the challenges in the cypherpunk movement was how you were going to deal with money in a future cypherpunk world, where people were interacting over the net and interacting via strong technical and cryptographic measures. And so a bunch of research came along, led especially by early digital cash work by David Chaum and others, that was designed to create new forms of value that functioned like money, like cash, in the sense of being anonymous and easily exchangeable, but also provided stronger notions of anonymity or privacy. And so early work in that area, and there's a whole interesting story about how that developed and why it didn't sweep the world. Early work in that area came together with the cypherpunk beliefs and the desire to have a strong currency that would be decentralized, online, and relatively private, to create the world from which Bitcoin was born, as well as the philosophy that many of the early supporters of Bitcoin, and even many of the supporters today, still follow. Bitcoin began in 2008 with the release of this white paper called Bitcoin, a peer-to-peer electronic cash system that was authored by Satoshi Nakamoto. This paper, which you can still get online easily, is the initial description of what Bitcoin is, basically how it works, and what the philosophy behind its design is. And so this is still a good thing to read if you want to get a quick idea of how the technical design of Bitcoin and how the initial philosophy of its operation was specified. So this was the beginning. This was released along with open source software to implement the Bitcoin system back in 2008, and this is where everything started. Now this was written by this person, Satoshi Nakamoto, and Satoshi is one of the central mysteries of Bitcoin. What do we know about Satoshi? Well, Satoshi is the author of this white paper in the original Bitcoin software. The name Satoshi Nakamoto was almost certainly a pseudonym. That is a fake name that some person or people have adopted for the purpose of doing things related to Bitcoin. The identity of Satoshi is associated with certain public keys, with certain accounts and certain systems, so that there are certain kinds of accounts or statements or certain kinds of digital signatures that would convince the community that something was said by or issued by or created by the real Satoshi. So Satoshi, while being a pseudonym, is also a person who can speak and who has spoken, especially extensively in the early history of Bitcoin. What do we know about Satoshi? Well, we know that Satoshi writes fairly well in English. Satoshi uses sometimes American, sometimes British spellings. There's been a lot of attempts to look at the text, to look at the code, and to try to figure out what is Satoshi's native language, where is Satoshi from, attempts to look at the hours and times, and what type of machine does Satoshi use, and all of these sorts of things, try to figure out who is this person or people, and what are they doing. Satoshi was fairly active in working on Bitcoin, on writing about Bitcoin, and participating in online forums until around 2010, and since that time, Satoshi has said almost nothing. There's one notable exception that I'll mention in a minute. Satoshi owns a lot of Bitcoins from early mining. In the beginning, Satoshi was perhaps the only miner, or one of the only few people mining Bitcoins, and those Bitcoins that were accumulated by Satoshi's accounts early on now are extremely valuable, and yet those accounts are not being cashed out. Everybody can see which accounts, which Bitcoin addresses probably belong to Satoshi. And so if those coins were to be cashed in, if they were to be sold and the proceeds transferred into any particular bank account, that would be a very notable event and would be an important clue to Satoshi's identity. And so interestingly, although Satoshi created the Bitcoin system and has on paper made a lot of profit from it, Satoshi is unable to cash in that profit without identifying him or herself, something that for whatever reason Satoshi doesn't want to do. The real identity of Satoshi, still unknown. The question of who's really Satoshi is a favorite parlor game at Bitcoin-oriented conferences. It's also something that a lot of reporters have tried to do. People have done all sorts of things. They've looked at text. The text written by Satoshi, try to compare it to other things. They've tried to look at other pieces of software, to patent applications. They've looked at who was writing papers about things that seemed like technical precursors to Bitcoin before Bitcoin came along, et cetera, et cetera. In a well-known incident last year, a reporter from Newsweek found a guy whose birth name was literally Satoshi Nakamoto and fingered him as the founder of Bitcoin, as the Bitcoin Satoshi. That was almost certainly incorrect, as we've since figured out. In fact, one of the few times, if any, that the original real Satoshi, has spoken since 2010 was to issue a short statement saying, nope, I'm not that guy. So as of today, and probably or perhaps forever, we don't really know who Satoshi is. And in some sense, it doesn't matter because of the notable feature of Bitcoin that it is decentralized and with nobody in charge. Satoshi's not in charge. To some extent, it doesn't really matter what Satoshi thinks anymore. Any special influence that Satoshi has is only because of respect that Satoshi would have within the Bitcoin community should Satoshi become active again. So it's possible that we'll never know who Satoshi is. So Bitcoin was started in 2008 by Satoshi, whoever he, she, or they are, and has grown since then. If we look at a graph of the transaction volume, the number of transactions per day, this starts on the left at the beginning of 2009 and goes up to the summer of 2014. What you see is something roughly like an exponential growth. And indeed, this is pretty much what you'd expect from something that's spread by word of mouth. Like the internet, like other popular technologies, Bitcoin has grown in a roughly exponential way, and when there are jumps, they typically correspond to bursts of publicity, moments when Bitcoin became known in the popular press, for example, or when there were newsworthy events. Transaction volume has gone up over time. The total value of Bitcoin also has gone up, perhaps in a similar way. What you see is this looks like zero, but in fact it's just very low. And you see a relative rise starting here, maybe beginning in the middle of 2012. This looks roughly like an exponential growth, but with two spikes superimposed on it. One here in roughly April of 2013, March or April of 2013, it spiked up and then relaxed back down to the underlying exponential curve. And then arguably here around the beginning of 2014, it spiked up to about this value and then relaxed back down again to something near the exponential growth which has happened since then. So arguably, Bitcoin has grown in a way that is relatively organic and at a relatively constant exponential rate since it was born. And those who believe that Bitcoin has a bright future ahead of it believe that this exponential growth will continue. Thus far in Lecture 7, we've talked about the growth of Bitcoin, we've talked about how Bitcoin operates, who's in charge of it. I want to spend the rest of Lecture 7 talking about governments interaction with Bitcoin and government attempts to regulate Bitcoin. And we'll start simply with the moment when governments noticed Bitcoin, when Bitcoin became big enough as a phenomenon that governments started to worry about the impact it might have, and governments started to talk about how to react to it. One reason why governments would notice a digital currency like Bitcoin is that an untraceable digital cash, if it exists, can defeat capital controls. Capital controls are rules or laws that a country has in place that are designed to prevent the flow of value, of capital, of wealth, either in or out of the country. And by putting controls on banks and investments and so on, a country can try to prevent these flows. Bitcoin is a very easy way under some circumstances, to defeat capital controls, because someone can simply buy Bitcoins with capital inside the country, ship those Bitcoins outside the country by electronic means, and then sell those Bitcoins for capital or wealth outside the country. By doing that, they could move capital or wealth from inside to outside, and similarly, you could do the same thing to move it from outside to inside. Because wealth in this electronic form can move so easily across borders and can't really be controlled, a government that wants to enforce capital controls in a world with Bitcoin has to try to disconnect the Bitcoin world from the local fiat currency banking system so that it's not possible for someone to turn large amounts of local currency into Bitcoin or large amounts of Bitcoin into local currency. And so we see countries that are trying to beef up or protect their capital controls do that. And a notable example is China. China has engaged in increasingly strong measures to try to disconnect Bitcoins from the Chinese fiat currency banking system. Another reason governments might worry about untraceable digital cash is that it makes certain kinds of crimes easier. In particular, crimes like kidnapping and extortion that involve the payment of a ransom or some kind of a payoff, those crimes become easier when payment can be done at a distance and anonymously. Law enforcement against kidnappers, for example, often has relied upon exploiting the handoff of money from the victim or the victim's family to the criminals. When that can be done by email, when that can be done at a distance in an anonymous way, it becomes much harder for law enforcement to follow the money. Similarly, tax evasion becomes easier when it's easier for people to move money around, when it's easier to engage in transactions that are not easily tied to a particular individual or identity. And finally, the sale of illegal items becomes potentially easier when the transfer of funds can happen at a distance and without needing to go through a regulated institution. A good example of that is Silk Road. Silk Road was essentially the eBay for illegal drugs. You can see here a screenshot of Silk Road's website when it was operating. It calls itself an anonymous marketplace. And you can see over on the left some sorts of things that are for sale. Illegal drugs were the primary thing for sale on Silk Road. You can see examples of the sorts of things that were for sale here. Silk Road allowed sellers to advertise goods for sale. They allowed buyers to buy those goods. The goods were delivered typically through the mails or through shipment services, and payment was made in Bitcoins. So Silk Road operated as a Tor hidden service, something that was discussed in an earlier lecture. So by operating as a Tor hidden service, the Silk Road servers could be hidden from law enforcement, so they were difficult for law enforcement to reach. Because Silk Road used Bitcoin for payment, it was also difficult for law enforcement to follow the money and figure out who the people participating in the market were. Silk Road was the largest online market for illegal drugs. As I said, it ran as a Tor hidden service and used payments in Bitcoin. The site held the Bitcoins in escrow while the goods were shipped. There was an innovative escrow system which helped to protect the buyers and sellers against cheating by other parties. The Bitcoins would be released once the buyer certified that the goods had arrived. Silk Road had an eBay-like reputation system that allowed buyers and sellers to get reputations for following through on their deals. And by using that reputation system, Silk Road was able to give the participants in the market an incentive to play by the rules, even though they would be very, very difficult to find otherwise. So Silk Road was innovative among criminal markets in finding ways of enforcing the rules of the criminal market at a distance, something that criminal markets have in the past had difficulty doing. Silk Road was run by a person who called himself Dread Pirate Roberts, and some of you may recognize that reference. Obviously a pseudonym. It operated from February 2011 until October 2013. Silk Road was shut down after the arrest of this guy, Ross Ulbricht, who was the alleged operator of Silk Road. He was arrested in October 2013 and he's currently awaiting trial. The government says that he was the operator of Silk Road and that he tried to cover his tracks by operating using various anonymous accounts, by using Tor, anonymous remailers, and those sorts of things. But they said that they were able to connect the dots and connect him to Silk Road activity, to connect him to the servers, and to connect him to the Bitcoins that belonged to the operator of Silk Road. They charged him with various crimes relating to operating Silk Road. They also charged him with attempted murder for hire. If the allegations are true, he more than once tried to pay to have people killed. Fortunately, he was bad at it and nobody actually got killed. But nonetheless, these are some pretty serious charges. The government, in the course of taking down Silk Road, seized about 174,000 Bitcoins. That's quite a bit of value. They then auctioned those off to the public. As with the proceeds of any crime under US law, they could be seized by the government, and the government did seize them. So Mr. Ulbricht is awaiting trial. We'll eventually perhaps find out the full evidence against him. Now, there are several lessons from Silk Road and from the encounter between law enforcement on the one hand and Dread Pirate Roberts, perhaps Mr. Ulbricht on the other hand. First of all, one lesson is that it's actually pretty hard to keep the real world and the virtual world separate. The operator of Silk Road believed that he could live his real life living in society and at the same time have a secret identity in which he operated a fairly good-sized business and technology infrastructure. That apparently is harder than you would think. It's difficult to keep these separate worlds completely apart and not accidentally create some linkage between them. It's hard to stay anonymous for a long time. It's hard to be very active and engage in a course of coordinated conduct in which you're working with other people over time while remaining anonymous. The reason being that although you can operate multiple identities, if there's ever a connection between two of those identities, if you ever slip up and use the name of one while wearing the mask of another, or if you ever slip up and create a link between them, that link can never be destroyed. And over time, the different anonymous or identities or masks that someone is trying to use tend to get connected, and there's a lesson there as well. The third lesson here is that the feds, the law enforcement, can follow the money. Because even before there was an arrest in the Silk Road case, the government knew that certain Bitcoin addresses were operated by the operator of Silk Road, and they were watching those addresses. The result is that the operator of Silk Road, while wealthy according to the blockchain, was not actually able to benefit from that wealth because any attempt to transfer those assets over into the dollar world would have resulted in a traceable event and probably would have resulted in rapid arrest. And so although Mr. Albrecht was allegedly the owner of 174,000 Bitcoins, the fact is he was not living like a king. He was living in a one-bedroom apartment in San Francisco, apparently unable to get to the wealth that he allegedly controlled. The lessons here are that if you intend to operate an underground criminal enterprise, and I hope you, as our students, are not, but if you are, that it's a lot harder to do than you might think. That the technologies like Bitcoin and Tor are not panaceas for people who want to do these things, and that law enforcement actually has some pretty significant tools that they can still use. And so although there might have been some panic in the world of law enforcement over the rise of Bitcoin, law enforcement is more and more realizing that they can still follow the money up to a point, and that they still do have a substantial ability to investigate crimes and to make life difficult for people who want to engage in coordinated criminal action. In section 7.6, we'll talk about anti-money laundering. What is money laundering and what are the rules that governments have imposed, especially in the US, that affect some Bitcoin-related businesses. So the goal of anti-money laundering policy is to prevent large flows of money from crossing borders or moving between the underground and legitimate economy without being detected. I talked earlier about capital controls, where countries are just trying to prevent money from crossing borders. In some cases, countries are just fine with money crossing borders, but they want to know who's transferring what to whom and where that money came from. Anti-money laundering is aimed at trying to make certain kinds of crime more difficult, especially organized crime. Organized crime groups often find themselves getting a lot of money coming in one place and wanting to ship it to somewhere else, but not wanting to explain where that money came from, hence the desire to get money across borders. Or they find themselves making a lot of money in an underground economy and wanting to get that money into the above ground legitimate economy so that they can spend it on sports cars and big houses or whatever it is that the leaders of the group want to do. Anti-money laundering is designed to make that more difficult, to either try to catch people trying to do those things or else prevent them from doing it in order to detect certain kinds of crimes or make organized crime more difficult. One of the rules that goes with anti-money laundering is something called Know Your Customer, sometimes called KYC. And the details of this can be a little bit complicated, depend on your locale, but the basic idea is this, that Know Your Customer rules require certain kinds of businesses that handle money to, first of all, identify and authenticate who their clients are, to know who these people are, and to get some kind of authentication that they really are who they claim they are, and that those claimed identities correspond to some kind of identity in the real world. So a person just can't just walk in and say, I'm John Smith from 123 Main Street in any town, USA. They have to actually give an identity and have that be checked in order to engage in certain kinds of business. Second, after identifying and authenticating the clients, the business may be required to evaluate how risky it is, what the risk is with respect to a certain client engaging in underground activities. And this will be based on how the client behaves, how long-standing their business relationship is with the company, how well-known they are in the community, and various other kinds of factors. But Know Your Customer rules generally would require some kind of risk analysis with respect to individual clients and would require a company that's covered by KYC to treat clients whose activities seem riskier with more attention. And then finally, third, typically there's a requirement to watch for anomalous behavior, to watch for behavior that seems to be indicative of criminal activity or of money laundering or of other sorts of things, tying that together with the risk evaluation to understand what's the level of risk with respect to a particular customer and what to watch for with respect to a particular customer. KYC will often ask a company to cut off business with a client who looks too dodgy or who's unable to authenticate themselves or their activities sufficiently for the rule. As I said, this gets complicated, but this is the basic outline. There are mandatory reporting requirements in the United States that are worth talking about. For example, companies in a broad range of sectors have to report currency transactions that are over $10,000. They have to file something called the Currency Transaction Report to say, what is the transaction, who is the other party to the transaction, and there's some requirement to authenticate who they are. This has to be reported to the government, and that goes into databases and then might be analyzed to look for patterns of behavior that are indicative of money laundering. Companies are also required to watch for clients who are engaged in what's called structuring, that is, in structuring transactions to avoid reporting. For example, if someone engages in a series of transactions that are $9,000 in value as a way to get around the $10,000 transaction reporting rule, that amounts to structuring. It looks like an attempt to evade the reporting requirements, and a company that sees structuring is required to report it, and they're required to watch for it. And so that requires filing of a suspicious activity report, again, filing that with the US government, and that again goes into a database, might lead to investigation of the client. The requirements here differ by country. I am by no means trying to give you legal advice about whether you need this or what you have to do. I just want to give an idea of what kind of requirements are imposed by anti-money laundering rules. But I do want everyone to note that the US government and other governments take anti-money laundering rules very, very seriously. This is not the kind of rule you can just blow off and deal with it if you get a complaint from the government later. Bitcoin businesses have been shut down. They've been shut down temporarily. They've been shut down permanently. Business people have been arrested. People have gone to jail for not following these rules. This is one of those areas where government will enforce the law vigorously, and where if you're interested in going into any kind of a business that is handling certainly large transactions or for sure currency or fiat currency value in quantity, you had better be talking to a lawyer who understands these rules. This is an area in which government absolutely does regulate Bitcoin, and has ever since they noticed that Bitcoin was large enough to pose a risk of money laundering. The R word, regulation. Now, regulation often gets a bad name, and it especially has a bad name among the kind of people who tend to like Bitcoin. Regulation is some bureaucrat who doesn't know my business or what I'm trying to do coming in and messing things up. It's a burden, it's stupid, it's pointless, etc. Now, those arguments often are correct, but I want to talk in a little more detail in this section about reasons why regulation might sometimes be justified. The argument against regulation is pretty common, it's pretty well understood. I'm not going to repeat it here. And so you'll hear me talking mostly about reasons why regulation might be a good idea, because that argument is not as well understood, and I want to lay it out here a little bit. But just to be clear, the fact that I'm spending most of this section talking about why regulation might be good shouldn't be read as an endorsement of widespread regulation, or as a feeling that regulation is the greatest thing ever. It's simply that I want to bring a little bit more balance to the discussion in a community where regulation is often considered as always bad or just stupid by nature. All right, so the bottom line argument in favor of regulation is just this, that when markets fail and produce outcomes that are bad, and often agreed to be bad by pretty much everyone in the market, then regulation can step in and try to address the failure. So the argument for regulation, when there is an argument, starts with the idea that markets don't always give you the result that you'd like. So let me give you an example of a way in which the market can fail, and this is a classic example called the lemons market, which originated in a discussion about used cars. So let's talk about a market in concept, a market for widgets, some kind of good that we want to sell. And let's say that widgets can be either low-quality widgets or high-quality widgets. A high-quality widget costs a little bit more to manufacture than a low-quality widget, but it's much, much better for the consumer who buys it. Consumers like high-quality widgets much, much better. Now, an efficient market, a market that's operating well, would therefore deliver mostly high-quality, or I'll write it HQ, widgets to consumers. Why? Because the price of the high-quality widget will be just a little bit higher, but the widget will be so much better that almost everyone will buy the high-quality widgets. And so this is what you would hope that a market would provide, and under certain assumptions, a market will provide that. But let's suppose that customers, for some reason, can't tell a high-quality widget apart from a low-quality widget. What if they really can't tell which widgets are good and which widgets are not. Think of a used car from the classic example. You're looking at a used car sitting on the lot. Well, gee, it looks pretty good, but you can't really tell if it's going to break down tomorrow or if it's going to run for a long time. The dealer probably knows if it's a lemon, but you as the customer can't tell the difference. So you can't tell high quality from low quality. So if you think about what happens, where incentives drive people in this kind of lemons market, you can see that as a consumer, you're not willing to pay extra for a high quality widget. Why? Because you can't tell the difference. And so if the used car dealer says, sure, this one is perfect, it's not a lemon at all, go ahead and buy it. It's only an extra $100. Well, it might be that you'd happily pay $100 for a higher quality car, but you don't really know whether that car, whether that widget really is high quality. So if you really can't tell which widgets are high quality versus low quality, then you're not willing to pay extra for the high quality one. And if consumers are not willing to pay extra for a high quality one, then producers can't make any extra money by selling a high quality widget. In fact, they lose money by selling a high quality widget because they don't get any price premium. They'd be better off buying the slightly cheaper low quality widget and selling it. And so the result is if consumers really can't tell which widgets are high quality and which are low quality, the market gets stuck in an equilibrium where only low quality widgets are produced and consumers are relatively unhappy with them. Now this outcome is worse for everybody than a properly functioning market would be. It's worse for buyers because they have to make do with low quality widgets when in a more efficient market they could have bought a widget that was much, much better for only a little bit higher price. It's also worse for producers because the widgets that are on the market are all lousy, consumers don't buy very many widgets. The widget market is relatively small, and so there's less money to be made selling widgets than there would be in a healthy market. And so both consumers and producers are worse off in a world where consumers can't tell the difference between high quality and low quality widgets. That's a market failure. It's called an asymmetric information failure, and the result is a market that's sometimes called the lemons market. Okay, so how can we fix this? Well, there are some market-based approaches that try to fix a lemons market. The first market-based approach relies on the seller's reputation. The idea is that if a seller tells the truth to consumers about which widgets are high quality and which are low quality, then the seller might get a reputation for telling the truth, and once they have that reputation, then maybe they can sell high quality widgets for a higher price because consumers will believe them, and therefore the market can operate more efficiently. The problem with this is, yes, this sometimes works, but sometimes it doesn't, depending on the precise assumptions you make about the market. But if you think about it, this is not going to work as well as a market where consumers can really tell the difference. Because for one thing, it takes a while for a producer to build up a good reputation. In order to build up a good reputation, they have to sell high quality widgets at low prices for a while until consumers learn that that seller is telling the truth. And that makes it harder for an honest seller to get into the market. The other problem that can occur is that that seller, even if they've been honest up to now, if for one reason or another their sales are shrinking or they think they want to get out of the market, their incentive is to massively cheat people all at once and then leave the market, rather than continuing to be honest and then leave the market. And so in the beginning of a seller's presence in the market and at the end of a seller's presence in the market, reputation tends not to work. This sort of reputation-based approach also tends not to work in businesses where consumers don't do repeat business with the same entity or where the product category is very new. And so there hasn't been enough time for sellers to build up a reputation, like, say, in a high-tech market like, say, Bitcoin exchanges. The other market-based approach is warranties. That's the idea that a seller could provide a warranty to a buyer that says that if this thing turns out to be low quality, if it doesn't work well for you, I'll give you a new one, I'll pay you back, or something like that. And that can work up to a point as well, but there's also a problem there, that this warranty is just another kind of product, which could also come in high quality and low quality versions. A low quality warranty is one where the seller doesn't really come through when you come back with a broken product. They don't really replace it, they don't really give you your money, they make you jump through all kinds of hoops. And so this is not a panacea either. So if you have a lemons market which has developed, and if these market-based approaches don't work for the particular market that you're dealing with, then regulation might be able to help. And there are three ways in which regulation might be able to help address a lemons market. First, regulation could require disclosure. They could require, say, that all widgets be labeled as high quality or low quality, and then have penalties on the firms for lying. That gives consumers the information that they were missing. A second approach to regulation is to have quality standards, is to require that no widget can be sold unless it meets some standard of quality testing, and have that standard set so that only high quality widgets can pass the test. That way you have a market that's all one kind of widget, but at least it's high quality widgets, assuming that the regulation works as intended. Or you could have required warranties so that all sellers have to issue warranties and then enforce the operation of those warranties so that sellers are really held to the promises that they make. So all of these are forms of regulation which obviously could fail, which might not work as intended, which might be miswritten or misapplied. They might be burdensome on sellers and so on, but there's at least the possibility that regulation of this type might help to address the market failure due to a lemons market. So this is one example of how regulation can be an efficient thing to do if it's done well when there's a certain kind of problem, namely the inability of consumers to tell the difference between a high quality and a low quality product offering. And so people who talk about Bitcoin exchanges, for example, and argue for regulation of them sometimes point to them as an example of a lemons market. Another example of a market failure, or a place where the market doesn't operate the way that you would like it to in order to serve consumers, is price fixing. Price fixing simply is a case where different people are selling a product in a market and they just agree with each other that we're going to raise prices or we're not going to lower prices. Related to price fixing is an agreement not to compete, where companies that would otherwise go into competition with each other agree not to compete with each other. For example, if there were two bakeries in town, they might agree that one of them will only sell muffins and the other will only sell bagels. And that way there's less competition between them than there would be if they both sold muffins and bagels. As a result of the reduced competition, presumably prices go up and the merchants are able to foil the operation of the market. Because after all, the reason that the market protects consumers well in its normal operation is through the vehicle of competition, that sellers have to compete in order to offer the best goods at the best price to consumers, and if they don't compete in that way, then they won't get business. So an agreement to fix prices or an agreement not to compete circumvents that competition and prevents competition from operating in the market. So another way that the market can fail is when people take steps that prevent competition. These kinds of agreements, either an agreement to raise prices or an agreement not to compete, these are illegal in most jurisdictions. This is part of antitrust law or competition law. In general, antitrust or competition law is aimed to prevent cases where the market gets stuck in a situation where there isn't enough competition to protect consumers, or cases where somebody acts in a deliberate way to try to prevent someone from competing with them, acting in a way other than simply offering good products at good prices. Antitrust law is very complicated. I've given you sort of a sketch of it, but this is another instance where we know that there are failures that can occur and where the law will step in to prevent, in the easy cases, things like price fixing or agreement not to compete, but in more difficult cases, even some attempts to reduce competition in the market through, say, mergers or other kinds of activity. Another example where regulation might be helpful. 7.8, I want to talk about New York State's bit license proposal. I've talked so far about regulation in general. I've talked about a few forms of regulation. I've talked in general about why regulation might be justified in some cases, why it might make good economic sense. But now I want to talk about a specific effort by a specific state to introduce specific regulation of Bitcoin. We'll dig a little bit into what the bit license proposal would do. This is an issue that is current as of the filming of this lecture, that'll be current as of the release of this lecture, and it gives you a snapshot of the kinds of things that regulators are doing. Okay, so the bit license proposal was issued in July of 2014. Down at the bottom of the slide here, there's a URL where you can go and read it if you like. Here's the heading on it, the New York State Department of Financial Services. That's the part of the state of New York that regulates the financial industry. And of course, the state of New York has the world's largest center of the financial industry in it. And so it's a part of the New York State government that is used to dealing with relatively large institutions. It's a proposed set of codes, rules, and regulations that has to do with virtual currencies. So this is a new regulatory proposal from the state of New York. And there's a lot of text here, but let's walk through it. It's worth talking about. What the regulation fundamentally says is that you would need to get something called a bit license from the New York Department of Financial Services if you wanted to do any of the things listed on this slide. If you wanted to engage in virtual currency business activity, that means any one of the following things if you're dealing with New York or a New York resident. So if you're doing any one of these 5 things and any of your customers are in New York, and perhaps consult your lawyer, if you have business partners or other aspects of your business in New York relating to this, you need a bit license. The first thing is receiving virtual currency for transmission or transmitting virtual currency. Second, securing, storing, holding, or maintaining custody or control of virtual currency on behalf of others. This might cover something like wallet services or other sorts of things, or perhaps exchanges. Buying and selling virtual currency as a customer business. You can apparently buy and sell it for yourself, but doing it as a customer business, you need a bit license. Performing retail conversion services, including conversion or exchange of fiat currency or other value into virtual currency, conversion or exchange of virtual currency into fiat currency, or the conversion or exchange of one form of virtual currency into another form of virtual currency. So if you're trading virtual currency for fiat currency or virtual currency for virtual currency. And finally, controlling, administering, or issuing a virtual currency. If you're doing any one of those things in the state of New York or operating with a New York State resident, then you need to get a bit license from the New York Department of Financial Services if this regulation goes into effect. You would have to apply for a license. To apply for a license, there's detailed language in the proposed regulation which you can read, but roughly speaking, you have to provide information on the ownership of your enterprise, on your finances and insurance, on your business plan, generally to allow the Department of Financial Services to know who you are, how well backed you are, where your money comes from, and what you're planning to do. You have to pay an application fee. You would have to pay. A licensee would have to do the following things once you had a license. You'd have to provide updated information to the Department of Financial Services about the things I talked about before, ownership, finances, insurance, and so on. You'd have to provide periodic financial statements so they can keep track of how you're doing financially. You'd be required to maintain a financial reserve. The amount of that would be set by the Department of Financial Services based on various factors about your business, what's the nature of your business, how well financed it is, who it is, how big it is, et cetera, et cetera. The DFS would be able to set rules about that. There are detailed rules about things like how you would keep custody of consumer assets. There are anti-money laundering rules which might or might not go beyond what's already required. There are rules related to cybersecurity, having a cybersecurity plan and penetration testing and so on. There are rules about disaster recovery. You have to have a disaster recovery plan and that meets various certain criteria. There are rules about record keeping. You have to keep records and make them available to the DFS on certain circumstances for some length of time about certain kinds of activities. You'd have to designate a compliance officer, someone within your company, your organization, who is in charge of compliance and has responsibility and authority to make compliance happen. You have to have written policies about compliance and about certain kinds of things that are satisfactory to the NYDFS. And there's a requirement that you disclose risks to consumers so that consumers understand what are the risks of doing business with you. The exact rules on that are not exactly clear at this point, but you might imagine something like the sort of prospectus that comes along with a mutual fund or with a publicly traded stock. Perhaps that's what the DFS has in mind. So these are fairly substantial requirements for companies that have a bit license, and anyone with a bit license would be required to do all this stuff. The state of the bit license proposal right now, the situation that it's in as of this filming, which is August 2014, is it has been proposed by the New York Department of Financial Services. It's been formally proposed. You can go read the document, the proposal at the URL that was on the earlier slide. The DFS has solicited public comments. They have asked members of the public to write in and give them comments about the proposal. Do you like it? Do you not like it? What's good? What's bad? What do you propose changed? And so on. And lots of entities are gearing up to send comments to the NYDFS. After all the comments are in accordance with the normal regulatory process, the NYDFS will decide what to do. They'll decide whether to withdraw the proposed regulation, whether to issue it in modified form, whether to issue it in exactly the original form, and along with that decision, they'll issue some kind of a document that gives the rationale for deciding what they decided to do. Now, various parties have asked the NYDFS to grant an extension on the original date for comments, and NYDFS has signaled, they haven't definitively stated, but it seems pretty clear at this point that they're going to grant an extension. Because of that, I don't currently know the date. I can't tell you the date by which you have to comment, but you can go and look at the NYDFS website to get the current status. If you're an interested party, by all means, I would encourage you to comment. I would encourage you to get together with others and comment together. And I would advise you to make comments which are thoughtful and constructive and give the NYDFS reasoned arguments. Comments of the sort of, this is the coolest thing ever, or you guys are total idiots, you don't know what you're doing, might make you feel good, but they're not going to affect what the NYDFS does. My prediction at the end of the day is that some kind of bit license is likely to be put in place by the NYDFS. Maybe it will be reduced from the scope or changed from what was originally proposed, but some kind of bit license, some kind of licensing regime which calls itself bit license, I predict, will be put in place by the New York Department of Financial Services. If this happens, or if New York doesn't do it and somebody else does something similar, the result will be that if you want to do business in any of the business sectors that we talked about in the previous slide, you would need a bit license from the state of New York in order to operate. And if this goes into effect, this would really be a major step in the history of Bitcoin. You would have a situation where not only NYDFS, but perhaps other jurisdictions would start to step in and regulate, and you'd start to see Bitcoin businesses get closer to the model of regulated financial institutions that traditional financial institutions have been in. This would be a step that really is in some ways contrary to some of the initial cypherpunk or cyber libertarian ideas about what Bitcoin was supposed to be. But in a very real sense, I think it's inevitable that as soon as Bitcoin became really valuable, that Bitcoin businesses became big businesses, that government got interested, it was more or less inevitable that regulation would ensue. Because Bitcoin businesses touch real people, because they touch the fiat currency economy, because Bitcoin is big enough to matter, government is paying attention and Bitcoin is getting regulated. This, on the one hand, represents a retreat from what the original advocates of Bitcoin had in mind. In another way, it represents the Bitcoin ecosystem growing up and integrating into the regular economy, which is much more regulated. Regardless of whether you like it or don't like it, this is a thing that's starting to happen. And if you're interested in starting a business in this area, you need to be paying attention to this trend. Will this be a success? Will it be good or bad? Well, I think there's one barometer we can look to understand whether a regulation like the bit license is actually successful from a public policy standpoint at improving the quality of Bitcoin businesses. And that's this. If something like bit license goes into effect, and if companies start advertising to customers outside New York that we have a bit license, therefore you can trust us, and if that argument that we're regulated, therefore you can trust us, is convincing to consumers, if consumers see regulation as a positive in choosing a company, then I think the regulation will be working in the way that its advocates wanted it to do. Whether that will happen and how this affects the future of Bitcoin is something that we'll have to wait and see.
In this lecture, we're going to talk about alternatives to Bitcoin's existing proof-of-work mining puzzle. Mining puzzles are at the very core of Bitcoin because mining puzzles determine the incentive system in Bitcoin. Bitcoin miners get rewards for the puzzles that they solve. We expect that miners will spend considerable effort trying to find any shortcuts available to them to solve these puzzles faster or more efficiently. If there's a faster way to solve puzzles, we think they'll take it. Also, if there's extra stuff to do that might help the network but doesn't directly help them solve puzzles any faster, we expect that they might eventually not bother to do so at all. Therefore, the nature of the puzzle plays a very important role in steering and guiding participation in the network. Now, we've talked about some of the basic features that Bitcoin's existing SHA-2 hash-based mining puzzle already satisfies. So for example, it's fairly difficult to solve a whole bunch of puzzle solutions. This makes attacks on the Bitcoin network very costly or unlikely to succeed. On the other hand, puzzle solutions are found at a fairly predictable rate, once every 10 minutes by someone. This means that honest miners, to participate, have some incentive to keep participating and compensate themselves for the resources that they put into the network. Now, if we were going to design a new puzzle system from scratch, or modify Bitcoin's puzzle system to be different somehow, what else could we design the puzzle to achieve? What other kinds of behaviors would we like to encourage or disincentivize? In this lecture, we're going to talk about a variety of possible alternative puzzle designs. Some of them are already used in practice in altcoins existing today. Others are research ideas that might turn out to be used in the future. The puzzles that we'll look at can achieve a variety of possible goals, such as ASIC resistance, which means leveling the playing field between users with ordinary computing equipment and users with special optimized custom hardware. We'll also look at puzzles that discourage users from delegating their participation to directors of large centralized pools. And we'll look at useful proofs of work that have some intrinsic social benefit. We'll also talk about some of the essential security requirements for mining puzzles. It doesn't do any good to have some fancy secondary feature if the puzzle doesn't still satisfy the basic requirements that it needs to keep Bitcoin secure. Before going into the alternate puzzle designs, let's talk a little bit about some of the essential requirements that any viable mining puzzle has to satisfy. Now, there are many possible requirements. We've talked about some of them before. Mining puzzles need to be cheap to verify the solutions because every node on the network validates all of the puzzle solutions, even ones that aren't involved in mining directly. Puzzles also have to have adjustable difficulty so that the difficulty of the puzzle can be adjusted over time as new users join the network with increasing amounts of hash power contributed. I'm only going to talk in detail right now about one other essential requirement, which is a little bit subtle. This is that the chance of winning a puzzle solution in any unit of time should be roughly proportional to the hash power contributed. In particular, this means that really large miners with very powerful hardware should only have a proportional advantage in being the next miner to find a puzzle solution. Even small players should have some proportional chance of being successful in receiving compensation. Now, to illustrate this point, let me show you an example of a bad puzzle that doesn't satisfy this requirement. Consider a mining puzzle that takes exactly n steps to find a solution. There are examples of puzzles like this. I don't need to go into details though, but consider these a sequential proof of work. A miner would be able to find one of these proof of work solutions by computing n steps in order in a sequence. Once it reaches n steps, finds a solution. Now, the problem is that if it takes exactly n steps in a sequence to find a puzzle solution, then the fastest miner in the network will always be the one who wins the next reward. Right? So consider a scenario with two equally powerful miners and a third miner that's slightly faster at making computational steps than the other two. For every step that the small miners take, the large miner takes 2 steps here. This means that the large miner finds its puzzle solution at the end of n steps while the smaller miners are still computing theirs. In this case, the fastest miner would be the only one who would receive any compensation at all. Therefore, none of the other nodes would have any incentive to participate in the first place. So the alternative to this, a good puzzle, is one that gives every miner a chance of winning the next puzzle solution in proportion to the amount of hash power they contribute. This forms a weighted sample of all of the miners. So imagine throwing a dart at a board randomly, at a board of different sized targets where the size of the target corresponds to the mining power. The more hash power you contribute, the better your chance of being the node that finds the next puzzle solution. A puzzle that has this property is sometimes called progress-free. Now, this was just one of the requirements. There are others, but for now, we're going to move on to types of alternative puzzles, and we'll discuss essential requirements as they come up. We're going to start by talking about ASIC-resistant mining puzzles. These are far and away the most widely discussed and sought-after alternative mining puzzles. Now, there are several reasons why we might want an ASIC-resistant mining puzzle. If you recall from previous lectures, Bitcoin mining used to be done using ordinary computers like CPUs and GPUs, then eventually moved towards customized FPGA devices, and now mining is mostly conducted using very powerful optimized ASIC chips, which are so vastly more effective than general-purpose computing equipment that it doesn't even pay off to use an ordinary computer or a very old generation of mining equipment. But this is too bad in a way, because it used to be very appealing that ordinary users could mine Bitcoins out of thin air just by leaving their computer on overnight, a computer that they already had. This was really good for a low barrier to entry because it gave a compelling reason for ordinary users around the world to join the Bitcoin mining network and participate. So wouldn't it be nice if we could go back to the good old days when it was possible to mine Bitcoins using ordinary general-purpose computing equipment? So the approach to go back to this is to come up with a puzzle that reduces the gap between the most cost-effective, customized hardware and general-purpose equipment that ordinary people already have. A separate goal is to try to prevent the very large ASIC manufacturers from dominating the Bitcoin mining game. There are only a few companies that are able to produce large semiconductor fabrication in order to actually produce the ASICs. So this represents a sort of consolidation of power. Now, a lot of customers of Bitcoin mining ASICs have this concern that the manufacturers are going to delay the shipment of their mining devices in order for the manufacturers to use the mining devices themselves in order to use them for their own benefit to get their own rewards at the expense of their customers. Another concern is that if there is some breakthrough and there's a vastly more efficient ASIC design, whoever comes up with that design might keep it a trade secret to themselves and use it to build their own very powerful industrial mining center. And then they would be able to dominate the network. So the approach here might be to build a puzzle that reduces the gap between potential future hardware ASIC designs and the ASICs that we already have, which are largely distributed to ASIC mining customers. We're going to start by talking about the most widely used approach towards having an ASIC-resistant puzzle. This is called a memory hard puzzle. Now, the premise here is fairly simple, and it's based on a well-known phenomena since the 80s about the change in the performance of computing equipment over time. Since the 80s, the performance of processing has increased at an exponential rate. You've probably heard of this referred to as Moore's Law. Now, the performance of memory and storage have also increased at an exponential rate, but this rate is much lower rate than that for processors. There's a performance gap between the most efficient processors and the most efficient memory and storage, and this gap actually grows over time. This means that if we had a puzzle that required lots of memory to compute, rather than just processing circuits, then the potential improvement from next generation's optimized hardware, the current generation of optimized hardware, or even general purpose computing equipment would be much lower, and that's what we want. So we're going to talk now about the most popular instance of a memory hard puzzle. This is called scrypt. Scrypt's actually a memory hard hash function, and an scrypt-based mining puzzle is the same as the Bitcoin mining puzzle, just replacing the SHA-2 hash with the scrypt hash. Scrypt is memory hard in the sense that it has a constant time memory trade-off. This means that the hash can be computed using a fixed amount of memory. It's possible to compute it using less memory, but doing so increases the amount of time that it takes to compute. Now, as I mentioned, this puzzle is actually widely used in Bitcoin alternatives, including the second most popular cryptocurrency, Litecoin, and a variety of others. One thing that is to scrypt's advantage is that this hash function is also used in other places in security, especially password hashing, which has similar goals to ASIC resistance in Bitcoin mining. This gives extra confidence that if there are security problems with the hash function, then other people are looking at them and might find them. Now, the basic way that script works goes in 2 steps. The first step involves filling a large block of random access memory with random values, and the second step involves reading from this memory in a random order. Now I'm going to give a detailed illustration of just how the script hash function works. Now the goal here is going to be to compute the script hash function of an input string x. Now, this is going to be the first step. The goal is to fill a block of memory containing n cells with random values. Here n is 36. Now these values are going to be filled in sequential order. The first value, v1, is simply the hash of the input string x, where the hash function h is an ordinary hash function like SHA-2. Now the second value, v2, is the hash SHA-2 of the previous value, v1. This is the same as the hash function applied to the input string x twice. And so on. The third value, v3, is the hash function applied to the input value x 3 times. And so on. After n iterations, all in-memory cells are filled up with pseudo-random values, and the last value is the same as the hash function h applied to x n times. Now in the next step, we're going to read back the values of memory in random order. Now we're going to begin by having an accumulator value a, which involves computing the hash function h one more time on the last value. Now for n iterations, we're going to use the current value of the accumulator a to pick an index I out of these n potential memory cells. Then we're going to read that value of memory, XOR it with the current accumulator value a, take the hash h once more of this value, and replace the accumulator's value with this updated value. Now, after n iterations, the final value of the accumulator a is the output of this hash function. Now let me explain the intuition for why this script hash function is memory hard. Now you can compute this by using the n memory cells as described just before. It's also possible to compute the script hash value using less memory. Suppose you wanted to cut down the amount of memory you needed by half. You could do this by only storing every other value v in the table, only the odd values in this case. Now, what happens if you need to access one of the even-numbered values of v which you aren't storing? Well, you need to compute it from the values of v that you are storing. Now, you can always compute vi by computing the hash h of vi minus 1. Now this works and you got away with using less memory, but you had to compute an extra value for h. Now this intuition holds up. On average, if you wanted to reduce the amount of memory by half, you would have to increase the amount of computation cycles you need by a factor of 1.5, and so on. Now to talk a little bit about script used in practice, there are a couple of disadvantages. One is that even though it has this advantage of being memory hard to compute, the script-based mining puzzle also requires n amount of memory and n cycles in order to check a proof of work puzzle solution. This puts a constraint on how large you can set n, in other words, how memory hard you can make it. Now a good question is this memory hard puzzle actually ASIC resistant? And there's some uncertainty here. Script ASICs are already available, at least the first generation of these, and they're at least somewhat faster than what you can do with general purpose computing equipment like CPUs and GPUs. There are several companies competing to make faster script ASICs, and it's unclear how much better this performance gap will be able to get. There's some concern that in the altcoins that currently use script-based mining puzzles that the parameter n hasn't been set correctly, and this is one of the factors leading to ASICs arriving. Now, this general approach of having a memory hard hash function is good because, as I mentioned, script is used in other applications like password hashing. And so if there's any future improvements in password hashing, then memory hard mining puzzles would be able to use these new password hashing functions and be able to achieve the desired effect. Now I'm going to talk about another approach to having a memory hard proof of work mining puzzle. This puzzle is called cuckoo hash cycles. And the main advantage this has over script is that it doesn't require any random access memory to check a puzzle solution. Now we're going to look at how this works, which involves for every mining attempt, we're going to start with a potential solution X, which you can think of as a random string. And we're going to use the following procedure to determine whether or not X is a puzzle solution. For the first step, we're going to select the E pseudo-random edges in this graph. Now for each edge, we're going to pick a random node from the top set of nodes and a random node from the bottom set of nodes. Now we do this by computing hash values using, again, the underlying hash value h, which can just be an ordinary hash function. Now the edges are filled in the graph as illustrated below. Once the graph's completed, we want to determine whether or not there's a cycle in the graph of size k. Now a cycle is a set of edges such that if you align the edges tip to tip or tip to end, then they form a complete cycle. So here's what a cycle of size 4 would look like in this illustrated graph. Now k is another parameter of the puzzle. If the graph determined by input x has a cycle of size k, then we say that this has a solution. And we just output the input value x as well as the evidence that there was a cycle, so the k indexes of the edges. Now it's not as intuitive why this is a memory hard function, but the explanation is that finding cycles in graphs is a fairly well studied problem, and the best known algorithms for doing this do require a large amount of memory. Now what is really clear to see is that this puzzle is very easy to check. The only thing you need to do in order to check the puzzle solution is to recompute what the edge endpoints would be for each of the k edges provided using the input value x. You only have to compute k hash functions and no random access memory is required. Now, there are even more approaches towards building ASIC-resistant mining puzzles. I'm only going to describe these really briefly. One is to simply build much more complicated hash functions than the ones that we've talked about so far. One example of this is the mining puzzle based on the X11 hash function, which is simply 11 well-known hash functions strung together in a sequence. Another approach is to have a mining puzzle that's a moving target. Here you would have a mining puzzle that actually changes altogether every so often. This means that optimized mining hardware for one puzzle probably wouldn't be good at solving all of the puzzles even after the puzzle changes. And customized mining hardware that's only good at solving one instance of the puzzle won't be very useful once the puzzle does change. Now it's unclear exactly how we would change the puzzle every so often in order to maintain the security requirements that we need. Now there's a counter-argument that says that there's really no point in trying to make an ASIC-resistant puzzle because the SHA-2-based mining puzzle that we already have is already good enough. Now, the SHA-2 circuit is pretty well understood. We have a good idea of what's the optimal way of computing SHA-2. As a result, Bitcoin mining ASICs aren't changing very much, and it seems unlikely that there's going to be a breakthrough in computing these proof-of-work solutions any faster. Now, even as it is today, mining ASICs consist of multiple copies of the same basic SHA-2 circuit. And the only difference between the largest ASICs and the smallest or cheapest ASICs is that they have more copies of the same essential circuit. This means that even the biggest mining ASICs are only a little bit more cost-effective than the smaller ASICs. They compute puzzle solutions faster, but they're also more expensive. Now we're going to talk about another possible desired quality for puzzles, which is for them to have some sort of socially beneficial intrinsic use. Now, there's a sense in which it seems like Bitcoin mining is extremely wasteful. If you recall from previous lectures, we think that Bitcoin mining consumes about 150 to 900 megawatts of power in total, and this is comparable to the power output of a really small hydroelectric power plant, for example. Now, this mining work is put towards computing these SHA-2 mining puzzles, which don't serve any purpose outside the Bitcoin mining system. So this raises a very natural question. Is there some way that we could have a puzzle where computing the puzzle solution actually provides some sort of useful benefit to society while still satisfying the basic things that Bitcoin puzzles need? This would amount to something like recycling, and it would have advantages such as lowering the overall cost of the Bitcoin system and potentially reducing Bitcoin's environmental impact. Now, there are a bunch of natural candidates for this that seem like they might work. The general structure of these possible candidates are problems that involve finding a solution in a potentially very large solution space, where the good solutions that you're looking for are very sparse within this space. This is like finding a needle in a haystack. Problems of this sort include protein folding, where the goal is to find a 3D configuration of a molecule that has a very low potential energy. Or searching for aliens and signals from radio signals in space and looking for anomalous patterns that might indicate extraterrestrial life. Now, for the same reason these seem like they might work as a Bitcoin mining puzzle, these have been successfully used in the past as crowdsourced distributed computing projects, such as Folding at Home and SETI at Home. Now, there are a bunch of challenges that would have to be solved in order to use a problem like this in Bitcoin. In the cases that I just described at home, like Folding at Home and SETI at Home, there's a trusted administrator of the distributed computing project that's able to choose which instances of problems all of the participants in the network are supposed to be working on. Now, in Bitcoin, there is no trusted administrator to choose the problems. So instead, instances of the problem have to be generated pseudo-randomly from public information, such as the hash of the last block that was found. Now, in order for these to be useful, randomly generated puzzle instances of this sort would have to still be useful, and also randomly generated puzzle solutions have to be hard. Now, it's not known how to turn any of these problems into such a puzzle scheme. Now, there is one example that seems to work and has already been implemented and is somewhat used in practice, which is called PrimeCoin. Now, the goal here is to have a mining puzzle where finding a puzzle solution involves finding a chain of very large prime numbers. In particular, to find a puzzle solution in PrimeCoin, you have to find a Cunningham chain. Now, a Cunningham chain consists of a sequence of prime numbers p, where each of the p's is of the form 2 to the power of some number times a constant a plus 1. Now, each p in this sequence has to be a large probable prime, where whether or not it's a probable prime uses a probabilistic prime checking algorithm. And also, the first instance of the prime number p has to be a multiple of the hash function of the metadata for the block, such as the hash of the previous block, the Merkle root of the transaction, and a random nonce value that miners get to choose. Now, this has been used in an altcoin called PrimeCoin, and it's actually paid off in some sense. Many of the largest known Cunningham chains have come from miners in the PrimeCoin network. Now, this is interesting because there have been distributed computing projects such as PrimeGrid, which have also tried to find prime number chains of this sort. This also adds some confidence that this is truly a hard problem because a lot of other people are also interested in finding solutions to this sort of problem. So is this actually useful? Well, possibly. There is at least one known use of Cunningham prime number chains, but the kind of Cunningham chains that are found by PrimeCoin miners are actually entirely overkill for this application. Now, there's another approach towards having a proof of useful work, which is rather than focusing on the amount of power or work output of the network, we might instead focus on the effect of investment in Bitcoin mining infrastructure. Now, just as an estimate, a lot more than $100 million have been spent on customized Bitcoin mining hardware overall. This includes designing new Bitcoin mining equipment as well as actually manufacturing it. Now, this Bitcoin mining equipment is very good at computing SHA-2 hashes, but this improvement in technology is only useful for the Bitcoin network. It has no other use otherwise. So the idea is, what if we could design a puzzle where the investment in newer and better Bitcoin mining hardware would itself be useful, even if the work that's done in the power output of the network is still wasted? Now, here's one example of a proposal that has this quality. It's called PermaCoin, and the idea is to replace Bitcoin mining rigs, which compute SHA-2 hash functions, with storage devices, such as hard drives and memory. Now, the side effect of Bitcoin miners investing in better mining equipment would be a side effect of having a massively distributed, replicated backup storage system. Now, the way that PermaCoin works begins by assuming that we have a large file F, which everyone knows about, and the goal of the network is going to be to store this file. Now for simplicity, imagine that F is chosen globally by a trusted dealer at the beginning. Each user is going to store a random subset of this file. Now Permacoin is based on an alternative puzzle that uses storage. Now assume that you have the file F broken up into several blocks. The first part of Permacoin involves building a Merkle hash tree over each of the blocks of the file. Now every user is going to generate a key pair in order to mine, which is going to include a public key PK. And they're going to use their public PK to pseudo-randomly select a subset of these file segments F that they're now responsible for storing. Now for each mining attempt, the miner is going to select a random nonce value, and they're going to compute a hash function h1 that includes the previous block hash, the Merkle root of transactions, their public key pk, and the nonce value that they chose. Now rather than checking if this is a puzzle solution immediately, they first have to fetch k pseudo-randomly chosen file segments from the subset that they're storing, which is determined from that hash value h1. Now they compute a second hash value h2, which includes all of the data used to compute the first hash, as well as the actual contents of the file blocks F. Now from the second hash value h2, it's compared to a target in order to see if the puzzle solution is actually a valid solution. So the idea here is that the only way to make attempts at finding a puzzle solution and determine if an attempt is a valid puzzle solution requires you to store the random subset of file blocks that you were supposed to based on your public key. Here's one application of the Permacoin storage puzzle. This involves a kind of subtle point about Bitcoin's incentives. There's a cost to being an honest miner in Bitcoin. Remember that honest miners are supposed to validate every Bitcoin transaction that's included in a block. However, validating a transaction requires storing the unspent transaction outputs database, which at the current time requires about 200 megabytes of storage. Now, maintaining this unspent transaction output database doesn't help you find puzzle solutions any faster. It's a little bit like unpaid overtime. So the idea would be to use the Permacoin storage-based puzzle in order to reward miners for actually storing copies of the unspent transaction output database. This would reduce the marginal cost of being honest versus just mining for the sake of getting all of the rewards. So to summarize this section, having a proof of useful work is a very natural goal, but the challenge is to have this secondary side effect while still maintaining the essential security requirements. There's an argument that any benefit would have to be a pure public good, because if there were a way for an individual miner to get the benefit of the useful work they were doing, then this benefit would also benefit an attacker. So it would make attacks on the network subsidized to the same amount that it would add any secondary improvement to society. Now, potentially viable approaches to this include storage and finding large chains of prime numbers. But other potential approaches could be possible as well. So even though some of these useful proofs of work have been implemented in practice, arguably the benefit to society so far from these is pretty minimal. Now we're going to talk about another topic for alternate puzzles, which are puzzles that discourage consolidation of mining power. Now, Bitcoin miners mostly participate by joining mining pools rather than participating as independent individuals. Now, this means that very large mining pools that are directed by a central pool administrator become a very large potential consolidation of power. Now, Bitcoin's core value is decentralization. So this consolidation of power poses a big threat to Bitcoin's core values. Now, if the power is consolidated in a few large centrally managed pools, then the large pool operators become a juicy target for attacks like coercion or hacking. So a point could be made that we might want to discourage the very large pools from forming. There's even an analogy to voting here. It's illegal in the United States, for example, to sell your vote to someone for money. Arguably, by participating in a pool controlled by someone else, it's akin to selling your vote in the Bitcoin network. Now, recently this has become a popular problem because the very largest Bitcoin mining pool, gigahash.io, has reached larger than 50% of the network's overall hash power. This has led to a bunch of public outcries explaining that this is a very big threat to Bitcoin and spells doom or something to that effect, and demanding technical solutions to this problem. Now, the observation behind one technical approach to this problem is the observation that members in a Bitcoin mining pool don't inherently trust each other. Actually, pools can only form and become very large because members of the pool are able to prove to the pool operator that they're towing the line and doing mining work that can only benefit the pool as a whole. This works by using the shares protocol that was described in earlier lectures. Now, recall that in a Bitcoin mining pool, there's typically a pool operator who has a well-known public key. Now, each of the miners sends their near misses, or their mining shares, to the pool operator to show that they're mining on a puzzle that directs the reward to the pool operator's public key. When a solution is found, the pool operator then distributes the rewards among the pool participants who have contributed to finding the solution. Now, there's an interesting attack on Bitcoin mining pools, which we're going to call the vigilante attack. Suppose that there's a pool member who's very upset with a large mining pool. He can participate in the pool by mining and submitting his near-miss share values to the pool operator just like normal. But in the event that he actually finds a Bitcoin puzzle solution that would reward the pool, he just throws that away and doesn't tell the pool operator about it. Now, the effect of this attack is that the overall effective mining output of the mining pool is reduced. However, the vigilante only loses a little bit. He still gets rewards for other puzzle solutions that are found. He gets a proportional reward due to the shares that he submits. Now, one problem with this attack is that a vigilante still has to lose something and doesn't gain anything. And so it seems unwise to rely on vigilantes like this, monitoring the network and rightfully choosing when to do this to only attack large pools. Here's an illustration of what the vigilante attack looks like. The vigilante still submits shares to the pool operator, and if he finds a solution, discards it. So the approach of a non-outsourceable puzzle is to encourage the vigilante to perform this attack in the following way. We'd like to make it so that whoever actually finds the Bitcoin puzzle solution is able to take the reward for themselves. Now, the vigilante would have an incentive, a direct personal incentive, to perform the same attack and harm the pool. Now, the approach to having a puzzle that works this way is to have a puzzle where each puzzle attempt requires signing the puzzle solution value using a private public key pair. In particular, each attempt at a puzzle solution requires knowledge of the private key, and that same private key would then be used to spend the reward later. Now, as an illustration of this, instead of the pool operator just having a key, any of the mining pool participants who are contributing mining resources also have to have knowledge of the private key in order for their mining to be effective. If any one of them does find a solution, then they would be able to take the money. A secondary goal is that we'd like to even provide the ability for mining pool members in this case to evade detection. Now I'm going to describe how a particular instance of a non-outsourceable puzzle would work. Now, a solution to this puzzle contains the same information as an ordinary Bitcoin puzzle, including the previous block hash, a Merkle root, which is a commitment to all of the transactions to be included in this block, and an arbitrarily chosen nonce value. Now, this also includes a public key PK, which the miner would have to know the corresponding private key in order to find puzzle solutions. It's also going to include two signatures made using this key pair, S1 and S2. Now, the first step to determining whether a particular nonce value is a puzzle solution is to create a signature S1 using the key pair. Now, this has to be a valid signature over the previous block hash, as well as the nonce value that's been chosen. Now, in order to tell if this nonce was a valid solution, you have to compute the hash h over the string containing the previous block hash, the public key, the nonce, and the signature S1. And then you compare this hash value to a target, just like in Bitcoin's puzzle. Now, only after you find out whether or not this nonce was a valid puzzle solution, you then compute a second signature, S2, using the same key pair. And only in this signature do you include the Merkle root of the transactions. So So the idea here is that you need to be able to compute the signature value S1 using the private key in order to find out whether or not you found a puzzle solution. And only if you found a puzzle solution do you then compute the second signature S2 in order to choose which transactions are going to be included. This means that to find a puzzle solution, you have to know the private key. And if you know the private key, you get to choose transactions that will direct the reward to yourself. There are several potential concerns with this non-outsourceable puzzle. One problem is that it basically throws the baby out with the bathwater. This non-outsourceable puzzle would discourage all pools from forming, not only the decentralized ones, which were the original motivation for this, but also the harmless decentralized mining pools like P2Pool, which were discussed in previous lectures as well. Now, the effect of this could be that if miners are discouraged from participating in any mining pool, they might find themselves steered towards other forms of outsourcing which are even more harmful, such as hiring hosted mining services to do their mining for them. Now, hosted mining services are potentially an even larger threat to the decentralization of Bitcoin's mining power because the hosted mining administrator is actually in physical possession of all of the Bitcoin mining rigs. Now, there are potential approaches to addressing these concerns, but that's an ongoing research project, and I won't get into the details here. In this section, we're going to talk about a technique called proof-of-stake mining puzzles, and a variety of related techniques which altogether I'll call virtual mining, because they don't involve any computational work at all. Now, the motivation for this is that Bitcoin mining seems to have an unnecessary step. If you look at the ecosystem of Bitcoin mining economics, Bitcoin miners earn monetary rewards in the form of Bitcoins. They have to spend money buying power and equipment in order to operate their mining rigs, and they use those mining rigs to find puzzle solutions, which in turn give them reward. So what would happen if we removed the step of spending money on power and equipment? In this case, you would have something that looks like the following, which is what I mean by virtual mining. Instead of mining with computational hardware like Bitcoin mining rigs, you could mine just by using the money that you would have spent on mining rigs directly within the system. Think of this as using your money and sending it to a special address, and then a winner is chosen in order to have a mining reward based on the amount of money that miners have contributed by sending it to this special address. Now, it would be possible in a virtual mining scheme like this to essentially recreate the same dynamics and reward structure as in current Bitcoin mining. The only thing that's removed is the external step of having to use real power and real hardware. Now, there are a bunch of potential benefits to a virtual mining system like this. One is that it definitely would lower the overall cost of the Bitcoin mining system. Virtual mining, since it doesn't involve using any power or manufacturing any special hardware, would have no impact on the environment. Now, you could think of the savings that would result from this as being distributed to all of the holders of coins in this system. There's another argument, which is that holders of the Bitcoin currency are stakeholders in the currency. They have an incentive to do things that would benefit the Bitcoin currency system as a whole because it increases the value of the coins that they hold. So this argument is that the very people who are stakeholders in the currency have incentives aligned to be good stewards of the system. Now, because there's no ASICs involved, there would be no concern about an ASIC advantage. So any virtual mining puzzle is also an ASIC-resistant puzzle. And there's finally an argument that this approach would reduce the hazard of 51% attacks, whereby the network is dominated by very large miners with extremely powerful equipment. Now, let me describe this argument in a little more detail. The way the argument works is basically that the Bitcoin economy is smaller than the overall world economy. It's possible for an attacker who has a lot of wealth outside the Bitcoin network to be able to acquire very large mining rigs that they might not be able to acquire if they could only use their wealth that's inside the Bitcoin network. So to illustrate this, imagine that there's a wealthy attacker like a nation state or just some very wealthy attacker on the network who's able to purchase very large mining equipment that's very powerful. Now, all of their wealth is outside the system, and they're able to acquire this mining resources, and then they can use it to attack the Bitcoin economy. Now, if mining were based on the coins that were inside the network, then a wealthy attacker wouldn't be able to go outside the network and find more mining power. The only way they could acquire the amount of virtual mining power they would need to attack the network would be to buy up 51% of all of the coins in existence. This would require them to go to Bitcoin exchanges and exchange whatever form of wealth they already had for wealth measured in the tokens inside the system. This would likely raise the price of the coins within the system while they were doing so. It's arguably much more expensive to acquire half of the value of the Bitcoins than it would be to acquire mining power that's larger than half the existing Bitcoin network. Now, this provides an extra disincentive against conducting such a large-scale attack. Now, there are a bunch of variations of virtual mining, and I'll describe some of these. The original one is called proof of stake, which assigns to each coin in the system a stake value. And the idea is that this stake value grows over time for every coin as long as the coin isn't used. Every time you spend a coin or make a transaction including a coin or enter a coin in a mining puzzle by using the coin to mine, the stake value for that coin gets reset. Another alternative is called proof of burn. And in this scenario, when you decide to mine using a coin, you actually have to send it to an unspendable address, and the coin essentially is deleted or gone forever. On the other hand, you do have a chance of winning a mining reward, and then that would replace the coins that you put in. Another variation is called proof of deposit. And this involves mining with your coins by depositing them in something like a time-locked account. Where they aren't burned forever, you'll be able to get them back eventually, but only after some amount of time has passed. Effectively, by choosing to mine with your coin in this scheme, you're losing the opportunity cost of whatever else you could have done with your coin instead at that time. The last variation is proof of activity. In this variation, everyone with a coin is automatically entered into the mining lottery. If one of your coins is chosen, then you're responsible for choosing the next block, and you have to respond by creating a signed message about the block that you choose within a certain amount of time. Now, virtual mining puzzles like these are an active area of ongoing research. And there's a large open problem which we don't know the answer to yet, which goes like this. Is there any form of security that you can only get by having a proof of work system that involves really burning real resources, requiring real computational hardware, and expending real electrical power in order to find puzzle solutions? If so, if there is some kind of security that you can only get by having a proof of work puzzle and not with virtual mining, then the apparent waste of the proof of work system is actually just the cost of the security that you get. On the other hand, if it does turn out that virtual mining can provide exactly the same security or more that you can get by having a proof of work system, then it seems likely that eventually proof of work systems, because they're so much more expensive, will eventually give way in favor of cheaper alternatives based on virtual mining. But this question is as of yet unanswered. Let's conclude this lecture by summarizing some of the things we've just talked about. We've discussed a variety of approaches towards designing alternate Bitcoin mining puzzles that achieve a variety of different goals. These include preventing ASIC miners from becoming a consolidated source of power in the Bitcoin ecosystem. We've discussed puzzles that prevent large mining pools from becoming consolidations of power. We've also discussed puzzles that have some intrinsic usefulness that can help society and reduce waste. And we've looked at the option of a mining puzzle that doesn't require any computational hardware at all. Now, for now, the best trade-off between these puzzles is unclear. And our speculation about the future is that for the near future, there will be many alternatives coexisting, and it will continue to be unclear exactly which alternative is the best. Now, in the next lecture, we're going to talk about Bitcoin as a platform. This is going to include applications beyond just the currency that we've seen so far. This includes applications like lotteries, prediction markets, smart contracts, financial derivatives, and many more.
Okay, in this lecture we're going to be talking about Bitcoin as a platform. So we spent a lot of time developing all of the technical underpinnings of Bitcoin and showing how it can be used as a currency. In this lecture we're going to be talking about what else we can do with Bitcoin. There's a lot of exciting things that we can build either without any modifications to Bitcoin or with pretty small modifications. So some of those things in order that we'll talk about in this lecture: secure commitments, secure timestamping, issuing new types of digital tokens and tracking those, things that aren't exactly currency, doing lotteries, generating randomness using Bitcoin, and finally prediction markets. So as a bit of a warning, these ideas are a little bit disparate, so there's going to be a lot of different things going on in this lecture, a little bit of a stew with lots of different interesting ingredients. We'll hop around a little bit, but hopefully the net result will be quite nice for you. So to start with, we're going to be talking about what we can do with the fact that Bitcoin is an append-only log. So remember, an append-only log means that it's a data structure that we can only write to, and once we've written data to it, the data will remain there forever. And we have a secure notion of time, so we can tell that certain things were written to the log before or after other things based on which block they're included in. So what we'd like to build using this is secure timestamping. And the goal here is that we want to be able to prove that we know some value x at a specific time t. We know it at no later than time t. And oftentimes we're going to want to be able to prove that we know what x is without actually revealing it at time t, but revealing it later. And we want the evidence to be permanent. So we have a permanent record that we knew some information x at time t or earlier that nobody can ever destroy after the fact. So recall that we can use hash functions to commit to data. So instead of publishing the data x that we want to prove that we know, we publish the hash of x. And the properties of the hash function guarantee that we can't later find some other value x prime that has the same hash value as x. If we did, that would be a break of the cryptographic properties of the hash function. And we also have the nice property that the hash of x shouldn't reveal any information about x. With the caveat, of course, that that's only true if x comes from a large possible space. Otherwise, somebody who has x or somebody who has the hash of x can simply try different values, different potential values for x, and see if any of them match. So the idea of doing secure timestamping with an append-only log is that we can publish a commitment to x, the hash of x, and then later on we can reveal what x was, and anybody can look at this and say that we must have known x at the time we published the hash of x, because there's no other way to have generated that data. So what can we use this secure timestamping for? This idea that we publish the hash of something and later on we reveal what that data is to show that we knew it at that time. So one thing is proof of knowledge. If we want to prove, say, that some idea that we file a patent on was actually in our heads months earlier, we can publish a hash, say, of a design document or a schema for that idea, that thing that we would patent, that proves that we knew it at that time, but we don't have to tell anybody. And then later on, when we file our patent or when we publicize the idea, we can publish the information, and anybody can look backwards in time and say, yes, they must have known it earlier when they published this commitment to it. We can also prove that we've received something. So if you're submitting data to a server, say something like a vote, the server can publish the hash of that vote, and that serves as a commitment that they actually received it at a specific time, and that will prevent them from later claiming that they never received that information from you. A whole bunch of other interesting things can be built just off of secure timestamping. There's actually a whole signature scheme that just uses hash functions, doesn't use any of the normally relatively heavyweight cryptography required to do public key signatures, just using hash functions in an append-only log. That's called the Guy-Fawkes signature scheme, which we won't talk about anymore in this lecture, but the existence of stuff like that goes to show that this is a really powerful primitive that we can build a lot of interesting applications with. So one thing that we can't do, that would be very nice if we could, is prove clairvoyance, prove the ability to tell the future. So you might think that this secure timestamping would be a way to prove that we know something before other people, before it actually happens. And the idea here would be that we publish the commitment to an event that's about to happen, say the outcome of a sporting event or an election, and then later on we reveal that information, and that proves that we knew the outcome ahead of time. So about a month ago, during the World Cup final, it was thought that somebody had actually done this, and they tried to prove that FIFA, the organization running the World Cup, was actually corrupt. And the way they did this is that they showed a Twitter account after the match was over that had tweeted a bunch of outcomes that happened during the game. For example, the fact that Germany won, the fact that Mario Götze would score, and they proved that they had tweeted this before the game actually happened. And for a moment, before you think about it, it looks like this proves that somehow this person either could tell the future or that the match was actually fixed and that they must have known what was going to happen ahead of time. But with a little bit of investigation, you can find out what they actually did is they had tweeted every possible outcome before the match started. So they had tweeted every single player involved in the match would score, all possible final scores, and a whole bunch of other information. And then before the match finished, they deleted all of the predictions that they had tweeted, which turned out not to be true, and they were left with only true predictions. So the same basic attack can be done against any secure messaging system, where you simply commit to a bunch of possible outcomes, and then you only reveal the commitments that turn out to be true. So if you want to prove that you can actually tell the future, if you have that ability, you have to prove that you aren't timestamping multiple predictions for the future. You have to prove that you're only timestamping one specific prediction and then it comes true. And normally if you're publishing a hash commitment, it's difficult to do that, especially in Bitcoin if we're writing hash commitments as our secure timestamping. If they're not tied to any individual, it's easy to just publish a large number of them, never reveal the ones that are incorrect, and then they won't be traceable back to you. So that was a long detour to say that you can't use secure timestamping to prove that you could tell the future. It would be interesting if you could. So before Bitcoin even existed, there was a solution to this basic problem, which was to publish a hash of predictions in a newspaper or some other media which is called widely witnessed media. So something that a lot of people see in a public place. There are a lot of records. Newspapers get maintained in libraries and online. They're cached all sorts of different places. So if you've taken the time to put a hash into the corner of the newspaper here or somewhere in the classified section, people have pretty high confidence that you actually put that hash the day that the newspaper was published. That serves as a pretty good timestamp. And for a relatively low cost, you can simply pay the newspaper as if this is an advertisement, and you can put the hash of whatever data you want. And then after the newspaper has been published, whenever you want to reveal the data that you committed to, you can just publish the data. People can refer back to the newspaper and the time, and they'll know that you committed to it on that date. So this is a really simple solution. It works just fine offline. The question is, how can we do this with Bitcoin? So the question is really, where can we put our hash commitment in Bitcoin? What's the right place in the blockchain or in transactions to stuff this data, which will represent the hash of some information that we're trying to timestamp? So the simplest idea that people came up with first is, instead of sending money to the hash of a public key, just send it to the hash of your data. You can send a very small amount, say 1 Satoshi, the minimum possible transaction value in Bitcoin, to that address. And of course, it's in your interest to send as little as possible because you're never going to get the money back. Since that is a hash of data and not a public key, there's not going to be any way to ever spend the coin that you send to that address. So the advantage is that this is a really simple, easy way to do it. It's compatible with Bitcoin. But the disadvantage is that you're creating this transaction that you're never going to be able to redeem. And the Bitcoin miners have to track this as an unspent transaction output forever. And they have no way of knowing that this was actually a timestamp and not a valid transaction. So the Bitcoin community takes a pretty dim view of this approach because it creates these unspendable outputs that have to be tracked. So a more sophisticated way to do this is called CommitCoin. And this is a little protocol for finding public keys and signatures that have the data that you want to commit to embedded in the bits of the public key and the signature. So you have to do some brute force work here to find a special public key by simply trying to find a lot of public keys and a lot of signatures so that the bits that you want, the bits that represent the hash of your data, are also the bits of a valid public key. And the advantage of doing this is that it's still compatible. It's invisible to miners. They can't tell that you're committing data. It looks just like any other valid public key. And you aren't actually adding any new unspendable transaction outputs. The downside of this is that it's more expensive to do. You have to do the brute forcing to find this key, and your data rate is going to be a little bit lower since it's more expensive to do this style of commitment. So the preferred way to do this now is with a provably unspendable output. And you include your data in the provably unspendable script that you're trying to commit to. And we talked about this earlier when we were talking about scripts, when we were talking about proof of burn, where you have this script with the op return, which can never be satisfied, and then you can push some arbitrary data. So the same way that you could use this to do proof of burn, you can use this to commit to some data. You just have a script that returns immediately. The return command, of course, throws an error, so this script can never be run successfully without an error, and you can include some data. So this is cheap. There's no bloat in the unspent transaction outputs. You only lose a little bit of money every time you do this. The only downside is that this still isn't a standard transaction, so it won't be relayed by default. But this is the preferred way to commit to data on the blockchain. And there are actually a bunch of startups that actually start up small websites that will do this for you. So they'll collect a lot of people's commitments into a large Merkle tree and then publish one unspendable output that looks like this form that has all of the commitments that everybody wanted to make for the day. So in fact, you don't even need to spend the small value yourself. A lot of people can amortize that cost together, and this is another way to limit the amount of bloat that you're adding to the blockchain. So what's the data rate of a scheme like this? Well, mostly you can get a 40-byte commitment for the cost of one transaction fee, which is currently about 1/10,000th of a Bitcoin, or about 5 cents US. And that's enough to commit to the hash of whatever data you want. So essentially, for about 5 cents, you can commit to an arbitrary amount of data. So the downside of being able to write arbitrary data into the blockchain is that people might abuse this, and they might abuse it by trying to write illegal content into the blockchain. And in some countries, there are things that are very illegal. So think about child pornographic images, copyrighted material, or other things that you may face very stiff penalties if you're caught having that data. So sure enough, several people have tried to do this as a griefing action against the Bitcoin community, simply to harass the community and try to bother people. They've at least claimed, I've never seen it actually verified, that they've published pornographic data into the Bitcoin blockchain. And the idea is that this makes it dangerous to download the blockchain onto your hard drive and to run a full node, because you're now downloading this illegal material. So this is basically just an unfortunate fact of life. There's no good way to prevent people from writing arbitrary data into the Bitcoin blockchain. If you force everybody to use pay-to-script hash, that's one countermeasure that would make it a little bit more expensive to write this data in. But in general, there's no way to prevent people from writing arbitrary bits into Bitcoin if that's what they really want to do. So an observation on the positive side from the fact that we can write whatever data we want into Bitcoin is that we can actually build an entirely new currency system without developing a new consensus mechanism. We can just use Bitcoin as an append-only log that already exists and write all of the data that we need for our new system directly into the Bitcoin blockchain. So this is called an overlay currency. Bitcoin exists as the underlying substrate, if you will, and you just write your new data directly into the Bitcoin blockchain, formatted as these unspendable Bitcoin transaction outputs. Of course, you don't have the miners actually validating that what you're writing into the blockchain is valid under the rules of the new currency system anymore, so you have to develop a more complicated logic for understanding the new currency, because you don't have miners policing what's written into effectively the new overlay blockchain. Anybody can write anything in there who's willing to pay the Bitcoin transaction fees. So instead of having miners reject double spends, everybody as a community has to simply look at the history of what's been written, and if two transactions attempt to spend the same coins, everybody has to understand that the second one is considered invalid. So the most prominent effort to actually do this is called Mastercoin. So Mastercoin is an overlay currency. It's built on top of Bitcoin. All of the Mastercoin transactions are written into the Bitcoin blockchain. And it supports a much larger, richer feature set than Bitcoin. So the idea is that they don't have to develop a new consensus algorithm, and since the Bitcoin miners don't need to know about the Mastercoin rules, They can support a lot more fancy features, more sophisticated smart properties, smart contracts, user-defined currencies. Essentially, the API is many times larger than the Bitcoin API because the miners don't have to understand it. They're willing to just blindly write anything into the blockchain, which is formatted as a valid Bitcoin transaction. And the Mastercoin community has to look at all of that data and piece together valid ownership of Mastercoins based on what's written into the Bitcoin blockchain. So this is very nice. You can develop a currency without having to create your own new consensus system. You don't need new miners. You can add more features. You can develop it faster. But you're inherently reliant on Bitcoin here. And this can be somewhat inefficient because you might have to write a lot of data because you don't have miners policing to prevent invalid transactions from being written into the blockchain. And I believe that we'll talk a little bit more about Mastercoin in lecture 11. All right, so now we're going to change gears. Like I said, we're going to be changing gears quite a bit in this lecture, and we're going to talk about using Bitcoins to represent smart property. So using Bitcoins to represent something other than simply one unit of currency in the Bitcoin system. So recall from the lecture on anonymity especially, we talked about the transaction graph of Bitcoins and the fact that you can trace ownership of value in the Bitcoin system over time. So every Bitcoin has a history. Of course, keeping the caveat in mind that there's no such thing really as a Bitcoin, just unspent transaction outputs, but we'll think about them as coins. And every coin has this long history attached to it, which anybody can view in the blockchain. A history of everybody who's owned any piece of a coin, which through transfer and transactions with other coins has turned into that current unspent transaction output or that current Bitcoin that you may hold today. In fact, for any Bitcoin, you can trace its history all the way back to some Coinbase transactions when coins were originally minted. And of course, there will be a bunch of other transactions that branch off that aren't included in this final Bitcoin. But every Bitcoin has this history that it carries around with it. And as we've said, and as we spent a whole lecture discussing, this is bad for anonymity because you can try and track ownership of coins. And it also potentially enables blacklisting. If you want to blacklist coins owned by a specific person, you can do so using the fact that history is maintained as coins move around. So there's an interesting observation here, which is that Bitcoins aren't fungible. And fungible is an economic term, which means every Bitcoin has the same value as any other, and they can be exchanged with no loss or change in value. So with Bitcoins, that's not exactly true. Every Bitcoin is in fact unique and has a different history. And if the history is meaningful to people, it may mean that my one Bitcoin is not the same as your one Bitcoin, and maybe I'm not willing to trade you, or maybe you're not willing to trade me, because one of us likes the history of the coin we currently have more than the history of another coin we might exchange it for. So could this property be useful? I've argued that it's bad. It's bad in that it has problems for de-anonymizing people or for potentially blacklisting, and that maybe it means Bitcoins aren't even fungible, which is a very interesting property for a currency to have from an economic standpoint. But I'll actually be arguing in the rest of this section that this can be a very useful property if we give meaning to that history. So let's think about what this would look like offline. What if we wanted to add metadata to offline currency? So some people actually do this. They like to stamp various things on banknotes, as I have some examples of here. And you'll notice that most of these are actually political protests talking about campaign finance or the fact that George Washington grew hemp. And the reason is that if anybody can stamp whatever they want on currency, it doesn't have that much value except as a form of speech. It's really just a novelty. So the question is, what if we could have authenticated metadata attached to our currency? So we want to add some metadata to the currency that has some authenticity and not anybody can simply duplicate. And the way that we're going to do this is to have a cryptographic signature on the metadata that we want tied to the serial number of the banknote. So somebody who has some authority and has a signing key is going to sign the combination of some metadata plus the banknote's serial number, and that's going to tie the metadata specifically to this note. How might this work? So let's say that a baseball team wants to start using dollar bills as tickets. So they don't want to go through the hassle of printing their own tickets anymore. They say we want to just have banknotes function as tickets. So the Yankees would simply assert that this specific serial number now represents a ticket to a specific game, maybe with a specific seat, and that whoever is holding that note has the right at the gates of the stadium to come in and sit down and watch the game with no other questions asked. The banknote is their ticket. And to add some authenticity here, there's going to be a signing key that the Yankees use, or whichever team we happen to be talking about. And they're going to sign that message saying the specific game number and the date and all of that sort of information, along with the serial number of the bill. And then they may want to just stamp that right onto the bill, say they use a 2D barcode to represent that signed data. Now, if you show up to the gates of the stadium and hand that bill over, maybe somebody can look up in a database and say, ah, yes, there actually is a signature saying that this serial number of a bill is designated to function as a ticket for this specific game. And you wouldn't necessarily need to use a stamp. Another solution that works just fine here, which doesn't illustrate quite as well, is you could just have a database at the stadium that has a list of different serial numbers and which seats the holder of the note with that serial number is entitled to. And when you showed up at the gate, they would just look at the serial number on your bill and then look up in the database which seat you are allowed to sit in. So what has this bought us? Why would we want to do this? Now currency can represent anything. So I had the example of a sports ticket, but we'll discuss more in a few slides. There's a lot of applications here. And we're inheriting the anti-counterfeiting properties that the bill already has. So if you believe that it's hard to duplicate the banknote and have the same serial number, and there's a whole bunch of people in the Washington, D.C. area who are working really hard to make sure that it's difficult to duplicate a banknote and have the same serial number, because currency would certainly be very different if that property wasn't true. So if you trust that the anti-counterfeiting properties of a bill are pretty good, you get to use those for free, because you simply tie that serial number to whichever metadata you want. And the other neat thing is that the underlying value of this bill as currency is maintained. So it may be a problem if everybody wants to physically stamp metadata on currency all the time, but if we use the database solution where you don't have to actually write anything on the currency, then you can have somebody use this dollar bill as a ticket to get into the baseball game, and then once they're in the game, they can use it to buy a soda. Of course, all of the authenticity here, all of the meaning in this new metadata is only as good as how much we trust the issuer that signed it. So everybody has to know that there's a specific key that's used to sign valid Yankees tickets or whatever other metadata you're interested in. Everybody else will look at this and just see a dollar bill. They may not realize that it's actually worth perhaps $100 if it's a lower box seat to a game. But that's okay, that's actually a desired property here, because once it's fulfilled its mission as a ticket, it can go back into circulation as a regular bill. So can we do this digitally in Bitcoin? There's a bunch of reasons perhaps why this offline scheme with banknotes hasn't quite taken off, perhaps some legal reasons, or perhaps the cost of printing simply isn't that high. But can we do this in a digital way on top of Bitcoin, which will give us all of the cool features we like about Bitcoin, the ability to do online exchanges, the ability to use the system quickly and without trusting a bank. We could have all of those properties for any type of metadata that we want. So the idea here is that we want coins to track a specific color. So just like we were able to stamp that metadata onto currency, the idea here is that you can color in Bitcoins with the color of your choice. They still function as valid Bitcoins. You haven't taken away anything from the fact that they're valuable as Bitcoins, but you've added a little bit of extra color. And of course, in reality, that color will be the metadata that we care about, but for the purposes of this illustration or the metaphor that's commonly used, we think of it as just adding color. So how does that work? Well, in one transaction, we're going to insert a special extra bit of metadata that declares that some of the outputs have a specific color. So we'll say we're issuing 5 purple Bitcoins. And the other output is 7 Bitcoins that continue to be normal Bitcoins with no color. And perhaps somebody else with a different signing key and a different transaction has issued 4 green Bitcoins. So now we have Bitcoins that have different colors attached to them. And we can do all the normal things that we do with Bitcoin transactions. So we could have one Bitcoin transaction that takes several inputs, some green coins, some purple coins, some uncolored coins, and it shuffles them around and has outputs which maintain the color. And there's going to be some metadata there to do all the bookkeeping and make sure the right color goes to the right coins. We can do all the other normal things that we'd want to do with a Bitcoin transaction. We can split a transaction output of 4 green coins into 2 smaller values. And later on, we could combine it. We could combine multiple transaction outputs with green coins to make one big transaction output with all of the incoming green coins. So the only thing that we've added here to the basic Bitcoin picture is the ability to add a little bit of metadata in transactions that designates some of the coins in one output transaction to have a certain color. And of course, there's going to need to be a signature in there somewhere so that not just anybody can use any color that they want. So the most popular proposal for actually implementing this is called open assets. And how does it work? Well, the issuance is done through a special pay-to-script hash address. So if you want to issue colored coins, you have to choose a pay-to-script hash address that will issue whatever color you want. And of course, the color might really be the fact that these are Yankees tickets. And then any coin that transfers through that address that comes in without a color will leave with the color designated to that address. And you have to publicize that somewhere, so there's various exchanges that track which addresses infer which color onto coins. And it's fine for coins to have more than one color. That's really no problem. Now, every time that you have a transaction that involves colored coins, you have to insert a special marker output. So this is an unspendable output, kind of like in the case of commitments, that allows us to write some extra metadata into the transaction. And that metadata, which I'm not going to discuss in detail because it's fairly tedious, but it simply says of all the colored coins coming into this transaction and all the outputs of the transaction, how the color is divided between the different outputs. So just like in any Bitcoin transaction, the normal metadata specifies how the value of all the input transactions is divided amongst the output transactions. You need to add this marker output when you're dealing with colored coins to decide how you're going to divvy up the color. And you can add some extra metadata in there if you want. The protocol supports that. So what can we say about this system? Well, the advantages are that it's compatible with Bitcoin. You don't have to change anything. And it gives you the flexibility for anybody to declare any color that they want and start putting any metadata on any coin that they want, and the system will track that. And it's a good thing that since it's compatible with Bitcoin, the rest of the community will ignore this. So the miners won't take any position on who can issue which color or rules for transferring colors. So nobody can censor this. You don't have to ask any central authority for the right to start issuing coins of a new color. If anybody believes you and thinks that you have a good reason to do so, they can start trusting your signature in the form of sending the coins through that pay-to-script hash address. And if they respect the color that you're putting on coins, then they have some value. The disadvantages of this scheme is that we do have to put that unspendable marker output into every transaction that involves colored coins, so we're adding a little bit of overhead, losing a little bit of money in the form of regular Bitcoins every time we want to trade colored coins. And because that marker output is special and the miners aren't enforcing any properties of it, it means that to verify that you actually own some colored coins, you have to check the entire transaction history. So it's not enough to just see that your colored coin transaction made it into the blockchain because the miners aren't verifying it. They don't understand colored coins and they don't care. And we've argued that that's an advantage of the system. But it means that you can't have a thin client doing SPV verification like we can for regular Bitcoin. If you want to verify colored coins, you have to download the whole blockchain, every previous transaction, and trace the color of your coins from the time that they were originally issued that color. So this means that it's harder to use colored coins on very limited platforms, on phones, or on anything that can't store the entire blockchain and maintain an up-to-date copy. So what are some applications of colored coins? I mentioned the ticket example, so you could have colored coins represent tickets that give you admission to some event. Another popular example that people have proposed is to have colored coins represent stock in a company. So every time you want to issue some new stock, you pass some bitcoins through the pay to script-dash address, which you say is issuing stock on behalf of my new corporation. And then people can trade the stock, and you don't need a stock exchange or any of the infrastructure that is used in the offline world. People can just trade the stock in exchange for regular bitcoins. Of course, people have to trust that you're actually going to honor that stock, but assuming that they do, then you can do all of your stock trading just like regular Bitcoin transactions. And there's also the somewhat more outlandish idea that colored coins might actually represent a deed to some real-world property. So maybe a colored coin says that you actually own a house or a car, and maybe you have a very sophisticated car that actually tracks the blockchain and will start and drive for anybody who owns the specific coin that confers ownership of that car. And then you could sell a car with just one transaction in the Bitcoin blockchain. So maybe we're still a little ways away from making that happen, and we'll be talking more in lecture 11 about some of the obstacles legally and socially to making that happen. But that's the dream of colored coins, is that any real-world property you can represent in the world of Bitcoin, and you can trade just like any other Bitcoin. And finally, one more interesting example, I think, is ownership of domain names. So maybe you could trade ownership of a domain name and the ability to run a server there on the Bitcoin blockchain just like anything else. That has enough caveats and enough weird properties, like you want to avoid people squatting on domain names and just buying up all of the good domain names. That's actually been launched as a separate altcoin called Namecoin. And in the next lecture, when we talk more about altcoins, we'll talk a little bit more about Namecoin, which is specifically launched to try to handle this property of domain name ownership. So you could do domain name ownership with simple colored coins, but in practice, there's enough extra properties that you want to enforce that the community has been pursuing a separate altcoin for that. Okay, time to change gears again. Now we're going to talk about doing a multi-party lottery in Bitcoin and hopefully doing it in a secure way. So again, we'll start with the offline version of what we're trying to build here. How would we do a real-world lottery between two people without any trust? And I'll get back to what without any trust means in a second. But there's a very simple solution for this. If Alice and Bob want to bet $5, they'll both agree to a bet. Bob will flip a coin. One of them will call it, hopefully while it's in the air. And then they'll both have a very clear understanding of who won, and they'll trust that this was a random process and that neither of them was able to influence the outcome. So maybe betting on a coin flip is sort of boring, but this is very easy to do in the offline world. And of course, they have to trust that whoever loses is actually going to pay. Maybe this isn't actually legally enforceable, so it's just an agreement of honor between Alice and Bob. That's a hard problem in the offline world. We'd like in the online world to do a lottery and solve both problems. So both the problem of generating randomness that both parties can agree is fair, and having the party who loses actually be forced to pay. Okay, so how can we do that online? So if a network is between Alice and Bob, they can't see the same physical coin in the same place, but they want to bet on a coin flip. So Alice might say, let's bet $5, I'll flip the coin, here it is. Maybe she'll turn on her video camera or something. And Bob might say, I don't know if I trust you here. I can't see your coin. Maybe you're showing me a video stream that you've already pre-recorded. I'm out. I don't want to do this. I don't have any trust that you're not going to cheat me. So a solution is to use hash commitments, our old friend from the first section of this lecture. So this is the same information. We remember that you can publish a hash commitment. We're not revealing any information. And we can later reveal the input to the hash function to open the commitment and show what our data was. So how can we do this to build an online lottery? So we'll have 3 parties now, Alice, Bob, and Carol, who all want to do a lottery together. So to start with, all of them will choose a random number, often called a nonce in cryptography. And they're going to keep that random number to themselves. And as long as each one chooses a random number, they should trust that the final outcome is random and that nobody else is able to cheat them. Now there's going to be two phases of communication in this protocol. In round one, everybody is going to publish a commitment to their random data. So all three parties are just going to publish a hash of the random number that they chose. And remember, this doesn't reveal anything about the random number as long as it's chosen from a large enough space. So say each one of them chooses a 128-bit random string. They can publish the hash of that. No worries, they haven't given away any useful information. Now, we have to make sure that the second phase happens strictly after the first phase is over. So after everybody has committed to the randomness that they chose. Now we'll have a second round where everybody reveals the random number that they've committed to. And of course, everybody should check that those values that they reveal actually match the hashes that they published earlier and that the commitment was actually valid. But assuming that happens, now everybody has published this random number that they all chose independently. Now there's a fairly simple program that will determine who wins the lottery. There's a lot of ways to do this, of course, but the simplest way is we could just take all three random numbers, take the XOR of them, which is going to mix in bits from everybody's random number. Then we'll take the hash of that, divide it mod 3, and that will give us randomly one of three outcomes. And we'll just assign each outcome to one of the participants, and that will determine that either Alice, Bob, or Carol is the winner. And everybody can run this protocol themselves and trust that this was a fair process. So an important property of that hash function is that it guarantees randomness. Nobody could try to choose their random number in such a way that it makes it more likely that the final outcome is them winning, especially considering that they don't know the randomness that everybody else is choosing. So without getting into a long formal definition of randomness and pseudo-randomness in hash functions, it's safe to say that the way hash functions currently work, with a good hash function, there's no way to cheat at this game. There's no better strategy than just choosing a random number, which gives you a 1/3 chance of winning. So what happens if somebody fails to reveal their commitment? So let's go back to round 2 of the protocol. And let's say that Alice and Bob each publish their commitments. And then Carol looks at these and she says, if I publish my commitment, I'm going to lose. I can see the random numbers that Alice and Bob chose, and I know which random number I chose. And I can run that script and tell that I'm not going to win. So if Carol wants to be malicious here, what she can do is not publish her random number and just say, oh, I'm sorry, I forgot it. Or maybe she can go offline, or for whatever other reason provide some plausible reason why she can't reveal what her random number is. And now it's impossible to run this final script because you don't have one of the inputs. And Alice and Bob can see this and they can say, Carol, that's not cool. You've just wrecked the lottery. You probably did this because you were going to lose. You cheated us. But they don't have any real recourse here. So by itself, this protocol doesn't really work if any of the participants are malicious, because whoever the last party is to reveal what their random number is can just refuse to do so if it's going to make them lose. So what we'd like is a scheme to publish a commitment that we have to reveal within some certain time. And Bitcoin is going to provide a really cool means for us to do that. So how can we do this? And again, the idea is we want to force the party who's chosen this random number and committed to it to reveal what the random number was, to open their commitment before time t. So let's say that Alice is trying to enter into a timed hash commitment with Bob. So Alice is going to put up a bond, and she's going to have a transaction that will pay the bond in 2 cases. So if Alice and Bob both sign, that's enough to claim the bond. Or if Alice signs and reveals what her data was, and you can check this in a Bitcoin script, you can check that there's a value in the redemption script, the script sig, that includes that value x that has a certain hash. So Bitcoin, without changing anything about the script, allows us to include this property that you have to specify this data with a certain hash in order to claim payment. So in that case, Alice can claim the money all by herself, but she has to reveal her chosen value. She has to open her hash. Okay, so now how can we use this funny, complicated transaction with 2 different ways to claim the money? Well, Alice and Bob are both going to sign a transaction that pays the entire value to Bob. And they're going to use this end lock time, which we talked about earlier, to ensure that Bob can't claim the bond before some time t. So now they've set up essentially a ticking time bomb where if Alice doesn't do anything else, Bob is going to get the value of that bond at time t. So as an alternative, Alice can publish a transaction before time t, reclaiming her bond, sending the money back to herself. But if she does that, she has to not only sign it, she has to reveal X. So I said that there were two ways to claim this original transaction, and either one of them are valid outcomes of the protocol. So either Bob gets this bond, some money that Alice put up, or Alice has to reveal her commitment. So it's not exactly forced. If Alice doesn't reveal her commitment, she's not going to be thrown in jail, but she will lose this entire bond that she put up. So her guarantee that she'll reveal the commitment is as strong as how much money she's willing to put behind it. So how can we use this primitive of timed hash commitments to do a more secure lottery? We'll have almost the exact same structure as before, except instead of using the simple hash commitments, now everybody is going to use a timed commitment where if they don't reveal their random value by a certain time, there's a bond that the other two players will get to keep. So if we get into that same situation where Carol can look at the other two parties' random values and say, I'm about to lose this lottery, the other possibility for Carol of not publishing is also not very appealing, because if she refuses to publish her random value, she's going to lose her bond anyway. So if the bond is higher than the value that's at stake in the lottery, we expect that Carol will publish her value and the lottery will go on as usual and everybody will get their bond back. So this lottery in Bitcoin using timed commitments has been proposed and can actually be implemented on top of Bitcoin today. Now the downside is that this is fairly complicated. Doing those timed hash commitments requires multiple transactions. And when you have n players in the lottery, it's actually an n-squared algorithm. And you also have to put money up in the form of a bond. And the key property is that the bond money you put up has to be more than the amount that you're actually betting. So this isn't the most efficient way to do a lottery because you have to put up more money than is actually at stake in the lottery. But it's pretty good, and for a small number of people, it might work okay. So we showed in the last section how multiple people could have a secure lottery on Bitcoin where each of them provides some randomness and we combine that to get group randomness and we use time hash commitments to make that process fair. In this section we're going to talk about using Bitcoin to generate public randomness. So the same situation, we want to do a lottery, but now maybe we have so many participants that it's impossible to have everybody send randomness in. Maybe that's not the most convincing protocol to the public, or maybe it's just something that people aren't aware of yet. So what do I mean by a public randomness protocol? I'll go through a couple of examples to show how this is done in practice, because this is already used for a large number of applications. So one example that happens every spring is the NBA draft lottery. So all 30 teams in the NBA get together and they randomly choose, with some weighting based on how the teams did in the previous season, who's going to have the rights to draft the top amateur player in the country. So this was first done in 1985, and it was a little bit of controversy then because the New York Knicks won in the first year and they were able to select Patrick Ewing, who was a very highly touted prospect. And almost immediately after that happened, people alleged that there was a conspiracy and that this process was rigged so that the Knicks, who happened to play in New York, which is a large media market, were able to select the best player. So if you go online, you can find all manner of conspiracy theories for how the NBA rigged this process, such as the famous bent corner theory, which says that they pulled an envelope that had a bent corner out of the bowl of envelopes with different team names in them. And even today, they do this lottery every year, and there are a whole bunch of conspiracy theories that come out immediately every time they do it, alleging that the process wasn't fair, it wasn't truly a random draw. A more serious example comes from 1969, when there was a conscription lottery in the United States to determine which young men were going to be forced to join the armed services, most of whom were sent to Vietnam. So this was a somewhat similar protocol. Several congressional representatives carried this out. They dumped small capsules with every day of the year into a large plastic drum that you can see there. And then they took turns reaching their hand in to pull the numbers out. And participants in the draft were given a priority number, which determined how likely it was that they were going to be forced to join the military based on what day of the year their birthday fell on. So this is the first time that this was done in 1969 on a national scale. And the goal was to make this process more fair and to demonstrate that this was a random process. But unfortunately, they botched it. So the statisticians looked at the results of this within a week after the lottery happened. And they noticed a funny pattern that was, while it's somewhat subtle, it was very unlikely to have happened due to chance. And that was that most of the days late in the year received very low draft numbers. And the reason this happened when they went back and looked at the tape is that they turned the wheel over exactly an even number of times so that the capsules that started on top tended to stay on top. There wasn't sufficient mixing. So while there was some mixing and it was somewhat random, it didn't turn out to be a truly random draw. So both of those examples show that it's very hard to do public randomness and convince the public that you've actually done a good job. There's both the risk that the public will not believe you and the risk that you'll actually screw it up in the process of trying to do this physical display of randomness. So for a long time, people have wondered, could we do better cryptographically? Could we have a service that we call a cryptographic beacon? And the idea is that this beacon, much like traditionally a beacon is like a lighthouse that sweeps out light at regular intervals, this cryptographic beacon will emit new random data at a regular rate. And the goal is that it will emit uniform randomness that nobody can predict in advance. So everybody agrees that there's no way to predict what values the beacon is going to output next. And yet every party can see the same values and agree on them. So if this perfect cryptographic beacon existed, the NBA draft lottery or the Vietnam conscription lottery, if you wanted to do a process like that, or even if you just wanted to play bingo at your local social club, you wouldn't need to use a large wheel or any physical display of randomness. If everybody trusted the beacon, you would save a lot of effort from having to have these small physical displays of randomness. There's a whole bunch of applications besides just lotteries. So various applications of auditing and voting systems, doing zero-knowledge proofs, cut-and-choose protocols. Throughout the security literature, there were a lot of examples of things that can be done much more simply and efficiently if you had a perfect cryptographic beacon that satisfied all of these nice properties. So unfortunately, we haven't found a perfect solution for this yet. Like I said, the public display of randomness, so using a wheel, flipping coins, rolling dice, spinning a dreidel, what have you, that has been a solution that's been very popular throughout history because it's cheap and easy and everybody can see it and understand it. But this really doesn't scale to remote scenarios very well because it's very hard for people to audit, even if they just see a video, that you haven't been a magician. You haven't done some kind of sleight of hand where you swapped out the dice for weighted dice, or you somehow rigged the process. So it's very hard to establish trust remotely in any kind of physical process, which is basically the problem that the NBA has had for years trying to convince fans that they're doing a fair process. And they've switched to a bunch of different technologies. They've done both the envelopes and ping pong balls bouncing around with fans. And people can always come up with some outlandish scenario where they're somehow cheating and there's more to it than you can see on the video. So for the purposes of this lecture, I think we can rule out a public display of randomness as something that we could ever have a high level of trust in. So the National Institute of Standards and Technology, NIST, has started in the last few years to run their own beacon. And the way they generate the random numbers is through a very complicated setup involving two entangled photons that gives you very strong guarantees that you have randomness generated from a quantum mechanical phenomenon. And if you believe the Heisenberg uncertainty principle and other basic core tenets of physics, then this should be random and nobody can predict it. And NIST has set this up as a machine, so every 60 seconds they publish a lot of random data and they sign it. So this is probably the most efficient thing to use. They just have a feed on the web. You can listen to their server broadcast this stuff and get all the randomness you want. And if you read their papers in the physics argument, there's a very strong argument that this is truly random and that there's no way anybody could predict it. Of course, you have to actually trust that NIST is doing this. You have to trust that somewhere in a building in Maryland they've actually built this, and they aren't just making it up, or that they don't have the ability at a specific time, if they want to overwrite the value with some other data that they happen to want. So this is sort of the limits, in a sense, of physical display of randomness, and it still hasn't gotten around this problem that you have one trusted party doing it, and unless you physically go there and observe the process yourself, it's very hard to have a high level of confidence that this was a fair process. So what if we use some natural phenomena that everybody can observe? So examples might be sunspots or solar activity on the surface of the sun, things like the weather, what temperature it's going to be tomorrow, how strong the wind will be, whether or not it will rain, or even cosmic background radiation, which is just noise that you can listen to from any point on Earth, and everybody should be able to read the same values. So these are phenomena that happen at such a large scale that it's fairly easy to convince yourself that nobody is going to be rigging the process. It's somewhat far-fetched to imagine that somebody would fly a spacecraft to the surface of the sun to modify what was going on in order to rig some lottery back on Earth. So that's great that it's publicly observable, and that in most cases we can accept the randomness here too. We have pretty good beliefs that enough days in advance it's impossible to predict low-level weather phenomena. The problem with these approaches is that they're fairly slow. For example, if your random signal is what the daily high temperature is going to be, you only get to read that once a day. The surface of the sun doesn't change too often. And you essentially reinsert the trusted party problem because you need somebody to observe the event. So let's say that we tried to use as a random signal what the temperature will be tomorrow in Princeton, New Jersey. We might get into a problem if I have my own thermometer that says that it was 73 degrees and somebody else has a thermometer that says that it was 72 degrees, and the difference between those two meant that a different person won the lottery or some other important outcome of the randomness. To get around that problem, we would probably need to designate and say we're going to use one specific person's thermometer to actually measure this phenomenon, or maybe we'll use the National Weather Service. But at that point, you've basically reinserted one trusted party who has control of the process. So a similar idea is to take financial data, specifically stock market prices, and say, can we build a randomness beacon out of that? And again, these are publicly observable, and there's a fairly good argument based on a bunch of complicated financial models that says that it's very hard to predict the low-level fluctuations of stock prices. If you could predict within a penny what the final price of a specific stock will be on the New York Stock Exchange tomorrow, you could make a lot of profit as a day trader from that knowledge. So the randomness is good, and it should be fairly costly to manipulate. You could try to rig this by, say, buying or selling stock to try to drive the stock price to a specific value that you want, but that has a real cost that you can compute. But the problem, again, this is fairly slow, because you can probably only read it once a day if you're reading one company's stock price. And again, it has this problem that there's a trusted party, namely the stock exchange, who has some control over the process. So even though the party running the stock market has a fairly strong incentive to establish that it's honest and that it's acting in good faith and reporting stock prices as they actually are based on market activity, there is the risk that they might try to change the price by a penny or so if it let them rig a valuable lottery. So the theme here with almost all of these approaches is that no matter what you do, it seems like you reinsert this one trusted party who has some control of the process. Of course, a big theme of these lectures so far is that Bitcoin has been an amazing technology at removing central trust from protocols that we didn't think that was possible to do before. So can Bitcoin pull the same trick off for a randomness beacon? Can we extract random data from the Bitcoin blockchain with the same decentralized properties that make Bitcoin so attractive? If we recall the fact that miners have to find a random nonce for each block, we think we might be in business here. Why can't we use the random nonces that miners are finding in the process of mining as a randomness beacon? So there's a fairly strong argument that you can't predict with high probability what the next nonce will be. If you could, you'd have a mining shortcut. So if you had the capability to predict what the next nonce will be with a probability greater than 1 over d, where d is the difficulty of finding a block, then you would have a faster way to mine than just trying nonces at random. And remember that d is pretty high right now. It's greater than 2 to the 66. So that means that every block that's mined in Bitcoin should have 66 bits of randomness that are impossible for anybody to predict. At least if Bitcoin is secure, there should be no way for any of the miners or anybody else to predict what those random bits will be. So once we realize that, it's fairly simple to turn the blockchain with minimal modifications into a randomness beacon. We simply take every block in the chain, take the entire value of the block header, and run it through an extractor function. And an extractor function, without going into all the details here, is sort of like a hash function and is designed to squeeze all of the random data out into one uniformly random string. And that will give us a nice randomness beacon, and every time a block is published in Bitcoin, we have new output from the beacon. So how costly would it be to manipulate this? So any miner has the capability, if they find a block, to discard it, to not relay it to the network, not publish it, not let it be the next block in the sequence. And they could do this if they find a block and realize that it produces a beacon output that they don't want. And it might not be the miner that decides this. It might be somebody who's trying to force the beacon to have a certain output, who says that they're willing to bribe miners. And if they find a block that's undesirable, this attacker will bribe and pay them more than the block reward in exchange for not publishing this. So let's say that you're trying to force some beacon output with probability p. This is just going to be a Bernoulli trial. So you have to discard some number of blocks until you happen to hit success. And the expected number of blocks that you'll have to discard is 1 over p minus 1. And recall that discarding a block is pretty expensive. You are going to lose the entire block reward, which is currently 25 Bitcoin, or around $15,000 US at today's prices. So what's the practical cost of manipulation? So say that you're doing a single coin flip. Like I said, the expected number of blocks that you are going to lose the reward for is 1 over p minus 1. And with a single coin flip, p is just a half. So you'll get that you have to discard about 1 block on average and eat that whole 25 Bitcoin cost. And if you have an n-party lottery where it's fair between all n parties, it's going to be 25 times n minus 1 Bitcoins. So this process will be secure as long as the amount that you're betting is less than that cost of manipulation. So essentially, if two people want to have an even odds bet, and they want to use Bitcoin as the source of randomness, this is going to be secure as long as they've wagered less than 25 Bitcoins, or again, about $15,000. So the advantages of this, it's somewhat remarkable that this is the first proposal that's really out there for a fully decentralized beacon. So a beacon that has no central point of trust. And compared to some other processes, it's actually fairly fast. It's not going to output as often as, say, the NIST beacon, which is designed to output as often as possible. But about every 10 minutes, you'll get new output from the beacon. And it's also nice that we can precisely analyze what the manipulation costs are here. So we have a fairly simple model, and we can price the cost of manipulating the random output and how many block rewards you'll have to sacrifice. So the downside of using Bitcoin as a beacon compared to some of the alternatives is that the timing is a little bit imprecise. So suppose we want to read the value of the beacon tomorrow at noon. We don't know exactly which block is going to be published tomorrow at noon, because blocks are just published whenever they're found, not at any specific schedule. So we'd have to guess, based on the distribution and the average times, what block index will be published around noon tomorrow, but that will give us quite a bit of variance. And we'll also have to delay when we accept the result of the beacon based on the risk of a fork. So just like with anything else in Bitcoin, we'll probably want to have that roughly 6-block confirmation time before we accept that this really is the final beacon output. And the cost of manipulating this beacon may be too low for some applications that we care about. So if we're actually running the NBA draft and there are millions of dollars at stake, it may suddenly look worthwhile for one of the teams to start paying Bitcoin miners to manipulate this process. So it's an open question if we can extend the security of this construction to make it secure in a case like that, even when we have millions of dollars on the line. So one more really cool idea for what we could do with a beacon built off of Bitcoin. What if we extended the Bitcoin scripting language so that there was a special opcode to call the beacon? So currently there's no way to have any randomness in a Bitcoin script. And that's by design because the miners have to be able to verify this and they want to all be able to verify it and get the same thing. But if we use the beacon, the public source of verifiable randomness, then you could use the beacon to insert randomness into scripts in such a way that any miner could run and they would run the script in the same way. So what could we do with that? Well, if we had one opcode that would make a random decision based on, say, the beacon output of the block before, we could replace that entire complicated lottery protocol with one script that just read the beacon once, and based on the results of the beacon, assigned the output to one of 3 keys or n keys, however many players we are, and you'd be done. It wouldn't be a multi-round protocol, we wouldn't need bonds, we wouldn't need time hash commitments, we could just use the beacon. So this is a somewhat out there idea, but there are a lot of cool applications for what we could do with this. So for the final topic today, we're going to be talking about prediction markets and bringing real-world data into Bitcoin. And this is going to be another big change of direction. And we're going to stray a little bit far away from Bitcoin in this one, perhaps, but it should be a really fun topic. So how can we make assertions about the outside world within Bitcoin? So the idea is we'd like to add a mechanism to assert facts about the real world into Bitcoin. And those facts might be who won an election, who won a sports match, what the price of some commodity is on a certain day, any kind of real-world data that is of importance to a lot of people. So if we had those kind of facts available in Bitcoin, say there was some script call that you could make that would just say what the current price of copper is on some common exchange, you could start doing all sorts of cool things with smart contracts. You could bet on the future price of commodities, on who's going to win a sports match. You could hedge. And you could derive all of the things like forwards and futures that financial markets are built to buy and sell and trade. So wouldn't it be great if we could do all of this in the range of Bitcoin? Basically every variety of betting on the future. And the most general formulation of this is called a prediction market, and we'll be talking about how to build a prediction market in Bitcoin, since if you can build a prediction market, you can essentially build almost any other financial derivative that you'd be interested in. So what's a prediction market? Quite simply, it's a market where you can trade shares in potential future events. So you can have a share in some event. The event might be the Yankees win the World Series in 2014. And that share will be worth some price X if the event actually happens, and it will be worth nothing if it doesn't happen. So before the event is certain during the season, say, there will be some price at which that asset is trading. And the price will indicate the probability that people have in their minds, the belief that they have of how likely the event is to actually occur. Okay, so let's take a look at an example which hopefully will make the concepts behind prediction markets make a lot more sense. Let's look at the 2014 World Cup, which just wrapped up last month in Brazil. And let's say we had a market where you could buy and sell shares in teams. And the idea is that these shares will be worth 1 only for the team that ultimately wins. Now going into the tournament, every team, of course I just have 5 examples here, every team would actually have some non-zero price. But before the tournament starts, every team's shares will have some price based on what the market believes their chances of winning are. So over there on the left, you can see Germany, their shares are trading for about 12 cents, which means that the market thinks they have a 12% chance of winning, and so on for Argentina, Brazil, the US, and England over here on the right, which the market gives about a 5% chance of winning. So again, that price that the market assigns is equal to the probability that people believe that that team has to win. Now, as the tournament goes on, these prices are going to fluctuate, and that's going to reflect the market's changing belief in how likely each team is to win. So after the group stage, we can see that England, which was trading at 5 cents, a 5% chance to win before the tournament started, has now gone to 0. So England was knocked out after the group stage. There's no way for them to win at this point, and the price reflects that. Their shares are now worthless. Whereas the US team, which people thought didn't have a good chance of even surviving the group stage, hence the 1 cent price at the beginning of the tournament, did fairly well to get out of a tough group in the group stage, so maybe they were trading for 6 cents after that point. And now here's the key insight, the most important thing to understand about prediction markets. If you had thought to buy US shares in the beginning when they were very cheap, when they were selling for 1 cent, you could sell them immediately after the group stage for 6 cents. You wouldn't have to wait till the end of the tournament. You could immediately profit, not from the fact that the US team won the whole tournament, because they didn't in the end, just from the fact that people's belief that they had a chance to win the tournament went up after their strong performance in the group stage. So the tournament's going to go on. When we get to the semifinals, there's only 4 teams left. Of course, sadly, the US is knocked out, so their share price has gone to 0 along with England. But when there are 4 teams left, now they all have a relatively high price. And the Brazilian team was trading for a very high price going into the semifinals. People thought they were a strong team, and they had a good chance to win. Of course, the German team actually defeated the Brazilians quite strongly, so Brazil's share price went to 0. And once again, you would have had a very strong chance to profit here if you took a short position. And there's a variety of ways to do that, but essentially you can set yourself up to profit if a share price goes down as well as going up. And within the span of a couple of hours, people's beliefs changed dramatically as the Brazilian team lost and lost decisively. And you could profit in a very short time frame if you were confident going into that match that the Brazilian team was overvalued, not as good as people thought it was, and that the share price was about to decline. And of course, going into the finals, there's only 2 teams left. So at this point, between the German and the Argentine team, the only 2 teams in the final, those 2 prices should add up to 1, because one of those teams has to win, and probability should always sum to 1. And after the whole tournament's over, everybody's ready to pack up and go home. The only shares that have any value are shares in the German team, because the Germans were the team that actually won in the end. But the most important insight here is that one way to profit certainly would have been to buy shares in Germany at the beginning for 12 cents and hold them all the way to the end, in which case you would make $1. And that would be basically equivalent to traditional sports betting, where you place a bet before the tournament starts that Germany is going to win. But in a prediction market, there's lots of other ways to play and lots of other ways to profit. You don't have to just bet on the right team and hope that they win. You can invest in any team at any time, or you can take a short position, and you can profit just on the ability to predict that people's beliefs will change. Here's another example, and this is from a real prediction market. This is the belief over time before the 2008 US presidential election and whether Barack Obama or John McCain would win. And now Barack Obama is represented in blue on the top, and McCain represented in red on the bottom. And you can see that as the months unfold and various things and gaffes happen on the campaign trail, people's beliefs about who's going to win the election fluctuate a little bit. And historically, you can go back to most of these fluctuations and trace them to a specific event. Either a candidate made a gaffe, or they did something good that made them more popular, and then people's beliefs changed. And you can see that as of about September 2008, so about 2 months ago before the election, all the way on the right side here, McCain almost got back up to a 50-50 chance with Obama. So at that point in time, the public really didn't know who was going to win the election. It was still a toss-up. But by the time the election actually happened, you can see that Obama was given a 90% chance to win the day before the election. So the market was well aware going into it, based on polling, that the election was basically over before votes were cast. At least it was very unlikely for Obama to lose the election. And this really demonstrates the power of prediction markets, because you could read all the newspapers and watch all the news that you want, and they'll offer a lot of expert opinions discussing either way who they think is going to win. But if you just look at the prediction market, where people have real money at stake, you could see that in the week leading up to the election, it was pretty clear that Obama was going to win the thing. So that's why economists really love prediction markets. They should reveal, if you believe in an efficient market and a couple of other assumptions, they should reveal all the knowledge that the public has about the future. So that share price in different events should be the best encapsulation of everything we know about the future. So they're a great mechanism for revealing information, and they allow you to profit from being able to make accurate predictions. So one description of prediction markets has been a tax on BS. So if you're saying things that aren't true or making predictions that are very unlikely to happen, if you have to actually put money behind them in a prediction market, that will be very costly. And it has been shown that in practice, prediction markets have pretty good predictive power. Collectively, they can often beat opinion polls or asking experts. But there's also been kind of a tortured regulatory history here. So InTrade was the most popular prediction market on the internet for a period of about 10 years, and it ran into all sorts of regulatory issues in the US for a variety of reasons. I won't get into all of the legal details here, but InTrade was eventually shut down in 2013, and a lot of economists were sad about this because they believed that this valuable social tool that revealed information about the future was lost. So could we build a decentralized prediction market? Again, decentralization being the name of the game with Bitcoin. So there's a couple of tasks that we'll have to decentralize to make a decentralized prediction market work. So we need payment, and we need enforcement of bets that people are making. That all has to be decentralized. We're going to need decentralized arbitration. Arbitration is the process of asserting which outcomes have actually happened. Most of the time, in the case of an election or a sports match, you may say it's pretty obvious who won and who lost, but there are gray areas. And we need a decentralized order book, so a way for people to buy and sell shares, for buyers to meet sellers, that's decentralized and doesn't rely on a centralized clearinghouse. So we'll go through each of these challenges in order. So payment and settlement. This is the easiest given Bitcoin. We can use Bitcoin to do payment. And in the simplest solution, maybe we could use trusted arbiters. So we could basically do escrow transactions, and the arbiter will enforce the contract, the fact that if you bet on something that didn't happen, you lose money, simply by not signing transactions. A better solution would be if we built an altcoin that had explicit support for prediction markets. So what would that look like? There's a proposal for doing this called FutureCoin. This isn't an altcoin, it hasn't actually been built, that adds a couple of transaction types in addition to just normal sales of Bitcoin or any other cryptocurrency. So the transactions that are added specific to prediction markets let you buy a portfolio in some event. So the idea is that for $1 or one future coin, you buy a share in every possible outcome. So say this is the World Cup, there's 32 teams entered. For one future coin, you buy a share in every possible team. And then on the bottom here, there's a sell portfolio, which lets you sell a share in every outcome to get one future coin, one unit of currency back. So obviously those two match. So for one future coin, you can buy a share in every outcome, and you can turn a share in every outcome back into one future coin. But you can also trade the shares one for each other, which is much more interesting. So you can buy a share in every outcome, and then you can sell the shares that you don't actually think you want to hold. So the teams that you don't want to bet on, you would sell to somebody else who did want those shares. And then you would end up with a position which wasn't just balanced on every team. Say you would buy a bunch of shares in the team that you actually wanted to back. And again, that would be one way of profiting. You could just buy a portfolio, wait for the prices to change, and then sell all of the shares directly for future coins, which you could turn into Bitcoin or some other currency and profit that way. And the other way to profit would be to buy a portfolio, sell some of the shares, and then eventually, at the very end of the market, there's a special close that happens, at which point you can sell portfolio and you only need one share in the winning outcome. So how can we do arbitration? How can we assert who actually won so that we can do this close and let people redeem their winning shares to get their money back, to get their winnings? So the simplest model is to just have trusted arbiters. So we say anybody who wants to can define and open a new market. They can stand up and say, I'm opening a market on the World Cup. I will decide who won in the end. And if you trust me, you should be willing to accept my signature that that's the correct outcome. And like many other things, they would probably build up a reputation over time, and they would have some incentive to arbitrate correctly to maintain their reputation. But there's always the risk that they could abscond, and this could be very dangerous in a prediction market. So for example, if one arbiter was in business for a long time and everybody trusted them, they might wait until the World Cup, and then they might assert, say, that Argentina won, even though they lost in the final, if they had bet on Argentina heavily and were trying to profit from it. So could we have a more decentralized arbitration model? This is a little bit tricky, but there's a few ideas here. One is to have all of the users, all of the people who hold shares in the market, vote on who won. And the idea wouldn't be really to vote as if there was a lot of uncertainty, but just that everybody would vote in what happened in reality. And there's various ways you could try to incentivize users to vote correctly. So you could have users put up bonds or maintain a reputation. And if they vote in a different direction than most other people vote, they suffer some penalty. They lose their bond or their reputation goes down. And then everybody is incentivized at least to vote in the same way that everybody else is voting, if not to vote in the way that reality actually happened. And you could set up a similar system where instead of the users voting, you have the miners in your cryptocurrency voting. And again, miners would be incentivized to vote correctly, because if they vote incorrectly, future miners might fork and then they would lose their block reward. But this runs into the problem that miners may not know about every market that people are interested in, and they may just not care about some. So it may be too high of a burden to put on miners if you expect them to be able to arbitrate every match that happens in the second-tier Mongolian football league that somebody somewhere wants to bet on. So there's been one attempt to actually make this happen, at least one attempt to make this happen, which is a protocol called reality keys. And the idea with reality keys is that you can actually sign statements that are usable in Bitcoin that assert yes or no whether or not one of two outcomes happened. So this is fairly simple. It's not as complicated as some of the more sophisticated arbitration models we'd like to get to, but this is a step toward having arbitration for an online prediction market. So there's a caveat here, which is that sometimes reality is complicated. I had assumed that what actually happened in reality wasn't in dispute. We just wanted to have a voting mechanism to insert the facts from reality into the digital world. Sometimes what happens in reality isn't quite so easy to discretize into a digital form. So my favorite example came from the Super Bowl this past year. There's an annual bet that a lot of people like to make in the Super Bowl, which is what color Gatorade the winning team will dump on the winning head coach. So this is a tradition after every Super Bowl or lots of other big football games. The winning team takes a bucket of Gatorade and dumps it on their coach. And you can actually make a bet on what color Gatorade they're going to use for this purpose. You can see that clear was the odds-on favorite, but orange and yellow were also strong contenders. Those are popular colors. And green, blue, red, less likely to happen. So this bet has happened for probably 20 or 30 years. It's been just a popular, fun bet. And in the last Super Bowl, something went a little bit awry. So the Seattle Seahawks won. They celebrated. They dumped some orange Gatorade on their head coach, Pete Carroll. And then a little later, a few other players decided to do it again. And they used yellow Gatorade. So this had never happened before, but the Seahawks decided they liked the dumping Gatorade on the head coach ritual so much that they would do it twice. And they used two different colors. So if you're running a prediction market where people had bet on this, what do you do in this scenario? It's not clear if orange or yellow should win. What happened in practice with a lot of sports books is that they said, we're actually going to lose money, and just to try to maintain our reputation with our customers as a show of good faith, if you bet on orange or if you bet on yellow, either way you win. Of course, in a decentralized prediction market, you can't do that because you can't just create money out of thin air to pay both parties. So there's a couple of solutions here. Maybe you could say that orange and yellow both win. They each win half of the winnings. So instead of closing at a value of 1, they close at a value of 0.5. But ideally, you would define your contract a little bit more carefully next time, and you might say, what will the first color of Gatorade be to be poured on the winning head coach? But the lesson here is that no matter how careful you are in defining what your market is, there can always be some event that happens in reality that wasn't something that you predicted. So something that people didn't have shares in might actually happen, in which case it's very tricky to know what to actually do. So the final piece to build is an order book. So in a real prediction market, or most financial markets, there isn't truly one market price. There's the lowest price that anybody's willing to sell at and the highest price that anybody is willing to buy at. So this is an example from a small prediction market that's being run today using Bitcoin called Predictious. And they have a market here on whether or not Scotland will vote yes in their independence referendum, which is scheduled 2 months from today. And you can see that there's a spread. In each case, there's a spread between what people are willing to sell at and what people are willing to buy at. And the goal of an order book is to match up those sellers and buyers, so that they make a trade and that they split the difference. Traditionally, this has been done in a centralized way. So you have one order book, they collect all of the orders, they actually keep them secret, they match people up, and they divide the difference down the middle. So the price you get is halfway between basically the lowest you were willing to sell for and the highest that the buyer was willing to buy for. And this has a couple of risks. So if the centralized order book is dishonest, they might put their own orders in ahead of time to try to get a better deal for themselves. So this is called front running. It shows up in a variety of financial settings, and it's considered a serious crime. So theoretically, this is something that you go to jail for a long time if you're caught doing. And centralized order books require that legal enforcement to prevent front running and to keep the security model sound. So in a decentralized order book, we're not going to be able to have strong legal enforcement like that. But there's a clever idea, which is to just forget about front running and say, instead of having front running be a bug or a crime, we're just going to have it be a feature. And the way to do that is that everybody can submit orders to miners, and the miners can match any possible trade. And instead of splitting down the middle, the miner actually keeps the entire spread as a transaction fee. And the beauty of doing this is that the miners now receive a transaction fee, and they have no incentive to front run, because front running will never be more profitable than just capturing the spread as a transaction fee. So this is a very nice, elegant way of doing a decentralized order book. The only downside here is that you have to pay potentially a high fee to the miner if there's a high spread. And to try to prevent paying that high fee, people might submit much more conservative orders. And as a result, this thing might be less efficient. People might make trades more slowly as they slowly iterate towards each other. They may not be willing to declare up front their exact willingness to pay, because doing so might lead to a large spread that the miner gets to capture. So it's not known yet how this will function in practice. There's some fear that it will be a lot less efficient than a centralized order book. But it seems to be a very promising approach to go. So to summarize, in trying to build a prediction market, what can we actually bolt on top of Bitcoin? So it looks like payment-wise we're in good shape. Bitcoin's a good currency to base a prediction market off of. In terms of doing settlement, it's fairly hard. You could draw up some contracts using reality keys where you have a position based on some future event, but there's no way in Bitcoin to really trade that position. So we don't have a way to do decentralized trades. In terms of arbitration, the only thing you can do is a trusted arbiter model. Again, the reality key model. The more sophisticated things where users or miners vote aren't going to be possible in Bitcoin. You'd need an altcoin for those things. And finally, order books. There's no built-in concept of an order book in Bitcoin, so you'd be stuck with an external centralized order book. So this lecture was really all about building things on top of Bitcoin. And it looks like we can't quite build a functioning prediction market, at least not in the way we'd like, directly on top of Bitcoin. This is something that we would really need an altcoin to build. And this is a lead-in to what is going to be covered in the next lecture, which is altcoins. So the observation is that for some things like prediction markets, Bitcoin only takes us so far. It really doesn't get us where we want to go in terms of building a secure decentralized prediction market and a decentralized order book and all those other things. So what if we could start again from scratch? What if we could forget about soft forks and hard forks and how to bolt things onto Bitcoin and just say we've learned a lot since 2008 when Bitcoin first came out. Why don't we design a new cryptocurrency and everything will be better? So the next lecture will be all about altcoins, which are attempts to do just that, and we'll talk about all of the promising ideas people have and all of the challenges to starting a new currency at this point.
In this lecture, we're going to talk about altcoins and the much larger ecosystem of cryptocurrencies in which Bitcoin actually just plays one important role. Let me start by giving you a sense of the sheer number and variety of altcoins that have launched since Bitcoin began. Bitcoin was first launched in January 2009, and it wasn't for 2 years, till the middle of 2011, that the first Bitcoin-like derived system, Namecoin, was launched. And in the following months, a handful of other altcoins were launched. And the rate of altcoin launch didn't pick up until year 2013. And at the current time, several altcoins are launched every week. And we're going to focus on only a few of the oldest and most well-established altcoins and talk about them more. Now, there's between, say, 150 and 500 altcoins that have been launched in total. This varies depending on what you consider a launch of an altcoin. Some altcoins are simply launched, announced, and perhaps their code's released, but their genesis block hasn't been created yet. Some altcoins have been launched, but then died very quickly after their launch. And we'll talk a bit more about that in the future. Most altcoins share a lot in common with Bitcoin. They begin with a genesis block and their own alternate view of transaction history from their beginning. Now, to give you some sense of the relative size or impact of Bitcoin in the ecosystem of altcoins, there are a variety of metrics we can use, but I want to show you one, which is market cap. And this refers to the price of an individual unit of coin, measured at perhaps the most popular third-party exchanges, multiplied by the total number of units of currency in an altcoin thought to be in circulation. Now, by this metric, Bitcoin is by far the largest, accounting for perhaps 95% of the overall market cap of all of the cryptocurrencies combined. Now, Bitcoin and Litecoin, the second largest currency by this metric, account for more than 99% of the total market cap of all of Bitcoin and the altcoins. The relative ranking of the other altcoins tend to vary quite a lot and fairly rapidly. This diagram in particular is already a bit dated. It's from January 2014. The significance of this is that when we talk about altcoins, many of them are very small in terms of their user base or their total impact relative to the handful of most popular coins. Another way of getting a grasp for the ecosystem of altcoins and their relation to each other is the concept of altcoin genealogy. When an altcoin or a Bitcoin-like system is launched, it typically isn't designed and implemented from scratch. Typically, an altcoin is launched by preparing a reference client, so the software for a node that actually connects to the network. And this is prepared by forking from an existing code base of the reference client of a more well-established altcoin or Bitcoin itself. So the top two most popular by market cap currencies, Litecoin and Bitcoin, are also the most widely forked code bases. Litecoin itself is also a fork of Bitcoin. It's actually Bitcoin's grandchild in a sense, that Litecoin was forked from Tenebrix, which was a short-lived altcoin that itself was forked from Bitcoin. Every altcoin has some kind of story to tell, which makes these fun to talk about. Most altcoins have something that distinguishes them from all of the others, or some reason for existing. In many cases, altcoins are distinguished by having some different technical feature, such as additions to the script language that express different kinds of transactions, or additional security. In some cases, the security can come from a different mining puzzle that discourages or encourages one kind of mining or another, or features that, for example, add additional anonymity and privacy for users' transactions. In many cases, an altcoin simply changes some of the built-in parameters to Bitcoin. This includes things like the average time between blocks, and a variety of parameters which altogether I'd call monetary policy, which include things like the schedule of rewards being created, the overall inflation rate of the altcoin, and whether or not the inflation rate gradually caps out at some finite limit the way that Bitcoin does. In many cases, altcoins are also launched with a theme or some sense of a community that the altcoin is targeted at or intended to support, or simply an interest or common interest that the altcoin should be associated with. I'll talk about some examples of these as I describe some of the major altcoins to date. The first altcoin we're going to look at in detail is Namecoin. This was the first altcoin that was launched, again, in the middle of 2011, April, roughly 2 years, a little more after Bitcoin was launched. Namecoin is very interesting because it has a very new technical feature, which is domain name registration. Namecoin is actually intended to be a decentralized replacement for the domain name system, which is, as you know, an essential part of our internet and World Wide Web infrastructure. Now, Namecoin actually works for that purpose. Now, you can't use this by default with an unmodified browser, but you can download a browser plugin for, say, Firefox or Chrome that would allow you to type in an address like example.bit, any website name that ends in .bit, and it'll automatically take you to the right location indicated by the registry stored on Namecoin. In order to register a name in Namecoin and maintain it, you send transactions to the Namecoin system, much as you would send a transaction to the Bitcoin network in order to move Bitcoin currency around. Namecoin mirrors a lot of aspects of the current domain name system. So for example, you can register a name that currently isn't taken by anyone by paying a small fee. Now, the fee to register an untaken name in Namecoin is only 0.01 of a Namecoin, which works out to about 1 cent in US dollars at the current price. So this is 1,000 times less than the cost of registering a domain name given the current system of DNS and registrars. Unlike the current domain name system, in Namecoin there's no renewal fee, but you do have to publish a transaction that pings your name every 6 months or so in order to keep your name under your control. Also, like the domain name system, Namecoin features a hierarchy of names. So if you register a root domain like example.bit, you can give out subdomains like subdomain1.example.bit to other people. You can also transfer domain names in Namecoin that you own to other people. And you can in fact make transactions that are a transfer and sale of a domain. So you can make a transaction that transfers ownership of domain to a buyer and at the same time transfers units of the Namecoin currency from the buyer to the seller. One other interesting property of Namecoin is that this was the first altcoin to feature merge mining, which is a really clever technique that we're going to talk about a little later, and this has been part of its success. Next, we're going to talk about Litecoin. And this was launched also in 2011, sometime after Namecoin. And Litecoin has, for the past several years, been the #2 altcoin next to Bitcoin in terms of overall popularity and user base. The main technical distinction between Litecoin and Bitcoin is that it features a memory-hard mining puzzle, like the kind we talked about in Lecture 8. Now, when Litecoin was launched, Bitcoin mining was mostly done by GPUs at that time, and so the point of Litecoin's use of a memory-hard mining puzzle was to actually be GPU resistant. So at the time Litecoin was launched, you could still mine on Litecoin with a CPU that you might have used to use to mine for Bitcoins. Now, the technology for mining in Litecoin has lagged behind the technology in Bitcoin. So once Bitcoin mining moved from GPUs to FPGAs and then ASICs, Litecoin mining also moved from CPUs, which is originally intended to support, up to GPUs. And now fairly recently, the first Litecoin mining ASICs are being delivered. Now, by most metrics, Litecoin is the second largest and most popular altcoin. In fact, it's the first most widely forked. Besides the memory-hard mining puzzle and a couple of small parameter changes, for example, blocks in Litecoin arrive 4 times faster than in Bitcoin, every 2.5 minutes. Besides that, Litecoin borrows as much from Bitcoin as possible and differs in very few other ways. And in fact, its development has followed Bitcoin. So as patches and improvements have been made to Bitcoin, Litecoin has also adopted these. So for this reason, Litecoin occasionally uses the slogan, "It's the silver to Bitcoin's gold." The next interesting altcoin to talk about is called Purecoin, sometimes called PP coin. And this was launched a little bit later, towards the end of 2012. Purecoin is very interesting because it uses a very different mining puzzle. This is the first altcoin that featured a proof of stake, which, if you remember from Lecture 8, is a form of mining that doesn't actually involve any computational work. Instead, it involves mining by making transactions using coins that you're already holding, and the coins accumulate stake over time as long as they aren't being moved. Now, Purecoin actually is a little more complicated than that, and it uses a hybrid mining approach. This means that it is possible to mine Purecoin blocks by using proof of work. You can mine for Purecoins by using a SHA-2 mining rig, the same kind you would use in Bitcoin. However, the catch is that this only works for minting new currency. You can mine one of these blocks and get a Purecoin reward, but the proofs of work in a mining block aren't actually included in the calculation to determine what's the longest or the main Purecoin blockchain. This means that proof of work mining is used to distribute coins, but it doesn't have any impact on the security. More proof of work miners that join the Purecoin network don't add any security to it. It also means that an attacker who has a lot of SHA-2 mining equipment isn't able to have any advantage in launching an attack on Purecoin. There's a third aspect of the hybrid mining strategy, which is somewhat controversial, which is that Purecoin administrators have a trusted public key which they use to sign checkpoints of blessed blocks every so often. This is intended to act as a safeguard against attacks, but the controversy is that it leads to a simple argument that this isn't truly decentralized because it has a position of trust in this administrator's public key. Now, this checkpoint system isn't inherent to its design. It could be removed in the future. The downside is that because of this, because it has the safety mechanism in place, we can't necessarily infer empirically that proof of stake has led to a very secure system. We don't know what would happen if this training wheel were removed. Next, we're going to talk about Dogecoin. This is a fun altcoin to talk about because it has a lot of fairly interesting and amusing differences to other altcoins that have come before it. Dogecoin is one of the newest altcoins. It's been launched less than a year ago at the end of 2013. Besides a few technical changes, the main thing Dogecoin has that distinguishes it is the founders of Dogecoin set the tone for a very clear community set of values that include things like tipping and generosity and not taking cryptocurrency so seriously. So while Bitcoin has an ethos of providing decentralized alternatives to centralized infrastructure to change the world, Dogecoin's culture begins with a notion of a sense of humor and having fun with cryptocurrency. So Dogecoin's had a bunch of interesting and successful marketing campaigns or public relations events. One of them is that they sponsored a NASCAR driver who participated in a race at Talladega. So there's a NASCAR car that's covered in the Dogecoin mascot, which is the internet meme of a Shiba Inu, and has Dogecoin logos over the car. Another interesting thing that the Dogecoin community did is they raised over $30,000 to support the Jamaica national bobsled team so that they could travel and compete in the 2014 Winter Olympics. This is especially funny because it almost exactly mirrors the plot to the 90s movie Cool Runnings. Right? And because of these interesting things, Dogecoin has become very popular throughout its short time since launch. One of the interesting technical differences Dogecoin has, or it had, is a notion of random block rewards. The idea is that rather than having a fixed block reward, or a reward that's predictable and changes over time, each block bonus in Dogecoin should be random. Now, the way that this was implemented has a flaw. The way that it's implemented is that the bonus given to the miner for each block depends on a pseudo-random function of the hash of the previous block. Now, the problem here is that miners of a Dogecoin block, before they're mining or while they're mining on a block, know in advance the reward that they would get if they happen to find a correct puzzle solution. And this means that if you know that the next Dogecoin block is going to have a very low value, you have an incentive to switch to mining on some other altcoin instead, which has a more predictable or ordinary value. Once this problem with the random block reward system was understood, the feature was eventually removed, really only a few months after it was launched. Another technical distinction of Dogecoin is that the rate of average block rewards decreases in half at a much higher rate than that of Bitcoin. So remember that in Bitcoin, the block reward is scheduled to decrease by half periodically over time. Originally, Bitcoin blocks were worth 50 Bitcoins each. Now they're worth 25 coins each. This switch did cut in half at some point a year ago, and the next halving event won't occur for a couple more years still. In Dogecoin, the reward rate is cut in half roughly every 2 months. So this is a timeline of Dogecoin's hash rate on its network for a period of time of about 4 months, so spanning from April 2014 up to the current date of August 2014. Now there's a couple of points, so in late April and in mid-July, when the block reward for Dogecoin was cut in half. And what happened is, When it was cut in half, each of these times, the hash rate contributed to the network diminished quite substantially from either an amount of about 30% to 50% of its decline. Now from this first halving event on this timeline, once the hash rate dropped, it eventually picked up again and reached a peak around where it was previously, and just in time for the next halving event, after which it reduced by half. Now, in comparison, over the same window, the hash rate in Bitcoin has essentially steadily increased at a slow exponential rate, while Dogecoin's hash rate has gone up and down. This indicates that the effect of having a much faster halving time has a significant impact on the contributed hash power of an altcoin. Just to compare, not all altcoins go up and down. Here's a timeline also of an altcoin that was steadily in decline during the same period. This was a smaller altcoin. I'm not going to bother naming it for the sake of not embarrassing them. Hash power can be compared directly between two different altcoins that have the same mining puzzle. So for example, the 5 terahashes per second for the altcoin depicted on the bottom is roughly more than 10,000 times less than the 100 petahashes per second of Bitcoin's hash rate. On the other hand, it doesn't make sense to directly compare the hashes per second between two different mining puzzle schemes because it doesn't take the same amount of computational effort to compute the hashes. A customized device for computing SHA-2 mining puzzle solutions isn't usable for computing S-crypt puzzle solutions, or if it's usable, it might only be so at a reduced rate of efficiency. Nonetheless, besides comparing hashes per second, in absolute terms, it does make sense to compare the relative change in hash power over time, because this is a reasonable measure of the amount of participation in the network. It's also possible to measure the price of units of currency in an altcoin as they change over time. And in general, this tends to correlate fairly well with the hash rate contributed to the network. So for example, this top graph depicts the hash rate contributed to the Litecoin network over time, which again is steadily increasing at roughly an exponential rate. And Dogecoin's hash rate over time, going up and down several times over the same time period, is shown at the bottom of the top graph. In the bottom graph, you see the relative exchange price at one of the largest third-party cryptocurrency exchanges. What you can tell is that just as the relative hash rate contribution in the Dogecoin network has diminished relative to Litecoins, so has the price of Dogecoin diminished relative to Litecoins. We've mentioned several metrics for comparing altcoins. I'm going to talk about in a little more detail about a few of these and describe their relative disadvantages or weaknesses to each other. The standard one, or perhaps most commonly used one, is market cap, which, to recall, is the price per unit of a currency at some current time, measured typically at a third-party exchange, multiplied by the total number of units of this currency thought to be in circulation. Now, this is almost certainly an overestimate, but it's not clear how much. It's an overestimate for one reason, because the price would change if you tried to sell coins. Suppose you had 1 million Bitcoins, this is around 10% of the current Bitcoin circulation supply. You wouldn't be able to sell all of those coins at the current price. Once you started trying to sell a fairly large amount of them, the price would begin to drop as you introduced more coins to buyers who wanted to buy them. All right, so it's not obvious how to account for the difference in available liquidity. Another thing that market cap's hard to account for is how many coins are actually in circulation as opposed to out of circulation. One way that an altcoin currency unit could go out of circulation is if the original holder of that coin loses their private key. They're no longer able to spend the coin, so it's really become unusable. But there isn't any way necessarily for the network to be able to tell whether or not this has happened. So a simple market cap calculation isn't able to account for this. One way of trying to measure the amount of activity on an altcoin is to look at its exchange volume. Now, to do this, you have to look at one of the large third-party currency exchanges, and this introduces some uncertainty. It depends in some way on the nature of which exchange you're looking at. They sometimes have slightly different prices. It's also possible to move the price. It's possible to join a third-party exchange and buy and sell units of the currency to yourself for a fairly low price, but this has the effect of influencing the apparent exchange volume. Right? You could also look at the transactions that are done on the network, but a transaction on Bitcoin or in most altcoins doesn't really mean that any change of value has taken place. It could just mean that users are automatically reshuffling the coins in their wallet, for example. And as we've looked at it, there are ways of comparing the hash power of coins or looking at how the hash power of a network changes over time. This is especially useful for comparing networks with similar mining puzzles, and it's difficult to compare in absolute terms puzzles with networks with different puzzles. Now, another more direct metric that you might want to use is some measure of merchant support or commerce being done. How many users are actually using their currency in an altcoin to do things like buy products or exchange them for other things of value and so on. And this is very difficult to measure because it would rely quite heavily on some way of aggregating all of this information from merchants. You would perhaps need the support from some of the large merchant tools or payment processors that handle both altcoins and Bitcoins. And in general, large exchanges and payment processors are hesitant to accept new altcoins into their system, and they only do so once an altcoin has already reached some level of status and it's perceived as being taken seriously. So far we've talked about just a small handful of altcoins. There are many more we could talk about and tell their stories as well. But we're going to move on for now, and we'll talk about a couple more altcoins as they come up. Next, we're going to talk about some of the ways that Bitcoin and the altcoins in this ecosystem interact with each other. All the altcoins in Bitcoin, in a sense, compete with each other. They have rivalries, and we've looked at some of the ways that they change in relative value and participation over time. It's also possible for them to interact in a more hostile or harmful way. So for example, given the way that the proof-of-work mining system works, it's possible if you have a lot of mining power to conduct various forms of attacks on Bitcoin or on an altcoin using this mining power. Now, in particular, this means that if there's a very large entity on a large network such as Bitcoin, for example, a powerful single miner or a large mining pool, this mining entity would have a very large power relative to the participation of a very small coin that uses the same proof-of-work puzzle. This means that a large miner on a Bitcoin network could fairly easily attack any small altcoin if it wanted to. Now, attacks like this have actually happened before in practice. There's a well-known story of an altcoin called CoiledCoin, which was quite small during the time of 2012. And one of the large mining pools, Elijah's in Bitcoin, decided that CoiledCoin was a scam and an affront to the cryptocurrency ecosystem and a very bad idea. And so the director of this Elijah's pool pointed his mining resources at CoiledCoin and launched an attack. This attack involved mining a lot of blocks that reversed days worth of transaction history in CoiledCoin, reversing the user's transactions, and as well as mining a long chain that had empty blocks containing no transactions at all, effectively making a denial of service attack. CoiledCoin users weren't able to make any transactions during that time. After a fairly short time of this siege, all of the users of CoiledCoin had left and moved on, and the altcoin doesn't exist anymore as such. Similar attacks have also been conducted on other altcoins such as TerraCoin and WorldCoin most recently, although in these instances the attacks were short and the altcoins did survive, at least to some degree after the attack. I want to talk now about a technique called merge mining, which I mentioned is a very clever technique, and this involves a way that mining on two altcoins can be combined. Now, ordinarily, mining on an altcoin is exclusive to a particular altcoin. Each hash you compute, each puzzle solution attempt you make, has a chance of either being a solution for one altcoin or for Bitcoin, but there's no chance of it being both. You can divert some of your mining resources to mining on one altcoin network or on another. You can change it over time, or you could split your resources, but at any one time, your hash power has to be divided from its total in this sense. Now, this is an obstacle to bootstrapping. If you wanted to launch an altcoin and convince Bitcoin miners to participate in your network, the Bitcoin miners would have to stop mining Bitcoin while they switch to your altcoin. So what if it were possible to mine both blocks on an altcoin and blocks on Bitcoin at the same time without having to sacrifice either? Now, just to illustrate this, the reason why each puzzle solution attempt has a chance of being either a Bitcoin block or an altcoin block is because each hash you compute is over a string, and the string contains, in the case of Bitcoin, the hash of a previous block, the Merkle root of a tree containing a bunch of valid Bitcoin transactions, and you have to compare it to Bitcoin's target difficulty in order to see if it wins. Now, for a basic altcoin, that would be just a fork of Bitcoin's code with a different genesis block but no other changes, so the same mining puzzle. Each puzzle attempt for this altcoin would include it would be a hash over a string including the hash of a previous altcoin block, a Merkle root of altcoin transactions, which would be different than Bitcoin transactions, and you'd compare it to the altcoin's difficulty target, which would be different than Bitcoin's as well. Each hash you compute either has the string of the top type or the string of the bottom type, and there's no way for a single hash to give you information about both. So merge mining is a way of designing the mining puzzle for an altcoin, such that every puzzle attempt in the altcoin is also a valid puzzle attempt in Bitcoin. Now, the secret to this is that there are places where a miner can put data in a Bitcoin block that they're mining on. They can put arbitrary data that isn't validated by the Bitcoin network, and it's up to them. So the approach will be to make the important data like transactions and previous block hash for the altcoin embedded in the Bitcoin block in this location. More specifically, one of the places in Bitcoin where you can place arbitrary data is in the script sig of the first transaction in the block, the Coinbase transaction. Right? The script sig field isn't checked at all by Bitcoin, so it can be arbitrary data and it would still be a valid Bitcoin block. So the approach for merge mining is to put all of the data that you need for your altcoin encoded in this script sig. This includes the previous block hash for your altcoin and the Merkle root of some transactions relative to your altcoin. Now then, the merge mining puzzle is to compute the hash over the string including an entirely valid set of Bitcoin block data and just happens to contain the altcoin data. And once you compute this one hash, you can compare it even to a different difficulty target for the altcoin that's typically less than the difficulty in Bitcoin. Now, notice that you can only compute one hash, and yet it still has a chance of being either an altcoin solution or a Bitcoin solution, or even both. Now, what we've just illustrated is a way of merge mining an altcoin onto Bitcoin, but it's possible to generalize this so that you can merge mine any number of altcoins at the same time as well. Now, merge mining is a mixed blessing. It makes it a lot easier to recruit mining participants, especially from a much larger existing network like Bitcoin, because mining participants in Bitcoin don't have to stop mining Bitcoin in order to also merge mine on an altcoin. On the other hand, it also makes this cheaper for attackers. So for example, the coiled coin attack that I mentioned, coiled coin was a merge mined altcoin. This meant that for a Bitcoin mining pool to attack coiled coin, it doesn't even have to take the opportunity cost of stopping mining Bitcoin while it launches this attack. Another problem is that miners don't have an incentive directly to validate transactions thoroughly if they believe that the chance of there being an invalid transaction published is fairly low, or if they delegate validating transactions to someone else, such as the leader of a mining pool. So while it might not be too expensive to fully validate transactions for a single network, if you wanted to merge mine on a very large number of different altcoins, it would be expensive to thoroughly validate transactions on all of them. Therefore, merge mining makes it more likely that only a smaller number of miners would actually perform transaction validation. Many large mining pools in Bitcoin actually provide the service of helping you merge mine many compatible coins at once. So for example, the largest Bitcoin mining pool, ghash.io or gigahash.io, allows you to simultaneously mine on Bitcoin, Namecoin, IXCoin, and DevCoin. So these become the most popular Bitcoin-compatible merge-mined altcoins. Next, we're going to talk about a way that transactions in two unrelated altcoin blockchains can actually be related and interdependent to each other. In general, a transaction on one altcoin is entirely independent of and has no way of referring to a transaction that happens on some other altcoin's transaction history. However, there is a way to do something to this effect using a technique that we've discussed previously. Now, the motivation here is suppose that Alice has one Bitcoin and Bob has one Litecoin, and they would like to trade with each other. This means that Alice could make a transaction on the Bitcoin network that transfers her Bitcoin to Bob. Bob can make a transaction on the Litecoin network that transfers his Litecoin to Alice. But they have a problem if they don't trust each other. Which one of them is going to go first? If Alice sends her Bitcoin to Bob, Bob might not make a Litecoin transaction and Alice would never get the Litecoin. Bob would end up with both of them. What you would like is for an atomic transaction property where either both transactions, the Litecoin transaction and the Bitcoin transaction, both complete or neither of them do. Now, the way that this technique is going to work, it's going to involve a couple of different steps. In the first step, Alice is going to generate a secret key, X. She's also going to compute the hash of X, and we'll call that hash value H. Alice is going to start by creating a pair of transactions. The first one is a deposit. It's a Bitcoin transaction that deposits her Bitcoin such that the Bitcoin can be spent in one of two ways. One of the ways is for Bob to take it. This way is colored in green on this slide. It only requires Bob's signature, but it also has to involve publishing the secret value X such that the transaction can check that indeed the hash of X is actually H. All right, this is the way of claiming the Bitcoin that'll happen if the protocol completes. Now, the other way of claiming Alice's Bitcoin requires a signature from both Alice and Bob. Now, Alice generates this deposit transaction, but she doesn't publish it yet. First, she generates another transaction, refund, which refers to deposit, and it contains both Alice and Bob's signature, and it is time-locked to a time in the future, which we'll call t+2. Now, once she gets Bob's signature on this refund transaction, she can publish the deposit transaction. Now, the important conditions here are that if Bob is able to learn the secret value X before time t+2, then he's able to take Alice's Bitcoin. This is what happens when the protocol completes normally. On the other hand, if Alice never reveals her secret X, then she knows that she will be able to reclaim her refund at time t+2. Now, the second step involves Bob also creating a similar pair of transactions. Bob's going to create a deposit B transaction, which contains his Litecoin, and his Litecoin can be spent in one of two ways. Again, one way is, in the ordinary course of the protocol, requires only Alice's signature, so it will transfer the coin to Alice, but it requires Alice to publish and reveal her secret string X, which again is checked to the hash value H. Now, Bob creates the deposit transaction but doesn't publish it immediately. First, he creates his refund transaction. He has to collect his own signature and Alice's signature as well. And this transaction is time-locked to a time t+1. And this means that this transaction is signed by Alice, but it isn't valid until sometime after t+1. Once Bob has Alice's signature on this time-locked transaction, he's free to publish the deposit B transaction. Now, the important qualities here are that if Bob is able to learn the secret value X, because Alice reveals it, before time t+1, then Alice is going to be able to take the Litecoin from this transaction. This is how the protocol completes normally. On the other hand, if Alice never revealed X, then Bob can claim his refund at time t+1. So putting this together, after all of the deposit transactions are published, Alice reveals X, and she creates a transaction that takes the Litecoin from Bob, but to do so she has to reveal X. So when Bob learns X, he can create the transaction that takes Alice's Bitcoin. Now the transaction's completed. Now, the important logic about why this is secure is that if Alice doesn't reveal X, then Bob gets to take his refund at time t+1. If Alice takes Bob's Litecoin, then the only way she can do that is if she does reveal X before time t+1. Right? And in any case that Alice reveals X before time t+1, Bob will learn it and have time to take Alice's Bitcoin before time t+2, the final deadline. This guarantees that either both transactions complete or neither of them do, which is the property we wanted out of this. So this is a clever transaction protocol. It has the potential to provide liquidity between altcoins in a secure and decentralized way. On the other hand, this technique hasn't been seen in the wild. There are a few reasons for this. The disadvantages of this protocol are that it requires many transactions, each of which typically has to carry a transaction fee or at the minimum take some amount of time to complete. Even though you're guaranteed that either both transactions complete or neither of them do, there's still a risk of denial of service. If you try to do this protocol with a random stranger, they might waste a lot of your time by starting protocols that end with everyone having to collect their refund at the time deadline. Because of these disadvantages, almost all exchanges between altcoins are done using large centralized third-party exchanges or ad hoc transactions like local Bitcoin exchanges. So to summarize so far, we've talked about Bitcoin and its role in the context of a large ecosystem of hundreds of altcoins. These altcoins compete and interact with each other in a variety of ways, some cooperative and some hostile. We've also looked at two specific ways that altcoins can interact at a technical level. We've looked at merge mining, which is interesting because an altcoin can support merge mining without even explicitly having to have support from Bitcoin. Not only does Bitcoin not have to change for an altcoin to merge mine on it, but it isn't even clear what Bitcoin could do to prevent merge mining like this from occurring. Similarly, you can use the hash commit technique in order to have interdependent transactions, even though they occur on entirely separate altcoins that have nothing to do with each other directly. This is possible with the existing script language that essentially every altcoin supports. Now we're going to talk about how to launch an altcoin and what happens to altcoins after their launch, what's involved with this process. Now, as we mentioned, an altcoin generally involves creating a new reference client, typically by forking the existing code base of some existing, more well-established altcoin or Bitcoin itself. And the easy part is to add in a bunch of technical features or modified parameters you think will work out well. To get people to join your network, you need to make this reference client available to them so they can download it. Typically, this involves announcing the source code to your reference client on the popular Bitcoin Talk forum. And that's the easy part. The hard part is actually bootstrapping your altcoin. The security and the value of an altcoin comes from this bootstrapping process of people who find it valuable. In order to get your altcoin bootstrapped, you need to find people who will be miners. Miners are needed to join the network in order to make it resilient to attacks from other altcoins. For your altcoin to have any value, there have to be people who are stakeholders who own units of the currency and consider them valuable or useful to them. An altcoin needs a development community because altcoins typically need to be modified to update, to respond to bug fixes, and to add new features, and to increase the scalability and efficiency as your altcoin becomes popular and more transaction volume occurs on the altcoin network. It's also important for people to buy and sell altcoins to provide a liquid market so that people who want altcoins or want to sell them can find a place to buy them from. Just to illustrate the point about the reference client being the easy part, I want to highlight a site that doesn't exist at the moment. It was only up for a short while, and it might come back. And it's called the CoinGen Beta, and it's an automated service that generates a modified altcoin for you as a service. It's a website where you can enter in a name of an altcoin that you'd like. You can make up a 3-letter currency code abbreviation. You can upload an icon for whatever mascot or logo you want for your coin. There are checkboxes so you can set a variety of different standard parameters. You can adjust some numeric parameters. After you've picked all of these settings, you actually just click Create My Coin, and you can download this modified fork of Bitcoin and immediately release it and start running it. Typically, you have to pay some fee to this service, like 0.05 Bitcoins for this. You can do this to very easily create any sort of altcoin, so there's really no challenge in just creating a reference client, so that clearly doesn't make the difference in whether an altcoin will be successful or not. Besides a reference client, there's a lot of technical infrastructure that most altcoins have, and altcoins seem to need in order to be successful. It's important to have some way of initially getting users to have coins. Some of the infrastructure that supports this in Bitcoin and in many altcoins are things like tip bots or faucets. Tip bots allow you to give units of your altcoin to users who aren't already users of your network. You can deposit some of your altcoin in a tip bot and it will send this person a message telling them how many altcoins they have available and how to download the reference client and claim it. This is a way of introducing new users to the system. Another thing is a faucet, like the Bitcoin faucet, that will give out small amounts of your altcoin units to anyone who shows up at a website, maybe enters an email address. Almost all altcoins have some kind of distinctive marketing or branding that makes them memorable and easy to recognize. This includes logos or a more comprehensive theme. Other infrastructure that's needed are exchanges or automated ways of exchanging Bitcoins or altcoins for other kinds of currency or altcoins, or exchanging altcoins for products or services from merchants. Now, there are a lot of existing exchanges and payment processors that already support many altcoins, so this is often a matter of just convincing them to include your new altcoin in their list of supported cryptocurrencies. Besides the reference client, there are a lot of developer and diagnostic tools, such as testing suites or an entire testing network version of your altcoin that people can experiment with, and things like a block explorer that allow people to look at the transactions and the blocks as they arrive. Most altcoins now have some kind of steering foundation, usually by the organizers or launchers of the altcoin in the first place. Now, Bitcoin's founder, the pseudonymous Satoshi Nakamoto, just released the source code for the reference client and basically disappeared after that. There's now a Bitcoin Foundation that does provide some of the function of encouraging development and lobbying, but it's in no way an official organization. Many altcoins, it's actually the founders of the altcoin and the people who launch it who continue to maintain the altcoin after its launch and form some kind of organization to do that. Now, a very important thing for an altcoin in a way of getting stakeholders initially is to provide some way of initially allocating units of the currency to individuals besides just the mining process. So in every mining-based coin, some new coins are created and handed out to miners who solve proof of work puzzles and earn mining rewards. But there are other ways of allocating coins as well. One is called a pre-mine, which is where the founders of the currency reserve some portion of the money supply for themselves. They get a stash of the units of their own altcoin. Sometimes they say that these pre-mine amount is intended to be used for further development of the currency, or to pay developers, for example. Another way of allocating units of an altcoin initially is through a pre-sale. This is where the founders, instead of taking these units of currency for themselves, they sell them to individuals for some other currency like Bitcoin or dollars or any other. Now, the people who buy those currencies are the initial holders of them. On the other hand, the founders get this revenue of ordinary money or Bitcoins, which they can also use to, for example, pay developers to build the currency. Another interesting way of getting an initial set of stakeholders in your altcoin is called proof of burn. Otherwise, this is called unilateral pegging. The way that this works is that a user who destroys 1 unit of Bitcoin that they own earns 1 unit of the currency in your altcoin. Now, this is intended to have the effect that whoever ends up holding an altcoin believes that it's at least worth as much as the value of the Bitcoin that they destroyed in order to get it. On the other hand, there's no way to recover the Bitcoin in this case. It's actually destroyed. An alternative is to have Bitcoin ownership grandfathered in. In other words, if you had, say, a current date, taken like a snapshot, if at a current date you own 1 unit of Bitcoin, then at the time of this altcoin launch, you also own 1 unit of the altcoin. All right, in this case, the original Bitcoin doesn't have to be destroyed. All right, and the final mechanism is called an airdrop, which is if the altcoin is targeted at some kind of community or group, then an initial allocation of coins is simply distributed to members of this group. Now I want to tell the story of an altcoin called Aurora Coin, which is fairly controversial. It's been widely considered either the most successful scam or one of the least successful altcoin launches. Now, the theme of Aurora Coin is that it's intended to be an altcoin that supports citizens of the country of Iceland. The idea is to distribute units of Aurora Coin to Iceland citizens who would be able to claim some fixed amount of Aurora Coins at some point. Now, in total, Aurora Coin has a total supply of eventually 21 million coins, half of which are given out to miners gradually, and the other half of which, 10.5 million, are set aside and dedicated to be available for Iceland citizens to claim their fixed portion. Now, Iceland has only about 330,000 people, and at the time that the airdrop began, the coins were not available for Iceland citizens to claim until several months after the coin was initially launched. Now, what happened was, during the time that the coin was launched, and in between that time and when the distribution to Iceland citizens began, the price fluctuated quite wildly. It reached a fairly high peak, but by the time the airdrop occurred, the price had diminished quite a lot. And once the date of the distribution began, the price dropped very rapidly, very low, and has never recovered since. Now, what went into this? One explanation is that there's a very high uncertainty about the monetary supply. At the time that the airdrop began, only a very small amount of the currency had been distributed to miners as rewards, and it was very uncertain exactly how many Iceland citizens would actually go through the effort of claiming their Aurora coins. This meant that the relative portion of the monetary supply that any miner would hold would either completely change or not change at all, depending on how many citizens actually claimed the coin. Another reason for this uncertainty is that the process of distributing portions of coins fairly to individual citizens is a very difficult process. Presumably this could be done by checking something like their national identity cards, but that would be a very difficult process even for someone who had planned it very well. The way that this was implemented was simply by the founder of the coin signing over units of the currency by making signed transactions with his public key. There's very little accountability or transparency into this, which led to a fairly large suspicion that he was either being inundated with fraudulent requests of attackers trying to claim more than their fair share of Aurora coins, or that the founder himself ran away and simply made transactions that gave himself a large amount of the Aurora coins, and then he could sell them off at an exchange. There's no clear way to know whether this is what happened or not, but the fact of this large amount of suspicion, I think, had a lot to do with the fact that the price very rapidly declined. Many altcoins are criticized as being pump and dump schemes. This is a phrase that refers to something that happens in small value ordinary company stocks all the time, and it also happens in altcoins. To conduct a pump and dump, you have to pick an altcoin that you're going to use as your target. This could be an altcoin that's about to launch, or it can be an existing low value altcoin that doesn't have a lot of participation and doesn't have a very high value. Now, while the price is so low and while the value is so low, it's easy for an attacker to acquire a large number of these altcoins. Now, after that, or around the same time, the attacker would launch a targeted marketing campaign to convince the public that the reason for this acquisition of coins was because a lot of people are interested in the coin. The coin has a lot of grassroots support, or it even has some big important technical merit that explains why it would become popular so rapidly. And at the peak of this excitement, as more people in the public try to buy this coin, the attacker would then sell all of his coins once the price has risen high enough. All right, now once the marketing campaign ends because the attacker has left and people realize that there weren't actually a very large following of grassroots support or the technical merits were overstated, the altcoin's price drops and eventually declines and users move away. This is profitable for the attacker, but it wastes a lot of cryptocurrency enthusiasts' valuable money. Now, there are many arguments against altcoins that essentially say altcoins are a bad idea and harmful to the overall cryptocurrency ecosystem. One of these arguments is that since altcoins rely on mining power for their security, having a large number of competing altcoins with total mining power divided among them means that any one of those altcoins is relatively weaker against attacks than they would be if, for example, they were all consolidated. A related problem is that there's a dilution of scarcity. One of the reasons why Bitcoin is valuable is because it's perceived as having a fixed, limited supply of these 21 million coins. And even if that's true, if it's very easy to create so many other altcoins that also have their own value, then in a sense it dilutes the scarcity of cryptocurrencies as a whole. Right? And another argument is that altcoins are very easy targets for these pump and dump schemes, and potentially of all the hundreds of altcoins, most of them can only be used as pump and dump schemes or only attract that kind of participation. On the other hand, there are a lot of compelling arguments for altcoins as well that basically say that altcoins are an essential part of the cryptocurrency ecosystem. For example, you could say that competition between altcoins leads to better systems overall. The best altcoin that has the most technical quality and the best features will eventually be the one that's most successful and has the most value. A reason to use an altcoin rather than simply trying to build new features into Bitcoin or build up Bitcoin are that the Bitcoin community is somewhat risk averse to adopting new features. If you have a new feature you want to try out, it's a lot easier to simply implement it in an altcoin and see how it fares than to try to convince the Bitcoin community to accept this as a change before it's been tested. In this sense, altcoins are like a research and development testbed for potentially new Bitcoin features. Another good thing about having a diverse variety of different altcoins with different technical composition is that if there's some uncertain event, like a catastrophic failure of one altcoin, it might not affect all of the other altcoins that have different makeup. This means that if one altcoin is taken out, the world of cryptocurrencies can still continue. Another interesting point is that having multiple altcoins has the potential to be a safeguard against the concentration of wealth occurring in any one particular place. The ability to launch new altcoins creates the option of something like a jubilee, which is a biblical kind of event where establishment of wealth is reset and debts are canceled or something like that. The ability to launch a new altcoin has the ability to start over again and measure wealth in a new way based on currencies of a new altcoin. This could happen, for example, if it was decided that someone unscrupulous eventually accumulated all of the bitcoins or too many of the bitcoins. It's always possible to simply create a new altcoin and start over again from scratch. Now we're going to talk about a topic that's at the cutting edge of cryptocurrency research. It's not something that's possible with Bitcoin today, but it's something that a modification to Bitcoin or to another altcoin could support. We've talked about several ways that a new altcoin could convince stakeholders of Bitcoin or another altcoin to become stakeholders of this new altcoin. Now, two of the options that we've discussed are sort of two extreme sides of the same concept. In the grandfathering approach, anyone who's a Bitcoin holder can become a holder of some units of this altcoin. On the other hand, this doesn't involve any risk to the Bitcoin holder at all. If the altcoin crashes, the Bitcoin holder is no worse off than he was before. He still has all of his Bitcoins. On the other hand, the unilateral exchange plan involves burning Bitcoins in order to get units of the altcoin. This involves a lot of risk taken by the Bitcoin holder. If the altcoin crashes, then there's no value in the altcoins he earned, but he also doesn't have the Bitcoins that he started with, since he deleted them in order to gain units of the altcoin currency. Now, with the unilateral peg, this means that 1 unit of Bitcoin is deleted forever in order to claim 1 unit of altcoin. There's no way to get a Bitcoin back. You could trade the altcoin with someone else who already has a Bitcoin, but the Bitcoin that you had is already taken out of the money supply irreversibly. On the other hand, instead of burning the Bitcoin, it would be interesting if you could simply deposit the Bitcoin in some place where it was held in escrow of some kind. You'd be able to get 1 unit of this altcoin and then transact with it in different ways. But if eventually you wanted to get rid of your altcoin and have your original Bitcoin back, you would have that as an option. You could take that Bitcoin that was deposited and retrieve it from its escrow storage. This would be called a bilateral peg. Now, ordinarily, 1 Bitcoin transaction can't refer to events that are happening in another altcoin blockchain. But a possible change would be to extend Bitcoin's transaction script language so that you could have all of the rules of an altcoin, including validating all of the transactions and checking the altcoin's proofs of work, actually encoded in the script of a Bitcoin transaction. You would be able to deposit a Bitcoin in such a way that the only way you can retrieve that Bitcoin is by presenting evidence, meaning all the data of a blockchain, showing that an altcoin had actually been deleted, and you could get the Bitcoin back out. Now, to implement this the direct way, it would actually require a very complicated script language, and it would require a lot of effort for Bitcoin validating nodes in order to check all of the data on every other altcoin. This would be way too complicated. Now, there's an approach towards improving the efficiency of this, which involves using SPV proofs. Now, if you recall, SPV proofs are a way of allowing not full validating nodes, so things like mobile clients, which don't have enough resources to perform validation of the entire blockchain, to nonetheless get some evidence that, for example, a transaction has occurred 10 blocks ago in the longest blockchain. Now, a full validating node has to validate every transaction and is supposed to only mine, for example, on the longest valid blockchain, where validating requires keeping track of all of the available transactions and checking all the transactions in every block. On the other hand, a mobile client that assumes that the rest of the miners are doing their job, a mobile client can become confident that a transaction has actually occurred just by looking at the proofs of work in a bunch of blocks and just checking that the transaction, a single transaction that they care about, is included in the Merkle tree of transactions, including in a block that occurred sometime in the past. This is a lot faster because it only involves checking block headers. And it's not a guarantee that this is the longest valid blockchain, but it is evidence to this effect. So the approach to allowing things like bilateral peg is to have a Bitcoin transaction script that's capable of doing SPV proofs about an arbitrary altcoin. Now, altcoins often have different parameters like increased block rates. If an altcoin has a very fast block rate, then this would mean that checking an SPV proof of all of the headers in a block, all the headers in a blockchain could still be pretty slow. It would take, for example, n steps to check the proofs of work for n blocks in the altchain. If instead of just having blocks form a chain, though, what if we could store the blocks in a data structure that supported some more efficient kind of SPV proof? We'd like to get something along the lines of taking log n time to check a blockchain that has n blocks in this altcoin. Now, one approach to this is based on the idea of a proof of work sample. Suppose that we have 4 blocks, each with difficulty 4 bits. This means that every hash of these 4 blocks has at least 4 0 bits in the front of it. Now, if all 4 blocks have at least 4 0 bits, on average, half of these blocks are actually going to also have at least a 5th other 0 bit in the front. And even one of these 4 blocks, on average, should be expected to have a 6th 0 bit, so 6 bits of 0 in the front. All right, and so on, depending on the number of blocks. Now, the average number of hashes that are needed to find 4 blocks with 4 bits of 0 in them is 4 times 2 to the 4. It would take, on average, 64 hashes to find these 4 blocks. This is exactly the same as the average number of hashes you need to compute to find just a single block that has 6 bits of 0 in the front. So an idea is, why not just check a single block, the one that has the most bits, and use that for your proof of work? Well, even though the average number of hashes needed to compute these blocks is the same, the precision of this estimate is different. Suppose an attacker computes only 32 hashes. This is half the expected number of hashes needed to find 4 blocks. The probability of finding these 4 blocks with 4 bits of 0 each is actually only 14%. You have a 14% chance of successfully finding 4 blocks in half the average amount of time it would take you to find those 4 blocks. On the other hand, the probability of finding just a single block with 6 bits, using only half the expected number of hashes it would take, is much higher. It's actually 40%. You can do these calculations using standard probability techniques. The number of blocks you find at a given difficulty level, given a fixed number of attempts, like 32 hashes, comes from the binomial distribution. All right? The upshot of this is that the more samples of proof of work you check, the more precise your estimate is, the closer to the average number of steps you can guarantee that it takes. This means that checking just a single proof of work might not be a good idea, but it is plausible that you could check a much smaller number of blocks than the whole blockchain and still get a confident estimate about the proof of work in the total blockchain. Now, to have a data structure that supports SPV proofs of this kind, we can build something like a skip list. Suppose that our goal is to support compressed proofs of work that involve checking only a quarter of the blocks on average in a large blockchain of proofs of work. The way to do this is to have every block contain not just a pointer to the previous block, all of which contain at least 4 bits of 0, but also the hash of the block in the past that's most recent that has 6 or more bits of 0 in the front. This would only incur an insignificant amount of cost to full nodes who are still going to validate every proof of work in every block. But in order to check a compressed SPV proof, it's only necessary to check the hashes that point backwards to the high-value lucky blocks. You can just follow the red arrows. On average, in this case, it would take an average of only a quarter of the blocks in proofs of work you would have to check. Now, this basic approach can be generalized to an ordinary skip list, where you could choose after the fact what kind of sample you would want to take, and you could skip as far back as quickly as you like, or get a more dense sample in order to have a more precise estimate. Let me conclude by talking a bit about sidechains and the potential that this holds. With a suitable modification to Bitcoin or an altcoin, you would have the potential to have other altcoins that hold units of other altcoins in reserve. Right? This could be used to smoothen out the risk of launching a new altcoin. You don't necessarily have to allow altcoins to be redeemed back to Bitcoin at the same rate. You could, for example, be guaranteed that if you spend a Bitcoin to get 1 unit of altcoin currency, you can either keep that altcoin, hopefully it rises in value, or you might be guaranteed that you can reclaim it if you want for at least, say, half, like 0.5 Bitcoins of the value that you initially deposited. This could be a way of having a safeguard against losing all the value in an altcoin if the altcoin crashes shortly after its launch. All right, now this isn't possible today, and it would require some changes to Bitcoin in order to support this. For an altcoin to support this, doesn't preclude any of the other options that we've talked about as well. The altcoin could either be merge mined with one of the coins that it uses as backing reserve, or it could avoid merge mining by having a completely different incompatible mining puzzle. So to wrap up this lecture, we've talked about how Bitcoin is an important part of a much larger ecosystem of cryptocurrencies and altcoins. They compete and interact in various ways, some cooperative, some harmful. There are also a lot of ways that they can technically interact with each other through techniques such as merge mining and hash-linked transactions that are interdependent between different blockchains. And it's also possible that in the future there will be more technical ways that transactions in one blockchain can explicitly refer to transactions in another blockchain. There remain several open questions that we aren't able to decisively answer at this time. Are altcoins going to consolidate or stay consolidated where there are a few vastly largest altcoins or one largest altcoin? Or will they diversify further so that there are a plurality of equally popular and valuable altcoins? Is Bitcoin eventually going to be overtaken by some other altcoin, like one of the ones that's been launched recently? Also, is it a good idea to even encourage interaction between Bitcoins? Or should interaction like this be discouraged, for example, by using incompatible mining puzzles rather than merge mining? We can't answer these questions right now, but we've talked about all of the concepts you need to understand and appreciate the importance of this question. In the next lecture, we're going to wrap up this lecture series by talking about the future of Bitcoin. Is Bitcoin going to bring about a new future society where all important infrastructure is decentralized? We're going to talk about several topics, including autonomous agents and smart property.